This deep learning course is designed to take you from beginner to proficient in deep learning. Ayush Singh created this course. He's an experienced data scientist and popular course creator. Ayush will teach you the fundamental concepts, architectures, and applications of deep learning in a clear and practical way. So get ready to build, train, and deploy models that can tackle real-world problems across various industries.
What if I tell you that there's a deep learning course that teaches you deep learning from very scratch to a core level? So what do I really mean by scratch is teaching you the core and the crux of the mathematics which is required for deep learning, like linear algebra, single variable calculus, and much more. And not only this, we give you detailed lecture notes along with the practical assignments on data wars for absolutely free so that you can follow through this course and become the master. Hi, this is Ayush. I'm co-founder of Second Brain Labs, and in the past, I've worked as a lead data scientist at Triplate, a UK-based esteemed organization working on large-scale creators economy product, as well as I've worked as an MLOps engineer in a core ZenML team in order to streamline MLOps frameworks, and furthermore, I've worked in several US-based companies as a contractual roles as a data scientist. And not only this, I love teaching. My courses has got millions and millions of views throughout the internet, and I've helped several thousands of students in order to get their first paycheck or their first job. But why you should consider learning deep learning? And what is the core problem which is coming into the deep learning content throughout the internet? Nowadays, all of the companies are asking for a deep learning skill set into a particular candidate. And to be honest, people think deep learning is extremely hard and pretty hard to understand. And it's my personal opinion. I feel that because of the instructors on YouTube, it's becoming a little bit hard to understand. It's not because it is very complex. I agree that whatever things are a little bit difficult or hard to interpret, but if taught in the right way, deep learning is the most, I think, easiest subject as compared to even core machine learning. I will teach you deep learning in a very core way, from very scratch. We will mathematically do every iteration by our mathematics so that you understand, okay, this is how the flow is going and this is how each step is helping your model to learn or become better. Let's get started with our course. Hey everyone, welcome to this first lecture on linear algebra. So today we are going to talk about vectors, and we'll be exploring vectors a bit. Okay, so first we'll start off with what is linear algebra. Why do we even bother to study this? As some of you already are familiar with algebra, you just want to just refresh your memory of your algebra, or you wanted to you're from very scratch, and then so that's why let's start with the definition of linear algebra. So I've written one definition of linear algebra is it's the mathematics of the data. Yeah, you heard me correct. I saw this definition online and I found this a very basic definition to tell you, rather than taking too much of mathematical terms. Is algebra, linear algebra is the mathematics of data. And why I'm saying it's mathematics for data, because linear algebra contains of matrices and vectors. So these two are the language of the data. So whatever we are going to study, which you will see in your machine learning or deep learning journey, whatever you are going to study. So that's why we just say that it's the mathematics of the data, because in machine learning, data is so much of a basic component or a mandatory component. The same way we use algebra or linear algebra to work with the data mathematically. Okay, so this is a simple definition of linear algebra over here. So let's get started with the first component, first thing which we'll study in this video is vectors. Okay, so we'll start with the vectors. So we'll starting with vectors. So if you have any definition of a vectors, please stop this video, pause this video, and then go down in the comment and please tell me what are vectors. So we will start with very scratch. You can assume a vectors as an arrows,
as an arrows. We have an arrow. So these are the geometric distribution of a vectors. So the definition of a vector can be it's an arrays of a numbers. Okay, so vectors are arrays of a number or a tuple of a numbers. Okay, or you can take it as an arrays. Okay, so you can consider a vectors can be arrays of a numbers, or you can consider this vectors as an arrow. You can consider vectors as an arrows, or you can consider a vector as a tuple of a numbers. You can consider a vector as a tuple of numbers. Okay, so these are you can just imagine this an array is maybe an array can be 1, 2, 3. This is called the row vector, which you'll study. You can safely ignore this. So this is also a vector, which is special type of vector, which is called the row vector. This can be tuple of a numbers, or it can be arrows. Okay, so the way I like to represent vectors, or to make you very much comfortable with it, is to make you familiar with an arrows. So this is the geometric distribution of a two-dimensional vector. So let's see how the vector looks numerically. Okay, in terms of mathematical. So let's see how the vector looks. So let's name the vector as u. Okay, so let's name the vector as u equals, so let's store 2 and 4. So u is a vector where you have the elements, so the numbers inside the vector you enclose into a square bracket. So here is 2 and here is 4. Okay, so why I'm saying this is like an arrow. So the first element is called the x component, and the first element is called the x component, and second element is called the y component. So let's see how this looks on a graph paper or an x and y plane. So let me plot that. So 1, 2, 3, 4, 5. 1, 2, 3, 4 and 5. Okay, so this is my y plane and this is my x-axis. Okay, so let's plot this vector onto this x and y plane. So x component is 2 and y component is 4. Okay, so x component is 2 and y component is 4. So here's the point, and it passes through the origin. So this is your vector u. Okay, so this is your vector u, where you have 2 by 4, where 2 indicates the x component and 4 indicates the y component. Okay, so this makes sense? I hope so. Okay, so vectors are arrays of a numbers, or you can say the tuple of a numbers, which consist of numbers, where here our vector is two-dimensional. Okay, but here you can have m number of rows. Here you can have, in vectors you can have m number of rows. You can have m number of rows, and in vectors you have only one number. You have only one column. Okay, so you can have any number of, you can have m number of rows. For example, let me show you a vector u can be a, b, all the way down to the n. Okay, so it can be n-dimensional vector. So here this vector is two-dimensional vector. This vector is 2D vector. Okay, and geometrically I showed you by plotting on this x and y plane that this is the two-dimensional plot. Means first of all on x we go through x is the 2 units on the x-axis and the 4 units on the y-axis, and then we taken from the origin and that point. Okay, so this is a graph for u, but let's take an example 8. So this is our vector A, where you can store n-dimensional vector. It's not key that you should only have two-dimensional vector. You can have n-dimensional vector. Okay, but showing you geometrically, you can show three-dimensional vector geometrically. So you can just draw a straight line over here, and this is your z. Okay, so you can plot a three-dimensional vector. So you can plot it. For example, you take in k as a vector, and you can plot 2, 3, 2 onto this three-dimensional plane or the three-dimensional graph. But you can't plot your you cannot plot your four-dimensional or five-dimensional vector over here. So for geometrically understanding, I have just showed you how this vector looks like, but it's not a matter that you can only have a two-dimensional vector or only three-dimensional vector. You can have an n-dimensional vector, because scientists or researchers most care about your n-dimensional, your numerically rather than most of them. Well, of course, they care about geometrical as well, but I just showed you it's not possible for me to draw a four-dimensional and show you how we are going to plot. But geometrical intuition of a vectors are we can plot it like this. And for example, you have a 2, 4, 3. So here your k is 3 by 1. So first is what are the number of columns, which you usually denote as 3 number of columns, and you have only one row. Of course, in vectors you can only have one row. Okay. So here you have x component, here you have x component, here you have y component, and here 3 is your z component, which is in three-dimensional, and so on. Okay, so this is how you represent vectors. So the whole intuition about vectors. So I hope that you understood what I'm trying to convey you over here. Okay, so let's go further into understanding some more intuitively one last examples of a vectors to get us what it's trying to convey, and it's much better for us to understand. Okay, so I'm going to just draw an x and y plane over here. So I'm just going to draw an x and y plane like this, x and y, and I'm going to take 1, I'm going to take 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5. Okay, so this is our x and y plane. Now what I'm going to do is make it, for example, you want to plot the vector 1, 2. Okay, so here you go 1 unit or x's unit or 1 unit onto the x, because this is your x component, this is your x component, this is your x component. So you go on x unit over here. So we'll go till here. Okay, and then 2 units above. So this is your final vector v. Okay, this is a final vector v, and for denoting always the name of the vector should be in lowercase with 1 arrow above. So this indicates that it's a vector. Okay, so this is how you have to practice. So just try to plot a vector u where x component to be 4 by 4. Okay, and a vector can be n-dimensional. It can be 6, 7, 8, 9. It can be n-dimensional. So this is what the vectors are. Okay, so vectors are a two-polar array of numbers which we just shown you today. Okay, so now let's see how we can take out the length of a vector. So for example, you just draw this vector, so the v vector. So how can you take out the length of this vector? It's a good way to think about this. Okay, so what I'm going to do now is to just remove this and show you. So take another example. So I'm talking about how do you take out. So let's take one example that you have a vector u. You have a vector u where your x component is 4 and 4 by 4 and 4. Okay, so here you have a two-dimensional vector. So you can also write w with a member of R2. Okay, so this is the w, u is the member of two-dimensional real numbers. Okay, so this is your example. So what you want to do is let's plot the vector on this. Okay, so 4 by 4, I should see over here. So x unit of 4 over here and 4 units above. Okay, and then let's touch this point. I think it's wrong bit, but no problem. This is you. So how are you going to take out the length of this vector? This is a good question to ask to you. So for taking out the length of this vector, okay, so what you can do, here you can see that this is also 4 units. This is also 4 units, and this is also 4 units. So I'm just going to change the this is also 4 units, this is also 4 units. Okay, and you can see this forms a right triangle at a 90 degree. Okay, so this forms a right triangle. So you know this is you, so you know this, so which is 4 units, you know this, which is 4 units, and you know this axis which is here the base 4 units. So here height is 4 units and here base is 4 units. Can't you take out the hypotenuse, okay, or the vector length by using Pythagorean theorem? Of course you can take out. So you can use the Pythagorean theorem. You can use the Pythagorean theorem to take out the hypotenuse. So for taking out the hypotenuse, so the u square plus equals to b square plus h square. Okay, so you don't know u square, you know b square, which is 4, you know the h square, which is 4. Okay, so u square equals to 16 plus 16, which is equals to 32, and then u square equals to 32. Now you want to u equals to square root of 32, that is actually 5.65 and nearest 100. Okay, so this is your length of the vector. This is the length. 5.65 is the length of the vector. So the norm, you usually say the norm. Okay, so in linear algebra terms, so the norm of the vector, which is equivalent to length of vector, is equals to 5.65, which is your the length of the vector. Okay, so I hope that you understood what I'm trying to convey with geometric intuition over here. Okay, so what if we have n-dimensional vector? Okay, so what if we have n-dimensional vector? So we will see what if we have an n-dimensional vector, but let's go further. Let's understand a bit more intuition about the how many number of elements, what are the terminologies, and then we'll see how do we take out the length of an n-dimensional vector. Okay, so just as a notation or terminology, or to remember, so that everything is clear. The elements in a vectors are the dimension of the vectors. I'm not saying that elements, it's the number of elements in the vector is equivalent to the dimensions of your vector. Okay, so the number of elements here is numbers. Okay, so elements are usually the numbers, like 4 is an element, 4 is an element. Okay, the dimension of the vector. Okay, so this is the first terminology. So here you can see that you have vector u, which has a and b. So here it has two elements. So here is 2 elements. So here the vector u is a 2D vector. Is a 2D vector. Is a 2D vector, 2-dimensional vector. So you can plot it. If it is three-dimensional, you'll be having a bit difficulty in plotting in a three-dimensional plane, but you can plot it. If it is 4-dimensional, you cannot plot it on over here. Okay, so this is a number of elements are the other dimensions of your vector. Okay, the next terminology. Vectors can be n-dimensional. As I stated, the vectors can be n-dimensional vector. N-dimensional. So you can have the u vector as a, b, all the way down to the n. Okay, so here it can be n-dimensional vector. So as I stated, that it should not be only 2D vector, you can have an n-dimensional vector. Okay, so as I left you, hey, how you are going to take out? So you take out the length of this vector u by just using the Pythagorean theorem. But how you are going to take out the length of vector u, which is an n-dimensional? So how do you take out the length? So the norm of u, so I'm talking about this u, the norm of u is the square root of u1 squared plus u2 squared plus u3 squared all the way down to the un square. Okay, so it's just equals to that, nothing much deeper, which we have talked, or I ui square. Okay, so this is what I want to convey over here. This is what I want to convey. Okay, so you can actually think about it in that way, that you want to take for taking the length, you just square u1 square plus u2 square all the way around to the whatever the number of elements in your. Okay, so over here what we were doing, we can simply do like this. We can simply do over here, if you want to take out, you can simply use this. It's of course it's just related to some Pythagorean theorem. Okay, so over here you can just add a square root of your b square plus h square, which is b square is u1, h square is u2. Okay, means this one 4 and 4. Okay, and then you take out, so it's just equivalent whatever we had seen over here. Okay, so the same way we take out the dimension or the length of our vector u, okay, which is an n-dimensional vector. I hope that I understood till now whatever I taught. Okay, so let's see a bit more. So we have studied what are the vectors, how do we take out the length, how do we represent the vector. Vectors can be n-dimensional. So now let's see let's do some of the operations on our vector. Okay, so we will start doing the operations on our vector. So I'm just going to give a headline. Doing operations on vector. Okay, on vector. So it's a very great, it will just not too much hard, it's very easy. So the first operation which you want to do is addition of a vector. So how are we going to do the addition of a vector? So the first component is addition. So you are given, so let me state the problem. You are given the vector A, which is 2 by 2, and you are given the vector B, which is 4 by 4. Got it? What you want to do? You want to calculate vector C by adding A plus B. Means you want to calculate the vector C by taking out adding by summing this two vector. Okay, so how are we going to sum this 2 by 2 and 4 by 4? Means, so what you can do the element wise. You can do the element wise. So you can, what you can do, C will be equals to 2 plus 4 and 2 plus 4, 2 plus 4, 2 plus 4, and then also 2 plus 4. Okay, so two element wise addition, so it will be nothing but equals to 6 by 6. Okay, where you add the one, when you add the vector 2 by 1 plus 2 by 1, 2 times 1, which is the dimension of the resulting vector will be also 2 by 1. Okay, so what do you do? You 2 by 1, which is the dimension of your A vector, and then 2 times 1, where there is 2 elements and the one column, so that is also B, and then the resulting vector is 2 times 1. Okay, so it is the 6 by 6. So you calculate C to be 6, where your x component is 6 and y component is 6, so the 6 is your resulting vector. So your resulting vector C is a two-dimensional vector. Okay, some of the things which I want to highlight is your dimensions of your both the vector, which is A and B, should match. Okay, if for example if your A vector is 2 by 2 and your V vector is 4, 4, 6, then you try to add it, the resulting vector will be undefined. Okay, so your dimensions of the addition of a vector should match. Okay, otherwise it is undefined operation. Okay, so this is what I'm going to convey over here. So let's see how you add the vectors, how you add the vectors geometrically. So we've seen the numerically how we add the vectors. So let's see how you add the vectors geometrically. Okay, so let's do something. Is we will do now some geometrical, because people tend to understand more geometrically rather than numerically. Okay, so we'll understand geometrically. So here I'm going to draw one x and y plane like this. Okay, x and y plane. Okay, so let's see that your vector a, that this is your vector a. So let's keep let's make it total. Okay, so this is your vector a, and this is your vector b. This is your vector b. Okay, this is your vector v, and this is your vector a. You want to add this two vector, geometrically speaking. You want to add this vector a plus vector b. Okay, you want to add this. So when you do this geometrically, okay, so what you want to do, you're going to take this vector a. So I'm just going to say, you want to take this vector a, and put the tail of this vector onto the top of the vector b. Okay, you put the tail of this vector onto the top of the vector b. Okay, and then you put this one onto the head of this. Okay, what you want to do is take this vector, whatever the length, okay, whatever may be the length, you just put it like this. I'm not drawing correct, but no problem in that. So the length of this should be same as whatever you are doing. You're just taking this a vector and putting it over here. Okay, you're just taking this vector a and putting this tail onto the head, and then you are putting it over here. And then what you do, you take this vector b, and put the tail onto the top of a, and put and just match this with this. Okay, so you take a vector b and then you just put it like this. I think it's not correct too much, but this is how you are going to do. You first to take the vector a, put it on the tail of that onto the head of b, and then you, whatever the length, you just put that over here, and then you take this and that, and then put this tail onto the head of this, and then you match the heads. Okay, and then the head, the resulting vector. So the resulting vector, I'm just going to take this. So you just take, this will be your resulting vector, where blue one indicates a plus b, a vector plus b vector. Okay, so this is how you add the vector geometrically, and then it makes sense as well. Okay, if it isn't, don't worry, let's see one more example to make more clarity. Okay, so over here, let's plot. So this is how you just take this and then you draw, and then you are done with this, and then you attach here's the tail on the origin. Okay, and then you attach, and then you draw a straight line on like that. Okay, so this is called the parallelogram method. Okay, so this is called the parallelogram. This is called the parallelogram method for showing the geometrically. Let's see triangle method. That will make more even sense. Okay, so that will make more even sense. So here is your vector a, and here is your vector v. Okay, here is your vector v. You want to add this up. So what do? You simply what you don't do anything extra. You simply attach this to make a triangle. Like this, and then this resulting vector is your addition of the two vectors. Okay, so the resulting vector, which I'm going to highlight with this, is your resulting vector, and this is how you do the addition, geometrically speaking. Okay, so this is called the triangle method. This is called the triangle method for addition of two vectors. Okay, try to play with it a much more better way, so that it could make sense to you as well. Okay, so try to play with it, try to draw some diagrams of it, and then try to just little bit juggle with it, and then you will better understanding rather than just seeing. Okay, so you will be getting some assignments on this as well, so you can approach the assignments in geometrically speaking. Okay, so let's see one more operations, which is the vector subtraction. Okay, so I'm just going to show you vector subtraction. So what this vector subtraction will do, so let's say you want to subtract vector u minus vector v. Okay, so that will be simply, we can frame it as an addition of a vector u plus minus v. Okay, so then it will be much easier to show it geometrically speaking. Okay, got it. So what I'm going to say over here is, you have a vector, so you can simply do like this for showing it geometrically. Now it will be very easy to show it geometrically like this by adding of the vector. Okay, so what you do, you just make this, and then just for showing it geometrically speaking. Okay, so for example, you have a vector u which is 2 by 3, and we have a vector and you have vector v which is 1 by 1 subtracted. So the resulting vector will be 2 minus 1 and 3 minus 1. That will be nothing but equals to 2. Okay, it's 1 2. Okay, so x component, y component. So this is your resulting vector. Okay, so let's see how it looks like. So it would make more sense to you as well. Okay, so let's assume 1 2 3. Okay, 1 1. Okay, so let's plot the u vector. So I'm just going to plot the u vector, which is 2 3. Okay, so okay, it's 2 now, so it's 2 3. So okay, I think I done wrong. It's 2 3. So just going to, okay, so this is your vector u. So this is your vector u, this is your vector u, and you want to plot the vector v. So this is your vector v, this is your vector v. Okay, this is your vector v, and the resulting vector is 1 by 2. Okay, so this is your resulting vector, which is your after subtracting. Okay, so after you subtract this from this, the vector v from u. Okay, so that will be your resulting vector. That makes sense geometrically speaking as well. Okay, so this is how you do the vector subtraction geometrically. If you don't understand geometrical, it's no worries, but it's not more than tough, which is very easy, not more than tough. Okay, so this is your vector addition and vector subtraction. So let's see the last concept which I want to make you familiar with is vector scalar multiplication. Vector scalar multiplication. So I'm just, but first of all, what is in scalar? What is in scalar? So scalars are given, scalars are just constant or numbers. For example, 4 is in scalar, 2 is in scalar, 1 is in scalar, or anything. Okay, so this is, scalars are just constant. Okay, so it's a number, but in algebra or linear algebra term, we call it as a scalar. Okay, so it plays an important role when we study about linear combinations or linear transformations. So it plays a very important role. So this is, so what if you multiply a scalar, for example, you want to multiply a scalar a times the vector u, times the vector u. So let's take the you take the scalar a to be 2 and the vector u as a 2 by 2. Okay, so you multiply 2 times 2 by 2, so it 2 by 2, so it do the element wise product. 2 times 2, 4 by 4, that will be equals to 2 times 1. Okay, so the dimensions will be 2 times 1. That is simply the vector scalar multiplication. So what it actually does, in geometrically speaking, it stretches the vector, so it doubles the vector. So for example, you have this vector 2 by 2. Okay, and then you multiply it with 2, then it will be doubled, then it will be stretched. Okay, then it will be stretched, means transformed the vector. Okay, or stretched the vector by following the linear structure. You stretched the vector like this. So this was your initial vector. So after applying the 8 times the vector u, that is stretched, which is your final vector after applying your the scalar and vector multiplication. Okay, so this is your stretched vector. So please ensure that it's stretched. So before applying it was u, and after applying this doubled. Okay, so this is the vector scalar multiplication, and the reason why we are studying these, because it helps to build a very good foundation. The stretching, the geometrical speaking, this helps a very good foundation when we talk about transformations, combinations, eigenvalues, eigenvectors. These plays an important role in that. So this was so we have seen a bit about vector and scalar multiplication. The last two concepts which I want to introduce to you is the unit vectors, and the zero vector. Okay, so the unit vector. So unit vector is any vector with a length 1. So the definition states the unit vector is any vector. For example, any vector with length 1, whose length is 1, that's a unit vector. Okay, what is a zeros vector? Zeros vector is whose length is 0, whose length is 0. Okay, so that is the zero vector. You usually denote the zeros vector in very bold way. Okay, that is the zero vector, and that is the unit vector and vector. Okay, so these are the two very basic terminology which you need to know about. Okay, so we have seen a lot about the vectors in this video. So I hope that you understood everything whatever we had to have a talk on this. So just to make sure that everyone understood this, so what you actually do, so let me show you one more example of that. So for example, you have this, okay, so you have this vector A, and you have this vector, and you have this vector B. Okay, so what do you do for addition of these two vectors? You can just make this a triangle. Okay, but let's approach within using a parallelogram method. Okay, so what do? You take this vector and put on this tail or the head, and then you just draw a parallel to this, and you take this, and then you take this, and then you join the, and this A plus B is a resulting vector. Okay, so this is how you go further into approaching these stuffs, and I hope, and maybe you can solve it using a triangle method to show you how it works geometrically speaking. Okay, so I hope that you understood whatever I'm trying to convey you over here. Okay, so I hope that you understood geometric intuition, the triangle method, what are unit, what are zeros, what are scalars, what are vectors, and etc. Okay, so I think that we are done with this lecture on its 30 minutes. So I hope that you understood vectors, what are vectors. So you can find the notes of this, the lecture notes, maybe all of these in the description box below. Or in LMS, and the assignments will be also related to this, will be released at the end of this week. And I hope, and I really hope that you understood this, and if not, please feel free to ask the question in the description down box below or in our Discord server. We will be very happy to answer your questions. The next announcement is, you can simply the next lecture will be based on matrices. Okay, so we'll talk about a bit about matrices. Okay, and then we'll talk about, after completing a bit of matrices, we'll talk about linear combinations, then linear transformations. Okay, so we'll be studying these things, so don't worry, we'll go at very slow pace and very easy way. Okay, so thanks for seeing this video. I'll be catching up to you in the next video. Till then, bye bye and have a good day. Hey everyone, in this lecture we'll be talking about matrices. In our previous lecture we talked about vectors, and I really hope that you understood about vectors. I know these are very easy concept for you, but let me tell you, these sets a foundation when we study about combinations or transformations and other stuff. So that's how we are only focusing on this. So from this video we'll be stepping up a bit difficult mode from matrices, and then we're talking about some matrices operations, and then we're talking about some properties of matrices multiplication, and then I will just end up with this video with matrix vector products, and then I will show you the wide results at the end of the video, that the linear combination of the column vector. Okay, so we'll be talking about I will just introducing a notion of a linear combination, so that in the next video is totally based upon your linear combination. So that's why I will just give you a taste of linear combination at the end of the video. So let's get started with matrices. So today we'll be talking about matrices. So let's recall a bit about vectors. So vectors are n-dimensional, where it can have n and where it can have n number of rows but only one column. Okay, so we were having this, so it can have 1, 2 all the way around to the n, and here this is n times 1. So the shape of this vector v, is n times 1, and it can have n number of rows and 1 number of a column, and this is a vector. Specifically, we can call this as a column vector. Okay, so we specifically call this as a column vector. Okay, so it is given a new name, and when I will introduce you a notion of a matrices, then we'll use it extensively in the later videos. But this is also called a column vector, and for example, your vector can be in this 1, 2, 3 all the way down to the end. Okay, so this is called the row vector. Okay, so this is called the row vector. So these are the two things which I want to introduce to you. So we'll be covering this again just after we complete the matrices. Okay, so let's start with what are matrices. So matrices are a set of numbers or a multidimensional ladder. Okay, where it can have n number of rows and m number of columns. It can have a multiple columns and multiple rows. Okay, so in vectors we were having only n rows and 1 column, which is the example will be 1, 2, 3. Okay, so this is an example of a vector v. Okay, so the matrices can have n number of rows as usual, but m number of columns. But can have m number of columns. So as an example, we can make that matrix A equals to 1, 2, 3. So 1 column, 2, 3, 4 second column, 3, 4, 6 third column. So it can have m number of columns and n number of rows. Okay. So here the shape of this A is 3 by 3. Where 3 is number of rows, and this one is number of columns. Okay, so over here this first indicates the 3 by 3 matrix. So this is the example is 3 by 3 matrix. So the formal definition of a matrix is matrices are a set of numbers. Okay, matrices are a set of numbers arranged in a rows and a columns, which is n rows and n columns, so to form a rectangular array. Okay, so here it forms the rectangular array. In other words, matrices can have n number of columns and m number of rows. Okay, so let me write a formal definition of matrices over here. So the definition, which is just let me write a good definition of this so that everyone can define what a matrix is. So here's the definition of a matrix, where it is arranged in a rows and a column. So I'm going to give the name of a rows. I'm going to give the name of a rows to n and columns to m, so to form a rectangular array. So for example, we can have here it can have A, B, C, D, E, F, G, H, I. Okay, so it can have any. Here we have this is an example of 3 by 3 matrix where it have 1, 2, 3 rows and 1, 2, 3 columns. Okay, or we can say in other words it can have n number of rows and n number of columns. Okay, so I'm saying n is for number of rows, and m is for number of columns. All those are in small letters. Okay, so this is your formal definition of a matrices, and the lecture notes is in the description box below. Please go there and assess your lecture notes for you to just revise in the meantime. Okay, so just let's write a formal notation of how the matrices are, so that it is easily interpretable. So I'm going to make a matrix A. where I'm going to make a matrix A, where I'm going to make this A 1 1. So how do we assess the first element? So here it is in first row and first column. So this A is in first row and first column. So that's why I've written I and Z. Okay, so A, I and Z indicates I, what is the row number, and G, Z, what is the column number. So for example, for assessing the elements, so over here you have this matrix, we have this matrix A, and what you're going to do is assess 3. So how are you going to assess? So the formal assessing things is A, I, J, so A, I, J, where I indicates the row number and J indicates the column number. So, okay, so over here you can see that 3 is on we start with 1 2 3, okay, not from 0. So 2 A2 means A2 means the row number is 2 and the column number is also 2. Column number is 2, that is nothing but equals to 3. Okay, so here's how you assess. So first of all, you write the row number, then you write the column number. So I indicates the row number and J indicates the column number. Okay, so I hope that you understood what I'm trying to say. So it is telling, and this is the first element where it's first row and first column, then it is first row and second column, then all the way down to the first row and nth column, okay, or m column, okay. And over here it can have 8 2 1, okay, so second row first column, second row second column, all the way down to the A 2 M and second row M column. Okay, so this can be A 3 1, A 3 2, A 3 M, okay, all the way down to the A N 1, so N is number of rows, or A N 2, all the way down to the A N M. Okay, so here it is the formal notation or a definition which we can write over here, which is the formal notation for writing. So this is a matrix. Okay, so here's how I developed this. So it can have m number of rows, n number of rows. So 1, 2, 3, 4, all the way down to the n, which is n number of rows, and it can have only m number of columns. Okay, so it can have only m number of columns. So this is your formal definition which I have given to you for matrices. Okay, so I hope that you understood. Now what I'm going to talk about is I introduce the notion of a row vector or a column vector. Is it? So I introduce you. So can you just go and just type me what is a row vector and what is a column vector? So let's take one example. Is you have a matrix, but just one thing, that the vectors are a subset of matrices. Okay, so the vectors are n times 1 matrix or n times 1 matrices. Okay, so the vectors are a subset of matrices. Okay, so if you extract this row, so this is just a vector. Okay, so what I'm going to do now is going to just to make a matrix A, which contains, just don't relate. I'm just taking examples. You have a vector A. I'm going to store 1, 2, 3, 4, 5, 6. Okay, so this is my 2 by 3 matrix. Okay, so what you do, you take the first row, okay, and then store it in another C. Okay, that is 1, 2, 3. Okay, so what is C over here? C is called the matrix with one row. Okay, the matrix with one row is called the row vector. This is called the row vector. The matrix which has only one row is called row vector, and the matrix with only one column, which is nothing but called a column vector. Okay, so if we take this 1 by 4, okay, in D, that is 1 by 4, it has only one column, that is nothing but equals to column vector, which is nothing but is column vector. Okay, I hope that you are understanding what I'm trying to tell over here. So these are the size of a matrix. Over here, size of a matrix, where we have a row vector. And what is row vector? Row vector are nothing but the matrix with one row. is called the row vector, and the matrices with one column is called the column vector. Okay, so if you take one example, so just assume that this is your first of all row vector, sorry, column vector, because you have column vector. So this one is a column vector, which is v1. So v1 over here is a column vector. Okay, so if we take this one, so here you have only one row, so that is v2, which is your row vector. Okay, so this is what the notion of a row vector and column vector means, and I really hope that you understood about this. Okay, so if not, please feel free to ask your question below. Where you're stuck, please use Discord server or whatever the doubt support which is provided to you, so that you can get most out of this course. And if you need any guidance for absolutely free, please feel free to reach out to me via email, Discord, comment. We can get on a meet to help you solve the doubts. It's for okay, cool. So we have seen what some matrices are. So just want to recapitulate everything. So matrices are a set of numbers arranged in a number of rows and number of columns to form a rectangular array where it can have an n number of rows and m for a mango number of columns. Okay. So the notation for the definition of geometrically over here is the A. So I have made this as an example to showcase you, and we have seen some of the matrix size where the terminology, which is where the matrix has only one row, that's the row vector, and where the matrix has only one column, that is a column vector. Okay, so I hope that you understood what I'm trying to convey over here. Cool. So now let's talk about some of the operations, because in previous video we talked about vectors and then operations. So the same way I'm going to talk about operations on matrices. Okay, so operations on matrices. Just going to show it to you. Operations. I think my handwriting is not good too much. No problem. Operations on matrices. Okay, so you're going to do the operations on matrices. So the first operation which you're going to do is matrix and a scalar multiplication. Okay, so what I'm going to do is matrix scalar multiplication. Okay, not a big deal. It's very easy to understand. Okay, so assume that you have a matrix A. You have a matrix A 10, 6, 4, 3, which is your nothing but a 2 by 2 matrix. Okay, 2 rows and 2 columns. Okay, and you have a scalar. A, which is nothing but 2. Okay, so you're given these two. Now what you're going to do is you're going to multiply A. Okay, so you're going to multiply a scalar with a matrix, which is nothing but 2 times 10, 6, 4, 3. Okay, that is, so what will be the result? Please feel free to pause this video. So what you're going to do is multiplying a scalar with a 2 by 2 matrix. So what will be the result? Anyone, please in the comment. Okay, how do you tell? Okay, no problem. But please feel free to ask, say in the comment box. I will be very happy to see that if you're till here. So the answer of this is, first of all, what do? You simply do the element-wise product with this scalar. Okay, so 2 times 10, which is nothing but 20, 2 times 6, which is nothing but 12, 2 times 4, what it is, 9, no, it's 8, okay, 2 times 3, which is nothing but 6, okay, so the resulting matrix is 2 times 2 matrix. So what do? You transform, or not transform, I would say, you just multiply a scalar with a matrix, and then you get a 2 by 2 matrix, which is the same size of your A. Okay, so 2 times 2 equals to 2 times 2, which results when you multiply with any scalar. Okay, so what it does is simply do the element-wise product. Okay, so the formal notation for this is you multiply C with A. Okay, and A have I and J row. Okay, so what it will do, it will simply do the element wise A, C times Aij. That is nothing but what it will do. First of all, it will so in more notational terms, it will just for example, you have a vector, you have a scalar A, and you multiply with C, D, E, F. Okay, so what do? You simply A times C, A times D, A times E, and A times F. Okay, so this will be the form. This will be the thing, and then you will be getting some values 2 by 2. Okay, which will be your values. Okay, so the same. This is what it is doing. So this is your formal definition of your matrix vector multiplication. Sorry, scalar matrix multiplication. And I really hope that you understood this. Let's go on to the next operation, which we're going to see. Let's go on to the next operation, which we're going to see is addition of matrices. Okay, so the next operation which we are going to cover is addition of matrices. Okay, additions of matrices. So let's assume. So you are given a matrix A. You are given a matrix A, which is 1, 3, 1, 1, 0, 0. Okay, and you are given matrix B. Okay, and matrices are always written in a capital letters. Make sure, and the vectors are always in small letters. Okay, with 1 over here, and the scalars are also in like this. Okay, so that's B is 0, 0, 5. 7, 5, 0. Okay, so what you're going to do, you're going to add these two matrices A plus B. You're going to add these two matrices. So this is the operations which you want to do. This is the operation which you want to perform. So how are you going to perform this operation? How are you going to perform this operation? So for performing this operation, for performing this operation, you will just what you will do. You want to just have this 1, 3, 1, 1, 0, 0 plus 0, 0, 5, 7, 5, 0. What you will do? You will nothing but 1 plus 0 element wise sum. Okay, in the scalar you are doing, so you will do the same. 1 plus 0, 3 plus 0, 1 plus 5. Okay, element wise sum. Okay, 1 plus 7, 0 plus 5, 0 plus 0. Okay, so this is what you do, and then you will be getting your answer, which is 1, 3, 6, and then you will be getting 8, 5, 0. That is the resulting matrix. Okay, which is also 3 by 3 matrix. Okay, so what do? You simply do this, and you are getting a 3 by 3 matrix. Okay, so what you do, you just added a 3 by 3 matrix, and the resulting matrix is also 3 by 3. Okay, so this is how you do the addition of a matrix, and the formal definition for this, which I can state. So because definition is very important for fundamentals, for making your fundamentals strong. Okay, so the definition is you're given a matrix A, which can have A, B, C, D, E, F. Okay, that is nothing, and your B is also some kind of K, G, I, H, O, P. Okay, so to add these two, so what you will do? A plus K, B plus G, C plus I, D plus H, E plus O, and F plus P. That will be nothing but equals to 3 by 3 matrix. Okay, so I have just taken this example. Your matrix can have n dimensional. Your matrix can have any number of rows and any number of columns, but there are some constraints which you need to. There are some properties like dimension property which you have to take care while adding the matrices. Okay, so it can have ABC. It can have a 10 by 10 matrix, the size of the matrix, and then you are adding the 10 by 10 matrix with another 10 by 10 matrix, and that will be resulting in another 10 by 10 matrix. Okay, so that is the thing. So some of the property which I want to highlight, which you all had to focus on. So some of the properties of a very simple property, that commutative property. So addition of a matrix is commutative. and all of this is written in your notes. Please feel free to see from there if you wanted to just revise it up, okay, in future. But I would highly recommend to complete this video. B plus A. So you have a matrix A, you have a matrix B, you can do B plus A. Okay. The next thing is associative property. Your addition of a matrices are associative as well. Okay. So associative property. I'm not writing a lot of properties over here, but the one who are important I'm writing over here. A plus B plus C, which is nothing but equals to A plus B plus C, and all of these can be proved very easy. The proof is very easy, not a hard. Please feel free to search on internet about the proof. It is very easy. Associative, commutative, it's the proof are available on internet. Okay. So the last thing the first property is commutative, the second is associative, the last one is dimension property. The dimensions shall be seen. The dimensions of your the two matrices should be same. The matrices should be same. The matrices should be same. Okay, the dimensions. Okay, if it is not, then it will be undefined. Your operations will be undefined. Okay, cool. So now we have talked about one of the operation, which is addition of a matrix, and I really hope that you understood addition. You understood a scalar. But one thing which I'm going to spend some 2 minutes talking about is, you may be thinking, do we really need to know about these stuffs? So I would say, yeah, you need to know about. Although you don't need to just worry about how I'm going to code it. You can actually develop it from very scratch. Not a big deal. But there are some libraries like NumPy, which will be in this course, we'll be using in this course, or PyTorch. I'll be using their library for scientific computation, for addition of a matrix, for multiplication of a matrix, which they handle, they are very efficient. Okay, because in real world your matrices are not 3 by 3 matrix. They are billions. The size is millions. Okay, millions by millions. So they are very large. So matrix multiplication with your own for loops are very time taken. Okay, so that's a big deal. Okay, so your time complexity will increase as your input size increases. Okay, so that's a big deal. So we are learning this to understand the inner workings of our functions, so that we can know how our algorithm is doing and how everything is working behind, so that it becomes very easy to debug something, or to get some error, or to have very good or decent knowledge of what your code is performing. Okay, cool. So addition of a matrix is also done. Now you can do the same with subtraction of a matrices. Please try it out by your own. The next thing which I'm going to spend some time talking about is matrix multiplication. Okay, bit more. I'll spend some time talking on this. Okay. So the next thing which I'm going to talk about is matrix multiplication. Matrix multiplication. Okay. So this is your next operation, which is one of the most important. What do you say? The operations which you need to learn. Okay. So you're given a matrix A. I'm going to take very easy example. 1, 7, 2, 4. Okay, and you're given a matrix B. Which is 3, 5, 3, 2. Okay. Now you need to Now what do you need to do? You want to multiply matrix A with matrix B. Okay. So how do you do? You may be thinking, here is 2 by 2, here is 2 by 2, here is 2 by 2. 1 times 3, 7 times 3, 2 times 5. That's not how you do. Okay, so the matrix multiplication, the way you do is like this. You take the first row of that A matrix, I'm going to change my pen. You take the first row of that A matrix and multiply with the first column of the B matrix. Multiply with the first column of the B matrix. Okay. So here's how you do. So resulting vector matrix C will be 1 times 3. Okay. Plus, I'm taking the dot product of your of your row vector times the column vector. So what you are actually doing is taking out the dot product, which you'll see in our later videos. Don't worry about that. Dot product of this is your, because if you see, this is your, it has only one row. Okay, so of a vector, of a row vector and column vector. So this is your column vector where it has only one column. So specifically you are taking out the dot product of a row vector and a column vector. What is dot product? So dot product is element wise. So what you do, you simply multiply and add it up. Element wise adding and add it up. Okay, so over here what are you going to do? You 1 times 3 and 7 times 5. 1 times 3, 7 times 5, and then you will add it. Okay, now you take this again this row with this row vector and multiply with this column vector. So that will be nothing but equals to 1 times 3 plus 7 times 2. Okay, now what do you do? You have this taking of the dot product of row vector and the second column vector, which is v2. Okay, now what do? You go further into this, the second row vector, which is 2 by 4, and then you do the same. 2 times 3 dot product of the 2, 4, which is called row vector with the column vector. Okay, 4 times 5. Okay, and then 2 times 3, 4 times 5, 2 times 3, 2 times 2. Okay, so 2 times 3 plus 4 times 2. Okay, that will be nothing but equals to C, which is nothing but equals to 1 times 3, which will be how much? 1 times 3, it should be 3 plus 5, 35. Okay, 1 times 3, 3 plus 14, 2 times 3, 6 plus 20, which is 26. 2 times 3, 6 plus 8, which is nothing but 14. Okay, cool. So this is your resulting, and then what do? You simply make your 38, 17, 26, 14 will be your resulting vector, which is 2 by 2 matrix, which is the 2 by 2 matrix. Okay, so when you multiply with this, you will be getting your favorite, after multiplication of a matrix, this is your answer of your particular question. Got it? And I really hope that you are understanding whatever I'm trying to say. But it can have n dimensional, but some properties are there. Okay, so let's visit the property. I'm just going to constrain that dimension property is very important in this. So what dimension should match to be, so that the matrix multiplication is not undefined. Okay, so the properties of a matrix multiplication. So the first property which I'm going to talk about, the first property is, for example, you are given a matrix A, B and C. So these are 3 matrices which are n by n matrix, where you have n by n matrix. Okay, so where you have n rows and n columns. Okay, so the first thing which holds is commutative property of multiplication of this multiplication does not hold. Okay, so matrix multiplication is not commutative. Is not. Okay, so when you multiply AB, BA, which will be totally wrong. It can be proved. It can prove very easily. Then the next property, associative property of a matrix multiplication is there. Okay, so associative property is there. Okay, so A, B plus C, which is nothing but A. Okay, so I think I have written for distributive. I have written for A, B, C, which is nothing but equals to A, B, C. Okay, it can prove rigorously, and of course you are multiplying it over here. Okay, it can prove very easily. It is distributive property. It is also distributive property. So what are you going to do? A, B plus C. That will be A, B plus AC. And you can prove these. You can prove this
very easily, which can be found on internet. The next thing is the most important, dimension property. Dimension property. So the dimension property is you can have m number of rows. You can have m number of rows. You can have any number of rows, but an n number of columns. Okay, this is for the dimension of a matrix A. Your dimension of a matrix B should be your number of rows should be same as number of columns in that matrix A. Okay, times k, any number of okay, so your resulting will be m times k. Okay, so it makes sense as well. If you can have m number of rows and a matrix, but you can have n number of columns. Okay, but with here you can have only n number of columns, n number of rows. Okay, so here you have a 2 by 2, so here it has 2, and the resulting will be 2 by 2 vector, matrix. Okay, so that the resulting size will be this. Okay, so this is your dimension property of your matrix multiplication. Cool. So we have talked a lot about matrix, and you are seeing that you are going, and you are seeing that we are going little bit up. So the last thing which I will end this video, which I promised you, is talking about matrix vector product. Is a matrix vector multiplication. Okay. So what I'm going to talk about is matrix vector multiplication. Okay. So let's do that then. So let's do that. So you have a matrix A. Which is nothing but. So I'm just going to define a rigorous, very definition of matrix vector product. So I'm just going to write it very fast. A11, A12, all the way down to the A1n, and A12, A22, A2n, AM1, which is N1. Okay. Okay, N2. Okay. That will be A and M. Okay. So this is your matrix. This is your matrix. So it is having m number of columns and n number of rows. Okay. This is your matrix A, and you want to multiply with a vector, a column, a column vector. Okay, x2, xm, xn. Okay, so to do the multiplication of it. So how do we do it? How will you do it? So you want to multiply a matrix which is A, which is m times n matrix, times the vector a scalar, vector a column vector x, which will be, the definition will be. So what will be the answer of this? So how will you perform the operations? So for performing the operations, this is nothing but equals to A11 x1. So what you are actually doing, you can take this A11, okay, and you multiply this with this, multiply this with this. Okay, so what you are actually doing, you are multiplying the column vector, row vector to the column vector, okay, element wise, and adding it up. Okay, so the dot product between your row vector and a column vector and adding it up. Okay, so A11 plus, we are adding plus over here, see, A12 x2 plus A13 x3 all the way down to the A1m times xm. Okay, then you do the same, A12 x1 plus A plus A2 all the way down to the A2 n. Okay, so you're multiplying with x, whatever the x. So what you are actually doing, you're taking this column vector, so a row vector, and multiplying with this. So you are taking on the dot product between, taking on the dot product and giving your answer. That's it. Okay, taking out the dot product between the row vector and the column vector. So let's see with one of the example.
So it would make more sense. So here you have minus 3, 0, 3, 2, 1, 7, minus 1, 9. Okay, and you have a vector, column vector, 2, minus 3, 4, 1. Okay, so what will be the output? So the answer will be minus 3 times 2. So you're taking this and multiplying with this. Okay, minus 3 times 2 plus 0 times 3. Okay, minus 3 is minus, plus 3 times 4 plus 2 times 1. It's 1. Okay, now you go further. 1 times 2 plus 7 times minus 3 plus minus 1 times 4 plus 9 times 1. That will be nothing but equals to, after you added everything, after calculating, okay, that will be A and B, which is 2 by 1 vector, so which is a column vector, which is 2 by 1. So after doing the matrix vector, you transform, what you do, you have this R4, where a 4-dimensional vector, you transform it to D. After using this vector, using this matrix A, you transform it into a A and B, which is the 2 by 1. Okay, which is from R4 to R2. Okay, so here you transform using this matrix A. So we'll see in our further videos that matrix multiplication are a linear transformation. Okay, so we'll see in our later videos. But now, as of now, I hope that you understood the matrix vector product. Okay, so in the next video, what I'll be showing you a wired thing over here, or not a wired thing, a very useful thing over here, is the linear combination using the help of matrix vector product. So I will take an example of matrix vector product as a linear combination of so that it would make more sense, and then we'll complete the linear combination in our next video, and then we'll end up so we'll be completing, and then we're talking about the linear transformation. I really hope that you understood this. I'll be catching up you in the next video. Till then, bye bye, have a great day, and please, and one more thing, the attendance is, you have to mark your attendance, so please feel free to do so. Bye bye, have a great day. Okay, so welcome to this lecture. In this lecture, we'll be discussing about linear combination of a vector. So this is one of the most important concept, as you will go further and will understand. Okay, so it sets up a very strong fundamentals to mathematically understand or to see the deep learning or machine learning into a linear algebra point of view. So this is one of the most important concepts which we'll focus on. So in this video, we'll talk about that specifically. So in this video, I'll be giving you some definition of linear combination, and then I will giving you some examples, and then we're talking about a matrix vector product as a linear combination, because in previous video at last we talked about matrix vector product. So that's why we are in this video, we'll be talking about as an example, taking that as an example for linear combination of our matrix vector product. Okay, so the definition states, so the definition of a linear combination states, so let's do something. Let's start with an example. An example states that you have. So first example that I want to take is, you have a scalar, and you multiply with the some vector u, okay, and then you have plus 2 with some vector v, okay, and that will be some resulting vector, which is just the scale version of u and v, which is nothing but for example d. Okay, so that is the resulting vector of our after applying of, first of all we added it up, multiplied and added the vector. Okay, so that will be the resulting vector. So the resulting vector is a linear combination of a vector u and a v. Okay, so again listen me, that what we have taken this example, and in this example we have one scalar 3, and then we multiply with a vector u. So for example, we can have vector u to be 2 by 2. So when you multiply 3 times, okay, that will be nothing but 3 6, that will be the 6, okay, 6, okay, plus you have some vector v, it is nothing but 4, okay. So 2 times 4, so when you multiply or do the scalar vector multiplication, that will be simply element wise product. So 2 times 4, which is 8, and 2 times 4, which is 8, okay. So when you now you add 8 by 8, okay, so that will be 8 by 8, that will be nothing but 8 by 8, okay. So the resulting vector will be 14 by 14, okay. So that the resulting vector will be 14 by 14, which is your d, which is your vector d. So the vector d is a linear combination of your vector u, and of your vector v, okay. So the resulting vector is a linear combination of these two vector, which is u and v. So I hope that you are understanding what I'm trying to tell. And this 14 is just the 6 plus 8, which is, okay. So this is the d is a resulting vector after you do. So what you specifically done is multiply, there is some scalar, so you are given any number of a vector. So I'm writing the definition. So what you specifically done, you're given any number of vectors, you're given any number of vectors, and the linear combination of the vectors. So you are given any number of vector, but the linear combination of this vector means these vectors are simply the result when we multiply each vector by a scalar and add the vectors. So how you get the linear combination is you are given any number of vectors, okay? So you are given any numbers of vectors, and the linear combination of those vectors, the given vectors, is simply the result. In this case, the result of when you multiply each vector, which is you are given u and v over here. So when you multiply each vector by a given scalar, which in this case is 3 and 2, okay, and add them up, that the resulting vector is a linear combination of those vectors, okay. So the formal notation which I can write is, you are given a vector a, you are given a vector b, you are given a vector c, you are given a vector d, okay. So you need to find out the linear combination of these vectors. So the linear combination of these vectors will be simply when you multiply with some scalar, okay, with some scalar. So I'm just going to write it a, okay. So this so let me write a different name of this. So I will just, so your given vectors are I think v, u, g, okay. So these three are your given vector, okay. Now what you do, you simply multiply with some scalar a, okay. So what will be the, so we want to ask what will be the linear combination of these vectors. So what is linear combinations? So the definition states that a linear combination is the result when you multiply the given vectors by some scalar and add the vector, okay. So that is the resulting vector. So what you do, simply multiply a scalar with a vector plus b with the u vector plus c with the z vector. The resulting vector d, which will be nothing but your linear combination of v, u, and g. Okay, so that will be the linear combination. So let's see more of the example to get comfortable with this, so that you could get a good feeling. Okay, this is the linear combination. Okay, so another example can be, you can have a vector u, and you can have a vector v. So what do? It can be like this: any number -1 times u vector, which is a scalar, plus 0v. The answer, whatever the resulting vector will be the linear combination of these two vectors, which are the given vectors. Okay, so it can be fraction as well. For the scalars can be fraction as well. 517 by 11. It can be multiplied with some vector u, and 195 by 2 with some vector v. The resulting vector will be your linear combination of these two vectors, which is u and which is v. Okay, so whatever the resulting vector is will be the linear combination of u and v vector. Okay, so let's take one formal example so that we could understand this much better. Okay, so one formal example of linear combination. Say you are given a vector u, which is two-dimensional vector, which is a 2 by 1 vector, or we can say it's a column vector, -5 by 0, because column vector is what the vector, the matrices with only one column, and over here we have only one column, so that's why it's called a column vector. So that's why we are telling it to the column vector. Please see the previous video to help you understand much more better way. Okay, and you have a vector v, which is 0, 2. Okay, so you are given a vector u and v. Okay, this is also a column vector, this is also a column vector. So what you want to do is to take out the linear combination of these two vector, and the linear combination can be, we can multiply this u vector. So what we can do, we can multiply any scalar with this u vector plus any scalar with this v vector. We'll be getting the linear combination of these two vectors. So let's take an example. So let's take one example. You multiply 1 with -50. Okay, -50 plus you multiply, you have a scalar 1 which is in place of v, and you have 0 by 0, 2. Okay, that is your vv, and the resulting vector, which will be nothing but -5 by 2. Okay, and this is the linear combination of these two vectors. And you can go ahead, you can try it at different scalars, and the same will be. So you try it first. You can try different scalar with 2, with a -50 plus 2. It can be any number, 0, 2. That will be nothing but, when you do this, 2, which is -10, and then -10, 0 plus 0, 4. That will be nothing but equals to -10, 4. So this is -10, 4 is a linear combination of these two vectors. Yeah, you heard me correct. This is the linear combination of these two vectors, as well as this is the linear combination of these two vectors. You heard me correct. It can be, you can multiply with some scalar 4, okay, with -50 plus, I think, okay, you can do with 1, 0, 2. The resulting vector, whatever the resulting vector after doing this, a, b, will be the linear combination of these two vectors. You heard me correct. Yeah, exactly. So the linear combination will be, it can be anything. Okay, after the whatever means you take any scalar, multiply with a given vector, and add it up, you will be getting a linear combination. So linear combination cannot be over some finite over here. Okay, except some exceptions which are there. Okay, so over here, linear combinations are said to be a vector if there exists a scalar a, b, okay, and then whatever the resulting vector will be the linear combination of those two vectors. Okay, do not think that linear combinations can be only linear combination of any two vector can be only one. No, it can be anything. It can be any number of a linear combination of that two vector. What you need to do is simply multiply the vector with some scalar a or b, whatever, and add it up. The resulting vector will be your linear combination of those two vectors. So again, I'm writing one formal definition. So we have already written one formal definition, but let's write one definition which will give you a more idea about what we have seen so far. So the definition states, a vector R. Okay, so a vector R is said to be the linear combination. Is said to be a linear combination of A, B, C. Okay, a vector is said to be a linear combination of a vector A, B, and C, etc. Okay, so a vector R is said to be the linear combination of these given vectors A, B, C, which in this case this was U and V. In this case this was U and V. These are the vectors. Okay, these are the given vectors. So the same way A, B, C, D, these are the given vectors. Okay, if there exists scalars x, y, z, etc., whatever the number of your vector is, such that your resulting vector is equals to xa plus yb zc all the way around to the end. So a vector R is said to be the linear combination of these vectors if you multiply the scalar with the given vectors respectively, and then the R is said to be the linear combination of these two vectors, of all the vectors. So again, I'm repeating what's a linear combination means. It simply means that the vector R is we can call it as a linear combination. Okay, how we can call? We are given a vector, we are given these vectors, and if there exists some scalar, and in such a way that the resulting vector is equals to the R is the when we multiply a scalar with a vector and add the vector, the resulting vector will be your linear combination of that given vectors. Okay, so let's take one example. One simple example is you want to say is 1 by 4. So you're given a vector u. So I'm just going to take one example so that everything is make you understandable. So your example is you're given a vector u. You're given a vector u, which is minus 5 0, which is a two-dimensional vector, and you are given a vector v. You're given a vector v. You're given a vector v, which is 0 2. So you want to show is your 1 by 4, which is your R, the vector R, is also a linear combination. Is also the linear combination of vector u and vector v. So you want to show is this vector is the linear combination of these two vectors. Okay, you want to show this. This is a problem. So you want to show this. Is this the resulting, which is R 1 by 1 4, is the linear combination of these two u and v vector? You want to show it. So how you are going to show it? So for showing it, we will see the systems of equations, solving the systems of equations later on. But I will just give you a tool. So 1 by 4. So this will be the resulting vector. So if there exists some scalar which is 1 by 5. So this is my scalar times your vector minus 5 0 plus there exists a second scalar times the 0 2. So your resulting vector is 1 by 4, and hence this 1 by 4 is the linear combination of this u and of this v vector. Okay, so I hope that you are able to understand what I'm talking about, the linear combination of these vectors. I hope so. Okay, so a linear combination of a vector u and a vector v, and I have given you also the formal definition of a linear combination. So let's see one terminology. The terminology states that the constants or the scalars, which is here 1.5, this is 2. So these are called the weights of the given vector. So we don't call it as a scalar, we call it as a weights rather than calling the scalar. So if you have seen your hypothesis function, so you have a theta, so that is the weights of your vector. So the same way over here, we don't call it as a scalar, we call it as a weight of that u and v vector. Okay, so I hope so that you are getting a point towards linear algebra and viewing machine learning or deep learning into the view of linear algebra. Okay, so I hope that you have your understanding. So let's take one example to understand the weights. So for example 1 by minus 5 is your linear combination of vector 1 4 plus 1 1. When we multiply with the some weight, this is called the weights, so 3, that will be this is the linear combination of these two vectors. Okay, and over here that 1 4 which is a vector, any vector, and 1 1 with weights which is minus 2 and 3. Okay, so my 1 by minus 5 is the linear combination of a vector 1 1 4 and 1 1 with weights minus 2 and 3. We don't call it as a scalar, we even call it as a weights of that thing. Okay, so I hope so that you are understanding whatever I'm trying to say you over here. So I'm just going to talk about one last thing if I have a time. Yeah, I do have a 10 minutes time. So what I can talk about today is the next concept, which is the span of a vector. So okay, so I'm just going to just make you familiar. This is just very easy. So we'll be talking about a span of a vector. I'll be just giving a small introduction to span, and in the next video if possible I can show you some geometric intuition of a span. Okay, so what is a span? So let me write it. Span of, okay, so what is span? Span is a set of all the possible linear combination of a given group of vectors. So for example, we showed you over here, you can have a multiple linear combination of a given vector u and v. You can have a multiple linear combination. Are you getting me? So you can have a multiple linear combination of that given vector u and v or u and v. So the group of all the set of all the linear combination of a given group of vector, in this case u and v, is the span of those vectors. I hope so that you are getting me. Okay, so let me show you with the help of example, or before that I'm going to give you a formal definition of this span, because I think I trust in definitions also. So definitions gives you a clear way of thinking this. So I'm going to just give you a definition. This definition of a span, the definition of a span is the set of all the possible, all the possible linear combinations. I'm just going to write linear combinations of given group of vectors. Okay, so group of vectors, what do I mean with this? That how the like in this example, for example, you have a vector u and you have a vector v. So you want to take out the linear combination. So these are the group of vector for which you want to take out the linear combination. Okay, so the given group of vectors is called the span. The span of those vectors. The span of those vectors, which is a group of vectors. Span of those vectors. So we'll see one example to help us understand is much better way. So let's take one example of that. The example which I'm going to take is not a very hard example. I'm just going to take a simple example. You're given a vector u, 2, 2, and then you are given a vector v, which is 1 1. Okay, so this is the two vectors, which is the, and you can take out the linear combination. You can take out the linear combination where when you have a 2 3 4 9 10, where you another vector is also the same size. Okay, so but should be the same dimension. So you can take out the linear combination of this. Just you need to multiply with a scalar and then add it up, and then you will be getting your linear combination. So over here, if you, so first of all, let's take out some set of linear combination. So what I can do, if we can multiply this u vector with some weight. I'm not taking the name of scalar, just for practice, a good practice. So we can multiply with some weight 2, which is, and here I can multiply with, I think 1, and you can add it up. That will be nothing but 4, and add it up. I'm just being transparent so that everyone follows the same, because I think being transparent just for the sake of it's very, very important, so that the conceptual clarity will be very, very easy for you all. Okay, so this is the first for this is the, let's take an example. This is your linear combination. So your linear combination is this. For example, we written V. Okay, no, not V. We have already went. So this is your first linear combination. Let's take out the second or third. Let's take out the second. We can multiply 3, 2, 2 plus. I'm just taking an example. 2, 1, 1, which will be nothing but 3 to 6, 6 plus 2, 2. That will be nothing but 8, 8. Okay, so this is your H, which is your second linear combination. Let's go on taking out the third. So which is the last one for us. 4, 2, 2, 3, 1, 1, which is 4, 8, 8 plus 3, 3, which is nothing but 11, 11. Okay, so this is your I, which is your another vector. Okay, not I. Let's give it as okay, not J as well. Let's give it as a K. Okay, let's give it as K vector. Okay, so these three just you can take out any, you can take out a lot more linear combination. You can just go ahead, just multiplying with some scalar and then multiplying with some vector and then adding it up. You'll be getting your linear combination of that two vectors. So I'm not arguing you with that. So I've just taken three linear combination. So these three, the 5 by 5, 8, 5, 5. This is our G. I'm just taking Z, H, and K. Is the span of vector u and v. Instead of saying lot of linear combination, so you can just say okay that these are the span of those two vectors. So span if you see geometrically speaking, if you see over it just your linear combination span whole 2D space. Okay, so please see some visualizations from three blue, 1 brown. They give, but I have given you geometric intuition that all the possible linear combination is called the span of those vectors. So the notation for writing this is just the span of the vectors v1, v2, v3 is written as a span of v1, v2, v3. Okay, just I've shown you over. Okay, please see the notes. The notes are also given to you just for your own good. Okay, so this is what I talked about, a bit about span, and I hope that you really understood this. Let's go on. A last topic of this video is matrix vector product. Okay, so matrix vector product. So what I'm going to do is I have already talked about matrix vector product, but just the last thing which I'm going to just talk about, so I do have time. So let's talk about matrix vector product. So let's say you're given a vector A. Where you have some A, B, C, D, E, F, G, H, I. Okay, so this is your matrix A, and then you have a scale. Then you have a vector X. Then you have vector X, which is X. For example, 1, X1, X2. And X3. Okay, so you want to take out the matrix vector product. So how do you take out? So it will be simply what you do. So what you do, you will simply this is your A X, which is simply nothing but you take this column, you take this column, you take this column, which is the column vector, and you take this row vector, you take this row vector and you take this column vector, you just multiply it up. Or you can say, you can take, we'll talk about the dot product, just don't worry. So what we can say, we take out the dot product of a row vector, and a column vector, okay? So what you are specifically doing is taking out the dot product between a row vector and a column vector. So what does dot product mean? Means it is just element wise product and sum it all up, okay? So that will be nothing but that will be A times x1 plus B times x2 plus C times x3, okay? And then when you add it, so let me write a resulting vector as well. Okay, so that will be a D. Okay, so after you multiply and add it, so that is just a dot product of two vectors, of a row vector and a column vector, which is this. We'll talk in detail about the dot product and a transpose later on. Okay, so and then you do the same, D times x1 plus E times x2 plus F times x3, and then do the same, G times x3 plus H times x2 plus, okay, this one, I times x3, okay, so you'll be getting E, F, so whatever the answer is, and this is your final matrix vector product, okay, so which we have seen in our previous video, but I'm going to relate as a linear combination. So I'm just going to do what I'm going to do, just see over here. So you have a vector A, where I'm going to do A, B, C, D, E, F, G, H, I, J, K, L. Okay, and I'm going to multiply this matrix with a vector x1, x2, x3, and x4. Okay, so we have this A vector and matrix A and a vector x. Okay, so what you are going to do, you are just going to do the same thing. You're going to multiply AX. Okay, so I'm going to show you how you can do how I'm going to represent this. Okay, so what I'm going to do is to categorize this matrix into column vector, different set of column vector. Okay, so we can take this, the first column, and say this. Okay, this is the, so you take it a V1. Okay, take the second column, you would say this V2. Take the third column, you say this V3. Take the fourth column, you say this V4. Okay, so specifically, you are not taking as a dot product or the element wise product of row and column vector. Here what you do, you categorize your matrix A into a different into a set of columm vector, which is V1, V2, V3, and V4. Okay, and then when you multiply AX, which is nothing but what you will do. You will simply do x1 times V1, x1 times V1. Okay, x1 times V1. You multiply all x1 with this A. Okay, x1 times V1. Okay, and this is your scalar. This is of course your scalar. So let me write in small. X1 times V1. Okay, so V1 plus x2 times V2 plus x3 times V3 plus x4 times V4. Okay, so that this is whatever the result will be. For example, R will be your linear combination. So just listen what I'm trying to say. You convert this. Now what do? You take this x1 and multiply x1 times x1 times x1 times C, and the x2 times x2 times x2 times x3 times x3 times x3 times and x4 times. So what do? You given a weight of these column vectors. So the resulting vector will be the linear combination of the column vector A. So this R will be the linear combination of vector A, okay, of a vector of a matrix of a column vector A, okay, of a column vector A. So these are the resulting vector will be the linear combination of the column vector A, of the column vector. I just have read column vector, which is V1, V2, V3, or V4. So you have seen me how I done this as is to showcase you in the form of linear combination. So I hope that you understood a lot from this video, and I really hope that you will try to mark your attendance as well, because it is an LMS. So try to mark it. Your notes are in the description box below. Please feel free to assess the notes. It is very important to work from there. And also the next video we'll be talking about linear transformation, where we'll be introducing the notion of a transformation when we multiply two matrix. So that is thus transforming one matrix into from one dimensional space to another dimensional space. That is a transformation, which we'll be talking about in the next video. And then I hope so that we'll be able to complete the chapter number 1 in some days, and then I hope it is much clear to you as well. The one of the announcement that I want to give is please share the video and mark your attendance in your quizzes, okay, by going to the assignment tab in your LMS. If you are in LMS, so please go there and please try to search for some problem sets, or try to search for some resources. Although you don't need, I've talked a lot about more than enough, okay, for your journey. So thanks for seeing this video. I hope that you enjoyed this and you have taken your own notes. Please feel free to access the notes from the description. I'll be catching up your next video. Till then, bye bye and have a great day. Okay everyone, welcome to this lecture on linear transformation. So in this video we'll be specifically talking about linear transformation. In the previous video we talked about matrix vector product or a linear combination, which was the very fundamental concept, and we also talked about span of a vectors. Now in this video we'll be talking about linear transformation, one of the most amazing concept or the beauty of algebra or linear algebra which you will ever see. And also this sets a very foundation of your algebra skills or have to study as of now, okay? And it is used extensively in the field of deep learning when you read research papers or when you are studying some algorithm. So if you want to understand by the point of view of linear algebra, then I think linear transformation is one of the best thing to study, and this is a compulsory topic to study, as the most concept is related to this. But you may think, hey, you just transformation, so can you just define what a transformation is? I just want you to search on Google what's a transformation means, and then put that in a comment box. Please give the timestamp so that I could know, okay, you're here. Okay, so please go on YouTube, try to search about transformation and then come back. Okay, so transformation like just transform something or do something to that a function, or if you know about function, so linear transformation can be thought of as a functions, okay, as the new name given when we deal with in linear algebra. Okay, so linear transformation is nothing, or can be just thought of as a functions, can be thought of as a functions, can be thought of as a functions. Why I'm telling this, in functions, what you do, you give some input value, and you want your f to map this input value to the output value y. Okay, so this is what the linear transformation is doing. Linear transformation takes some vector as an input, maybe two-dimensional vector, which is two-dimensional vector. It wants a function t that maps from n-dimensional to m-dimensional vector. Okay, this is the definition of linear transformation. Again, we will see some of the definitions to help us more clear what actually linear transformation means. But in big picture, linear transformation can be thought of as a functions, like it takes some sort of vectors and transforms from one n-dimensional vector to another dimensional vector or a different space into that plane. Okay, so this is the basic thing which you need to study about. So linear transformation can be thought of as a function that takes some vectors or just transforms this vector from n-dimensional space to m-dimensional space, and that can only be possible with a t, which is a function t. So the functions are the one which take some value and maps input values to output values, but in transformation we transforms xn, means n-dimensional vector, to m-dimensional vector. Okay, so that's a linear transformation, the definition. So let's start with an example so that we could understand it much more better way. Okay, so just I'm gonna write a definition and what we do in a case of functions and what we do in a case of linear transformation. So in functions, we take some values, input values, and we map our input values to output values. Okay, so to make a function f that takes some value and output the square of x, which is parabola, if you plot it out. Okay, then in case of linear transformation, we make a function t that transforms from one vector space, transform the vector from Rn, and this is the Rn, from n-dimensional into a vector to Rm. Okay, so it just transforms one vector from one vector space to another vector space. Okay, so this is the basic thing which you need to which we'll see. I will just prove you out this equation, so why it seems to be legit. So let's start with an example so that I could just prove you that whatever I'm telling is correct. Okay, so let's take one example. Say you have a if you multiply say you multiply your m by n matrix. So you have an m by n matrix. You have your m by n matrix. This is your favorite matrix. You have your m by n matrix, and what you want to do is simply multiply with a column vector which is n times 1, which is your column vector which is n times 1. So we'll just multiply this matrix with a column vector n times 1. So let's multiply it out with the column vector n times 1. Okay, so here it has only one column, and the resulting vector, what we are specifically doing, we are multiplying our matrix with a vector. Okay, and then that will be nothing but your n by 1 column vector, m times 1 column vector. Okay, m times 1 column vector, which is resulting vector. That will be the resulting column vector. Okay, so what it does, it took your or in other words, we see over here that an m times n matrix, transforms an n times 1 vector into an m times 1 resulting vector, which is another space. Okay, so using this matrix, we transform this vector into different vector space like this. Okay, so for example, let's see some example to make sense. Here we are taking the matrix vector product, which we have already seen in our previous videos. So let's consider this matrix A. Let's consider this matrix A as a 3 by 3 matrix. So 1 2 0 and 2 1 0, which is a nothing but 3 by 3 matrix. Okay, now I wanted to show that by matrix multiplication, by matrix vector multiplication, or that matrix multiplication, you want to show by matrix multiplication, A transforms this matrix A transforms vector in R3 vector in R3, which is the column vector, which is three-dimensional vector like this. A vector which is a three-dimensional x, y, z, which is from R3 from R3
to R2 or to R2, okay, into a vector in R2. So you using A, you want to transform this vector X, you can transform the vector X, and then that will into an R2, which is nothing but your X and Y, only two-dimensional rather than being a three-dimensional. That's when we call linear transformation of a matrix. Okay, so let's see. So with an example, you have a vector. So R3. So over here, R3 are a vector of a size 3 by 1, which is the 3 by 1 three-dimensional vector. While vector R2, which you want to transform, you want to show is 2 by 3. 2 times 3, which is the 2 times it's 2 times 1, it's two-dimensional vector. So it's using the A, you want to transform your vector, means you using A or A transform, you just show that A transforms the vector from R3 into a vector R2, okay, which you want to show. Okay, so when you do this, so this is of size 2 by 1, which is your row vector. I think it's column vector, and then if you multiply A, which is your 2 by 3 matrix, which is a it's 2 by 3, okay, it's 2 by 3 matrix, by a 3 by 1 vector, the resulting vector will be nothing but 2 by 1. So you just showed using using A, you multiplied this A with which you want to show, means R3, and then the resulting vector, which you can see that you showed, okay, using A, you transforms the vector in R3, which is 3, which is this one, into a vector R2, which is 2, 2, okay, or AB, which is a two-dimensional vector. Okay, so that is what it is telling. So let's see one of the example just to numerically show you. So 1 2 0 2 1 0, and what you and you have this matrix A, and you want and you have a three-dimensional vector X Y Z, and this is an A and this is a vector X, and you want to show that A transforms means what do you say? The A transforms a matrix which is from R3 into an R2. Okay, using A, you want to transform from R3 into R2. So that will be nothing but X plus 2Y and 0. Of course, we don't write it out, and 2X plus Y. Okay, and then it will be after you add it up, it will be either A and B, which is your R2. Okay, so that is the following. That what you done, you simply transform your one vector space to another vector space using a function A or using A, which is your matrix. Okay, so let's define it out. So what you done, you made a function T to transform from n-dimensional to m-dimensional, means a function T transform the vector M, transform the vector Rn into a function T to transform from Rn to Rm, which is another dimensional space. Got it? The linear transformation should satisfy your two constraints. The two constraints are, the first constraint, your transformation T x plus y, it would be is equals to the Tx plus Ty, transformation of x plus transformation of y, and then your transformation, and then this is scalar A and this is a vector x, and then it should be A and transformation of x. So these are the two conditions which you need to satisfy. Okay, these are the two basic conditions which you will ever see. Okay, but the more formally which I could state over here is linear transformation is the function that transforms your vector from one-dimensional space from Rn to Rm. Okay, that is your linear transformation of your vectors or a matrix or of a vector. Okay, so one theorem is there. The theorem states let T be a function or transformation that transforms from one vector's Rn to Rm, which is the transformation of your transformation of x, which transforms Rn to Rm. Okay, so I'm just going to write the theorem, which I'm not going to prove rigorously, but you can prove it. You can prove it. T equals to R. You're going to make a function T. You're going to make a function T to transform Rm to Rm. Okay, be a transformation defined by the transformation is defined by T of x. Okay, you give one vector which is of n dimensional, and just what it will do using A, which is a matrix, just transform that vector. Means the matrix vector product. So I just showed you that a matrix vector product is a linear transformation. Okay, so what you do is, if even you multiply to a vector with a matrix, that will just give you the linear transformation. Just it should satisfy the conditions which are listed over here. The geometric understanding is also it's very easy. You can consider watching 3 blue 1 brown videos for this. I hope that will make more sense there. Okay, so that was a short video on linear transformation, about 15 minutes, and I really hope that you like this video. In the next video, we'll be talking about transpose of a matrix and dot product, which is one of the most important concepts. So let's get on to the next video. Hey everyone, so today we'll be talking about transpose and a dot product of a matrix or a vector. So we'll be talking about that, because in the video of linear combination, I have taken one example of matrix vector product, and I showed you how you can represent that matrix vector product as a dot product between the column vector and a row vector. So we'll be talking about what does it exactly means, what is a dot product and a transpose of a matrix. So these are again two most important concepts which you will ever see in your journey of linear algebra. Again, it's one of the basic concepts which is very easy to understand, but still it's very good to know about these things, which gives you an extra tools to work efficiently in your deep learning problem or machine learning problem or other stuffs. Okay, so let's get started. So what is the transpose of a matrix? So I'm going to start with the transpose of a matrix. So what is a transpose of a matrix? So the transpose of a matrix is a kind of operator which flips over the diagonal, okay, or make all the rows, for example, if I could show you the visualization. So for example, you have you have a column vector or row vector like this, 1 2. So it's, if the diagonal is this one, the diagonal is this one, so it simply flips it. Okay, so it simply flips it, then it would be, if you take out the transpose of this, so it will be 1 2. So what it does, it flips over the diagonal. For example, let's take one more. Let's take one more. You have 1 2 3 4, which is a 2 by 2 matrix. Now if you take out the transpose of this matrix, so what you do, you have this diagonal, so if you flip over this diagonal, if you flip this over the diagonal, it will be nothing but 1. If you flip this over the diagonal, if you flip it, it's 1 3 and 2 4. Okay, and 2 4. So what you done, you simply flip it, and then above gone down and down gone above. So that is what it is trying to tell. Or in other words, what you can interpret is, you make every every column as a row, and you make every column as a row. Okay, so that you can expect it. So for example, you have another, so if you have another matrix, let's take an example that is 6 4 3 2, and you apply the transpose onto this matrix. So what will be the output? So the output will be, what you do, you take this or you say the column vector, and make it a row vector like this. Make it a row vector 6 and 3, and you take this another, you make this 4 and 2. Or in other words, what you can interpret is, you flip over the diagonal, you make this 3 above, and you make this 4 down. Okay, so what you are specifically doing is to flipping over the diagonal like this. Okay, so you will get the same result as you are doing. So it's just not a big deal to understand these things. It's very easy to understand. Okay, so I hope that you are able to understand what the transpose of a matrix is. So let's write a formal definition. Let's write a formal definition of your transpose of a matrix. So the transpose of a matrix, the transpose of a matrix is a type of operator or operator is an operator which flips over the diagonal. Okay, so this is the transpose of a matrix. So what it does is that the definition states that it just flip over the diagonal or to the main diagonal to obtain the A transpose. So for example, you are given a vector A. So what you do, you reflect A over its main diagonal to obtain the A transpose. Or it is just a technical words to flip or reflect. But specifically what it's doing, making the column vector as a row vector and a row vector as a column vector. That's it. Okay, vice versa. It can be anything. So making a column vector to a row vector. That's it. Okay, so that is what it is telling, and a row vector to a column vector. Whatever seems good to you. So A transpose is just exactly doing that. Okay, so for example, you have your matrix A. Okay, you want to take out the transpose. Where I represents your row and J represents your column. So now, after applying the transpose at this matrix, now your will be AJI. Now your column represents your rows and rows represents your column. Again, this is very easy to interpret. So you have this 2, 2, 2, 2. And you have this a matrix. What you do, you apply the transpose on this matrix. After applying the transpose of a matrix, here you are having A transpose, okay, and you have I, which is 2, or I and J. Okay, you have I and J. When you do that, when you apply the operator, this will be nothing but, or I could say 0, 0. Let's take this 0, 0. Okay, so when you sorry, we should not take this 0, 0. Let's take it as a 1. Let's take it as a 6. Okay, just for understanding. Okay, so if you have the transpose over here, after applying the transpose of a matrix over here, your row becomes your column, and column becomes your row. Or yeah, so your row becomes your column. So your row is the first row becomes your column. So after flipping over the diagonal, so when you apply, so it is 2, 2, and then your second column becomes your second row. Okay, 1 and 6. Okay, so what you specifically done, you flipped over or reflected the main diagonal, or flipped over the diagonal, and then you obtain your transpose of a matrix. So that is what it is telling. So you can do in high dimensional spaces as well. For example, you have a matrix where you have 6, 4, 9, 10, 11, 12, 13, 14, 15. Okay, so if you want to apply the transpose on this matrix, that will be nothing. You take this and put it over there, 6, 4, 9, and then you take this, 10, 11, 12, and you take this, the 13, 14, I think 15. Okay, so this is what you are doing, is flipping over the main diagonal, okay, or reflect it over the main diagonal to obtain your transpose of a matrix. So we have done a lots of examples. So we'll see one or two more examples to make you more sense. So let's make one or more example. So I just hope that you are able to make sense what actually the transpose of. So that is the transpose of a matrix. So it is just what it is doing, reflecting A over its main diagonal to obtain the A transpose. That's it, what the transpose is doing. So if you take one more example, so you have a 1, 2. Okay, if you have 1, 2, if this is a A or A, okay, here is a column row vector. If you transpose this A transpose, that will be nothing but 1, 2. Okay, just flipping over or making the row as a column vector. Okay, the next thing can be, for example, you have A. I want you to solve this. 1, 2, 3, 4. Apply the transpose on this and say me what the result would be in the comment box. write this answer in the comment box. It will be very, very easy to understand. So I could see whether you're watching or not. Okay, so that is the transpose of a matrix. So just I'm going to write out some of the points. Please pause this video and write your answer of a transpose of a matrix. So just I want you to write it out. Okay, so let's see some of the properties of the transpose. Okay, so you have to take out A transpose and then you take out the transpose. Now, so tell me what it will be. Tell me it will be nothing but A. It will be nothing but equals to A. You first of all transpose it, okay, and then you take out the transpose of that. So for example, you have A which is 1 by 2. Okay, you have 1 by 2. Okay, so what you do, you take out the transpose of this, which will be 1 2, and then you take out the transpose of this, which will be 1 2. So these are equals to or not? These are equals to. So that's why we are telling that is the one of the property of a transpose of a matrix. Another property of a transpose of a matrix. Is A plus B transpose, which will be nothing but A plus B transpose, which is nothing but A transpose plus B transpose. Okay, so that will be equal. So you have a 1 2 3 4. Okay, and you have a B and you have a B 1 2 3 4. You want to add it by taking on. Now you want to take out the transpose of these three. So what you can do, you can take out the transpose of take out the transpose of this, and that will be your answer. Okay, so let's do this. We're going to take out the transpose of this. That will be nothing but 1 3 and 2 4. Okay, plus 1 3 and 2 4. Okay, which will be nothing but 1 plus 1 2, 3 plus 3 6, 2 plus 2 4, 4 plus 4 8. Okay, that will be your final answer, which is 2 by 2 matrix. And this is what this property states. You can even what you can do, you can prove it extensively. You can prove it. You have a you take out the transpose, and then what you do, first of all, let's do the same thing. You first of all add it up. So when you add it up, 1 2 3 4 plus 1 2 3 4. Okay, when you add it up, so 1 plus 1 1, 2 plus 2 4, 3 plus 3 6, 4 plus 4 8. This is 2 4 6 8. Okay, that will be your answer of this particular. And then what you do, you take out the transpose of this because you added it up. Now you take it, when you take out the transpose, it will be nothing but 2 6 4 8, and this is your answer. So these both are equal. So you can do separately transpose and then add, and or you can do just first of all add and then take out the transpose. Both are equivalent. Your answer will be equivalent. Okay, so let's see another let's call it another page. Let's make another page. How do we add another page? Yeah, let's add one more page. So another property is AB transpose, which will be nothing but equals to B transpose and A transpose. Okay, so you have let's for the sake of an example, let's take a vector 1 2 1 2, and then you take a B vector. You take a B vector which is 2 2. Okay, and then what you want to do, you want to take out the transpose of this. Okay, so let's first of all do this. So that will be 1 times 2, 1 times 2, which will be nothing but 2 times 2, which is 4. Okay, and then what you do, you take out the transpose of this. So when you take out the transpose of this, that will be 2 4. That will be 2 4, which is a column vector. Okay, so that will be your first. Understand, this is your first. Now let's check for equivalent for this. So you have B, so which is B 2 2. If you take out the transpose of this, which will be nothing but 2 2. Okay, and then then what do? You first of all do this 1 2. Okay, which is after taking the transpose of this, that will be 1 2, and then when you multiply it out, that will be nothing but 2 4, which is both equivalent. So we have proved this. We have proved this. Let's go on fourth property. The fourth property is you have a scalar C and you have a matrix A. When you take out the transpose of it, that will be nothing but C A transpose. Okay, what you can do, you can first of all, rather than after multiplying and then taking the transpose, you can first take out the transpose and then multiply by the C. Both will be same. Okay, the fifth, you can actually verify this. You can actually verify this is not a big deal. Okay, just the way I'm doing. Okay, so you need to take out the determinant of A transpose. That will be nothing but determinant of A. And if you don't know about this, please ignore, which we will be studying this extensively in our later videos. Okay, you can ignore this. The determinant is just the area of the parallelogram, so you can easily ignore this as of now. Okay, sixth one. The sixth one is the last one which I'm talking about, A transpose minus 1. Okay, to the power of minus 1, A minus 1 transpose. So these are equivalent. Okay, so you take out the transpose and then inverse it. First of all, you inverse it and then take out a transpose. Both will be equivalent. Okay, so these are some of the most used properties in your transpose, and I hope that you are able to understand this. It's not a big deal to understand. Okay, these are the transpose which we have talked about. Let's go on to the dot product to understand much better. So let's talk about a bit about dot product. So what is dot product? Dot product, what it do? It do element wise product and sum it all up. That's it. That's what the dot product is doing, is to do element wise product and add a sum it all up. That's what the dot product is doing. So for example, the dot product. So for example, let's take, for the sake of an example, you have a vector A where which is your row vector. So A1, A2, all the way down to the AN, all the way down to the AN, and you have a B vector, B row vector, which is B1, B2, all the way down to the Bn. Okay, so this is your two vectors. Now what you need to do, if you want to take out the dot product between these two vectors, if you want to take out the dot product between these two vectors, so how do you take out? So what you simply add a summation. So you take out the A dot, you write dot B, this is nothing but equals to I equals to 1 all the way down to the n, AI BI. So what it will do, first of all, A1 times B1 plus A2 times B2 plus A3 times B3 plus all the way down to the AN times BN, and your final output will be one scalar C, which is your dot product between these two row vector. Okay, so that is the particular the algebraic definition. So this is the algebraic definition of your dot product, or in other words, what you can tell is the dot product between two vectors is nothing but A B transpose. The dot product, the product between A and B transpose, that is your algebraic definition, or this is your formal definition of your dot product. Wise product. So for example, you have this and you have another vector like this. Your output will be A, B, C, D, E, F. Your output, when you take out the dot product between these two, A plus D, A times D plus B times E plus C times F, and your output will be a scalar. Okay, so if you have seen our matrix vector product, so we were having. So let's see which we have seen already in our previous videos. So let's say for the sake of an example, you have A, B, C, D, E, F, G, H, I. Okay, and you have a vector which is x1, x2, and x3. You want to take out the product between these two. So what you do, you categorize this into a different. What do you say? The column vector, or sorry, row vector. Yeah, column vector. V1, V2, V3. Then what you do, you take out the dot product. Between V1 and a vector X. So when you take out the dot product between a column vector with a column vector, so when you take out the dot product between these two, that will be your answer, which you have already seen in our previous videos. Okay, so I don't think that we should care about this. So I hope that you are able to make sense of these things. And please feel free to review the previous video on linear combination, which I talked in detail about these things. Okay, so this is what the dot product is. You simply take out the element wise product and sum it all up. Okay, and that will be your simple scalar. Okay, so that is what the dot product means. And if you have seen our videos on hypothesis function, which if you know about hypothesis function of linear regression, if we talked about hypothesis function. So in hypothesis function, what we were doing, we were taking out the dot product between our x and w. We are taking out the x or a theta. We are taking out the dot product between x and w. That was resulting in our prediction y hat. Okay, so x was also maybe a matrix or a vector. So you have a matrix or a vector. So a vector of x can be the matrix, for example, 2, 4, 6, 7, and your w can be also 2, 4, 6, 7, whatever. These are the weights of these feature. And what you do, you take a, sorry, it's not a matrix, it's a vector. It's a vector dot product. So you simply multiply it up. And then what do? You simply add it up, and that will be one scalar, which is your answer. For example, 2 times 2 plus 4 times 4 plus 6 times 6 plus 7 times 7, and then after doing plus all those stuff, then you will be getting your answer C, which is your answer of this particular question. Okay, I hope that you are able to make sense out of it. So we have seen our algebraic definition of our dot product. Now it's time for seeing the geometric definition to help you make more sense of your dot product of two vectors. Okay, so let's see of that. So let's see the dot product. Let's take an example. You know, take out the dot product between two vectors, which is vector A and vector B, which is geometrically speaking. I'm going to talk about geometrically now. So for the sake of an example, let's take an example that you have a vector like this. So sorry, it's bad. You have like this, and you have this. Okay, so this is your vector A. This is actually vector A, and this is actually vector B. And just one thing, if you're a calculus student, there is a small fun quiz. Is it continuous? Function. We have a function. Let's take an example that is a function. Okay, is it a continuous function? Is it differentiable? If it is continuous function, is it differentiable? That is your question. Okay, so please feel free to put in comment. Just for those who are a calculus student, just tell me. Just ignore this A and B. Just say this is a function, and then just tell me it is a continuous, and if it is, then if it is differentiable or not. Okay, this is your question to answer. But the one who is studying linear algebra, please feel free to stick me with this. Okay, kindly ignore the question which I told you. Cool. So the angle between these two vector, is nothing but the angle between is 59.5 degree. Okay, so that is the angle between these two vector. Okay, so this is the angle between these two vector. So you want to take out the dot product between vector A and vector B. So taking out the dot product between vector A and vector B, which will be nothing but I would say it will be nothing but norm of A times the norm of B times cosine of theta. So theta, the angle between them is theta. So the norm of A. So for example, let's assume the length of A is 10. Okay, length of A is 10, and your length of B is 13. So here your vector A is nothing but 6, 8, and when you take out the length is 10 using the Pythagoras theorem, and then the vector B is 5 and 12. When you take out using the Pythagoras theorem, that will be or the norm of a vector. When you take out the norm of a vector, that will be 13. Okay, so the length of these I have already told you. Okay, so that is 10 and 13, and when you multiply with the cosine of 59.5, okay, so then you'll be getting what you will get 10 times 13 times 0.5075, and then when you multiply, that will 65.98 whatever, and then it was approximately 66. If you want to what do you say, take out now if we got 66. Now if you want to take out the algebraic definition states 6, 8 and 5, 12. When you do this, 6 plus 5, 11, 8 plus 12, 20, 8 plus 12, 20. When you add this, so sorry, we are actually taking all the, okay, that's 6 times 5. It should be 6 times 5. Why I'm doing 6 times minus 5? Sorry, it's 5. Yeah, 6 minus 6 times, it's minus 6. It's not 6, it's minus 6. Okay, so when you do this, 6 minus 6 times 5 and plus 8 times 12 minus 6 times 5 plus 8 times 12, and you will get minus 30 plus 96, which will be 66, and this is equivalent to this. And you can also do with this one with the high dimensional spaces. Okay, so I hope that you are able to make sense out of it, and I also hope that you are able to understand a little bit about this. Okay, so that is the dot product between these two vectors. Just you need to understand the numeric understanding of dot product, that element wise product, and add it all up. That's it. Okay, so I hope that you are able to make sense out of it, and I also hope that you are able to understand everything. This was the dot product between these two vectors and a transpose of vectors on a matrices. And I also hope that that till now you're able to understand most of it out of it. And I also hope that you will utilize this resource and share this resource to everyone. That motivates me to work on these contents. And so in the next video, we're talking about some of the types of matrices, and then we'll talk about rank, trace operators, determinant, eigenvalues, eigenvectors, and solving the systems of equations. And then our linear algebra will be done. So I hope that you like this video. I'll be catching up your next video. Till then, bye bye. Hey everyone, welcome to this next lecture on linear algebra and MS002, and I really hope that you are enjoying this course. First of all, I want to thanks you and congratulate you as well that you had completed your first week, and I'm very much happy to see so much of enthusiastic students who are watching these lectures without any kind of problems, and they're able to understand and leaving their great feedback in the comment box. And I'm seeing the watching hours increased, so I would like to thank. It's giving me a lot more motivation to make these such videos for free, as well as I would just salute you for your consistency, and I would also salute for you utilizing these kind of materials who are for free. And one thing which I wanted to say, that we recently yesterday we released our first homework assignment of the previous week, which is the homework assignment consists of the questions from the 5 lectures, previous 5 lecture 1 to 5. That is your first week lectures. So basically in that we included the homework assignments, all the questions from the topics which are already taught. Okay, so if you go and see, and I would like to thank Vinayak Vishnu, who has contributed 70% of preparation of these questions, who is one of the teaching assistants of our CS ML002. So I would like to thank him, and I would also like you to thank him on the Discord server or whenever in the comment box. Thanks Vinayak Vishnu. So it would motivate him as well. He's doing the community work for free. So here's the programming assignment to you. Sorry, not programming assignments, homework assignment, where you're getting around 32 questions, and these questions are covering from very basics to a conceptual understanding of the particular subject, having in mind to have a good practice of yourself of the topics which are already taught. So you may think, hey Ayush, you're doing this stuff. The reason why I'm making you practice this stuff is mainly when you go in deep learning to have a conceptual understanding of what are vectors and how it is performing computations and what are the resulting vector size, and etc. So it will help you to practice a lot, and it will also help you to understand a conceptual understanding or the very depth understanding of these vectors, and we also seen some matrices, and then we are performing something, and then I also taught you about linear combinations. Section 3 contains a linear combination where we are talking about various stuffs over here, and these are the questions which are very nice questions which are prepared by Vinayak Vishnu, and as well as I had also added some questions over here which are also related to your deep learning context. And then you finally have a transformation, and this is also great, amazing the questions which are there, and it will help you in deep learning journey, that how actually the linear transformation works and behind that. And then we talked about transpose and the dot product of two matrices or vectors. Okay, so that is the specific thing, and then we ask you to verify this property. So I would definitely ask you to visit these things. It solve this homework assignment, upload it in your LMS, learning management system, if you have enrolled into that. It's absolutely free for everyone. Please see the student handbook in the description box below, and go over there into the LMS and submit your homework assignment, and then you'll be getting the detailed feedback on what questions you've done wrong and what question you haven't done wrong. Okay, so let's get started with this video. So the title of the video, you might have already imagined, is the types of matrices. Types of matrices. So what are the types of matrices that we will study? And some of the types of matrices are maybe not come in your journey of deep learning, but I would say ki whenever you're studying the something, let's study full of that. Okay, so let's not study the partial stuff. So let's study full. But most of the thing which I'm going to teach is being used frequently, not too much frequently, but it's being used sometimes when you talk with some great mathematicians or deep learning engineers, to take these kinds of words, so it should not might confuse you. So that's a way I asked about. So the types of matrices. So the first types of matrices which you already know about, in other words, like row vector, which is something called as row matrices, okay, or a row matrix. Row. So let me add one thing over here. Row matrix. Row matrix. Okay, so what is row matrix? So can you define what is a row vector? Can you just define it? So the row vector is the matrix which have only one row. So the same way, row matrix are the one which has only one row. So you can say just a row vector. Yeah. So the matrices which have only one row is called the row matrix. So for example, the example can be 1, 2, 3. Okay, so this is the first. This is your row matrix. Okay, so because it only have only one row, so we can mathematically we can write that A is equal. This A is a matrix where Aij, where we have a m times n matrix, where m denotes the number of rows and n denotes the number of columns. And this you have m equals to 1. You have m equals to 1, then it is called as a row matrix. So what is a row matrix? Row matrix is the one which has only one row. Let's talk about second kind of matrix, which is column matrix. Column matrix. So sorry for on the eve of Diwali, many of the people are just busting up the crackers in India. So yeah, no problem in that. So what is a column matrix? So column matrix which have only one column. So and you have heard about column vector. So the same way we have column matrix which only have one column, and these are used very frequently in the era of deep learning, and it is very precise to use these names in deep learning to follow the mathematical conventions rather than saying the shape. Either the shape, you can just say that okay, it is a row matrix, or it is a column matrix, or it is a row vector, or it is a column vector. Okay, so here you have a matrix A, where you have m times n, which is the size, and where the m can be anything. You can be any number of rows, but you have only one column. Okay, so here n should be equals to 1, so you should remove this and write 1 to be considered this as a column matrix. Okay, the next kind of matrix we will talk about is zero or null matrix. So as you have already imagined about this, zero or null matrices, and these are very easy kind of remembering. It's not I'm not teaching any rocket science. It's very easy to understand. So so if in all the matrices, all the elements into that matrices are 0, okay, so all the elements in the matrices are zeros, then that matrix is called zero matrix, okay. So for example, you have A, where you have 0 0 0, here is 0 0 0 0 0 0, where you have a 3 by 3 matrix, and this is called a zero matrix, or sometimes we call it as a 3 by 3 null matrix, okay. So when someone tell you, hey, can you just tell what types of matrix this is? Okay, this is a zero matrix. Okay, when someone asks you, hey, you're given a null matrix, what happened when you multiply this null matrix with another matrix where the matrix satisfy all the matrix multiplication properties or dimension property? So you will say, okay, what is a null matrix? So null matrix are nothing but a zero matrix, okay. So that is just a zero matrix which is given another name, which is called null matrix. Then in that you have all the elements to be 0, okay. The next is your favorite singleton matrix, okay. So in Java, one of my friend was taking a singleton, doubleton. So in the same way we have singleton matrices, okay. So singleton matrices. So in singleton matrices, all the matrices are or you say you have only one element into that matrix, okay? Not all the matrices, you have total of one element in that matrix, okay? So that's why we call it as a only one element in the matrix, And so sorry, I'm not too much of creative. I don't follow the rules of changing the color and then writing it out. I should develop that thing. So let's use different color then. So the fifth one is horizontal matrix. So let's give some examples of this, because I haven't given an example of this. So which is 2, then it can be 1, then it can be 3. These are the, for example, A is a matrix where we have, this is a singleton matrix, and etc. So these are called the singleton matrix. You may have singleton in your sets or discrete mathematics if you have taken the course on discrete mathematics. So I would ask you to do not take the course, but yeah, remember the singleton. Either it is not used too much, but yeah, you should know what are singleton, because when someone asks you, you should be able to answer it. Horizontal matrix, that is a good deal. So horizontal matrix, who can define? If anyone has taken the linear algebra class, please feel free to go down in the description box below. No description, it's comment. Okay, so please feel free to go in comment box. Please write what is a horizontal matrix, and it's very easy. It's again very easy. So for example, here you have 1, 2, 3, 4, okay, and then you have your favorite, and then you have 6, 9, 8, 2. So I'm going to consider this matrix as a horizontal matrix. You may ask why you should consider this as a horizontal matrix. So just tell me the size of the matrix is. The size of the matrix is what? 2 by 4, 2 rows and 4 columns, and here the columns is greater than rows, so that's why that is a horizontal matrix. So whoever matrix where the number of columns is greater than the number of rows, then that's called the horizontal matrix. Got it? So that is the horizontal matrix, where your number of rows, number of columns is greater than the number of rows. So that is one of the example of a horizontal matrix. Now let's see some more examples, some more matrix types, which is something called as vertical matrix. So can you tell me what is vertical matrix? Just define me what is a vertical matrix. So let's make a matrix. Let's make a matrix where you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so I'm going to consider this as a vertical matrix. Now tell me why. This is a vertical matrix. The reason why it is a vertical matrix, so let's count the size. So we have a total of 4 by 3 matrix, and here your number of rows is greater than the number of columns. So that's why this is a vertical matrix. In horizontal, your number of columns should be greater than number of rows to be called as a horizontal matrix. But in vertical matrix, is totally opposite of that. Here, your number of rows should be greater than your number of columns. Okay, to be called as to be said as a vertical matrix, or in formal definition which is taught in a school, is a matrix is said to be a vertical matrix if and only if its number of rows is greater than the number of columns. It's taught in my school. I just want to thank my school to teach me these definitions. No, not exactly the definitions of vertical matrix, but yeah, the definition format or template to tell is that this is said to be this because this. Okay, so I follow the template of my school. So thanks to my school. Shout out to Sun parents. Okay, cool. The square matrix. So what is a square matrix? I would say pay attention to this. Square matrix is used extensively, whatever we'll study in the like a diagonal matrix or whatever, okay, like a determinant or eigenvectors and eigenvalues, we are going to take this square matrix. So what are square matrix? So just tell me what are square matrix? The matrix which looks like square. Is that it? Yeah, so the matrix where or just wait. Now here's your matrix. Here's your matrix. 1, 2, 2, 4, and here's your A matrix, and here's your B matrix, which is 1, 2, 3, 1, 2, 3. Okay. Or let's consider this as a. Let's consider this as a. Okay. So here you have a total of 2 by 2 matrix, and this is a total of what do you say? A 3 by 3 matrix. So here your number of rows matches with the number of columns. So the square matrix are the one where the number of rows matches with the number of columns. Okay, so the square matrix is where your number of rows is equals to the number of columns. Okay, so the square matrix is in which your number of rows is equal to the number of columns. Then it is said to be a square matrix. So again, my school's formal definition, a matrix is said to be a square matrix if and only if its number of rows should be exactly equal to the number of columns in your matrix. Okay, so that is your square matrix. Again, shout out to Sun parents. Just for your information, these are the things which are not taught my school till now. I'm in class 9, so till now they haven't taught this. But yeah, I know the form. I know the definition template because in my school I used to study a lot more definitions. So I know the definition of this. The definition starts with this, the same way. This is said to be this because this and that. So that's why we call it this. So the same way I frame a square matrix is said to be a square matrix. A matrix is said to be a square matrix if and only if your number of rows is matched with the number of columns, and so thus if it is follows, then it's a square matrix. So we know about the square matrix now. So let's go further into understanding the diagonal matrix. So what is diagonal matrix? What is diagonal? What is diagonal matrix? Can anyone tell me what a diagonal matrix is? Anyone try it out? So all the elements except the principal diagonal, or let's start. I just want to scold that guy who is bursting these crackers. I don't want to see him. I'm making my video. Why is bursting his crackers outside? Oh my gosh. No problem in that as well. Okay, cool. So let's make a matrix 1, 2, 3, 0, 0, 0, 0, 0. Okay, so this is called the diagonal matrix because your all the elements in your diagonal matrix except the principal diagonal. This is the principal diagonal. And this is the principal diagonal. So all the elements into that matrix except the principal diagonal of a square matrix. So diagonal matrix should be a square matrix because it is a 3 by 3 matrix, so it is a square matrix are 0. So all the elements into that diagonal matrix of a square matrix are 0, then that is called as a diagonal matrix. So let's see some more. So for example, you have 0, 1, 2, oh my gosh, 0. I think I done wrong. So 1, 0, 0, 0, 2, 0, then 0, 0, 3. So this is, oh, I made the same thing again. No problem in that. Oh, this is left. Okay, so that is all the principal diagonal is your what do you say, the non-zero, and every element cell except that is your not zero, then that's called a diagonal matrix. So I hope that you are able to make sense out of it. So the diagonal matrix should be a square matrix, and a square matrix is nothing, a matrix which is said to be a square matrix if and only if your number of rows matches with the number of columns, and thus it is called the square matrix because it looks like square. But what is rectangular matrix? So one thing which I'm going to mention, rectangular matrix. So what is a rectangular matrix here? Where your number of rows does not matches with number of columns. Oh my gosh, there's a contradiction. So that is nothing but called a regular matrix. So, oh my gosh, it's a rectangular matrix. So let me define this through my school words. So thanks my school. Sit down. Yeah. So what is rectangular matrix? A matrix is said to be a rectangular matrix if and only if its number of rows does not match with the number of columns. So that's the rectangular matrix. So the following example is a rectangular matrix. So maybe you may have 2, 1, 3, 4, 2, 1, 3, 4. That is, your number of rows is 2 by 4, where 2 is not equals to 4. So that is the rectangular matrix that looks like rectangle. So that's why we have written the rectangular matrix. Cool. So let's go further into learning about scalar matrix. So what is scalar? So first of all, define a scalar and then try to identify what is scalar matrix. Please go ahead and write your answer. Just give the guess, guys. I'm just here to have a fun with you all. So give a guess. What do you mean by scalar matrix? Because when I studied first, I given a very good guess, and that was totally wrong because this is like scalar matrix. So I was little bit okay. Scalar is just a number, and scalar and this matrix are the arrays of numbers. So how I can consider a scalar as arrays of numbers? That is the best assumption that I made at that point, but no problem. The scalar matrix, here's your scalar matrix in front of you. Here's the scalar matrix in front of you. So you have -7 0 0 0 minus 7 0 0 0 minus 7 0 0 minus 7. So listen, so this is called scalar matrix. This is called the scalar matrix. This is called the scalar matrix. But now you will say, hey, just now you taught the diagonal matrix. In the diagonal matrix, all the elements except the principal diagonal are equal or 0, then it is a diagonal matrix. So here also, all the elements except your principal diagonal are 0. So why not be calling it as diagonal matrix? So I would ask you to have a closer look at this and tell me what you see over here. So if you zoom in further, or if you wear your sunglasses, not sunglass, if you wear your goggles with -2.5 power, you will see that your diagonal matrix, principal diagonals, scalars are all equal. Okay, so that's what make it as a scalar matrices. Okay, so what is scalar matrix? A scalar matrix is a matrix is said to be a scalar matrix if and only if it is if all the elements in the principal diagonal are 0, and the principal diagonal elements should be equals to each other. Okay, so that is called a scalar matrices. So if all the elements in the diagonal matrix, okay, so all the elements in the diagonal matrix, and what are diagonal matrices? Diagonal matrices are the matrices where the elements except the main diagonal are 0. So if all the elements in the diagonal matrix are all the matrices in the diagonal matrices are of the is equal, means the principal diagonal is equal, then that is called the scalar matrix. So that is a scalar matrix. So please see the notes in the description for the definition, whatever I'm telling. So you could not write it out. Please see the description for the notes of whatever I'm telling. Okay, so this is your first example. So let's say second example, root 5 0 0 0 root 5 0 0 0 root 5. What is this? This is a scalar matrix. Now what do I tell to you is to multiply it with the sum matrix. Okay, so multiply with the same matrix, multiply some matrix, and then you will getting some other result. But I want to tell is to have a matrix like this, where all the diagonals are 1. That is your, so now multiply with any matrix just to make sure that is a matrix multiplication is defined. Multiply with any matrix or a vector, or a vector. You will be getting your matrix. So this is your scalar matrix. So let's say S as of now, and this is your any matrix or vector V. So when you multiply S times V, answer will be V. Means exact. So it is by multiplying by 1 you will get exactly. So please do and see the experiment. So when you multiply this matrix with some other matrix or a vector, you will be getting, it is just like multiplying this vector. This is 1. So whenever you multiply S times V, means these types of matrix where your principal diagonal is 1, all are 1, then you multiply with some matrix or vector, then that will yield or result to this vector, original vector to which you multiply the scalar matrix to. Okay, so that is so researchers, so scientists have seen this Y result and named this as a identity matrix. Name this as identity matrix or a unit matrix Okay, so when you multiply this identity matrix with any matrix, that is simply by multiplying 1, and you will be getting a result which is V. Okay, so you'll be getting the same result. So you may consider this matrix with 1, and if you multiply any even 10, you will be getting your 10 as output. So it is the same as that identity matrix. Oh my gosh, that the one who's is just flying the of pollution. I am really not liking that. No problem again. So over here, your identity matrix are just like a multiplication by 1. So please feel to, this is a wired property which we have given a new name, is the matrix or the scalar matrix where in your principal diagonals are all 1, then that's nothing but identity matrix. Okay, let's go on the next page. The next page, so let's talk about some last matrices with something called as triangular matrix. Triangular matrix. So the triangular matrix are of two types. So a square matrix, I'm just trying to matrix. So a square matrix is said to be a triangular matrix if the elements above, oh my gosh, my handwriting, above or below the principal diagonal, are 0. Okay, so for example, you have the diagonal 3, 4, 6, 1, 2, 3, and 0, 0, 0. Okay, so this is your, oh my gosh, what do I made over here? 3, 1, 2, 0, 4, 3, 0, 0, 6. Okay, so it is telling the triangular, this is a triangular matrix because all the elements, if the elements above means above, this is your principal diagonal, okay, so whatever above, if either above or below, either above or below. Or, here is your or. Okay, so either above or below, either above or below, either above or below to the main principal diagonal are 0, then that's called a triangular matrix. So here above is non-zeros but below is 0, so that's how we call it as a triangular matrix, because it forms a triangle. So that's why it's called a triangular matrix. And this is called the upper triangular, and here it forms the triangle. So here it forms the triangular part. Okay, so that is the upper triangular. So this where your zeros are below the main principal diagonal, so that is called the upper triangular matrix. Upper triangular matrix. And for example, you have 1 0 0 2 3 0 4 5 2, and over here this is your main diagonal. Okay, and above you have 0 and below, so that is the lower triangular matrix. That is a lower triangular because it forms the triangle low and below of the main diagonal. Okay, so that is the lower triangular matrix and upper triangular matrix. Cool. So I hope that you understood. So just to recapitulate, the triangular matrix is said to be a triangular matrix if the elements above that principal diagonal or below the principal diagonal are zeros. The elements what do you say? If the zeros are below the principal diagonal of the triangular matrix, then that is called the upper triangular matrix because it forms the triangle upper of the principal diagonal. And if the in the triangular matrix of your principal diagonal, if your zeros are above your principal diagonal, then that's nothing called as a lower triangular matrix. That is of two types. Cool. The last thing which I'm going to discuss is about symmetric matrix. Okay, so it is about symmetric matrix. It's about, what do you say? Repeat me with me. Symmetric matrix. Symmetric. Who knows? So you have this. So you have and when you do this, so it should be foldable. So that is symmetric. So this paper is symmetric. Okay. So the same way the matrices can be symmetric as well. The matrices can be symmetric as well. So what is symmetric matrix? So the definition of a symmetric matrix. If your A transpose is equals to the if your A transpose is equals to the A, so that's where we call that as a triangular or a symmetric matrix. Okay, so it's called as symmetric matrix if your A transpose is equals to A itself. Okay, so for example, I'm just going to take you can think of any example. This is your task, but I'm just going to take a small example of 2 4 6 9. Okay, so 2 4 6 9. So when you add the transpose, so this is your 2 by 2 matrix, and then if you do the transpose, it will be nothing. 2 6 4 9, 2 by 2, 2 by 2. Okay, so that is the 2 by 2. So over here you follow the equality of a matrix. So if you remember the equality of a matrix, of the matrices, so if a matrix A is only equals to matrix B, if its corresponding elements, this to this, this to this, this to this, this to this are equal, and they are of same order and they are of same size. Okay, so they are of same size, but this is equals to this. Okay, 4 is not equals to 6, so here this is not a symmetric matrix. Okay, so this is not a symmetric matrix. So your all symmetric matrix should be square matrix to be symmetric. Okay, but not every square matrix can be symmetric, but for being symmetric, your matrix should be square matrix for being symmetric. But it's not guaranteed that your every square matrix will be symmetric. But for being symmetric, you have to have a square matrix. For example, you have 2 2 2 2. Apply the transpose on this. What it will be? 2 2 2 2. 2 by 2, 2 by 2. This is correct. This is correct. Correspondings are also correct. The size is also correct. That is the symmetric matrix. That is the symmetric matrix, and I hope that you understood about the concept behind symmetric matrix. So this is all. So we had a talk on this stuff. So I hope that you liked this video, and I also talked a lot. And sorry for the crackers. Please find that guy and beat him as much as you can who's throwing up the crackers outside. So sorry, I included Hindi, but no problem. Okay, please feel free to scold that guy. Not beat him, because Diwali is a festival of having fun. But yeah, please scold that because they disturb you in studying. No problem. So I hope that you understood, and please feel free to do your homework assignments. So here is the homework assignment, the discussion for the solutions of the programming assignment, homework assignment is being released soon in the form of video. So you can assess that, but I will wait for two or 3 days, and then I will release one video on solving these homework assignments. Please feel free to do this, and please feel free, and I'm not giving these notes because these notes are already available in the description box below in the form of good handwriting in the description box below. Please feel free to assess. Thanks for seeing this video. I'll be catching up in the next video. Till then, bye bye. Have a great day. Bye bye. Hey everyone, so let's get started with a new lecture on lecture number 7, which is on determinant. And this is one of the again, I would say, important concept to study, because in principal component analysis, or whether you it comes a lot in your machine learning journey as well as in deep learning journey, because it tells you how to solving the linear equations, or if I talk about in terms of linear transformation, it just tells you how the change in area or a volume occurs. Okay, and determinant is nothing but you just give some matrix and then you get one number. So we'll be talking about that in detail in this session. I think you'll get a lot from this session, and you can make your own notes, or the notes is in description box below. Either it would be updated soon, but yeah, it is already being made. It's just sent for processing, and then it will be into your description. If you like this video, please be sure to subscribe this channel, as well as like this video and comment, because YouTube algorithm knows, okay, this is a good video to recommend, because many other people say your channel is underrated. So I want this channel to be a rated channel, because I work a lot on this channel. Okay, cool. So let's get started with solving what is determinant. So we'll get onto the geometric meaning soon, but in determinant, what you do, if you know about the square matrix, which we talked about, and I have told that is very important. Square matrix are very important. It's used extensively in linear algebra to use this terminology. So square matrix is nothing where your number of rows is equals to the number of columns. For example, your matrix A is maybe it can be 2 2 2 2. Okay, so this is a 2 by 2 where n equals to 2 and m equals to 2. So n times n matrix, where your square matrix is equals to where your number of rows is equals to the number of columns. Okay, so that is so what you do, you take your square matrix, and determinant takes one square matrix where the number of rows is equals to the number of columns. You write determinant of an A should be the square matrix. A should be the square matrix, and then you get one scalar or a number as an output when you apply the determinant function, or when you take out the determinant of that matrix. Okay, so now how this is useful, we will see how do we take out the scalar A just in a second numerically, but when you how the determinant is useful, this is one of the most important concepts to know. So the determinant is useful in solving linear equation. In linear equation, it's used very extensively solving linear equation, or maybe it can be useful in knowing, okay, in knowing how linear transformation, in knowing how linear transformation change their area or the volume. Okay, change their area, transformation change their area over volume, or volume. Okay, not over, it's or volume. And it is also and it is also useful in other stuffs like when solving some computationally. It does reduces some computer, not exactly means doing efficiently, not exactly I would say efficiently, I would say very precisely, so solving the particular linear equation, and is used a lot in that. So that's why we take out the determinant of a matrix, and that when you take out the determinant of a matrix, you simply give a square matrix to the determinant, and after when you take out the determinant, you will get one scalar. Okay, so this is what the this is what we use. And if you talk about and machine learning use case, so in machine learning, if you know about machine learning, in machine learning you have something called as dimensionality reduction method, and in that you take out the determinant of that covariance matrix. So covariance matrix. Okay, so when you take out the determinant of that covariance matrix, and then you and then go further into solving the particular problem. Okay, so not exactly covariance, yeah. So you take out the determinant, and then you go further into other stuffs like the eigenvectors and eigenvalues, and they are extensively used. The determinant are extensively used in the eigenvectors and eigenvalues in principal component analysis. Okay, so I hope that this is clear why we use determinant and what the determinant is. Now we need to care about how do we take out the scalar value, because we give a function, because we just give a square matrix into that determinant, and then we are just getting a scalar as an output. So how do we even do that? So for doing that, assume that you have a matrix A. You have a matrix A, which is nothing but 2 by 2. So I'm just going to write A, B, C, and D. Okay, so you have a matrix A, B, C, D, which is a 2 by 2 matrix. So when you take out the determinant of that matrix A, which is nothing but so AD means you take out the product of their diagonals. You take out the product of the diagonals. AD minus BC. AD minus BC. So for example, you have a matrix 2, 3, 4, 6, and then you want to take out the matrix, the determinant of that matrix, 2 by 2 matrix, which is nothing but 2 times 6 minus 3 times 4, 3 times 4, which is nothing but 6 to 12 minus 3, 4, 12. That will be nothing but 0. 0 is the answer, or determinant of this matrix. Okay, so determinant of a matrix can be 0. We don't have any conditions, but yeah, the determinant of this matrix is 0. Okay, so this is how you take out the determinant of a matrix, geometrically speaking. Okay, so one thing that I want to highlight over here, let's say for example, what does it mean geometrically? What does it mean geometrically? So let's let me make one more page so that I could explain you what does it mean geometrically speaking. What does it mean geometrically speaking? Either I could just go on some website to mean what is actually trying to tell. So let's go on one website. Which I want to show you all is this one. Okay, so assume that over here you have, let me choose my black color. Okay, here it is. So you have a matrix A, B, C, D. Okay, you want to take a determinant of this. So this is what you take out. So for taking out the determinant, you just write either in this A, B, C, D, giving pipelines like this. Okay, or you write determinant of this A matrix, and this A matrix is either A, B, C, D, like this. Okay, so this is the notation for showing that you want to take out the determinant of this matrix. Okay, that pipeline, that big pipeline. Okay, line. Okay, now over here your A is 1, your B is 0, your C is 0, and your D is 1. Okay, you want to take out the determinant of this. You want to take out the determinant of this. You want to take out the determinant of this. So how do you take out? So what does it mean geometrically speaking? So geometrically what it's trying to tell is, when you plot this matrix over here, first of all you take this and then you go over here. So this is nothing but the determinant of a 2 by 2 matrix is the area of a parallelogram with the column vectors AC and BD. Okay, so this is the determinant is nothing but the area of this parallelogram, where the column vectors are AC and BD. Okay, so when you plot the 2 by 2 matrix, which looks like this, and this the determinant, which means geometrically speaking, is nothing but area of that parallelogram which formed by joining everything, and that area of that parallelogram is nothing but determinant of that matrix. Okay, this is what does it mean geometrically speaking. I would ask you to watch one video on 3 blue 1 brown to see how is shown geometrically. But yeah, the determinant is nothing but the area of that parallelogram, whatever form. So for example, so let me reduce the a bit, and then let me do something with this. I don't know how it is working. Yeah, so let me do something like this, and let me increase the area. Okay, let me increase the B. Okay, here it is. So when you have the column vector, when you have a column vector at 0.86 and 0, okay, and then you have another column vector which is 0.52, and there the parallelogram is formed is nothing but your favorite, the determinant. Okay, so this is what the determinant means, and you can play with it by just going to demonstration Wolfram and this website. So let's go on the 3D view. So how does it look 3D? So 3D is nothing but area of that parallelozoid. Okay, so if you just see over here, the area of that parallelozoid is nothing but a determinant. We'll see how to solve this determinant one. Okay, we'll see how to solve how to take out the determinant of a 3 by 3 matrix, and we will also see how to take out the determinant of a n by n matrix. Okay, so it's a bit hectic task, but we will try to do it. So this is what the geometrically means, and for 2D the area of a parallelogram, and for 3D area of a parallelozoid. Okay, which you can see from the diagrams which are shown over here. So if you just if I could zoom in, I can't zoom in, but yeah, I can just show you. This is what you have, your 3 by 3 matrix, and then this is the parallelozoid which is formed, and then when you try to take out the determinant of this is nothing but the area of this parallelozoid. Okay, so this is what it means, and the determinant geometrically is nothing but the area of a parallelogram or parallelozoid in 3D dimension. Okay, so this is what you need in a geometric intuition, just to make sure that what the geometrical it means. Okay, so now let's see. Now one of the important thing which I want to show you up is we have seen how do we take out the determinant of a 2 by 2 matrix. So the determinant, so here's your A, here's your A, and you want to take out the determinant of this A, B, C, D, and I'm just writing pipe to denote, okay, this is a determinant. So when you try to take out the determinant of this, so it's nothing but equals to AD minus, oh my gosh, it's AD minus BC. That's then when you take out, this is simple scalar, which is E, not exactly that, not 3 plus 3.711, it's E. Okay, so let's give it any scalar which is E. Okay, so this is what it means in 2 by 2 matrix. I'm talking specifically 2 by 2 matrix. Now let's talk about how do we take out the determinant of 3 by 3 matrix. So determinant of 3 by 3 matrix. 3 by 3 matrix. So how do we even approach be taking out? So you want to take out the determinant of A, B, C, D, E, F, G, H, I. Okay, so G, H, I is this is your matrix. This is the determinant of this matrix. Okay, so how do you take out the determinant of this matrix? And of course it should be a one scalar. Okay, it should be one scalar or a number. Okay, so how do we take out the determinant? So can't we do A times E times I, and then it will not work. This is not, you can just guess how do we do it. Just try and comment. Maybe I can just see and be a bit funny and joke. So please be sure to write it, and I will try to see what you write it. Okay, so let's start approaching. How do we even approach this problem? So what we do we simply, so what we do, just make sure that first of all we go to the A11, okay, so means first element in that matrix, and then what we do, we simply leave this column and this row and write a minor matrix or a sub matrix of that big matrix, or you can say that we take out the minor of this matrix. How do we take out the minor of this matrix? You simply, when for example you choose this number, okay, so what do? You leave this column and you leave this row, and then you write and then what you do, you take out the minor and then you take out the determinant of that by multiplying by a. Okay, so the first element is this, and then you have E, F, H, I. We left this column and this row, and then we write E, F, H, I. Okay, we want to take out the determinant of E, F, H, I. Okay, now what you do? Yeah, here is your plus sign. Now it will be a minus sign over here. Okay, you go to the B, you leave this column and you leave this row. Okay, which is nothing but B and D, F, G, I. D, F, G, I, because we left this column, this row, and this column, just D, F, G, I. Okay, and then here is your minus, then here will be plus, you write C. Now we left this column, this column, and the first row, which will be left the determinant of D, E, G, H. Okay, and then we have convert. Now these are called the minor or a sub matrix or the minor of our matrix A. These are called the minor. These are called nothing but the minor. These are nothing but called the minor of our matrix A. Okay, so when you try to now it is very easy. A times EI. Now you can just apply your 2 by 2. A, EI and FH. EI minus FH. Okay, minus B, DI FH. DI minus FH. Okay, plus C, and then you have DH EG. Okay, DH minus EG. Okay, and then you'll be left with some scalar, and then you can simply do this thing, and then you simply multiply with this, and then you do some calculation, and then you'll be getting your output as maybe some scalar value. Okay, so let's see one of the problem or the stuff to see how it looks like. Okay, so let's assume that you have a matrix or a 3 by 3 matrix. So here's a question for you. Okay, maybe you can try to approach it. You want to take out the determinant of, I'm writing this pipe that denotes that you want to take out the determinant of that, for example, 0, 1, 2, 1, 2, 0. Let's write 1, 1, 0. Okay, it's just a random. I'll be walking you through it. So take out the determinant of this. This is a 3 by 3 matrix. Try to take out the determinant of this. So how do we take out? So first of all, we go to the first element, and then what we do, we take out the minor of this matrix. So the minor, so we leave this column and this row. So we'll be left with 0. And then we write our minor, and then we take out the determinant of our sub matrix. Okay, plus. Now no, it will be not plus over here, it will be minus, because here is our plus. Minus, okay, 1, you leave this column and this row, which will be 1, 0, 1, 0. Okay, so 1, 1, 0, 1, 0. Okay, and then you write plus 2, and then you have you leave 1, 2, 1, 1. Okay, you leave this column and this row. Okay, you leave this column and this row, you'll be left with 1, 2, 1, 1. Okay, and then you do the sum, and then you do the sum. So, and then you take, and then what you do, you try to take out 0. 2 times 0, which is 0, minus 0. Okay, minus 1 times 1 times 0, of course 0, and 1 times 0, 0. Okay, plus 2, 2. Okay, 1 times 1, 1, 2 times 1, 2. Okay, then you'll be left with, of course, 0, then it will be done, then it will be done. It will be also 1 times 0, which is nothing but 0. Okay, we'll be left with 2 times minus 2, 2 times minus 2, that will be minus 4. Okay, which is your determinant of this matrix. So minus 4 is your determinant of this matrix, which you are seeing over here. So sorry, here is 1 minus 2. It's not, it's It's simply -1, so 2 times -2 is the determinant of this matrix. So so here you got the determinant of this matrix, which is nothing but -2. Okay, so this is how you take out the determinant of a 3 by 3 matrix as well. So there are some problem for you to work on. So I'm just going to write it out. So there's one problem which you can approach. Okay, so you have to take out the determinant of 3, 7, 1, -4. Please answer the HW. Please answer in the comment box. It's just a quiz which you will see in your attendance as well. Okay, so this is what the determinant of that matrix, of the 2 by 2 matrix or a 3 by 3 matrix. We will try to solve the determinant of a 3 by 3 matrix using Leibniz formula or the rule of Sarus. Okay, so it's this very good formula to work on. So we'll see that. But before that, I want to highlight some of the properties of that properties of determinant matrix, of determinant of a matrix. So the first one is, for example, you want to take out the determinant of this matrix. For example, you want to take out the determinant of 1, 0, 0, 1. Okay, so try to take out the determinant of this. 1 times 1, which is 1, and then minus 0. Okay, what it will 1. And can you identify this is an identity matrix? Even if you have 3 by 3 identity matrix, then that will be nothing but 1. So whenever you have identity matrix, whenever you have if it is identity matrix, then the determinant of that identity matrix will be 1. Okay, this is one of the property. Second property, if the rows are the same. Okay, so for example, if the rows are the same for example A B B, okay, A B B, then AB minus BA will be nothing but 0. Okay, so this is another property. Third property is you have a scalar multiplied with some A, and you have another scalar C and B D. Okay, so what it will be, it just makes sense, RAD minus RCD or RCB. Okay, you can write it down like this, and then it's nothing, you just take that out of okay, you just take that as a common, R AD minus BC. Okay, so we can write this as a R times ABCD. Either we can write it now. So we proved it, so it is just equivalent. You can write this, so far it will be easily for us to solve. Okay, so it is R times, either it is same as over here, so we get AD minus BC, so it's just equivalent to that. So this is another property which you see a lot in while taking out the determinant of a matrix. Okay, so these are some of the properties which I want to highlight in front of you. So now let's go on to the another stuff, is how do we take out the determinant? How do we even bother taking out the determinant of 3 by 3 matrix? So you can just say, okay, I'm just going to take out the minor of the sub matrix of the matrix, and then I will do that. So here's another trick which is called the rule of Sarus. I think it's not a I would say okay, it's a good technique, but okay, you can try it out, but eventually I like that my approach. But yeah, it is very straightforward approach which I'm going to tell over here. Okay, so assume that you have a matrix M, okay, so A11, A12, A13, okay, A21, A22, A23, A23, A31, A32, A33. Okay, so you have this 3 by 3 matrix. Now when you wanted to take out the determinant of this matrix M, so how do we even bother doing that? So so you can use the rule of Sarus. I think the funny name he has, but yeah, again I'm no one to comment on his name. He's again a great people. Okay, so not even a 1% of these people. So these are amazing people who give a lot to the world. So I think about, I'm no one to say about, but yeah, amazing name. So what you do, you take out the determinant. So you want to take out the determinant of A11, A12, A13. Okay, so this matrix, I'm just writing this matrix, A21, A22, A23, okay, A31, A32, A33, okay. And then what you do, you take out the first two column and write it in another format like this, A11, A12, A21. This is a trick for solving a 3x3 matrix, A22 and A31, okay, so A31 and A32. So this is A22. Okay, it says A21, okay. So this is what now you write this. Now what you do? So what you do, you simply take out the product. You simply take out the product like this, the first diagonal, okay. So this is the diagonal. So what you do, A11, A22, A33, okay, A11, A22, A33 plus A12, A22, A23, okay, A23 and A31. So what you do, you take out the product of these three. So A12, A23, okay, A23 and A31, okay. Now what do, you simply do this, simply multiply the next diagonally, okay. So plus A13, A21, okay. I'm doing a bit messy, so let me do A31, if I'm not wrong, A13 na, A13, A21 and A32, okay, A13, A21, A32. Now you are done with this. Now what you do, you now go from bottom to top. Here you are going from top to bottom. Now you will go from bottom to top by changing the sign now, okay. Now you go from bottom to top. So here's how you do, here's how you go further, okay. So the way you go is, you have A31, so from here A31, okay, and then A22, and then you go to A13. So now you start going at this side like this, okay. So A31, I'm just going to write A31, A22, and then A13, okay. And then what do you do? And then plus, no, you minus, because you go from bottom to top, so here you minus it. Now you go at this one. Now you do this, and then A32, okay, this one, and this one. A32 times A23, yeah, it's A23 if I'm not wrong, yeah, A23 and A11, okay. Now minus, now this is done. Now you go at last one, which is this one, A33, A21, A12, okay. And here's how you take out the determinant of a matrix using Sarus rule, okay, or a rule of Sarus, okay. So and then you'll be getting, after doing this, all those stuffs, you can just cancel it out something if it is. So you just come do the computation. Then here's your matrix, and this is just a scalar number or other stuffs. So here's the rule of Sarus. So here's how you do write the first two column at the side, so that it could be easily. So what you do, you simply take out the product from top to bottom for the first three, and then you take out the bottom to top for the second three, starting from the last, okay. So here's what the rule of Sarus means. Here's how you take out the determinant of that matrix like this, okay. So now I'm going to talk about is, you can see the Wikipedia pages for a Leibniz rule, because they write a very kind of Leibniz stuff. So you can just go there and see more about this rule, okay. So the next thing which I'm going to talk about is, how do we take out the determinant? How do we take out, even bother taking out the determinant of n by n matrix, the determinant of n by n matrix? So how do we even take out that, and how do we even bother taking out that, okay. So I'm just going to write the n by n matrix. I'm just going to write the n by n matrix, or let's start with a particular example. So it would totally make sense, okay. So let's start with a particular example, and then at last we'll just write a definition, and then we'll end this video. Okay, the example is a bit long, so I'm just going to maintain my handwriting. So the example is, you want to take out the determinant. You want to take out the determinant of a 4x4 matrix. 1, 2, 3. Oh my gosh, 3, 4. Okay, 6, 6, 9, 2, 1. And then you have a 4, 9, 2, 1. And then you have a 0, 1, 1, 1. Okay, so here's your determinant of this matrix. So you want to take out the determinant of this matrix. So how do we even approach taking out the determinant of this matrix? So how do we take out the determinant of this? So for taking out the determinant of this, for taking out the determinant of this, you first of all take out the minor or a submatrix of this. Okay, so you go to the first column, first element, and then you leave this column and this row, and then write the submatrix. So you just 1, and then you take out the determinant of 9, 2, 1, 9, 2, 1, 1, 1, 1. Okay, this is plus sign, so it will be minus sign. Now you go at this, take out the submatrix, leaving this row, this column, and this row. So it would be 2. First of all, you take a product it, so you multiply with that 2 times the determinant of 6, 2, 1, 6, 2, 1, 4, 2, 1, and 0, 1, 1. Okay, and then you change the sign plus, and then go through with 3, and then you leave this column and this row, so it will be nothing but 3, and then you have 6, 2, 1. I also just write, okay, 6, 6, 6, 9, 1. I just leave it, so I'm 3, 6, 9, 1, 6, 9, 1, 4, 9, 1, 4, 9, 1, and 0, 1, 1. Okay, 0, 1, 1. Now the last one is there, 4. Okay, so there is 4, and then you take a determinant of leaving all the column 1 and then row 6, 9, 2, 6, 9, 2, 4, 9, 2, and okay, I think it's wrong, 4, 9, 2, and 0, 1, 1. Okay, so these are the submatrix of that matrix. Let's name it as a M. Okay, so this is a matrix M, and then you have to take a determinant of that matrix M. So here's the 4 by 4. Now you do this. Now you have this. Now what you do? Now here you convert it to 3 by 3 determinant. Now what you do? You convert that to a 2 by 2. Here's how you do. So you don't want to use the Sarus rule, because I eventually don't like that rule. It's a very hectic rule. Sometimes it maybe cause you error, but no problem in that. So here's how you do it. So first of all, what you do? You simply multiply 1. Okay, you simply go ahead and take your 1 as a, so if you can see, I just want to take that 1 as an this one, and then I go and approaching this. So here is your 9. So first of all, go at this element and take out 9. You want to take out the submatrix of this matrix, so 9, and then you want to take out the determinant of 2, 1, 1, 1. So how this came? 2, 1. So you leave this row and this column, 2, 1, 1, 1. Okay, now you simply change the sign minus. Okay, you make sure that you're only doing for this. You're only doing for this. We'll come to this later on, but we are only doing for this. A2, 1. Okay, minus. Now we go to this 2. Now we go this 2. We leave this column and this row, which is 9, 1, 1, 1. Okay, so which is array. What happened? Yeah, so which is nothing but what do you say? 2, because here is our 2, leaving this row, this column, and this row, 9, 1, 1, 1. Okay, the determinant of 9, 1, 1, 1. Okay, and then what you do? Plus. Now you change the sign, and then you go at last 1, leaving this 9, 2, 1, 1. Okay, so the 1 and the 9, 2, 1, 1. Okay, so you take out that. Okay, now this was plus, now you make it minus. Okay, now here is your 2, so I will take that outside. I will take that outside. Okay, and then I will just go ahead into solving this. So you take this as a, now you take out the minor of this matrix or the submatrix of this matrix. So here's how you do it. So you simply add it minus. So here is minus 6, 2, 1, 1, 1. So here's how you go with this. You ignore this column and this row 2 1 1 1. Now you go to this, you ignore this 4 1 0 4 1 0 1, and then you go to over here, ignore this 4 2 0 1. Okay, so this is how I'm gonna write -2. Okay, because you go over here 2 over -2, changing the sign, take out the determinant of 4 1 0 1 4 1 0 1. Okay, and then you simply plus, now you change the sign, you go 1, go to 1 4 2 0 1 4 2 0 1, plus 1 4 2 0 1. Okay, and then what do you do? And oh my gosh, yeah, so then what do you do? Now you converted that 3 by 3 matrix for this one and for this one. Now you go to this one, okay, by changing the sign, plus, and then you go and then you write separate 3. Now you write separate 3, and then you take out the first one 6. Okay, so you leave this, go to column and this row, which is nothing but 6, and then 9 1 1 1, which is the sum matrix of that matrix, minus 9, because this was plus 9. And how 9 came? You go at this column, leaving this column and leaving this row, 4 1 0 1, which is nothing but 4 1 0 1. Okay, plus changing the sign 1 4 9 0 1. How this 4 9 0 1 came is you have this, you leave this and this, you leave this column and this row, which is 4 9 0 1. Okay, so this is how you came it, and then you're done. Okay, now what do? You do for the last one, you do for the last one, this, because you're done for this, you're done for this, you're done for this. Now you converted that to a 2 by 2 matrix, which is easily determined, which we can easily take out the determinant. Now you go to this. Okay, so here's how you do it. So -4. Okay, and then what do? You leave this column and this row, taking out the first element. So 6, take the determinant of, I think it was 9 2 1 1 9 2 1 1 9 2 1 1 minus 9. Okay, so over here it was leaving this, the sec going to this and leaving this column and this row, which is 4 2 0 1. I think about it, yeah, that's 4 2 0 1 4 2 0 1, and then you change the sign, plus 2 4 9. I think it's more about, you go over here 4 9 0 1. Okay, that is 4 9 0 1. Okay, now you're done. Now this is what you have written. So you converted the first matrix, this one and this one as well, into a minor matrix, which is 2 by 2 determinant, so you can easily take out and then do the product and then you take out. Okay, so let's do over here, if I have a chance to do over here, but no problem, I will do over here. Okay, so here's how you do it. So for doing it, first of all, you have the one available, which is over here. What do? You simply 9 minus 16 plus 7. How we came? So you have the particularly 9 times, because of course you always want to multiply it out. Okay, so I think about this is, you have if you go over here, 2 times 1, okay, and 1 times 1. So 2 times 1, how much? 2 times 1, how much? It would be 1 minus 1, I would say 2 minus 1, which is 1, so it will be 9. Okay, minus over here, 9 times 1, which is 9, minus 1, which is 8, 16, minus 16 hua, done. And then you have 9 times 1, and then minus 2 times 1, so 9 minus 2, which is 7. Okay, so here's how it came. Okay, and then this is the left, minus 2. Now you go on second one, 2 over here. So when you take out 2 times 1, how much? 2 times 1, how much? 2 times 1, 2, minus 1. Okay, so that is 6 over here. So we write 6 minus 8 plus 4. Okay, so here's how you do. So it is 6 minus 4 times 1, of course, 4 times 2, it's 0 times 1, of course, 0. So 4 times 1, 4 times minus 2, which is minus 8, which you have written over here. Okay, then you go over here, 4 times 1, how much? 4 times 1, 4, and then you 4. So here's a plus 4. Now you go on the next, plus 3, because you go over here. Now 9 times 1, how much? 9 times 1, how much? 9 times 1, 9, of course, minus 1, which is nothing but 8. 8 times 6, 48. So you have 48 minus 36 plus 4. Okay, so here's how 48 minus 9. So 4 times 1, 4. So 4 9 36, because this 2 times 0 is 0. then you go over here, then you have this 9 times 0 is of course 0, 4 times 1, so 4 2 ja 8. So over here, I think I'm wrong over here. You have this 4 times 1 4, 9 times 0 0, so 4, it's 4, okay? So it's 4, it should be 8, okay? It should be 8, which is nothing but what you do, you 4 times 1 4, and then you simply multiply with 2, which is nothing but 8, okay? Now you simply minus 4, 28 minus 36 plus 8. So how you take out 9 times 1, how much? 9 minus 2, 7, 7, 7, 6, 7, 7, 6, ja? How much? Oops, it should be 9 times 1 minus 2, 9, 8, 7, 7, 6, 42, okay? So which will be nothing but 42. What the hell I've written over here? So I have to just couple it out. So I have to just return it. It will be nothing but 42, okay? Minus 4 times 1, of course, 4 9 is 36, plus 2 4 4 1 is 4, 4 2 is 8, okay? So here's how you do it. Now you simply multiply with this, and then first of all do the calculation, then you'll be getting one a scalar as your output. So please feel free to put your answer in the description box below. I know the answer, but yeah, I want to leave it to you to do the rest of the calculation, because I have done a lot. So here's how you take out the determinant of an n by n matrix, and how you do it, it's very easy. You just keep converting that to a lower or a sub matrix, and then after that you are done, okay? So here's how you do it. So you define one sub matrix Aij, you define one sub matrix Aij, which is nothing but the matrix, the n bar minus 1 times n minus 1 matrix, n minus 1 matrix. If you ignore the ith row and ith column, if you ignore the ith row, which you are doing, ith row and jth column, which we were doing, okay, that is your new matrix which we were forming. That is a recursive. This is a recursive. You can write a Python program for write a recursive solution for this, okay? So you were writing A1 and then you were adding the determinant of that submatrix, and then you are doing so and so on. That is a recursive solution. So you are writing the recursive stuff. So we already written a lot. So I hope that you understood. For formal definition, which you can see, yeah, we have gone through one of the example, which is very much important for us to know, okay? So I hope that you will get a lot from this video. And determinant, I hope that concept is clear with my examples, and I also hope that you enjoyed this video. I think I have to wrap up with this video. I'll be catching up in your next video. Till then, bye bye, have a great day, meet you in the next lecture. Okay everyone, let's get started with another lecture. I know it's a bit late lecture, but I apologize for that. I'll be making sure that I'll be providing you around 3 to 4 videos this week. So I already provided 2 videos now. I think about 2 or 3 videos will be provided more this week till your next assignment or a homework assignment. And please make sure that your homework assignment is released. If we find any student who are not active, we will remove them from our LMS, because this is an opportunity which are given for free for others to learn. Because if the people do not take this opportunity, we are gonna to drop that student. So we highly recommend to be active on LMS. Please do your assignments, please attend your attendance and every stuff, okay? So please go there and mark your attendance, and as well as complete your assignments. Even if you complete around, out of 25 questions, you have to complete around 20 questions. You can complete 20 questions, write in notebook, and then give it to us, okay? So your programming assignment, the homework assignment will be evaluated, and then that will be till the end of the course. And if we do not find you active in the course, we will drop you out, okay? So this is one of the announcement that our team has told me to give it to you all through me, okay? Cool. So what's the mode of this lecture? The mode of this lecture to talk about the cofactor, the minor and adjugate or the adjoint and inverse of a matrix. So these are very correlated. These are very correlated. For taking out the cofactor you need minor, and for taking out the minor you need determinant, and for taking out the adjugate you need cofactor, and taking out the inverse you need adjugate. Okay, so again I'm explaining. For taking out the cofactor of a matrix, you need minor, and for taking out the minor you need determinant, and after you take out, and for taking out the adjugate, you need cofactor, and then for taking out the inverse of a matrix you need adjugate. Okay, so these are very correlated, and they are heavily used for mainly this inverse of a matrix because they are so correlated. So I thought, okay, let's start with this video so that everyone knows about cofactor, how the inverse of a matrix is calculated, because it is extensively used in the industry. Okay. Mainly in linear algebra. It is not too much used in machine learning. Sometimes used in machine learning, but it's very good to know about these stuffs. Okay, so first of all, how do you be now let's go ahead and talking about the first two stuff, which is a minor of a matrix or the cofactor of a matrix. So let's start with a minor. Minor of a matrix. So a minor of a matrix A, as if you remember, the minor a minor of a matrix A, matrix A is the determinant of the some smaller square matrix. A minor of a matrix A is the determinant of some smaller square matrix. As you remember that what we do, we were removing the column and the row for that point or the element, and then we were obtaining a sum matrix in the determinant, and that's actually when you take out the determinant of that sum matrix, that's actually the minor, which we will see one example just in a second. For example, let's take an example that you have the following matrix. Okay, you want to take out the determinant of this matrix or the minor of this matrix. You want to take out the minor of this matrix. So for example, you told, okay, you want to take the minor of matrix M for ith row and jth column. Okay, that so you take out, so you, for example, you choose, okay, you want to remove the second row and the third column. Okay, so you are saying 2 3, so you want to take out the minor of a matrix given I equals to 2 and j equals to 3. So what it will do, it will leave second row and it will leave the third column. Okay, so the minor of this matrix A will be left with the sub matrix will be left with 1 4 minus 1 9, as you all are knowing. Okay, so now when you take out the determinant of this matrix, so 1 minus this is first of all for taking out the determinant of a 2 by 2 matrix. What we do, we simply multiply the diagonals and then subtract it. So 1 times 9, okay, minus of course this minus and minus 4. Okay, so that will be left with 9 plus 4, which is nothing but 13. So 13 is a minor of a matrix given I equals to 2 and j equals to 3. So what does it mean? We leave the second row and third column, or we delete the second row and third column to obtain the sub matrix. So that is the minor of that matrix. Okay, so again explaining what we do, we simply remove just one row and one column, and we take what row you want to remove and what column you want to remove by the user I and j. You remove one row and one column from the square matrix and make sure that is a square matrix. What is a square matrix? The square matrix is the one where the number of rows matches with the number of columns. Okay, so the number of rows matches with the number of columns, and over here when you take out the minor of this matrix A, given you remove one row and one column, so you remove the second row and the third column. For example, if you want to take 1 1, so the minor of this will be, you want to remove the first row and first column, the minor will be determinant of that 3 0, so sorry, it will be I think 0 5 9 11. So take out the determinant of this, so 0 times 11, 0 minus 9 times 5, 45. What it will be? It will be 45 or minus 45. Okay, so that will 45 around according to this. Okay, so that will be minus 45. So that's how what this minor tells you. Minor tells you, okay, you want to remove that column I, you want to remove that ith row and jth column, and then write down the matrix, and then take out the determinant of that sub matrix, and whatever the determinant will be, that will be your minor of that matrix. Okay, so this is what it's trying to tell you. So over here, oh my god, what is this? Where is my pen? So this is what it's trying to tell you over here. Okay, so what does minor means? Minor of A, a minor A is the determinant of some smaller matrix. Okay, so a matrix A is the determinant of some smaller matrix, for example, which you're seeing over here. And then so how do you take out? You remove one row and one column, and you write the rest of the matrix element into a new matrix, and then you take out the determinant of that matrix, and whatever the determinant, a scalar value, that scalar value will be the minor of that matrix. Okay, so this is how you calculate the minor of the matrix. So using minor of a matrix, you can calculate the cofactor of a matrix. Using minor of a matrix, you want to calculate the cofactor of a matrix. So why do we need to calculate the minor of a matrix? To calculate the cofactor, we need to calculate the minor. So what does it mean? So why do we even care about cofactor? Why do we need cofactor? So cofactor is required for computing determinants, computing high level determinant or larger determinants. Okay, computing larger determinants or determinants, and taking out the inverse of a matrix indirectly. Inverse of matrix indirectly, as it is not used directly over there. You want to take out the adjugate of that for taking out the inverse, but adjugate uses cofactor, and cofactor is being indirectly contributing to taking out the inverse of a matrix. We'll see the inverse of matrix, just we will visit after some slides. Okay, so this is what it means to be minor. So let's talk about the cofactor of a matrix. Let's talk about the cofactor of a matrix. So what is a cofactor? Cofactor is calculated. First of all, we need to calculate the minor. So for example, you have the following matrix. You have the following matrix 1 4 7 3 0 5 minus 1 9 11. Okay, so this is your 3 by 3 square matrix. You take out the minor of this matrix. Given I to be 2 and j to be 3. Okay, so you want to take out the determinant of the sub matrix So for example, I'm just taking one example. Given I equals to 2 and j equals to 3, so what you do, you leave the second row and third column, so left with 1 4 minus 1 9. So this is, and then when you take out the determinant of m23, that will be what? 9 times 1 9 minus 4, that will be nothing but 13. And as we shown, 9, first of all the product of the diagonals and subtract it minus 4, so that will be what? 13. Okay, so that is the minor of that matrix. Now when you take out the minor of the matrix, how to calculate the cofactor of a matrix? So for calculating the cofactor of a matrix, I and j, and make sure that I matches with the minor of that, and j matches with the minor of whatever the j over here. So these two should match, equals to minus 1 to the power of I plus j times the minor I and j. Okay, so this is how you calculate. So for example, for this example, let's calculate the cofactor. So how do we calculate the cofactor? So the here I is 2, 3, j is 3, is which is nothing but equals to minus 1, 2 plus 3 times 13. Okay, so whatever the value will be over here, we don't care of that. It will be minus 1 because it's 5 means minus 1 to the power 5. What it will be? Minus 1, of course, because if it is 6, then it will be 1. So it is minus 1 times 13. So the output will be, the answer will be minus 13 will be the cofactor of this matrix given I to be 2 and j to be 3. Okay, of that minor. Okay, of the 2, 3 and 3. Okay, so how you write the cofactor of 2, 3 and 3, where 2 is the row and j is the 2 is the row and 3 is a column, entry is minus 13. Okay, so this is how you calculate the cofactor of a particular matrix. Okay, so let's see one more example to make intuitive sense to you, so that it would not left in sense, oh my god, what is happening, with some example. So let's take an example that you have 2, 4, 6, 2, 1, 2, 1, 1, 1. So this is your matrix. So you select OK. You are selecting the third row. You're selecting the third row. You want to take out first of all minor. So you want to take out the third row and the first column. Okay. So third row and the first column. Okay. So you want to take out the minor of that. So first of all, you leave the third row and the first column. So the minor will be the sum matrix will be what? 4, 6, 1, 2. And when you try to take out the determinant of this, what it will be? 4 times 2 minus 6 times 1, which is nothing but 8 minus 6, which is nothing but 2. Okay, so the minor of 3, 1 entry is nothing but equals to 2. Okay, so after you calculate the minor, you wanted to calculate the cofactor, because you want to calculate the cofactor. So for calculating the cofactor, you need a minor. So you taken out the minor. Now when you calculate the cofactor of 2 by 3 entry of the it's 3 by 1 na? It's 3 by 1 entry, which will be what? So Cij, so formula is Cij, the cofactor of 3 I and j entry is nothing but minus 1 to the power of I plus j times the minor matrix I and j. So in this example, 2, 3 equals to minus 1, 2 plus 3 times 2. So what it will be? It will minus 1 to the power of 5 times 2. Okay, so that will minus 1 times 2, which will nothing but minus 2 is your cofactor of that matrix. Okay, so the cofactor of that matrix for that entry 3, 1 is minus 2. So this is how you calculate the cofactor of a matrix. So I'm just going to write the steps for you to calculate the cofactor of a matrix. So first of all, you take out the minor. You take out the minor Mij. How you take out the minor? So first of all, you take out the sum matrix. So you remove the one row, ith row. I'm just going to write remove ith row and jth column. Okay, and then whatever the sum matrix will be left, and then sum matrix, and whatever the sum matrix, take out the determinant of that sum matrix. Okay, that will be a minor. After you take out, now you can simply calculate the cofactor, which will be nothing but Cij, which is nothing but minus 1 to the power of y plus j times Mij. Okay, so this is how you calculate the cofactor of a matrix Cij for that Ij entry. Okay, so I hope that you understood what's the cofactor and what's the minor of that. So some of the applications. So over here, what you're trying to actually do is to so we can write. It's basically this cofactors are basically used prominently in Laplace formulas for the expansion of the larger determinants. Okay, as we have already seen. So the formula of determinant of A which is nothing but I equals to 1 all the way down to the n, aij minus 1 I plus j mij. Okay, so this is for taking of the determinant, as I told you, to one of the most best application of the cofactors it is used in is a Laplace formula for taking out the determinant of larger determinants. So this is the formula for taking out the determinant of A by using the cofactors. So I equals to 1 all the way down to the m aij times times, of course, minus 1. This is the cofactor of your matrix, and this is a minor of that. Okay, for that two I and j entry. Now, so we had seen the cofactor, we have seen the cofactor, and we have also seen the minor, and we have talked a lot about determinant, and we talked a lot about determinant. Now let's talk about the adjugate of a matrix. So the adjugate of a matrix, or sometimes call it as the adjoint of a matrix. So adjugate matrix. Okay, so we have to take out the adjugate of a matrix. So let's write it out. So how we take out the adjugate for matrix. So first of all, what is the adjugate of a matrix? So the adjugate of a matrix, or sometimes there's lots of names. Sometimes we call it as the adjugate, sometimes we call it as a classical adjoint, and a lot more. Okay, so this is a classical adjoint, we also call it as that. So how do we take out the adjugate of a matrix? Is nothing but the transpose of its transpose of its cofactor matrix. So adjugate of a matrix is nothing but the transpose of its cofactor matrix. Okay, so here's how you define it. So the adjugate of a matrix A is nothing but transpose of that cofactor matrix. Okay, so this is the cofactor matrix which you taken out for every I and j in your matrix. Okay, so adjugate is what? Is the transpose of that cofactor matrix. So here are some properties. So over here, the adjugate of A is nothing but C transpose, and it is nothing but minus 1. Of course, I'm writing the formula I plus j times mij. This is the formula for calculating. Okay, and I and j should go for all the elements. So I and j. Okay, so this is the I and j, and this is how you take out the adjugate of a matrix. This is the definition of the adjugate of a matrix. Okay, so one of the property is A times the inverse of the matrix. It means you have a matrix A and you have a matrix inverse of that. So the output will be, of course, always the identity matrix when you multiply the A matrix and the inverse of that matrix. So what is inverse of a matrix? So here's how we deal with it. So inverse of a matrix is nothing but the AI, how you calculate it. If you know about 1 over A, this is what we write, but here's how we do that. So 1 over the determinant of A times the adjugate of A And how do we calculate the adjugate of A? We calculate the adjugate of A by taking the transpose of our cofactor matrix. And you all know for taking out the cofactor matrix, we have this equation minus 1 to the power I plus j times m subscript I and j. Okay, so this is how you calculate the inverse of a matrix. How you calculate the 1 over the determinant of A times the adjugate of that matrix A. This is how you calculate the inverse of a matrix. It's not a big deal, it's just a small stuff which you are seeing over here. Okay, so we have a talk about inverse of matrix. So I'm just going to write it out in one detail about what we had a talk on this now. And one more thing over here, if the determinant of A is equals to 0, then your matrix, the matrix is not invertible. If your determinant of that A is 0, then your matrix A is not invertible, then it will be non-defined. Okay, so let me write it out what we had studied. We have our cofactor of a matrix. Cofactor of a matrix is nothing but minus 1 I plus j to the power of times m ij. Okay, and then you take out the adjugate of a matrix. The adjugate of a matrix A is nothing but what? The transpose of our cofactor matrix. And for taking out the inverse of that, for that matrix, for matrix A, we have 1 over the determinant of A times your adjugate of A. And if the determinant of A is 0, if determinant is 0, then your matrix is not invertible. Your matrix is not invertible. Okay, so this is whatever we have studied in this video, and I hope that you are able to understand. So in the next session, we started talking about the systems of equations, and we also talk about and then we will talk about eigenvectors and eigenvalues. We'll also talk about rank of a matrix and a trace of a matrix. So I think we should end this video. I'll be catching up in your next video. Till then, bye bye. Have a great day. Hey everyone, welcome to this next lecture on trace of a matrix. So in this video, I'm going to talk about a trace of a matrix. Okay, trace I will talk about how do we calculate the trace of a matrix, and this video is not only about trace. We'll talk about something called as Hadamard product, which is one of the most important stuff. We'll talk about its properties. We'll talk about a cyclic property of a trace as well. We'll talk about some more properties of a trace, and then we'll talk about what are some exceptions in trace, and then we'll talk about Norker product. I don't know how to pronounce it. I think a K is silent over here, so I think Ronnecker product. So we'll talk about that and how with one example. Okay, so this is the agenda for this video, and the notes for this video is in description box. So I hope that you will be able to go in the description box and see there the notes of this video. And maybe if you're wondering whom I'm writing on, it's the updated Microsoft whiteboard, and I simply think this is amazing. This is going to beat every whiteboard available in the market. So this is just an information from my side of the stuff. So let's get started talking about a trace of a matrix. But before that, I want to give you some class announcement. The first announcement is we are removing around 5 students from the course by personally emailing them, first of all, understanding what they're facing, and if we think okay, we can remove. If we don't get a response from that student, we are going to just remove them from the LMS. Okay, so new seats are being available, so you can go ahead and enroll for that LMS for absolutely free. It's absolutely free, so you can go ahead, and assignments are also being released. Okay, so if you're not able to do the assignments, you are most likely not going to get you are not getting the grades, and you'll most likely not able to pass the course. Okay, so let's talk about trace of a matrix. So these are some of the class announcements. So let's get ahead and talking about a trace of a matrix. So for taking out the trace of a matrix, it should be a square matrix. So for example, let's say you want to calculate the trace. You want to calculate the trace of a square matrix. So you want to calculate the square of you want to calculate the trace of a square matrix A. Okay, and usually write that and usually write that TR, and so this is the formal notation for denoting that we are taking out the trace of the matrix A. So this is read as taking out the trace. This one is nothing but your trace. There's nothing but your trace. Okay, so you're actually taking out the trace of a matrix A. Cool. So I think that this is good to go. So the trace of a matrix A is defined by TR, and then in bracket you write A. Okay, So how do we calculate the trace of a matrix? So how do we even bother calculating the trace? How do we even bother calculating the trace of a matrix? For calculating the trace of a matrix, we do sum of elements on the main diagonal of the matrix A. On the main diagonal of the matrix A, or you can say of A. Okay, and A is a matrix or a square matrix. So how do we calculate the trace of a matrix? The trace of a matrix is calculated by the sum of elements on the main diagonal of the A and B. Say for example, you have a matrix A. So let's assume that the matrix is 3 by 3 matrix. So let's assume the matrix is 3 by 3 matrix. So just I'm going to take the maybe this color shoots. Okay, so you have so let's write it out. A11, A12, A13. So let me just draw it over here as well. Okay, so we have that, and then let's draw A21, A22, A23, and let's pick this green color. Maybe 31, A32, and A33. So you have this matrix. A. So you have this matrix A, and you wanted to calculate the trace of this matrix. So for calculating the trace of a matrix A, what you will do, you will just sum the elements of the main diagonal. So A11 plus A22 plus A33. Okay, so the main diagonal is this one, and this one, then this one. Okay, so and then you'll be getting your scalar as an output. It can be C, whatever the number is. Okay, so this is how you calculate the trace of a particular matrix, and formally I can define this as a, oh my god, I think summation is not written correctly. I equals to 1 all the way down to the 3, means in this case we want for a 3 by 3 matrix. So I equals to 1 all the way down to the 3, all the way down to the 3, I. Okay, so if we go on, first of all, I equals to 1, then that will be A11 plus A22 plus A33. Okay, so this is what the formal notation for summation notation, or the for loop for taking the trace of a matrix. Okay, so let's take one example to perform the necessary actions. So let's say for particularly you have a data, you have the particular matrix, you have particular matrix A. So just drawing the same matrix, and let's draw let's take 1 0 3, and let's take this yellow, and let's write 11 5 2. Let's take green, and let's write 6 12 minus 5, and then let's draw a matrix. So you have this matrix. Now you're going to calculate the trace of this matrix. The trace of a matrix is nothing but you're going to calculate the trace of the matrix A. The trace of a matrix A is nothing but it will go from I equals to 1 all the way around to 3, AI times AI. I think it's AI times I. Okay, this is what you, and then summation. This is the summation. So it will add it up. So 1 plus 5 plus minus 5, which will be nothing but 1, and 1 is the trace of a particular matrix. Okay, so this is the 1 is a trace of the particular matrix, and I hope that you are able to make sense out of it. And why do we even bother studying trace? Because when you go further, when solving some linear equations or systems of equations, and this is mostly used and in other formulas, mainly not in specifically in linear algebra, mainly some other formulas. These straight trace of a matrix helps the computation to be easier, or help the too much notations, as well as it has some cool properties. Okay, so this is very, very helpful, not in only the context of deep learning or machine learning. It is most in the context of maths and mathematics, and you get in linear algebra, and you get in other maths field or discrete applications. Okay, so this is what the trace of a matrix. So we have to show you one example, so I hope that you are able to make sense out of it. Cool. So let's see some of the properties of the trace of a matrix. So some of the properties of a trace of a matrix, I'm just going to write in black. So the properties. So the first property which I want to highlight, is the trace of the matrix A plus B can be written as the trace of the individual matrix A plus trace of a matrix B. So I can write in this particular format. Now the second, so you can just think about it a bit. Means let me just show you if I can. I will just ask you to do experiment with it, but I will just take an example to prove it. Example. Okay, so let's assume that you're given a matrix A, which is 2 2 2 2, and you're given a matrix B, and you're given a matrix B 3 3 3 3. Okay, and you want to calculate the trace of a matrix A plus B. Okay, A plus B. So what you can do, first of all, you can calculate the trace of a matrix A. Calculate the trace of matrix A. So the trace of a matrix A is nothing but 2 plus 2, okay, which is 4. Okay, and the trace of a matrix B, which is nothing but 3 plus 3, 6. And then trace of A plus trace of B, which is nothing but 4 plus 6, but 10. Okay, so this is how what you can take it out. Or in other words, now if you first of all, now this is the 10. We have taken out the this side, RHS side. Let's see the LH side. So in LHS, so let's say for a particular example, for example, let's take these one matrix and then try to add it first. So first of all, we'll add it. So let's add this matrix A and B. So 2 plus 3, which is 5, then 2 plus 3, which is 5, 5, 5. So we got 2 by 2 matrix when adding these two matrix, two element wise addition. So you get a matrix A plus B, which is this one. Now if you calculate the trace of this particular matrix A plus B, so the trace is the sum of the elements in the main diagonal. So 5 plus 5 is what? 10. And we had proved, therefore LHS is equals to RHS, and hence proved. Okay, so this property is proved like this. Okay, so this is how you can prove the properties if you want, and this is very, very useful if you want to get the clarity in your particular matrix. Okay, so another property which I want to showcase to you all is another property, which is the trace of a matrix when it is multiplied with some scalar C, Okay, so what is the trace of this matrix? So A is a matrix and C is some scalar. So that is equivalent equals to C trace of A. Okay, so first of all, you take out the trace of A and then multiply with that C. Okay, and that actually, C, what it does is just stretches. It simply means it stretches your matrix. Okay, and if you talk about a geometric view, okay, so it's exactly what it's trying to do. You can hence prove it as well. Say for example, you have a, let's say for a particular example, let's say you have a matrix A which is 2 2 2 2, okay, and you have the scalar C which is 2, okay, which is 2. So this is, and then you want to take out the trace of CA. So first of all, you can take out the trace. So the trace of A is, so it is, first of all, let's take out the trace of A. The trace of A is 4. The trace of A is 4. 2 plus 2, 4. And then when you multiply the trace of with 2 times the trace of A, which is nothing but 4 times 2, which is nothing but 8, is a particular answer of that question. Okay, so 8 is the particular answer for that question, and it makes sense. You can, this is your RHS proved, and sorry, yeah, RHS proved. You can prove it the same. So when you take out the trace of the matrix, which is the matrix is 8, it's 4 plus, oh my god, 4 4 4 4, and then we take out the trace of this matrix, which is 4 plus 4, 8. So, and hence proved. So RHS under E equals to LHS. Okay, so these are the properties which are not going to prove all of the properties. I've just showed you how I proceed proving this stuff. Okay, so another property is a trace of a matrix A is equals to the trace of a transpose of that matrix. It gives you a clarity whether we transpose it, that the main diagonal will be the same and the trace will be also the same. Okay, so I need to prove it to showcase to you all to see the interesting property of this. The interesting property of this, let's say for example, you have a 2, 2, 2, 2, my favorite matrix. So it is a square matrix, because for particular trace you need to have a square matrix, and yeah, it would work well. Okay, so you have a square matrix 2 by 2. Okay, so when you do the transpose of this matrix, when you do, not exactly, you don't need a square matrix to be done transpose, you just need to dump some of the elements of the main diagonal. You don't need to do the you need not to have only the square matrix. I'm just taking an example to make it convenient for you. So first of all, you take out the trace of this. So let's first of all take out the trace of this matrix. The first which is 4. Trace of this will be 4, because the main diagonal 2 plus 2 is 4. Okay, when you transpose it 2, 2, 2, 2. Okay, 2, 2. Okay, so this is how it looks, and when you go ahead and then add it, it is also 4. Okay, the transpose does not matter, and of course I have taken very easy examples and hence proved. Okay, so whether you do the transpose, the diagonals will remain same. Now next property is the trace of a product. So let's talk about another great stuff, which is a trace of a product. Trace of a product, and the trace of product is the trace of A transpose B. Okay, is equals to a trace of AB transpose, which is also equals to trace of B transpose A, which is also equals to trace of BA transpose. Okay, so these are equivalent, equal, whatever we have written. These all are equivalent, equal, whatever I have written over here, and is nothing but we are multiplying the two matrices, the trace of the product. Okay, so I hope that you are able to make sense out of it. It's not a big deal for you. Okay, so this is just a basic properties which I'm highlighting. Okay, so we have seen some of the properties, and I want to talk about some more properties which are more useful. Means we are also going to gather some information about other kind of products, okay, that we are going to deal with. Okay, so let's talk about the Hadamard product. Okay, and Hadamard product is one of the most important product which you will see. So let's talk about Hadamard product. And it's very important as well, because if anybody go on Wikipedia and see some properties, what is Hadamard product and what is Kronecker product, we shall see that. But before that, I want to highlight one more property of a trace. The trace, the cyclic property, which I can't forget. Means I can't forget it. If I forget it, no one is gonna relieve me. So I'm just highlight the cyclic property of trace. Okay, and then we'll talk about two kind of product, which is Hadamard product and Kronecker product. Okay, so we'll talk about that two kind of product in detail. Okay, so the cyclic property says that let's say for example, you're going to calculate the trace of a matrix A, B, C, D. Okay, A, B, C, D is just a multiplication of a 4 matrix. So it is nothing but equals to, you can just B, A, C, D, which is nothing but equals to trace of C, B, I think it's C, D, A, B, C, D, A, B, which is nothing but trace of D, A, B, C. Okay, so first of all, B gone to the B gone first, then C gone first, then D gone first. Okay, that's a cyclic property. It goes in cycle. Okay, but arbitrary permutations are not allowed. But arbitrary but these are not allowed. I think I done wrong over here. It should be something like first of all it was B, and then it should be C, B, A, D. I think so, like this. Yeah, I hope so. It should be like this. And then when you go ahead, yeah, so it should be something like this. And then you keep on rotating. I have to recheck the thing, but it keeps on rotating. So the trace of the cyclic property says over here. So BCDA, then you have a CDAB. So first of all, B gone first, and then we have CD and A gone last. Okay, and then this is a cyclic permutations. That trace is an invariant under the cyclic permutations, and the permutations you all know. You can check this out. This is the property. This property is known as cyclic permutation. And one more thing I want to highlight over here, that no arbitrary permutations are allowed. You cannot do something like this. Okay, so you have to have the symmetric matrices are considered. It means if the product of three matrices, symmetric matrices are considered, then any permutation is allowed. So for example, if it is symmetric matrix, and for being a symmetric matrix, it should be equal to its transpose. The matrix product should be equal to transpose, and the trace of a matrix should be equal to the transpose of that matrix, trace of the transpose of that matrix. Then it's called the symmetric matrix, and then any permutations is allowed. Okay, any permutations is allowed, except this is the only case where the any permutation is allowed. Otherwise we don't allow any permutations are allowed in cyclic property. Okay, so this is cyclic property which you have to remember. Okay, I may have written it wrong, but I hope that you will correct it out by the Wikipedia page. So this was the cyclic property which I want to highlight, and I hope that you are able to understand it in a much better way. So let's talk about let's talk about Hadamard product. So let's talk about Hadamard product, which are big because we hadn't have a chance to talk on this Hadamard product as it seems to be a bit useful for me, because it is also used in various quantum computing as well as machine learning as well as deep learning. So let's assume that you want to take out the I'm saying dot product. It should be Hadamard product. Hadamard product, when it multiplies with the two matrices, it just do the element wise product. Okay, and the matrix, and just do the element wise product, and gives another matrix of this of the same dimension. Okay, so let's say for example, to give a matrix A, multiply the matrix B. Okay, and this is the sign for the Hadamard product is just a small o. Okay, so let's say you have a matrix A. We have a matrix A, A11, A12, A13, A21, A22, A23, A31, A32, A33. So you have this matrix A. You have this matrix A, and you have another matrix B, and you have another matrix B, and another matrix B is maybe B11, B12, B13, B21, B22, B23, B31, B32, B33. Okay, you have the two matrices, and when you take out the Hadamard product between these two matrices, which will be nothing but the product wise multiplication. So A11, B11, A12, B12, A13, B13, then A21, B21, A22, B22, A23, B23, okay, A31, B31, it should be A32, B32, and then A33, B33, okay. So this is your matrix, the Hadamard product, which is element wise product. Okay, so I hope that you are able to get out means element wise product. It's not a big deal. It's very easy to understand. Okay, so some of the properties of this, some of the properties which I want to highlight, properties which I want to highlight. Some of the properties of this particular product is you can write it out in this format, which is equals to this. Sorry, B times A, B dot B circle A, and then A, and then B C, which is nothing but equals to A B dot C. I hope that you all remember the properties name. Okay, another is A B plus C which is nothing but equals to A B plus A C. Okay, so these are some of the properties which are highlighting over here. A C is nothing but equals to okay, you can write it out something like this: A0, which is nothing but equals to 0 time with 0A, which is nothing but equals to 0. Okay, so these are some of the properties of a Hadamard product, which I want you to think about it and solve it on your own and prove it and prove these properties if you want. Okay, and just like I've taken some examples and proved it. So let's talk about another. So I'm just going to show you one of the property of the trace of a trace of a Hadamard product. The trace of the Hadamard product. Where is that? Trace of a Hadamard product. I'm not seeing where that, but yeah, it's one of the important stuff. But yeah, let's go ahead and talking about Kronecker product. I don't know how to pronounce it. I'm pronouncing it good or bad way, but I want you to think about this. Means you wanted to the something called as a Kronecker product. Kronecker product. So I think we have to talk on this. So Kronecker product. Let's talk about this Kronecker product. So you have a matrix A. You want to do the Kronecker product A and B between A and B. Okay, so let's say, and this is the Kronecker product sign for showcasing. Okay, this is a Kronecker product, and this is how it looks: 1 2 3 4, and then like this, 0 5 6 7. Okay, and this is how the Kronecker product works. So what you do, you make a big matrix, means a big matrix like this, and you take this first element and multiply with all as a scalar, and multiply with the matrix on another matrix B. So something like this: 0 5 6 7. Okay, and then you go on as a 2 as a scalar in the second element. You have 0 5 6 7. Okay, third element you 3 0 5 6 7. Okay, 4 0 5 6 7. Okay, this is how it should work. And then what you do, you simply and then you follow your whole procedure. The whole procedure is which is nothing but 1 times 0, then 1 times 5, 1 times 5, then we have 1 times 6, 1 times 6, 1 times 7. For this one, I'm doing like this. Okay, and then you keep on doing this: 3 times 0, 3 times 5, 3 times 6, 3 times 7. I'm doing for this, and then let's do for the same: 2 times 0, then 2 times 5, 2 times 6, 2 times 7, 4 times 0, 4 times 5, 4 times 6, 4 times 7. Okay, and then when you do this stuff, you'll be left with 0 5 0 10, 6 7 12 14, 0 5 15 actually, 0 20, and 18 21 24 28. And this is what you get as a 4x4 matrix. This is nothing but called the Kronecker product, and one of the property and trace, this is the trace of this Kronecker product can be written like this, can be written like this, trace of A, and then times the trace of B. Okay, so you can write it something like this. But one thing which I want to highlight over here, you cannot do something like this in a regular case in your if I could show it to you, if I could have a chance to show it to you. So let me just show it on a Wikipedia page. I think that exactly not equals to So the trace, if you see the trace of a matrix product, okay, the trace of matrix product, it cannot be written like A times B as a matrix product, a usual matrix product, which is trace of A, which is completely wrong. It cannot be written. But there's a case which is the Kronecker product, which we can write it something like this. But in matrix product, we are not allowed to do that. Okay. So this was the bit about this Kronecker product, and I hope that you understood the Hadamard product and the trace of a matrix. So I hope that we are done with the core concepts of linear algebra. From the next session, we'll be starting talking about systems of equations, solving systems of equations, LU decomposition, Gaussian mixtures, and then we are done with this chapter. And I hope and I really appreciate your patience throughout this course. And I guarantee that you will learn calculus in the easiest way that I can. And I also hope that I will providing so much values to you all. I think it motivates me, like if I see the watch hours and it's a bit increasing, and it motivates me a lot. Okay, people are watching these videos, so please keep watching. Please share this course. It's very, very important for me so that it could reach to lots of viewers, and I know this course will be boom in upcoming future, and many people are going to take benefit from this. And some of the comments are said that please don't stop uploading the videos. This course will be boom on future if I just complete the course and then I show it to the viewers. Hey, see, the course is completed. Complete this. It is more than a premium course. You're getting for absolutely free. You're getting the assignments. You're getting everything for free. So I think that it is so much of the features which are available for free. The people do not give when you pay for that. Okay, so I hope that's it for this video. I'll be catching up in the next video. Till then, bye-bye. Have a great day. So let's get started talking about systems of equations, as this is the last video on linear algebra series. And I hope that you are able to understand everything in linear algebra, as well as some of the videos of linear algebra is already released before, around nine videos. And I hope that you are able to make sense out of it. So we had a talk on everything which is required for deep learning, for further deep learning, is we have already talked about that. And one concept which I haven't talked is eigenvectors and eigenvalues. I'm going to talk about, I have already talked about this in my PCA videos. So as I haven't seen much of use in deep learning, but yeah, surely you can go to my PCAB video or principal component analysis video in ML001, and you can see there about eigenvectors and eigenvalues if you're interested in learning that. So this is the last video on systems of linear equations. So I'm just going to write linear as it does not make sense. So linear equations. So we'll try to solve. We'll first of all see what the systems of linear equation means. And we will see also how to solve this linear equations and every stuff. Okay, so what are linear equations? So first of all, let's start with the what is a linear equation. A linear equation it's an equation for a line. So as we have seen in linear regression, so this will be your linear equation. Whatever the hypothesis is, maybe the hypothesis h of x equals to theta 0 plus theta 1 times x1. Okay, so this equation is your linear equation. The reason why I'm saying it's a linear equation, because over here it does not have any powers. It has a power of a 1, and it is a straight line or a line. Okay, so some of the examples of linear equations, some of the examples of linear equation. So I'm just going to give some examples. So maybe y equals to 3.5 minus 0.5x. Okay, another example, maybe y equals to 0.57 minus x. Okay, but they both mean the same. They both is actually equivalent, whatever you write in that form or you write in that form. And you can also write this out in y plus 0.5x equals to 3.5. You have written that into another mode. You can also write y plus 0.5x minus 3.5 equals to 0. You have written that into a new mode, or you have written this into new mode. So they are equivalently the same linear equation. Equivalently, they are same linear equations. Same linear equation. They are not different linear equation. As you can see over here. So let me just show you. So first of all, let's see this one. Okay, y equals to 3.5 minus 0.5 times x. And if you compare y equals to 0.5, and when you do the manipulation of algebraic manipulation, you will get this, and you can check that exactly equivalent to that. Okay, which you can see 0.5 times 7 minus 0.5 times 6, exactly what that second equation is telling. And then you have just converted this 0 plus 0.5x on the left hand side, okay, and making that equals to 3.5. You just manipulated. This is algebraic manipulation, and they mean the same. Okay, so these are the linear equations which I have to show it to you. So we had a talk on linear equation. That is an equation for a line. Okay, so it's an equation. It's an equation of a line, or for a line, whatever. Okay, so what is systems of linear equation? So systems of linear equation is when we have two or more linear regression. It's linear equation. They are working together. Okay, so as from history, we have seen a particular statement is called something, and a group of particular statements are called something. Okay, so in the same way, for example, if you have seen my linear combination videos, so we had told the set of all the linear combination. I think, yeah, the linear combination is called span, and only one there is called a span. Okay, so the set of they are working together. So in the same way, the systems of equations are the set of, or when we have two or more linear equations working together. Okay, so system of equation, the definition of a systems of equation is when we have two or more, 2 plus linear equation, 2 plus linear equation, 2 plus linear equation. When we have 2 plus linear equation, when we have 2 plus linear equation, they are working together. They are working together. Then that's called system of equation. Working together. They are nothing but they are called system of linear equation. Okay, so systems of linear equation means there are two or more linear equations working together. That's nothing but the systems of equations. So for an example, so let's say for example, 2x plus y equals to 5 minus x plus y equals to 2. That is, you have the system of linear equation, and you need to find the value of x and y by solving this system of equation. We'll see how to solve system of equation using substitution, elimination, and algebraic manipulation. We'll try to see how to find x and y. So they both are working together. This is a system of linear equation. These both equations are linear equation, and using the system of linear, or you need to solve this system of equation by finding the value of x and y. Okay, so let's see how do we proceed further in solving the systems of linear equations. So I'm just going to see the recordings is being recorded. Yeah, correct, it is being recorded. Let's go ahead and solving the linear, it's systems. Why I'm saying the linear and linear regression, just want to share one incident. I was giving a speech, and there was a kind of stuff deep meaning. Okay, so I was having a quote, and then I was telling the beautiful line is the title of this, and the deep meaning. So I was in the stage and told the deep learning of this quote. So I was like, so seriously, I told the deep learning, but no problem. Again, I corrected it. But yeah, it was a funny. No one was knowing about deep learning in my school at that point. Okay, so solving. So we need to solve. Let's take one example. Let's take one example to solve one linear equation. To solve one linear equation. So let's go ahead. Let's go ahead. to solve the linear equation. So let's say solving, you need to solve this x plus y equals to 6, 3x plus y, which is nothing but equals to what? 2. Okay, so you need to find the value of x and y. So how you're going to proceed further? What we can do is simply merge them together, merge them into one question, into one equation by making the LHS to the LHS side and RHS to RHS side. Okay, so x plus y minus 3x plus y. Okay, so what I'm going to do is have over here we subtract it, so let's subtract it out. Okay, 6 minus 2, so we are subtracting the linear the equations. Okay, so from the second equation from the first equation, subtracting the second equation from the first equation, and then we are done. So we are subtracting it this. Now if we x plus y plus 3x minus y equals to 4, and then you proceed further, which is 4x, and then it is cut. Okay, 4x equals to 4 and x equals to 1. Okay, so when you say that you got 1, what you can do, so we now know the value of x, so after knowing the value of x, you can put them together. 1 plus y equals to 6. When you put x equals to 1, x equals to 1, 1 plus y equals to 6, and minus 3 times 1 plus y equals to 2, and y equals to I think 5, and maybe y equals to 5. Okay, so y equals to 5. Of course, you check with both the equations, and both the equations yields the same y when you put x's. Okay, so you can solve any of these equation, and maybe the first equation or the second equation, and then take y. I've just done to show you the check that okay, the second equation means the same what exactly the first equation means. Okay, so the value of x and y will be x equals to 1 and y equals to 5 is the solution to the system of equation. Okay, so when you find the value, so the question was to find the value of x and y, and you are done with finding the x and y values, and it is nothing but a beauty of algebra, and I seriously like algebra in these cases, and we'll see some of these geometric examples that how it is working, and geometry, the geometrical interface of the systems of equations. Okay, so I think that we are able to make sense out of it, and I also hope that you are able to understand it. Now we had seen the numerical understanding. Now let's try to simply understand the geometrical aspect of this. Okay, the geometrical aspect of this, let's say you have an x, you have an x and y axis. This is x and this is y axis. Okay, so let me to not write this out. Okay, but it make more sense in context of linear algebra. So let's write 2, 4, 6, 8, 10, 12. Okay, so let's go ahead with solving the same thing. 2, 4, 6, 8, 10, 12. Okay, now let's plot both of these equations. Let's plot both of these, x plus y equals to 6 and 3x plus y equals to 2. And graphing these is not a big deal. If you want to graph the equations, graphing the equations, I would like you, we'll cover that in the pre-calculus, but I would like you to have some context understanding of how we graph the equation. And the way we graph, the way I used to just in this example, let's assume that you want to grab the function, maybe f of x equals to x squared. How you're going to graph it? So you can just put the values of different x's and point and keep mark on the point, and then after certain x's value, just join that points, or not in the other words. Let's say for example, you do the same. You try with different values of x, you try with different values of y, and keep pointing over there. So then you are able to graph the equations. And if you're still confused, I would like you to send to one video, which will the link in description, like graphing the equations which is not a big deal. They just form a table and they just try different x's values, and then they get the y values, and then they try the y value, and then they get the x value. Okay, and they keep on doing it until they found some pattern in it, and it's not a big deal to find a pattern, or to have maybe 3 to 4 input values of x's and y. Then you'll be getting your the graph of that equation. Okay. So I think let's plot this x and y. So the plot of this x and y table will be nothing but what 6 and 8. I'm just going to have a good understand. So sorry, I'm not able to plot clearly. Let me just touch this. So it is touching actually 8. Okay, but it's looking very bad actually. So let me try. Okay, so let's assume that it touches 8. Okay, so this is 8. Okay, and this is 6, and this is an equation for your x plus y equals to 8. Let's try to plot maybe this one, this particular stuff. 3 minus 3x plus y equals to 2. Okay, so how you are going to plot it? So the plot of this would look something like this. So it looks something like this. So when you go ahead and touch this, so this is your the graph of 3x plus y equals to 2. This is a graph of that equation. And when you see over here, so now you have these two equations. Now if you go closer and closer to this, if you go a little bit closer to this, you'll be noticing that, okay, I think I have done a little bit wrong over here. I've done little bit wrong over here, of course, and I have done a little bit wrong over here. I should give 2 over here rather than giving 2 over there and 1 over here. Okay, but if you draw a graph formally on the graph paper, you'll be getting exact stuff, but I'm just assuming. Okay, something like this. Now the intersection which you're seeing over here, the intersection which you're seeing over here is actually your solution of x or the values, okay, or the values of x and y, or you find the solution to both of these. You already solved using graph of the value of x and y. How, where the points intersect. So I'm just going to write it out. Let's remove it first of all. So with the point it intersects, so it is nothing but 5, okay, at y, and there's nothing but 1 at x. So x equals to 1 and y equals to 5. So you get the answer from here as well by geometry purpose. So the point of intersection is where the lines intersect is actually the solution to that system of equation. Okay, so when you can plot it, maybe 3 linear equation, and it will be in if you 3 linear equation with the 2 variables. Okay, so maybe it may be on a 3-dimensional plane, and where the plane intersect, exactly that's the solution of x, y, and z. If there are 3 values x, y, and z, that's not a problem of a two-dimensional variable. That is of a problem with 3-dimensional variable, where you plot the plane. You have a plane, something like this, of x value, y value, and z value, and you have this is one of the linear equation. Maybe you have another linear equation, and maybe you have another linear equation. The point of intersection, maybe this one, is actually your solution to that x and y and z. Okay, so we'll see one geometric purpose later on, but this is how the 2D geometry. In 2D plane, this is if you want to find the value of x and y. The point of intersection of the linear equations is actually the solution to the values of you're able to find. We want to find it. Okay, so I hope that you're able to make sense out of it, and it's not a big deal to understand it. Okay, so I would like to go further into, we had a talk on this is the 2 variables, which is 2D plane stuff. So now let's go ahead and talking about what that linear equation, when we call a particular equation as a linear equation, and when we call the particular equation as a non-linear equation. So who can tell me that 2x plus y minus z equals to 4, is it a linear equation? Yes or no? I think this is a linear equation, but is this a linear equation? So sorry, I think I have done a wrong example, but no problem. 2x plus y squared minus z equals to 4. Is this a linear equation? Yes or no? It's no, because here the power is true as a quadratic equation. Okay, so this is not a linear equation over here, but this is a linear equation. Okay, so I'm just going to get started with talking about variables which you are dealing up. Okay, so variables which you are dealing it up. So if you see this example, if you see this example of this, x plus y equals to 6 and 3x plus y equals to 2, and then you add minus over here. So over here the system equation is a two-dimension. System equation is a two-dimension variables. Okay, why? Because you have only two variables, okay, x and y. But what if I add x plus y equals to, or plus maybe z equals to 6 and 3x plus y plus z equals to 2? So you are able to find x, y, and what about z? So this is a three-dimensional problem. The system equation is a three-dimensional. The system of equation is a three-dimensional stuff, and okay, so this is how we are able to make sense out of it, as of a two-dimension and three-dimensional variables. Okay, so let's get started solving up our problem. So we have this two-dimension and three-dimension. Okay, so I hope that you're able to understand what I'm trying to convey over here. But let me show you some other stuff. So here we are seeing only two linear equation in the system equation. This just identify minus 3x plus y equals to 2, and maybe 2x plus 2y equals to 16. Okay, so just let me know what is this a two dimension or three dimension? It is a two dimension because there are only two unique variables which you need to find. Okay, but what if I change 2z and maybe 2z, I just change it, and 2z plus 2y. It's a three-dimensional problem then. Okay, so it's just totally based upon the unique variables you have in your problem statement. So here we have more variables. You in a system equation you have more variables, and etc. Okay, so I hope that you're able to make sense out of it, and I also hope that you are able to understand it. Okay, so let's go. So I hope that it's just not a big deal for you at least, and please recapitulate if you're not even comfortable. Please rewatch the video again, I would ask you. Okay, so we had seen that maybe the line of intersection is called the solution to the system equation, but there are three types of possible solution cases. So the first type is no solution, second type is one solution, third type is infinitely many solutions. So for the system of equation, you can have either no solution, you can have either no solution, you can have either one solution, and you can have either infinitely many solution. Okay, so you can have one solution, no solution, exactly no solution for that system equation. You can have one solution for that equation, and then you can have infinitely many solutions for that. Okay, so when there is a no solution for that equations, that's called inconsistent, or if there is a one or infinitely many solutions, that's called consistent. Okay, so I will just go through the note again, but let's see what that geometric means. No solution, one solution, infinitely many solutions. Okay, so here is our graph. So over here, let's say for a simple example, this is your one. So this is maybe two variable stuff and two-dimensional stuff. So you have a two linear equation in that system of equation, and you have the first equation and you have the second equation, and which you can see over here, they do not intersect. They are parallel to each other. So that's why they have the no solution. Okay, so if there's a point, so this is an example of no solution. Another example is if you have this one, and you have the another equation something like this. The point of intersection, which is see over here, is this graph an example of one solution because there is one intersection at that point. Okay, the infinitely many solution graph would look like something like this. If you have something like x and y graph, and you have the first equation, and the second equation is on the same line of that first equation, then that's where we will be having the infinitely many solution to that linear equation. Okay, cool. So I hope that you are able to make sense out of it, and it's not a big deal to understand it. Okay, so these are three types of solutions, and when we call this, when there is a no solution, we call that as an inconsistent. We call this as an inconsistent, and these two are called the consistent. Okay, so I hope these are diagrams of two equations in a variable, in two variables. Not a big deal to understand it. Cool. So now we are done with it, and I think I spoke Hindi just before, no problem again. So solving system of equation. So now let's start solving system of equation. We had solved one system of equation using regular algebra, but basically in real world you not get a system of equation in very easy mode. You have to understand it, and I will ask you to solve this system of equation just to make sure that you're able to understand everything. So let's start with solving system of equation. So solving system of equation. So let's go ahead. 3x plus 2y equals to 19. So let's take one example. We'll solve this algebraically. Okay. Manipulation. We'll do a lot of manipulation in this. So let's take one example, and the example states 3x plus 2y equals to 19, and x plus y equals to 8. Okay, so over here you have this, and what we specifically do, we make that to I would say make that y, or whatever the variable which you find, into one side, and other stuff in the left opposite side of that, which is in RHS. So what I'm going to do is 3x plus 2y equals to 19, y equals to 8 minus x. So y equals to 8 minus x. So now my trick will be, I will replace the y over here with 8 minus x. Okay, replace y with 8 minus x So 3x plus 2, 8 minus x plus equals to 19, and you have y equals to, of course, 8 minus x. Okay, 8 minus x. Now what I will do, I will expand this. Okay, so after I expand this, 3x plus, let's try to expand. Okay, 3x plus 16 minus 2x equals to 19. Okay, so now you have this y equals to 8 minus x. Okay, so you have expanded it. Now what you will do, you will try to solve this. Okay, you will try to solve this one. So 3x minus 2x, which is of course x, and we have left with 16, so which is nothing but x plus 16 equals to 19, and y equals to 8 minus x. So x equals to 19 minus 6, and y equals to 8x, and this will be yielding to your favorite 16 minus, okay, it's 16, no? Yeah, it's 16, which is with 3, and then we got the value of 3. We got the value of 3. Now you put the value of 3 over here. So over here, 8 minus 3, which is nothing but 5. So you found x equals to 3 and y equals to 5 as a solution to this linear equation of the system of equation. I hope that this is very easy, not very hard to understand. This is the method called substitution, solving by substitution. Okay, so we substitute the values. So what I did, my technique was, first of all, make x on the one side, with all the variables on the one side, and all the things on the opposite side of that variable, which is the RHS in this case, and then try to take out and try to do the algebraic manipulation, and then you're done. You just find one variable, and another variable is in front of you. Okay, so now we are seeing these two variables. Now let's try to solving the system of equation of 3 equations in 3 variables. So we'll be having the 3 equations in 3 variables. Okay, so now let's see that how we are going to proceed further solving that. Okay, So let me just make that this point, and let's see, let's go further. So let's say x plus z equals to 6. Okay, x plus z equals to 6, z minus 3y, okay, z minus 3y equals to 7, and 2x plus y plus 3z equals to 15. I will try to be as much neat as possible to make sure that everything is going very fine. Okay, so what I will do, what in my hand is to do, is to, I'm seeing this x, I can make this x equals to 6 minus z. Okay, I can do something like that. Okay, so what I'm going to do is I can just make that x equals to 6 minus z. So let's go further. X equals to 6 minus z. Okay, x equals to 6 minus z. Now we have minus 3y plus z. Okay, minus 3y plus z, because I or in further. So let's assume, let's try it for or what I'm going to do is to give you a good idea about how to be clean. So what I will do, I'll make a separate spaces for all of them. So this is for x, y plus z, because we don't have y in this case, so we just leave the space for it, which is 6. Okay, z, which is z. Okay, so what I'm going to write, z plus 3y, okay, minus 3y equals to 7, and we have 2x plus y, which is for this, plus 3z equals to 15. This is called the neat. And then you go further, then what you do, you first of all x equals to, also sorry, I don't have to, first of all you have to go further. Okay, x, then you leave all the space for y and z. Okay, equals to 6 minus z. Okay, 6 minus z. Okay, so that the equation left alone, the variable left alone, and the end our LHS side. Okay, now you write the same thing again, minus 3y plus z equals to 7, and 2x plus y plus 3z equals to 15. Okay, now what I'm going to do is to substitute the values of x over here. Now I'm going to do is to substitute the values of x over here. So after substituting the, so let's substitute the values of x over here, which will be nothing but x, then we leave this space, equals to 6 minus z minus 3y plus z equals to 7, and 6 minus z plus y plus 3z, which is nothing but 15. Okay, now you substitute the values of x, and if you try to solve it, if you try to solve it, if you go ahead and try to solve this, we will getting this. If you go ahead and try to solve this, let's go ahead and solving this. Over here, if I just solve it, which is nothing but y plus z equals to 3. Okay, just I'm solving this, the last one, which is the last equation. I'll be getting a y plus z, which you can check it out. Okay, so if we are solving this 2x minus plus y plus 3z equals to 15, we are getting 6 minus z. Okay, now we are left with, x equals to 6 minus z. Okay, minus 3y plus z equals to, as usual, now we write y plus z equals to 3. Okay, now because this is the which we have solved. Okay, now we repeat the process again. Now over here I can just make z equals to y minus 3. Yes or no? Yes or no? Minus 3y plus z equals 7, and z equals to 3 minus y. I can do something like this to make the variable alone, so that we can substitute it. Now if we go ahead and substitute it, so if you go ahead and put the values of y, so x equals to 6 minus z, maybe 3y plus, sorry, z values. So z, what we're having, 3 minus y, isn't it? We were having, or not? Exactly, we're having the y cut, I think 3 minus y, okay, equals to 7. When you go ahead, which is nothing but z equals to 3 minus what do you say? You go further. Okay, so you are left with minus 4y plus 3. Okay, so you'll be and z equals to 3 minus y, which you are seeing over here. Okay, now we have this, now we have substituted the values. Now we'll try to solve it. So when we solve it, when solving minus 3y plus 3 minus y equals to 7, when you simplifies to minus 4y equals to 4, okay, or y equals to minus 1. Okay, when you try to solve this linear equation, and it's not a big deal to solve, what you can do, you can just add, you can just say, okay, this is minus 4y plus 3, which is minus 4y equals to 7 minus 3, and then we're left with 4, and when you try to, and when you will be left with minus 1. Okay, so this is what you get, y equals to minus 1. Okay, now you got the value of one value, which is x equals to 6 minus z, y equals to minus 1, and z equals to 3y, 3 minus y. Okay, 3 minus y, which you're having. Now we got the values of y. We can substitute the values in z. So x equals to 6 minus z, y equals to minus 1, and z equals to 3 minus 1. Okay, nothing but 4. Now we got the values of z. So x equals to 6 minus 4, which is 2. Okay, so we are done with x equals to 2, y equals to minus 1, and z equals to 4, which is our solution to our system of equation in a higher dimension, or in 3 variables. Okay, so this is the process called solving that by substitution, and it works nicely. Okay, it works very nice to most of the cases, but it's a very long process. Okay, it's a very long process, but I would recommend you to have a hands-on on this if you're not able to solve the system equation using regular algebra. Okay, so we had solved using this kind of stuff. Now let's try to solve the system equation by elimination. So I'm just going to write solving by elimination. Okay, so how do we even bother solving it? Example: 3x plus 2y equals to 19, and x plus y equals to 8. Okay, so this is we are going to solve it. Okay, so what this elimination means, we are going to either multiply, add, or subtract the equations from each other. So we'll see how to do that. So let's say, so over here, we are going to multiply the equation. So we are going to multiply. So you can see that over 2y is over here. So here is also y. So we are going to multiply the second equation with the 2. The second equation with the 2. So we are going to multiply the second equation by 2. 3x plus 2y equals to 19, and 2x plus 2y equals to 8. Okay, so when you will go further, you have this, and what you do, you simply have the particular, now you subtract the second equation from the first equation. You subtract this equation from the first equation. Okay, now you do the subtraction over here. So you're eliminating the variables from the first one. So 3x plus 2y minus 2x plus 2y, which is nothing but 3x plus 2y minus 2x minus 2y. So it get cut down. So you'll be left with x equals to what? 3. Okay, x equals to, because when you do this, 19 minus what are you saying? I think it's 19 or it's 16. Yeah. So this will be also 8. I don't know why I haven't multiplied the both side by 2. Now we have to multiply both side by 2. So 19 minus 16 will be 3. Okay, so 19 minus 16 will be 3. So now we got the values of x. So x equals to 3, and when you do this, 2x plus 2y equals to 16. Put the values of 3. 2 times 3 plus 2y equals 16. The y value would be 5, and you found x equals to 3 and y equals to 5. This is called the solving by elimination. First of all, you multiply the number by 2 for the second equation, and then you subtracted the second equation from the first equation, and you are done with solving your linear equation or system of linear equation. Okay, so this elimination is a little bit faster, but it needs a neatness. It needs you to have good logic, and it needs to have a good strategy. But you can solve whatever you like in the system equation. You can make use of any of them. If a system equation using elimination, algebraic manipulation, or maybe substitution, it totally makes sense to you. Okay, so thanks for seeing this video. I hope that you're able to make sense out of it. This was the last lecture on linear algebra. Well, I'm very excited to start with calculus. Okay, I'm going to teach the first time calculus, and whatever I know about calculus, I'm just going to put that in front of you, so that it would recapitulate whatever I studied as well. Okay, so and it makes sense. Okay, I am able to teach, then I'm able to understand that as well. Cool. So I'll be catching up in the next video. Till then, bye. Have a great day. Hey everyone, so let's get started with a new lecture on lecture number 7, which is on determinant. And this is one of the again, I would say, important concept to study, because in principal component analysis, or whether you it comes a lot in your machine learning journey as well as in deep learning journey, because it tells you how to solving the linear equations, or if I talk about in terms of linear transformation, it just tells you how the change in area or a volume occurs. Okay, and determinant is nothing but you just give some matrix and then you get one number. So we'll be talking about that in detail in this session. I think you'll get a lot from this session, and you can make your own notes, or the notes is in description box below. Either it would be updated soon, but yeah, it is already been made. It's just sent for processing, and then it will be in your description. If you like this video, please be sure to subscribe this channel, as well as like this video and comment, because YouTube algorithm knows, okay, this is a good video to recommend, because many other people say your channel is underrated. So I want this channel to be a rated channel, because I work a lot on this channel. Okay, cool. So let's get started with solving what is determinant. So we'll get onto the geometric meaning soon, but in determinant, what you do, if you know about a square matrix, which we talked about, and I have told that is very important. Square matrix are very important, is used extensively in linear algebra to use this terminology. So square matrix is nothing where your number of rows is equals to the number of columns. For example, your matrix A is maybe it can be 2 2 2 2. Okay, so this is a 2 by 2 where n equals to 2 and m equals to 2. So n times n matrix, where your square matrix is equals to where your number of rows is equals to the number of columns. Okay, so that is so what you do, you take your square matrix, and determinant takes one square matrix where the number of rows is equals to the number of columns. You write determinant of an A should be the square matrix. A should be the square matrix, and then you get one scalar or a number as an output when you apply the determinant function, or when you take out the determinant of that matrix. Okay, so now how this is useful, we will see how do we take out the scalar A just in a second numerically, but when you how the determinant is useful, this is one of the most important concepts to know. So the determinant is useful in solving linear equation. It's used very extensively solving linear equation, or maybe it can be useful in knowing, okay, in knowing how linear transformation, transformation change their area or the volume. Okay, change their area over volume, okay, not over, it's or volume. And it is also useful in other stuffs, like when solving some computationally, it does reduces some computer, not exactly means doing efficiently, not exactly I would say efficiently, I would say very precisely, so solving the particular linear equation, and is used a lot in that. So that's why we take out the determinant of a matrix, and that when you take out the determinant of a matrix, you simply give a square matrix to the determinant, and after when you take out the determinant, you will get one scalar. Okay, so this is what we use. And if we talk about in machine learning use case, so in machine learning, if you know about machine learning, in machine learning you have something called as dimensionality reduction method, and in that you take out the determinant of that covariance matrix. Okay, so when you take out the determinant of that covariance matrix, and then you and then go further into solving the particular problem. Okay, so not exactly covariance, yeah. So you take out the determinant and then you go further into other stuffs like the eigenvectors and eigenvalues, and they are extensively used. The determinant are extensively used in the eigenvectors and eigenvalues in principal component analysis. Okay, so I hope that this is clear why we use determinant and what the determinant is. Now we need to care about how do we take out the scalar value, because we give a function, because we just give a square matrix into that determinant, and then we are just getting a scalar as an output. So how do we even do that? So for doing that, assume that you have a matrix A. You have a matrix A, which is nothing but 2 by 2. So I'm just going to write A, B, C, and D. Okay, so you have the matrix A, B, C, D, which is a 2 by 2 matrix. So when you take out the determinant of that matrix A, which is nothing but so AD means you take out the product of their diagonals. You take out the product of the diagonals. AD minus BC. AD minus BC. So for example, you have a matrix 2, 3, 4, 6, and then you want to take out the matrix, the determinant of that matrix, 2 by 2 matrix, which is nothing but 2 times 6, 2 times 6 minus 3 times 4, 3 times 4, which is nothing but 6, 6, 2, 12 minus 3, 4, 12. That will be nothing but 0. 0 is the answer or determinant of this matrix. Okay, so the determinant of a matrix can be 0. We don't have any conditions, but yeah, the determinant of this matrix is 0. Okay, so this is how you take out the determinant of a matrix geometrically speaking. Okay, so one thing that I want to highlight over here, let's say for example, what does it mean geometrically? What does it mean geometrically? So let me make one more page so that I could explain you what does it mean geometrically speaking. What does it mean geometrically speaking? Either I could just go on some website to mean what is actually trying to tell. So let's go on one website. Which I want to show you all is this one. Okay, so assume that over here you have, let me choose my black color. Okay, here it is. So you have a matrix A, B, C, D. Okay, you want to take a determinant of this. So this is what you take out. So for taking out the determinant, you just write either in this A, B, C, D, giving pipelines like this. Okay, or you write determinant of this A matrix, and this A matrix is either A, B, C, D, like this. Okay, so this is the notation for showing that you want to take out the determinant of this matrix. Okay, that pipeline, that big pipeline. Okay, line. Okay, now over here your A is 1, your B is 0, your C is 0, and your D is 1. Okay, you want to take out the determinant of this. You want to take out the determinant of this. You want to take out the determinant of this. So how do you take out? So what does it mean geometrically speaking? So geometrically what it's trying to tell is, when you plot this matrix over here, first of all you take this and then you go over here. So this is nothing but the determinant of a 2 by 2 matrix is the area of a parallelogram with the column vectors AC and BD. Okay, so this is the determinant is nothing but the area of this parallelogram. Where the column vectors are AC and BD. Okay, so when you plot the 2 by 2 matrix, which looks like this, and this the determinant, which means geometrically speaking, is nothing but area of that parallelogram which formed by joining everything, and that area of that parallelogram is nothing but determinant of that matrix. Okay, this is what does it mean geometrically speaking. I would ask you to watch one video on 3 blue 1 brown to see how is shown geometrically. But yeah, the determinant is nothing but the area of that parallelogram whatever form. So for example, so let me reduce the A bit, and then let me do something with this. I don't know how it is working. Yeah, so let me do something like this, and let me increase the area. Okay, let me increase the B. Okay, here it is. So when you have the column vector, when you have a column vector as 0.86 and 0, okay, and then you have another column vector which is 0.52, and there the parallelogram is formed is nothing but your favorite, the determinant. Okay, so this is what the determinant means, and you can play with it by just going to demonstration Wolfram and this website. So let's go on the 3D view. So how does it look 3D? So 3D is nothing but area of that parallelozoid. Okay, so if you just see over here, the area of that parallelozoid is nothing but a determinant. We'll see how to solve this determinant one. Okay, we'll see how to solve how to take out the determinant of a 3x3 matrix, and we will also see how to take out the determinant of a n by n matrix. Okay, so it's a bit hectic task, but we will try to do it. So this is what the geometrically means, and for 2D the area of a parallelogram, and for 3D area of a parallelozoid. Okay, which you can see from the diagrams which are shown over here. So if you just if I could zoom in, I can't zoom in, but yeah, I can just show you. This is what you have, your 3x3 matrix, and then this is the parallelozoid which is formed, and then when you try to take out the determinant of this is nothing but the area of this parallelozoid. Okay, so this is what it means, and the determinant geometrically is nothing but the area of a parallelogram or parallelozoid in 3D dimension. Okay, so this is what you need in a geometric intuition, just to make sure that what the geometrical it means. Okay, so now let's see. Now one of the important thing which I want to show you up is we have seen how do we take out the determinant of a 2x2 matrix. So the determinant, so here's your A, here's your A, and you have and you want to take out the determinant of this A, B, C, D, and I'm just writing pipe to denote, okay, this is a determinant. So when you try to take out the determinant of this, so it's nothing but equals to AD minus, oh my gosh, it's AD minus BC. That's then when you take out, this is simple scalar, which is E, not exactly that, not 3 plus 3.711, it's E. Okay, so let's give it any scalar which is E. Okay, so this is what it means in 2x2 matrix. I'm talking specifically 2x2 matrix. Now let's talk about how do we take out the determinant of a 3x3 matrix. So determinant of 3x3 matrix. So how do we approach be taking out? So you want to take out the determinant of A, B, C, D, E, F, G, H, I. Okay, so G, H, I is this is your matrix. This is the determinant of this matrix. Okay, so how do you take out the determinant of this matrix? And of course it should be a one scalar. Okay, it should be one scalar or a number. Okay, so how do we take out the determinant? So can't we do A times E times I, and then it will not work. This is not, you can just guess how do we do it. Just try and comment. Maybe I can just see and be a bit funny in joke. So please be sure to write it, and I will try to see what you write it. Okay, so let's start approaching. How do we even approach this problem? So what we do, we simply just make sure that first of all we go to the A11. Okay, so means first element in that matrix, and then what we do, we simply leave this column and this row and write a minor matrix or a sub matrix of that big matrix, or you can say that we take out the minor of this matrix. How do we take out the minor of this matrix? You simply, when for example you choose this number. Okay, so what do? You leave this column and you leave this row, and then you write and then what you do, you take out the minor and then you take out the determinant of that by multiplying by A. Okay, so the first element is this, and then you have E, F, H, I. We left this column and this row, and then we write E, F, H, I. Okay, we want to take out the determinant of E, F, H, I. Okay, now what you do? Yeah, here is your plus sign. Now it will be a minus sign over here. Okay, you go to the B, you leave this column and you leave this row, okay, which is nothing but B and D, F, G, I. D, F, G, I, because we left this column, this row, and this column, which is D, F, G, I, okay. And then here is your minus, then here will be plus, you write C. Now we left this column, this column, and the first row, which will be left the determinant of D, E, G, H, okay. And then we have now these are called the minor or a submatrix or the minor of our matrix A. These are called the minor. These are called nothing but the minor. These are nothing but called the minor of our matrix A. Okay, so when you try to now, it is very easy. A times EI. Now you can just apply your 2 by 2. A, EI and FH. EI minus FH, okay, minus B, DI FH, DI minus FH, okay, plus C, and then you have DH EG, okay, DH minus EG, okay, and then you'll be left with some scalar, and then you can simply do this thing, and then you simply multiply with this, and then you do some calculation, and then you'll be getting your output as maybe some scalar value. Okay, so let's see one of the problem or the stuff to see how it looks like. Okay, so let's assume that you have a matrix or a 3 by 3 matrix. So here's a question for you. Okay, maybe you can try to approach it. You want to take out the determinant of, I'm writing this pipe that denotes that you want to take out the determinant of that, for example, 0, 1, 2, 1, 2, 0. Let's write 1, 1, 0. Okay, it's just a random. I'll be walking you through it. So take out the determinant of this. This is a 3 by 3 matrix. Try to take out the determinant of this. So how do we take out? So first of all, we go to the first element, and then what we do, we take out the minor of this matrix. So the minor, so we leave this column and this row. So we'll be left with 0. And then we write our minor, and then we take out the determinant of our submatrix. Okay, plus. Now no, it will be not plus over here, it will be minus, because here is our plus. Minus, okay, 1, you leave this column and this row, which is 1, 0, 1, 0. Okay, so 1, 1, 0, 1, 0. Okay, and then you write plus 2, and then you have you leave 1, 2, 1, 1. Okay, you leave this column and this row. Okay, you leave this column and this row, you'll be left with 1, 2, 1, 1. Okay, and then you do the sum, and then you do the sum. So, and then you take, and then what you do, you try to take out 0. 2 times 0, which is 0, minus 0. Okay, minus 1 times 1 times 0, of course 0, and 1 times 0, 0. Okay, plus 2, 2. Okay, 1 times 1, 1, 2 times 1, 2. Okay, then you'll be left with, of course, 0. Then it will be done. Then it will be done. It will be also 1 times 0, which is nothing but 0. Okay, we'll be left with 2 times minus 2. 2 times minus 2, that will be minus 4. Okay, which is your determinant of this matrix. So minus 4 is your determinant of this matrix, which you are seeing over here. So sorry, here is 1 minus 2. It's not, it's simply minus 1. So 2 times minus 2 is the determinant of this matrix. So here you got the determinant of this matrix, which is nothing but minus 2. Okay, so this is how you take out the determinant of a 3 by 3 matrix as well. So there are some problem for you to work on. So I'm just going to write it out. So there's one problem which you can approach. Okay, so you have to take out the determinant of 3, 7, 1, minus 4. Please answer the HW. Please answer in the comment box. It's just a quiz which you will see in your attendance as well. Okay, so this is what the determinant of that matrix, of the 2 by 2 matrix or 3 by 3 matrix. We will try to solve the determinant of a 3 by 3 matrix using Leibniz formula or the rule of Sarus. Okay, so it's this very good formula to work on. So we'll see that. But before that, I want to highlight some of the properties of that properties of determinant matrix, of determinant of a matrix. So the first one is, for example, you want to take out the determinant of this matrix. For example, you want to take out the determinant of 1 0 0 1. Okay, so try to take out the determinant of this. 1 times 1, which is 1, and then minus 0. Okay, what it will be? It will 1. And can you identify this is an identity matrix? Even if you have 3 by 3 identity matrix, then that will be nothing but 1. So whenever you have identity matrix, whenever you have, if it is identity matrix, then the determinant of that identity matrix will be 1. Okay, this is one of the property. Second property, if the rows are the same, okay, so for example, if the rows are the same, for example, A B B, okay, A B B, then AB minus BA will be nothing but 0. Okay, so this is another property. Third property is you have a scalar multiplied with some A, and you have another scalar C and B D. Okay, so what it will be? It just makes sense. RAD minus RCD or RCB. Okay, you can write it down like this, and then it's nothing. You just take that out of. Okay, you just take that as a common, R AD minus BC. Okay, so we can write this as a R times ABCD. Either we can write it na. So we proved it, so it is just equivalent. You can write this, so far it will be easily for us to solve. Okay, so it is R times, either it is same as over here, so we get AD minus BC, so it's just equivalent to that. So this is another property which you see a lot in while taking out the determinant of a matrix. Okay, so these are some of the properties which I want to highlight in front of you. So now let's go on to the another stuff, is how do we take out the determinant? How do we even bother taking out the determinant of 3 by 3 matrix? So you can just say, okay, I'm just going to take out the minor of the submatrix of the matrix, and then I will do that. So here's another trick which is called the rule of Sarus. I think it's not a I would say okay, it's a good technique, but okay, you can try it out, but eventually I like that my approach. But yeah, it is very straightforward approach which I'm going to tell over here. Okay, so assume that you have a matrix M, okay, so A11, A12, A13, okay, A21, A22, A23, A23, A31, A32, A33. Okay, so you have this 3 by 3 matrix. Now when you wanted to take out the determinant of this matrix M, so how do we even bother doing that? So so you can use the rule of Sarus. I think the funny name he has, but yeah, again I'm no one to comment on his name. He's again a great people. Okay, so I'm not even a 1% of these people. So these are amazing people who give a lot to the world. So I think about, I'm no one to say about, but yeah, amazing name. So what you do, you take out the determinant. So you have to take out the determinant of A11, A12, A13. Okay, so this matrix, I'm just writing this matrix, A21, A22, A23, okay, A31, A32, A33, okay. And then what you do, you take out the first two columns and write it in another format like this: A11, A12, A21. This is a trick for solving a 3 by 3 matrix. A22 and A31. Okay, so A31 and A32. So this is A22. Okay, it says A21. Okay, so this is what now you write this. Now what you do? So what you do, you simply take out the product. Like this, the first diagonal. Okay, so this is the diagonal. So what you do, A11, A22, A33. Okay, A11, A22, A33. plus A12, A22, A23, okay, A23 and A31. So what do? You take out the product of these three. So A12, A23, okay, A23 and A31. Okay. Now what do? You simply do this. Simply multiply the next diagonally. Okay. So plus A13, A21. Okay, I'm doing a bit messy, so let me do A31. If I'm not wrong, A13 na, A13, A21 and A32. Okay, A13, A21, A32. Now you are done with this. Now what do? You now go from bottom to top. Here you are going from top to bottom. Now you will go from bottom to top by changing the sign now. Okay, now you go from bottom to top. So here's how you do. Here's how you go further. Okay, so the way you go is you have A31. So from here A31. Okay, and then A22, and then you go to A13. So now you start going at this side like this. Okay, so A31, I'm just going to write A31, A22, and then A13. Okay, and then what do you do? And then plus, no, you minus, because you go from bottom to top. So here you minus it. Now you go at this one. Now you do this, and then A32. Okay, this one, and this one. A32 times A23. Yeah, it's A23 if I'm not wrong. Yeah, A23 and A11. Okay, now minus. Now this is done. Now you go at last one, which is this one. A33, A21, A12. Okay, and here's how you take out the determinant of a matrix using Sarus rule. Okay, or a rule of Sarus. Okay, so and then you'll be getting, after doing this all those stuffs, you can just cancel it out something if it is. So you just come do the computation. Then here's your matrix, and this is just a scalar number or other stuffs. So here's the rule of Sarus. So here's how you do. You do write the first two column at the side, so that it could be easily. So what you do, you simply take out the product from top to bottom for the first three, and then you take out the bottom to top for the second three, starting from the last. Okay, so here's what the rule of Sarus means. Here's how you take out the determinant of that matrix like this. Okay, so now I'm going to talk about is you can see the Wikipedia pages for a Leibniz rule, because they write a very kind of Leibniz stuff. So you can just go there and see more about this rule. Okay, so the next thing which I'm going to talk about is how do we take out the determinant? How do we even bother taking out the determinant of n by n matrix? The determinant of n by n matrix. So how do we even take out that, and how do we even bother taking out that? Okay, so I'm just going to write the n by n matrix. I'm just going to write the n by n matrix, or let's start with a particular example. So it would totally make sense. Okay, so let's start with a particular example, and then at last we'll just write a definition, and then we'll end this video. Okay, the example is a bit long, so I'm just going to maintain my handwriting. So the example is, you want to take out the determinant of a 4x4 matrix. 1, 2, 3, oh my gosh, 3, 4. Okay, 6, 6, 9, 2, 1, and then you have a 4, 9, 2, 1, and then you have a 0, 1, 1, 1. Okay, so here's your determinant of this matrix. So you want to take out the determinant of this matrix. So how do we even approach taking out the determinant of this matrix? So how do we take out the determinant of this? So for taking out the determinant of this, you first of all take out the minor or a submatrix of this. Okay, so you go to the first element, and then you leave this column and this row, and then write the submatrix. So you just 1, and then you take out the determinant of 9, 2, 1, 9 2 1 1 1 1. Okay, this is plus sign, so it will be minus sign. Now you go at this, take out the sum matrix, leaving this row, this column, and this row. So it would be 2. First of all, you take a product it, so you multiply with that 2 times the determinant of 6 2 1 6 2 1 4 2 1 and 0 1 1. Okay, and then you change the sign plus, and then go to a 3, and then you leave this column and this row, so it will be nothing but 3, and then you have 6 2 1. I also just write, okay, 6 6 6 9 1. I just leave it, so I'm 3 6 9 1 6 9 1 4 9 1 4 9 1 and 0 1 1. Okay, 0 1 1. Now the last one is there, 4. Okay, so there is 4, and then you take a determinant of leaving all the column 1 and then row 6 9 2 6 9 2 4 9 2 and okay, I think it's wrong, 4 9 2 and 0 1 1. Okay, so these are the sum matrix of that matrix. Let's name it as a M. Okay, so this is a matrix M, and then you have to take a determinant of that matrix M. So here's the 4 by 4. Now you do this. Now you have this. Now what you do? Now here you convert it to 3 by 3 determinant. Now what you do? You convert that to a 2 by 2. Here's how you do. So you don't want to use the Sarus rule, because I eventually don't like that rule. It's a very hectic rule. Sometimes it maybe cause you error, but no problem in that. So here's how you do it. So first of all, what you do? You simply multiply 1. Okay, you simply go ahead and take your 1 as a, so if you can see, I just want to take that 1 as an this one, and then I go and approaching this. So here is your 9. So first of all, go at this element and take out 9. You want to take out the sum matrix of this matrix, so 9, and then you take out the determinant of 2 1 1 1. So how this came, 2 1, so you leave this row and this column, 2 1 1 1. Okay, now you simply change the sign minus. Okay, you make sure that you're only doing for this. You're only doing for this. We'll come to this later on, but we are only doing for this. A21. Okay, minus. Now we go to this 2. Now we go this 2. We leave this column and this row, which is 9 1 1 1. Okay, so which is array. What happened? Yeah, so which is nothing but what do you say? 2, because here is our 2, leaving this row, this column and this row, 9 1 1 1. Okay, the determinant of 9 1 1 1. Okay, and then what you do, plus. Now you change the sign, and then you go at last 1, leaving this 9 2 1 1. Okay, so the 1 and the 9 2 1 1. Okay, so you take out that. Okay, now this was plus, now you make it minus. Okay, now here is your 2, so I will take that outside. I will take that outside. Okay, and then I will just go ahead into solving this. So you take this as a, now you take out the minor of this matrix, or the sum matrix of this matrix. So here's how you do it. So you simply add it minus. So here is minus 6 2 1 1 1. So here's how you go with this. You ignore this column and this row, 2 1 1 1. Now you go to this, you ignore this 4 1 0 4 1 0 1, and then you go over here, ignore this 4 2 0 1. Okay, so this is how I'm gonna write minus 2. Okay, because you go over here, 2 over minus 2, changing the sign, take out the determinant of 4 1 0 1 4 1 0 1. Okay, and then you simply plus, now you change the sign, you go 1, go to 1 4 2 0 1 4 2 0 1 plus 1 4 2 0 1. Okay, and then what you do, and oh my gosh, yeah, so then what you do, now you converted that 3 by 3 matrix for this one and for this one. Now you go to this one, okay, by changing the sign, plus, and then you go and then you write separate 3. Now you write separate 3, and then you take out the first one, 6. Okay, so you leave this, go to column and this row, which is nothing but 6, and then 9 1 1 1, which is the sum matrix of that matrix, minus 9, because this was plus 9. And how 9 came? You go at this column, leaving this column and leaving this row, 4 1 0 1, which is nothing but 4 1 0 1. Okay, plus changing the sign, 1 4 9 0 1. How this 4 9 0 1 came? is you have this, you leave this and this, you leave this column and this row, which is 4901. Okay, so this is how you came it, and then you're done. Okay, now what do? You do for the last one, you do for the last one, this, because you done for this, you done for this, you done for this. Now you converted that to a 2x2 matrix, which is easily determined, which we can easily take out the determinant. Now you go to this. Okay, so here's how you do it. So -4. Okay, and then what do? You leave this column and this row, taking out the first element. So 6, take the determinant of, I think it was 9211 minus 9. Okay, so over here it was leaving this, the sec going to this and leaving this column and this row, which is 4201. I think about it. Yeah, that's 4201, and then you change the sign, plus 2 49. I think it's more about, you go over here 4901. Okay, that is 4901. Okay, now you're done. Now this is what you have written. So you converted the first matrix, this one, and this one as well, into a minor matrix, which is 2x2 determinant. So you can easily take out and then do the product, and then you take out. Okay, so let's do over here, if I have a chance to do over here, but no problem, I will do over here. Okay, so here's how you do it. So for doing it, first of all, you have the one available, which is over here. What do? You simply 9 minus 16 plus 7. How we came? So you have the particularly 9 times, because of course you always want to multiply it out. Okay, so I think about this is, you have if you go over here, 2 times 1. Okay, and 1 times 1. So 2 times 1, how much? 2 times 1, how much? It would be 1 minus 1, I would say 2 minus 1, which is 1, so it will be 9. Okay, minus over here, 9 times 1, which is 9, minus 1, which is 8, 16, minus 16 hua, done. And then you have 9 times 1, and then minus 2 times 1, so 9 minus 2, which is 7. Okay, so here's how it came. Okay, and then this is the left, minus 2. Now you go on second one, 2 over here. So when you take out 2 times 1, how much? 2 times 1, how much? 2 times 1, 2, minus 1. Okay, so that is 6 over here. So we write 6 minus 8 plus 4. Okay, so here's how you do. So it is 6 minus 4 times 1, of course, 4 times 2, it's 0 times 1, of course, 0. So 4 times 1, 4 times minus 2, which is minus 8, which you have written over here. Okay, then you go over here, 4 times 1, how much? 4 times 1, 4, and then you 4. So here's a plus 4. Now you go on the next, plus 3, because you go over here. Now 9 times 1, how much? 9 times 1, how much? 9 times 1, 9, of course, minus 1, which is nothing but 8. 8 times 6, 48. So you have 48 minus 36 plus 4. Okay, so here's how 48 minus 9. So 4 times 1, 4. So 4 9 36, because this 2 times 0 is 0. Then you go over here, then you have this 9 times 0 is of course 0. 4 times 1, so 4 2 ja 8. So over here, I think I'm wrong over here. You have this 4 times 1, 4, 9 times 0, 0. So 4, it's 4. Okay, so it's 4. It should be 8. Okay, it should be 8, which is nothing but what you do. You 4 times 1, 4, and then you simply multiply with 2, which is nothing but 8. Okay, now you simply minus 4, 28 minus 36 plus 8. So how you take out 9 times 1, how much? 9 minus 2, 7, 7, 7, 6, 7, 7, 6 ja, how much? Oops, it should be 9 times 1 minus 2, 9, 8, 7, 7, 6, 42. Okay, so which will be nothing but 42. What the hell I've written over here? So I have to just couple it out. So I have to just return it. It will be nothing but 42. Okay, minus 4 times 1, of course, 4 9 is 36, plus 2 4 4 1 ja 4 4 2 ja 8. Okay, so here's how you do it. Now you simply multiply with this, and then first of all do the calculation, then you'll be getting one a scalar as your output. So please feel free to put your answer in the description box below. I know the answer, but yeah, I want to leave it to you to do the rest of the calculation, because I have done a lot. So here's how you take out the determinant of an n by n matrix, and how you do it, it's very easy. You just keep converting that to a lower or a sub matrix, and then after that you are done. Okay, so here's how you do it. So you define one sub matrix aij, which is nothing but the matrix, the n bar minus 1 times n minus 1 matrix, if you ignore the ith row and ith column. If you ignore the ith row, which you are doing, ith row and jth column, which we were doing. Okay, that is your new matrix which we were forming. That is a recursive. This is a recursive. You can write a Python program for write a recursive solution for this. Okay, so you were writing a1 and then you were adding the determinant of that sub matrix, and then you are doing so and so on. That is a recursive solution. So you are writing the recursive stuff. So we already written a lot. So I hope that you understood. For formal definition, which you can see, yeah, we have gone through one of the example, which is very much important for us to know. Okay, so I hope that you will get a lot from this video. And determinant, I hope that concept is clear with my examples, and I also hope that you enjoyed this video. I think I have to wrap up with this video. I'll be catching up in your next video. Till then, bye, have a great day. Meet you in the next lecture. Hey everyone, welcome to this first lecture on single variable calculus. From this video, I know it's been 6 days still the video is not being uploaded. It's because I was having some examination that I was preparing for, and I was preparing for the content for single variable calculus. So in this series of lecture, we'll be talking about single variable calculus. It's I would say we'll come to calculus, but we had a talk on linear algebra and some of the videos like eigenvector and eigenvalues to be added. Okay, so that is to be added, and that is sent into, that is we are making some good examples so that everyone could get some familiarity with the eigenvectors and eigenvalues. So we always want to deliver you the quality content, not in a fast way or whatever the content, so that everyone could understand eigenvectors and eigenvalues. That is left, and soon it will be added. So over here now we'll be starting off with single variable calculus. I don't know what happened just in front of my screen, but that's a MySQL update. No problem. Just for those who wants to know. So we'll be starting with the lecture number 1, which is a single variable calculus. In this video, I'll be talking about, I'll be giving you an introduction to calculus, and what are the content which you're going to cover, okay, and what is the next series of videos in this ML002. Okay, and from now on the video lectures will be around 3 to 4 videos per week. Now my everything is got over. I'll be focusing on the completing this series as soon as possible. Cool. So so in this video we'll be talking about that friendly introduction to calculus. I have prepared my own lecture notes so that I could not miss any topics. The first thing we can talk about is giving you what is calculus. Many people think there is some misconceptions about that. I will say you I will just give you some examples, geometric examples of what calculus is and what calculus is not. Okay, what are the problems that can be solved using calculus? What are the problems that cannot be solved using calculus, that does not require calculus? Okay, we'll talk about 2 big ideas in calculus, such as differentiation and integration. Now you may think, hey Ayush, we are going to start with differentiation, integration. Don't worry my friend, it's very I will just give you an I will say a trailer, means a 0.1% what is going to come in differentiation and what is going to come in integration. Okay, the geometric view only. Okay, so then we'll end this lecture.
talking about this lecture. Now, what will be the content which will be in this lecture, single variable calculus course? So first of all, I don't want anyone to be missed. For example, many high school students watch this video. So we are going to start with the pre-calculus. So I hope that everyone will be comfortable with the pre-calculus. I'll be not covering logarithms. I'll be not covering basic algebra because I require you to have a knowledge till class 10th math. And I hope so you will be having that, like logarithms, like I'll be talking about trigonometry as well, and don't worry about that. So I want logarithms and basic algebra like factoring, GCF, and a lot more. So these are the algebra 1 and algebra 2 which I require, like exponential functions as well. So in pre-calculus we'll be talking about the two main concepts, which will be not two main concepts. I'm talking about functions, mainly the functions, and we'll talking about the second one is we'll be after talking about functions, we'll be talking about trigonometry. Okay, so just review these two topics from scratch so that everyone could be familiar with what's going on in the in the further lectures. So we'll be covering pre-calculus in 2 videos. Okay, so we'll be talking about calculus, then we'll talk about limits. Okay, and after talking about limits, we'll talk about differentiation, taking out the derivative, some of the power rule. Then there are a lot of the rules which are going to learn for taking out the derivative. We'll talk about integration, solving, taking out integral for a function, and then infinite series. Okay, so these are the things which will be taught in this single variable calculus series. So let's get started with this video. So basically in this video we'll define what is calculus. Anyone could define me what is calculus? Just go in this description box and tell me what is calculus. What is calculus? So anyone could give it a try. So calculus is you may think it's a different subject. It's not a different subject. It's not a something, oh my god, what is this, a rocket science. It's a very advanced version for your algebra and geometric problem. Okay, so calculus, I think is Isaac Newton and other great physicists and mathematicians invented it for solving some of the great problems. So calculus is nothing but an advanced version of your regular algebra, advanced version of your regular algebra, which you see regular algebra and geometry which you see in real world. Okay, so we'll see some examples. So what do I mean with this? I will give you a formal definition of calculus when we go further in the course. The reason why I don't want to give you the formal definition so that you could not confuse with the definition, because I want to be very, very clear in the first lecture. So I want to take some example of it. Okay, so let's take an example. Let's take one example. So example can be, let's say that you want to find the slope of this line. So slope of this line can be find over like this. So you run, so this is called run and this is called rise. Okay, rise. Okay, so slope can be found using a regular math of the straight line by the slope can be regarded as a rise over run. Okay, or y2 minus y1 divided by x2 minus x1. Okay, so it just tells how much the y changes when x changes. Okay, that's how it is. This is telling, which will come to that. We'll talk about slope briefly in our future videos, but over here you can calculate the slope of this line by simply your regular math problem, isn't it?
you're using a regular mathematics. Okay, mathematics. But you're told to find, maybe you select this point and want to find the slope at this point, and at every point in this, for example over here, the slope will be same for this line. So over here, if you want to find the slope at this point, you can take another point and then take out the slope. For example, it goes one at the rise and goes up at the top, so that will be slope. For every point, the slope will be of same. Okay, so this is you can calculate. So for every point in that line, the slope will be the same. Now coming to the another, this is your first figure. This is your first figure number 1. Okay, so this, you can calculate the slope of this line using your regular math, which you can see over here. Now if I just tell you, if I just give you a line, so let me just oh my god, what's this? Okay, so this is your thing, and you have, just draw a little bit big line, something like this. You want to calculate the slope of this curved line. You want to calculate the slope of this curved line. You cannot use slope over here. Slope over here will be not use your regular math. Your regular math cannot be used, because every time the slope is changing, every time the slope is changing. So you cannot use your regular mathematics over here. Okay, you may think I will just take out the slope and then take out the average. But what if I tell you take out the exact slope? Okay, so that it could be same at every point. How do we do it? How do we even do that? So for example, if I try to do it over here, okay, I try to take out the slope at this point, you may think, okay, I'm going that side, but isn't it changing? If I go over here, the slope is changing. The slope is changing. So what if I say you to calculate the slope of this line? You'll be not able to calculate using a regular algebra. Okay, so it is solved. So mathematicians has came up with calculus. They have came with calculus. So using calculus, you can take out that slope on any particular point in that curve. Okay, so using calculus, you can calculate the slope of maybe curve. Okay, so using calculus, there's topic called differentiation, which I'll come to that. So using you can calculate the slope of a curve. Okay, so that's what one of the calculus problem is. Okay, so you can see that I differentiated the regular math problem with a calculus problem. This is a calculus problem, this is a regular math problem. Now let's see, you have a one tower. Okay, so assume I'm taking another example. Okay, I'm taking another example over here. Let's for the sake of an example, let's say that you have a tower over here. So assume this is a tower of yours. Okay, so this is a tower. I'm measuring T1, which is tower number 1, and this is your tower number 2. Okay, tower number 2. Now you need to calculate. Now this is your straight line. Okay, this is your straight line. Cool. So you can calculate the length of this using your regular math. Okay, using your regular mathematics problem. The length of this can be calculated using a regular math problem. But what if I give you, there is one tower, and there is another tower, and the wire is something like this. And you're given this stuff, calculate the length. You're given the specific stuff and you calculate the length. How are you going to calculate it? You cannot calculate using regular mathematics, whatever you have in your toolbox. So there the calculus comes. For calculating the slope of a curvy line.
Okay, so this is there is the calculus plays an important role. So let's say example, you want to calculate the slope of course over here the slope will be 0, but you are told to calculate the slope of this, you'll be not able to calculate using a regular problem. Here you need calculus. Okay, so these are some of the instances where the calculus are being used extensively in real world examples. Okay, so there are two big ideas in calculus which I want to highlight. There are two big ideas in calculus which I want to highlight. The first, the ideas in calculus, let me write what are the ideas in calculus. The ideas in calculus, the first is a differentiation. Second is integration. Okay, so there are two big problems, which are differentiation and integration. So I will just go over it very quick way to make you understand about this. What does these term means? So let's talk about a differentiation. Let's talk about what does it mean, differentiation. And of course there will be long lectures coming on this, briefly talking about this a lot with lot more examples. Okay, so differentiation is a process for finding the derivative of a curve. So it's the process for finding the derivative of a curve. Okay, so differentiation is the process of finding the derivative of curve. But what is a derivative? Derivative in calculus is just a fancier version for saying slope. Derivative is nothing but just a fancier version for slope. Okay, so in calculus we call slope as a derivative. Okay, derivative for the curve. Okay, so you find the derivative of a curve, and derivative is nothing but the slope of a curve. Okay, so derivative in a nutshell, a derivative is nothing but is equals to slope, and is as well as it is a rate. It is a rate of instantaneous change. Okay, so we'll talk about that, but you can think of it as a derivative as a rate. So what is rate over here? So let's take an example. You want to calculate miles per hour. Okay, how much the miles changes when hour means if we go 1 hour, then the miles is bigger, like that. Miles per hour taken, or profit per item. These are the rates. Okay, profit per item. So these are the derivative is that. Okay, so derivative is just a fancier version for a slope, because in slope we can't take out the slope of a curved line, but using the derivative you can calculate the slope of a curved line. Okay, so this is what I want to tell is over here you have this problem, and you have this problem. So this is the run. You run x in x direction, and you go and then you rise. Okay, so the slope is nothing but rise over run. So it just tells how much the y changes when x changes. Okay, so this is what the slope is, and the derivative is nothing but the slope of a curve. Okay, so what's the slope of a curve? What is the slope of that? The slope of a curve is the let's take one example. I just believe in taking an example. Okay, so we have an example, something like this. You have a x and y plane, and you have an x and y plane, something like this. Okay, so you have something like this. Oh my god, what is this? Okay, so this is your curvy line. You take out the slope. Okay, so you select any 2 point A and B. Okay,
You select any 2 point A and B and join as made a secant line over here. So we'll talk about this later on. So you joined it. Okay. Now what you do, now over here, the slope or the steepness of this curve, the slope or the steepness of the particular curve is constantly changing between your point A and B. Okay, so if you go over here, the slope and steepness is constantly, it is very steep over here, but it is so over here is the slope or the steepness is constantly changing for this curve between your 2 points, which is A and B. Okay, so let's take an example that you want to calculate the slope at the exact slope at the point C. So how you're going to calculate? So the geometric view which I want to tell, what you do in basic differentiation, you zoom in infinitely far in that at that point. So for example, you zoom in infinitely far. I'm telling you the geometric view. So what do you do? You zoom in. So when you zoom in infinitely far, this curvy line becomes your formula straight line. Okay, so when you zoom at this region, you zoom in extremely far, infinitely far, although you cannot get too much infinite, but just assume as a geometric view, you zoom in a lot. There is something called a limit property, which we'll talk about. But when you zoom in too much, this curved line will become a straight line. Okay, so when you zoom it, so this curved line will become a straight line. So let's take an example that we zoomed in too much, and now over here this curvy line becomes a straight line. Now here's your point C. Now this is a regular calculus problem. So sorry, regular math problem. You can just go over rise, okay, rise over run. Okay, now you'll be calculating the slope at that exact point. Okay, so what you're actually exactly doing is zooming infinitely far. Okay, zoom infinitely far that curve. Okay, at that point C. So the curve becomes straight. At that point. Okay, and then you can solve using a regular math problem, which is rise over run. Okay, so it's not a big deal to understand it, just geometric view, but we will again revisit differentiation, these topics again in our later videos. Okay, so that is differentiation, which is finding the derivative or the slope of a curve at any point C. Okay, so we have seen differentiation. Now let's see integration, the definition of integration. So we'll talk about integration. Means it is not, if you're getting confused, bear with me. These concepts are too much. I'll explain in too much easy way, so you don't need to worry about these. But if you're being worried, don't worry. I'm just giving you a geometric view. We'll again revisit these concepts times and times. So let's say, for an example, that it's the area under the curve. It's the area under the curve actually. Okay, so I'll just give you what is happening in integration. So this is your favorite x and y plane, and this is your, oh my god, so this is your thing, and then you have a line, something like this, and you're told to calculate the area of the shaded region. So this is a rectangle. This is a rectangle. You can just calculate the area of this shaded line. So sorry, what you can do actually do, so say for example, this is your y5, and you want to calculate the area of this shaded line. Okay, length in the breadth. Okay, not a big deal to talk about it, because maybe this is very easy to understand it, isn't it? So over here this is regular math problem. This is a regular math problem. But what if you get something like this? What if you get something like this? So you have this and you have this, and let's say for example that you have the curve like this, and you are told to calculate the area of the shaded portion. Over here
it does not make any sense that how you're going to calculate the area of this straight line, because not anything, we cannot use our regular math over here. So here's what we calculate. The integration is nothing but area under the curve. Area under the curve. Okay, area under the curve. And differentiation is nothing but the derivative or the slope of the curve. Slope of the curve. Okay, so integration helps you to find the area under the curve. Okay, by adding the it is nothing but addition. Okay, it's not a big deal. We'll understand it much better way. So you write a differentiation for a function. We'll talk about. I'm not going to introduce it as of now. So this is your integration, which is the area under the curve, and that is your differentiation. The first topic will be differentiation we're talking about, and then we'll go on integration. Okay, so I hope that's not a big deal, and I also hope that you understood this. Now this was the first lecture. If you have understood a little bit about calculus, and I hope that you understood a little bit about this, so please give a thumbs up to this video, and I hope that you liked this video. I'll be catching up your next video in talking about pre-calculus, about functions, and then trigonometry, and then talking about differentiation. And I hope that you enjoyed this tutorial. I'll be catching up in the next video. Till then, bye-bye. Have a great day. Hey everyone, welcome to this second lecture on single variable calculus. So in this video, we'll be talking about pre-calculus. Basically, we'll be completing our pre-calculus in two videos, as I think that I should review functions and I should review trigonometry, so that everyone who has lost touch in this, they can review it, and the one who has at least seen these functions and trigonometry before, they can just refresh up. It is not a full videos on functions and trigonometry. I'll recommend watching some other lectures on trigonometry and functions if you want to learn actually trigonometry and functions and solving it. But basically it will provide you everything you need for calculus, mainly what you need for functions, and you will whatever the trigonometry you need for taking of the trig values. About we'll talk about Sakatoa. We'll talk about one more thing, which is the special right triangles. We'll see some of the tricks for solving for solving it. We'll also see the unit circle, where we'll be seeing the radians, degrees, and every stuff. We'll give you the graph of cosine and sine. We'll try to give you the graph of that. So I hope that you will enjoy these two set of videos on pre-calculus. If you're completely new to math and your class, I think class 10, then I think that you're good to go. Just review the lecture of this. If you are a little bit go ahead, that means you can, if you're in college or other set of classes, I would say these video will be good refresher for you. Cool. So we'll be reviewing our function. So what is the function? If you can go ahead and write in the description box. Basically the functions tells you the relationship. It's a relationship between your two things, in which one depends on other for doing some processing. Okay. So basically, I think about the functions. It's a relationship. It's a relationship. It's a relationship. Just let me write relationship between two things. In which one depends on other. It may happen that you're not able to get this, what the definition is. So let me write a function which takes any value x and returns the square of that x. If you are into programming, and I hope that you are in, so it's okay that you are not in. So you may have seen functions before, and I really hope that in your programming you just define the function. So what the function does, it takes some arguments. Okay, so over here it takes some input values. Okay, and the function do something and returns the output.
Okay, so what is doing is taking the value input value and returning and doing the square of this. So what is doing in the box, so we are giving x to the function, which is f. It is doing the square of this, and giving your output y. Okay, so for example, the function f, let's say we give 2 to this function, it will take out the 4, and then it will give y as a 4. Okay, so basically it is the function f is doing some processing and giving some output. Okay, the same way you think about the functions, it's kind of a processing what it is doing. For example, in this f of x equals to x squared, so it is taking the input value and then squaring them up. The functions can be, let's take an example. It takes maybe a set. Okay, a set, I would say giant x, and giant x is nothing but x equals to the x1, x2, and x3. Okay, and it doing what it does. This function tries to multiply with some theta. Okay, for example, it multiply with some constant. So 2 times x1 plus 2 times x2 plus 2 times x3. So it can take the set of input values. Okay, so I hope that that function is making sense what the function actually is. So it takes one input value and do the square of it and give the output value. So y is considered over here output value, and x is considered as input value. Okay, cool. So let's go ahead. Basically, input value is the one which we input anything. For example, in this case, we input 2 into that, and then it does some processing, as I said, and returns the square of that, or gives the output value. Cool. So I hope that you made sense out of it. So now let's talk about some of the terminology which I want to introduce to you. First of all, domain of a function. The domain of a function. So set of all the inputs, of a function, set of all the inputs of a function f, let's take a function f, is called the domain. And what is the range? The range is set of all the outputs. Set of all the outputs. Set of all the outputs of a function is the range of a function. Okay, so say for an example that you have a function f that takes the value, first of all, that do the square of that, so you give 1 and you give -2 over here to return 1 and 4. Okay, so the domain is 1 comma -2 and range is 1 comma 4. Okay, it may happen that you may enter the third 2 and it will give 4. So it can be the same thing. 4 it can be the same thing. Okay, so these are the certain terminology which you will see a lot in the upcoming videos. Okay, so I wanted to introduce you 2 things, which is independent variables. So all the input values are independent variable or values. Okay, so basically all your input values are the independent variables. Okay, all the input values are the independent variables, and all the output values are called the dependent variable. Output values, it makes sense, are the, I just want to include this one. You can just write it out. Okay, are the dependent variables. So it makes sense that, for example, we give the function f maybe x. Okay, and x is not dependent on anything to be relied, because x we have to give, it is independent, it is not dependent on anyone, but this y is dependent on these x, on the input value. So that's why we say the output value is dependent variable and input values are independent variables. Okay, these are two things. So let's take an example. I'll take one small example. Let's say you have a function f of x, okay, x squared, and you have another function g of x, okay, which is 5x minus 8. Okay, so you have two functions, f of x, g of x minus 8. Now there is a chain of functions. So let's say f of g of 3. If someone asks you to evaluate this function, so how will you do? So these functions are called as composite function. Composite functions. These type of functions are called the composite functions. Okay, so what we do, first of all, as you already might have been guessed, okay, I'm going to just evaluate g of 3, and whatever the output g of 3 will give, I will give the input to the f of x. Okay, so how this workflow will do, first of all, we'll evaluate the g of 3. Okay, so 5x minus 8, we give 3 to the input, and we get output as a 7. Now we give this 7 as an input to our f, x squared. Now that is f, and then we get the output 49. Okay, and 49 is our output value. Okay, so 49 is the answer or the result when we apply the g of 3 with the output f on the output of the g of 3. Okay, so these functions are called composite function. Okay, and I hope that you will see a lot when we study chain rule of differentiation, and it's very used there. You'll make use of composite function. You make use of the terminology of composite function. Cool. So maybe if you just you can just go ahead. We have a line. So let's talk about slope. Okay, it's always better to talk about slope. Okay, so let's go ahead, talk about the slope. Say for example, you have the line. Okay, so I just draw a very bad line. So let me just pick up this, and let me just, I don't know how to do it. Leave it. So let's take an example that you have a line. Okay, that you have something like this, and you have a line, and you are told to find the slope of this straight line. And you can do with regular math. It is nothing but the slope of this line will be rise over 1. Okay, so you can take any two values, y2 minus y1 divided by x2 minus x1. So how much y changes when x changes. Okay, so it is just telling how much y changes when x changes. Okay, so this is nothing but the slope. Okay, slope is not a big deal to understand it. So I hope that it makes sense out of it. Now let's try to do one thing. Let's plot one line. So graphing of a function, how we do the graphing of a function. Let's talk about that a little bit. So graph of a function. So let's say you have a function y, and you write the function y equals to 3x plus 5. You can also write the function something like this. Let's take an example. You want to make a graph of this function. So how are we going to do that? So basically, what I'm going to do, let me just remove these straight lines. I'm just going to draw everything over here. So let's take an example. 2, 4, 6, 8, 10, 12, 14. Let's do 14, 16, 18, and 18 and 20. Okay, you have 2, 4, 6. Oh my God, this is 8, 10, 12, 14, 16, 18, and 20. Okay, so how do we even plot our function y equals to 3x plus 5? So we make a table. So let's make a table. Something like this. Let's make a table. Okay, something like this, and you give x and y. Okay, so you put the values of x. So for example, you choose x equals 0. So when you evaluate 3 times 0 means the output will be 5. Okay, so the first point you got 0, 5. So you put the point on that. Okay, so on y value we have some over here. Okay, now you put 1, and when you evaluate 3 times 1, 3 plus 5, which is 8. Okay, so 1, 8 is another point. So 1 and 8. Okay, 1 and 8. So maybe you go ahead. My diagram is not good, so you'll keep doing that and just to draw a straight line over there. Okay, just draw a straight line over there, just joining the points, and you'll be getting your graph of a function. I think because of my x and y plane it is failing to draw, but you can just take a graph paper and work on that. Okay, so we had a talk on slope, and we'll revisit the slope in times and times when we talk about differentiation. So don't worry if you don't understand it, but I can just hope that you understand a little bit. So a straight line is if you know about slope intercept form. Okay, so over here you have y equals to mx plus b is an equation for a straight line. Okay, a straight line. Okay, where m is the slope, if you all have already been seen, and b is the y-intercept. Okay, so what is the y-intercept and x-intercept? If your line crosses from here, so the y-intercept of this will be 4 because it intercepts the y-axis at the point 4. Okay, so that's called y-intercept, and slope is nothing but rise over run. Okay, which is y2 minus y1 over x2 minus x1. Cool. So these are some of the talk on functions, and I hope that you are able to get the sense out of it. Now let's do one thing. Let's try to talk about the two kind of functions which you will see a lot in your calculus journey is parabolic function and absolute value function. Okay, so let's talk about that, mainly the graph. So let's take f of x equals to x squared. This is an equation for your parabola. Okay, so maybe let me take my black pen. I think that works. Okay, so now when you try to plot it, just make a table x and y1 and try to put the values and get the values. So you put the values of x, you'll get the value of y, put the random value of x, get the value of y, and keep putting on the over here. So you will get the parabola something like this. Let me touch it. I think it's not a good parabola, but yeah. Okay, so this is the diagram of your f of x equals to, or a graph of f of x equals to x squared. Okay, so you'll think that this function is a continuous function. We'll talk about that. I just don't want to introduce you over here. Okay, so this function is a continuous function. We'll see how to it is also differentiable. So we'll talk about this. So that's why I'm introducing you the graph of these plots, so that it will be easy to understand at that point. So this is your, don't worry if you don't understand what is continuous and what is differentiable. Just I've told you, we'll talk about in detail in our later videos. Okay, so this is a function for your f of x equal. This is a graph of your f of x equals to x squared. Okay, so I just want to draw another, make a graph of another function, f of x equals to absolute value of x. So absolute value of x. So the graph of the function will look like straight line. Let me join it over here. Okay, so this is your graph of the function. Okay, this is your graph of the function f of x. This is a graph of function at g of x. Let's name a g of x because it will be confusing. G of x. Okay, g of x, where this is your graph of function. Okay, you can put the values, you will get the exact graph of this. Okay, but one thing which I want to tell you, that this is a continuous function. This is non-differentiable. You may think, hey, why you're telling this now? You can tell me later on. So just for your information, I'm just telling so that why we are introducing these kind of graphs and in front of you. So first of all, I told you one property, that which is continuous and which is differentiable. If you don't understand, ignore it. The second conclusion which you can make out of it, the second insight which you can get of this is both are symmetric. Both functions are symmetric. Both functions are symmetric with respect to y-axis. Okay, so if you know symmetrical, okay, this makes them even function. These are being symmetric. These functions are called the even functions. Okay, another thing is the polynomial function like this, or less function like this, f of x, okay, equals to 9x to the power 4 minus 4x squared plus 3. So this function is also the even function. Can you guess why? Because all the powers are even. Okay, all the powers are even. Okay, so that's why it is a even function. So that's why it is an even function. If the powers are odd, okay, then that will be a odd function. Okay, so I hope that you understood. Either it's not important to know what is an even function, what is an odd function, but just for a general purpose, I told you. Cool. So we had a talk on functions. Now let me see how much the time is being there. I think 20 minutes. We can go ahead talk about trigonometry now. So we had a brief talk on functions, and I hope that you had got a very good sense on that. So now what I will do, I will just start off with the basics of trigonometry. Either we can get started in the next video, I think. Yeah, so I think I will just prefer the next video for trigonometry because there's a lot to talk. I can't continue with this video, so I'll be catching up your next video in trigonometry because this is a 2-pagers. So I need to make around your 40 minutes to talk on trigonometry because trigonometry is a big topic to understand. So after trigonometry, we'll talk about limits. We'll talk about, there are 2 videos coming on limits. First of all, what is limits? The evaluating limits, squeeze theorem. So we'll talk about that. I mean the sandwich theorem. So we'll talk about that. So I hope that you had understood this very properly. I'll be catching up your next video. Till then, bye-bye. Have a great day. Now we'll start with the trigonometry. I think we'll just review trigonometry in such a way so that you could be comfortable with upcoming calculus videos. And this is not a math channel. I don't know why I'm feeling like I'm teaching mathematics. It is a part of our machine learning course. Sorry, deep learning course which I'm teaching. So that's why I want everyone to go from very scratch to such an advanced level, because deep learning is an advanced field. So that's why you have to first of all make your fundamentals strong. Okay, so we'll be getting started with the trigonometry. Okay, we'll just review some of the trig functions. We'll also review the unit circle. Maybe some of you have forgotten it, or I don't know about that. I will also review how to graph sine and cosine. Okay, so basically, what is trigonometry? First of all, maybe you can just it's a study of triangles, or maybe the right triangles which you see. So mainly the trigonometry is the study of right triangle, and there are a total of 3 main trigonometric functions. So there are a total of 3 main trig functions. I'm just going to write trig functions. So there are a total of 3 main trig functions. The first one is sine.
okay, sine. Second one is cosine. The third one is tangent. Okay, so these are the three main trigonometric functions, and there are some more which are called cosecant, secant, and cotangent. So these three, and their reciprocals, their reciprocals are also there. Some important trig functions. So their reciprocals are also the very important trig function, such as cosecant, secant. Second one is secant, and third one is cotangent. Okay, so we'll talk about these in detail in our whole session. We'll talk about these 6 trig functions, as these 3 are the reciprocal of this. So we'll study everything today. These 6 functions. Our whole lecture will go around these trig functions. Okay, so I want to introduce to you something called I would say a good weapon for you. Okay, a weapon that helps you to solve trig functions very easily, and very important, the sign, to remember what is the sign of the particular angle. So that is nothing but SOHCAHTOA. So maybe some of you have seen this and some of you have not. So this SOHCAHTOA is very important in your trigonometry journey. It's again I'm saying very important. Many people has different stuff, but it's very easy to understand, and very easy to it helps you to remember the definition of your sine, cosine, and tangent. So using SOHCAHTOA, you can remember the definition of what that sine means, what the cosine means, and what the tangent means. And it is very useful and very important about this. Okay, many people say different rhymes to identify the definition of sine, cosine, and tangent, but I think this is the best and only thing which is easily rememberable to anyone. Okay, so what I'm going to do is I'm going to make a right triangle. Okay, so but before I'll just introduce you in that right triangle. What does it mean? So first of all, let me make the pen a little bit lower. Yeah. So let's say for an example that you have this one and you have this one. Okay, I just don't know how to draw a good line, and this one is, and this is your right triangle. Okay, so basically this is called the hypotenuse. So let me just give a name. So this is called the hypotenuse, which is given h. Okay, and hypotenuse is the largest side in your triangle. Okay, this is this is your angle, let's say x, and this is called the adjacent side to that angle x. Okay, adjacent side to that angle x, as is the right triangle, and this is called opposite side to that angle. Opposite side to that angle. Okay, so basically what I'm saying, that this is a hypotenuse h. Okay, and we have an angle x where this let's give some name ABC. Okay, and BC is the adjacent side to this angle x, and AC is an opposite to the angle x. Okay, so which is opposite to the angle, which is a side which is opposite to angle x. So now what I'm going to do is to take out, is just to give you the definition of sine of x, cosine of x, and tangent of x. Okay, so what I'm going to do is to, using the definition of SOHCAHTOA, so what I'm going to do, SOHCAHTOA, so sine of theta, and theta is an angle. Over here it will be x. We'll solve it, but before that, over here, which you can see, sine of theta, okay, cosine of theta, and tangent of theta.
So let's go with the definition of so let's try to define sine of theta. So when you define the sine of theta, so opposite over hypotenuse. So sine of theta is equals to the opposite side over the hypotenuse. So opposite over hypotenuse. So that's a definition for your sine of an angle. The sine of an angle is nothing but the opposite over hypotenuse. What is the cosine? What is the cosine of an angle? Cosine of an angle is adjacent over hypotenuse. Adjacent over hypotenuse. Okay? Or in other words, A over H, as we given the name A and H. Okay? So this is a sine, this is a cosine, and for taking out the sine of an angle, the definition for sine of an angle is nothing but the adjacent over hypotenuse. If you want to calculate the tangent of an angle, which is nothing but opposite over adjacent, opposite over adjacent, which is O and H. Okay, so with the definition opposite over adjacent, so using this rhyme SOHCAHTOA, you are able to define these three trig functions. Okay, so now let's use this SOHCAHTOA to take out the trig values. Okay, so but before that, let's say that adjacent side over here, the adjacent side, let's assume adjacent side is 4, whatever the centimeters or meters. Let's assume centimeters. The AC, which is opposite side to that angle, or the height, so it will be 3. And you can take out the hypotenuse. How you can take out the hypotenuse? This is very, very easy using Pythagorean theorem. Pythagorean theorem tells a square plus b square equals to c square. A square is your BC. B square will be your AC equals to C square. So when you go ahead, 4 square plus 3 square equals to what? C square. Okay, 4 square plus 4 square 16 plus 9 equals to what? C square. 16 25 equals to C square. And when you just remove this, so it will be root 25 equals to C, which will be C equals to 5. So the hypotenuse will be 5. Okay, so you are given the sides of a right triangle. Now what you need to do, you need to take out the sine of the x, sine of x. So how are you going to take out the sine of x? For taking out the sine of x, the sine definition is SOHCAHTOA. So sine is opposite over hypotenuse. So opposite over here is 3 and hypotenuse over here is 5, is your sine of that, sine of the x. Sine of x is nothing but the 3 over 5. So what is cosine of x? So what is cosine of x? Cosine of x is CAH. So CAH. So adjacent over hypotenuse. So adjacent side over here is, I think, BC, and this is 4 divided by H, which is 5. So cosine of x is 4 by 5. What about tangent of x? So tangent of x is nothing but opposite over adjacent, and opposite to that angle x is 3, and adjacent to that angle is 4. Okay, so which is nothing but 3 over 4 is the tangent of x. Okay, so these three, sine, cosine, and tangent, we have taken out, and this gives you definition: what is a sine, what is a cosine, and what is a tangent. Sine is nothing but the opposite over hypotenuse. Cosine is nothing but adjacent over hypotenuse. Tangent is nothing but opposite over adjacent. How you remember it? Using the SOHCAHTOA definition. I think this is pretty much easy. Okay, so we had used this SOHCAHTOA. We had used this SOHCAHTOA to identify this sine of the particular x, cosine of the x, and tangent of x. Okay, so we have seen this sine, cosine, and tangent. So we have seen the definition of these three. Now what about the reciprocals of it? Now what about the reciprocals of this. So the same way, the other trig functions are the reciprocal of sine, cosine, and tangent. So let's talk about that. So other trig functions are the reciprocals of these sine of x, cosine of theta, and tangent of theta. So let's give the theta name, theta angle. Okay, so let's talk about the first one, which is the cosecant. Okay, cosecant. So what is this? Cosecant is a reciprocal. Cosecant is the reciprocal of sine. Cosecant is a reciprocal of sine. We'll see what the reciprocal means just in a second. Second one we have, which is secant, and we denote this as a SEC. Okay, sec. So secant is nothing but is the reciprocal of your cosine, and the last one, which is the over here, is cotangent, which we didn't denote as a cot. Okay, is the reciprocal of your tangent, and how do you define cosecant? Cosecant is SCC, CSC. Okay, secant, SEC, and what about cotangent? COT. Okay, so in sine we write SIN, cosine COS, tangent TAN. Okay, so these are short form given to them. So now what do you mean by reciprocal? So let's take out the definition of cosecant of theta for any angle. Okay, which is nothing but the reciprocal of sine theta. So 1 over sine theta. So reciprocal of the sine of that angle, sine theta. Okay, so it will be 1 over secantova. Let's remember our favorite definition from one and only secantova. So sine is opposite over hypotenuse. Sine is nothing but opposite over hypotenuse. It goes above, it will be h over o, which is nothing but your cosecant. So the definition of a cosecant of a theta is nothing but a hypotenuse over opposite of that angle. Okay, the next one is secant of theta. Secant of theta is the reciprocal of cosine, which will be 1 over cosine of theta. So it will be nothing but, so what is the cosine? Adjacent over hypotenuse. 1 over adjacent over hypotenuse. It goes above, so it will be nothing but h over a, which is the hypotenuse over adjacent. Okay, so the definition of secant of the theta is nothing but the hypotenuse over adjacent. The last one over here is cotangent. So what's the time? So the last one is over here is cotangent. Cotangent, which is cot of theta, is the reciprocal of your tangent, 1 over tan of theta. So tan of theta is nothing but opposite over adjacent. So 1 over opposite is over here O by A. Okay, so that is, so it goes above 1 over, so sorry, A over O, which adjacent over opposite angle. Okay, so opposite to that angle theta. So cotangent, the definition of a cotangent is adjacent over opposite of that theta. Okay, so we have given you definition of secantova, sine, cosine, and tangent, and we have also given you the definition of cosecant, secant, and cotangent of theta. Okay, so we have given you everything about this. Now I hope that you had got a good idea about what is these angles tells you. But before that, what I'm going to do is to solve for the triangle. We have taken out the sine of that triangle which we have built up. Sine of this was 3 over 5, cosine 4 over 5, tangent 3 over 4. So what will be the cosecant of these of this triangle? Okay, so let's take out the cosecant of x, of the angle x, which will be 1 over the sine of theta. Okay, so which will be nothing but, again, when you go ahead, so let's not write it again. Let's use our formal definition. So cosecant of theta is hypotenuse over adjacent. Hypotenuse was 5 and adjacent was 4. So 5 over 4 is the answer of this. So sorry, it's 5 over 3. Okay, because adjacent, because over here your adjacent opposite angle. So this is opposite. Okay, I don't know where it is. Oh, yeah, so it is opposite, so 5 over 3. Okay, which is the reciprocal of your sine. If you are told to take out the cotangent or the secant, first of all let's list secant of x, which will be nothing but secant of x, which will be nothing but, let's say for the sake of an example, secant of x is hypotenuse over adjacent. Hypotenuse was 5, adjacent was 4. Okay, so that is just the reciprocal of your cosine. What is the tangent of x? What is the tangent of x? So tangent of x is adjacent over opposite. Okay, so adjacent will be 4 and opposite is 3. 4 and 3. Okay, so we have taken out for this triangle, we taken out the cosecant, secant, and who told tangent? It's cotangent. Okay, so mainly we will add cot. Okay, so so these are the things which I want you to remember, and I hope that you remember it as well. Okay, now I hope that you have got a better idea about what is this SOHCAHTOA means and the formal definition of this SOHCAHTOA and these 6 definitions. I want to introduce you to 2 special right triangles. It is very, very important to know. Okay, so I'm just going to introduce to you about 2 important, 2 special that helps you to remember these trig values, because these will be very handy in your calculus journey. So I'm just going to introduce to that. So I'm just going to write 2 special right triangles. 2 special right triangles. So the first one is 45 degree, 90 degree triangle. 90 degree triangle. This is a acute angle. Okay, so over here, when you try to make a that, so let's make a line. There is one angle which is of 90 degree, and other 2 angle are 45 degree. Okay, so I'm just going to write 45 degrees and 45 degrees. Okay, so this is the following, and you have, let's say for you'll be getting these base. So base will be 1, it will be also 1, and the hypotenuse will be 1.41, which is root 2. Okay, and the hypotenuse will be root 2, because when you take out the hypotenuse, so how you'll do 1 plus 1, 1 squared plus 1 squared equals to c squared. When you do this, 2 equals to c squared when you root 2. Okay, that is your hypotenuse. Now let's apply SOHCAHTOA and their reciprocals to take out the sine of the 45 degrees. Okay, so let's apply the SOHCAHTOA over here to take out the sine of 45 degree. Okay, of this angle. Let's apply that. Let's go ahead. Yeah. So sine of 45 degrees will be first of all SOHCAHTOA. Let's remember our definition. SOHCAHTOA. So opposite over hypotenuse. So opposite 1 over hypotenuse root 2. Okay. So which will be nothing but, when you rationalize it, it will be nothing but root 2 by 2. I hope that you know how to rationalize. You simply multiply something like this. I think that some of you do not know about it. So root 2 times root 2. Root 2 will be root 2 by 2. That's what you get. Okay, so you get this, and when you go ahead, it is approximately equals to 0.71. You can calculate using your calculator. Okay, so that is your sine of your 45 degrees. What is the cosine of 45 degrees? Cosine of 45 degrees. Cosine of 45 degrees, katoa, adjacent over hypotenuse. So adjacent is 1 and hypotenuse was 2. Okay, so adjacent is 1 and root 2. 1 over root 2, which will be again root 2 over 2 by rationalizing, approximately equals to 0.71. That is the cosine of 45 degrees. Now, what is the for this triangle? What is the tangent of 45 degrees? 1 over 1. How do you say? Opposite over adjacent, which will be around 1. So 1 is the tangent of your 45 degrees for this triangle. So what about the reciprocals of it? So what about the reciprocals of it? So the reciprocals of it will be, first of all, secant. First of all, let's talk about cosecant of 45 degrees, which will be the reciprocal of it. So hypotenuse over opposite angle. So hypotenuse is root 2 by 1, which is nothing but approximately equals to 1.41. Okay, what is the secant of 45 degrees? So secant will be h over a. Hypotenuse is root 2 over 1, which should be also approximately 1.41. What is a cotangent? So what is a cotangent? It will be 1 over 1, because adjacent over hypotenuse, which will be 1. Okay, so these are the reciprocal, the trig values. So we got the trig values of, you can see over here that using this special, these special right triangle will be so much in your journey. So that's why I'm introducing to you this one. Okay, now let's go ahead. Let's talk about another. Now you got to know these trig values. Let's talk about another special right triangle, which is nothing but 30, 60, 90 degree triangle. 90 degree right triangle, and of course this is a acute angle. Okay, so when you have this, let's print it out. Yeah, so over here you have this, and let's say for sake of an example, your 30 degrees, 60 degrees, 90 degrees. Okay, adjacent side of 30 degree is root 3, which is approximately equals to 1.73, and it is 1. The height, or AC is, sorry, the height will be 1, and the hypotenuse is 2, because this is all, because mainly people, what they do, they put that into the base, and that is wrong, because the hypotenuse is also always the longest side. Okay, now let's do one thing. Let's apply the katoa. So katoa on 30 degree. Okay, for the 30 degree angle, okay, so go ahead, apply the katoa for the 30 degree angle, then go ahead and apply the katoa and the reciprocals as well, for the 60 degree angle, and you are good to go, and you'll be getting your trig values, and that will be yielding to around so much of trig values in no time, which you got it. Okay, so I want you to do these two things, taking out and write the answer in description box. I'm saying in comment box about all the trig value and the reciprocals for the 30 degree, and all the trig functions with their reciprocals for 60 degree. Okay, cool. So we have done lots of practice. Okay, but you may think, hey, can't we do for a greater angle, because all these are acute angle? Can't we go ahead talk about the large angles, like maybe 270 degrees? Okay, so maybe bit more than that, something like cosine of pi over 3, cosine of maybe 3 pi, or sine of 3 pi over 3, sine of 7 pi over 6, maybe anything can be happen. Okay, so how you go ahead and do that? So you can just maybe, what is the sine of 210 degrees? What is this cosine of 120 degrees? There are a lot more things. So for that we have something called as unit circle. We have something called as unit circle, which is very important. And it may happen, some of you may think, yeah, Yush, I cannot remember a unit circle, because many of you has an enemy with a unit circle in your, I think, class 9th and in class 10th. I think mostly in class 10th. So don't worry about it. Very trick is available online about remembering it, and you don't need to remember it. It makes sense as well sometimes. Okay, if you think about geometrically, don't think about remembering everything. You can just make sense out of it, because it's kind of very important in your calculus journey, because these are the very frequent radians which you get, or degrees which you get in your whole calculus journey. Okay, so what I'm going to do is to introduce to you a unit circle. I'm not going to give you a trick for remembering the unit circle, but I will leave a link in the video description about the trick for remembering this. But as always, Google is up for you. You don't have to worry about it. Okay? Cool. So let's go ahead. Let me show you the unit circle. Let me show you the unit circle. Where is my unit circle? Here we go. So I'm just going to take in between, make it a big. Okay, so this is your unit circle. I'm just going to make it a little bit big. Yeah. So this is your unit circle, and very scary or disastrous unit circle, and it's very important as well. So I'll just introduce you so that everyone is familiar. Here you have three things. The first thing is coordinates. Second thing is you have the radians, okay, of the coordinates, and then you have the degrees, angles in radians and angles in degrees. Okay, so you have the coordinates, which we'll talk about that. Coordinates. You have angles in radians, and you have angles in degrees. Okay, so first of all, let's talk about this one. Let's talk about this one. So first of all, over here you have y-axis and x-axis. So the radius with this origin to this point, the radius of this circle is r equals to 1. So the coordinate at this point will be 1, 0. Why 1, 0? 1 on x-axis, and this is 0 axis 0. Okay, so 1, 0. It is the same 0, 0, 1 on x-axis is 0. So radius is r equals to 1 everywhere. So it will be 0, 1. So this is y-axis. This is -1. This is x-axis. This is 0, -1. So these are coordinates. The same way, these are also coordinates. This is for x-axis and this is for y-axis. This is for x-axis. This is for y-axis. Okay, and you may think how you have come up with these kind of coordinates. How you come up with this? It's basically more about geometric understanding. You can go ahead, see if you can go in much more detail as a bit out of the bound of this video, because we are just reviewing it. So over here, which you're seeing over here, x and y coordinates. So these are all the things which you're seeing outside the circle are the coordinates. Inside which you are seeing this pi, whatever the fraction which you're seeing, is the radians, is the radian. Okay, so over here you have 2 pi, and then pi over 6, pi over 4, pi over 3 for that coordinate. So there are 3 over here, and pi over 2. Then go ahead. We have these. All the things are where the radian is 4 pi over 3. The coordinates are this. 5 pi over 4. The coordinates are this. Okay, so these are the things. The next thing is you have the degrees. You have the degrees. You have the radian. You have the degrees. 120 degree, 135 degrees, 90 degrees, 60 degrees. Maybe you all remember using a protector. Okay, it was very familiar to you. So I hope that's not a big deal now. But there's one thing which I want to tell you is how do you remember these things? So first of all, what do? You have the three points over here. You give 2, 2, 2, 2. So all the denominator will be given 2. Okay, and now 1, 2, 3, 1, 2, 3. Okay, you do the square root of every numerator. If you put it does not require it. Root 3, root 2, root 2, root 2, and of course it does not require. So you get this. So these can sound kind of tricks for remembering it. It's very useful in this. Okay, so it's very useful as well. Okay, so you remember these coordinates. These pi is the 1/3. Pi over 6 is 1/3 of pi over 2. So you need to only remember some of the coordinates and some of the radians. Only that, and using that you are getting. Using that you can get more radians or whatever. Okay, so there are some tricks which you need to remember. Maybe you can search online. Otherwise, the link is in the description box about the trick for remembering these things. Okay, so you have the radians, you have the degrees. Okay, now what? So every coordinate every coordinate is a pair of x and y. Okay, x coordinate and y coordinate, but it is indicating that this is this cosine of theta and sine of theta. So x indicates the cosine of that, maybe the radian or an angle, and sine, maybe this theta can be the radian or that angle. Okay, so let's say for the sake of an example, let's take an example. You want to find out the cosine of pi over 3. How are you going to find it? So you search pi over 3 over here. What is the x coordinate? What is the x coordinate? Because x coordinate indicates the cosine of theta, which is 1/2. What is the sine of pi over 3? So y coordinate is root 3/2. Okay, so these are the trig values. Okay, which is very useful. Maybe in your examination or in calculus, you can take out anything with this. Say for an example, you're told to find cosine of pi over 6. Maybe cosine of pi over 6. So over pi over 6 will be the x value is root 3/2. Let's take an example. You're told sine of 3 pi over 6, 3 pi over 4. So what it will be? It will be nothing but root 2/2, because that indicates the y coordinate. So coordinates indicates the pair of the cosine and the sine of that angle or the radian. Okay, so some of the interesting thing which I want to show you is what is the tangent of 3 pi over 4. What is the tangent of this 3 pi over 4? So tangent, you all know, tangent is equals to sine of that 3 pi over 4 divided by the cosine of 3 pi over 4. Okay, so sine of theta divided by the cosine of theta. So it will be the sine of theta 4 will be root 2/2. Okay, minus root 2/2, because that's cosine is which is minus 2, which you can see over here. So the denominator cancel, which will be minus 1. The tangent of the 3 pi over 4 will be minus 1. So this is all about manipulations, all about other things which you need to just apply some logic, and you're getting your trig value. So this gives you lots of trig values. Okay. Now what I'm going to do is to do one thing. First of all, what is the cosine? What is the cosine of 3 pi? Over here we only till have 2 pi. Okay, but what is 3 pi? So it here the radian is 2 pi. So what is the cosine of 3 pi? So how it is constructed? 1 pi, okay, then 2 pi, then 3 pi over here. It will come over here. So 3 pi, the cosine is always referred to as minus 1, so the answer will be minus 1. How? First of all, here is your pi, okay, you rotate, there is 2, first of all, you go over here, you rotate half circle, pi, then 2 pi, then 3 pi over here. So 3 pi will be becoming minus. So what is the sign of 3 pi, which is 0, because the y coordinate is 0. So it does not matter ki whatever you can have, it does not matter. Okay. Now there is one last thing which I want to tell. Is what is the sign of minus pi over 4? What is the sign of minus pi over 4? Which will be nothing. So over pi over 4, but this is pi over 4, but there is minus. So you here it is in second one. So what you do? You start going into the negative direction. Okay. So leaving 1, you go to 2. Okay, because here the second coordinate. So you go over here 2 1, and that is so sine of minus pi over 5 will be sine of 7 pi over 4. Okay, so that is nothing but 2. Okay, so it's minus 2 over 2. Okay, so this is how you go in the negative direction. If it is over here, then you go from here. So this is how everything is working using the unit circle, and I hope that you understood very, very intuitively, and I hope that's not a big deal to understand these things. So this is the whole thing, and basically you will see whole calculus and revolving around this. Okay, most of the calculus problems, trig calculus problems. Cool. So I just want to talk about the last thing, which is very, very useful over here, is how do you graph sine, cosine, and tangent? Maybe you can search online, but I'll just show you the graph of sine of y equals to sine of x looks like. So here is your thing. So it will look something like this. It will look something like this. It will look in cyclic form. Okay, in cyclic form, it will look in cyclic form something like this. Okay, so it will look in cyclic form, but the same way your cosine will be different. Because over here it is something y equals sine of x is something like this. But what is the cosine? Cosine will be little bit different. It will be okay. It will be okay. So it will be cosine y equals to cosine of x will be something like this. And these are the graphs which you will see later a lot when I will teach. I will take these kind of graphs about when I will go in different differentiations. Very, very important. Okay, so I hope that you understood the trigonometry, whatever I taught, and as just a review, there are a lot to learn in trigonometry. There are a lot to practice in trigonometry, like inverse trig functions and asymptotes. We have a lot more things which you can explore. Please go ahead, see some tutorials if you're going to go ahead deeply in trigonometry. These are things which I need to revise before going to the calculus. Now we are ready to go in calculus. From the next video, we'll be talking about limits. And we're completing, I think, limits in 3 to 4 videos. I think only 3 videos will be required for limits. Short videos. We're completing limits, and then we are good to go. And then we start with differentiation. Okay. So, and then we will go ahead talking about solving taking out the derivative, like quotient rule, chain rule, and a lot more. And then we'll go ahead. There's also power rule, which I can't forget about that. So there's after differentiation, I think we'll go ahead with integration. Okay, so I hope that you understood. I'll be catching up the next video. Till then, bye bye. Have a great day. Hey everyone, welcome to this lecture. From this lecture, we'll be actually starting off with limits, and limits is one of the most important topic which I cannot leave. We'll not too much talk about limits, we'll not do that much kind of examples, but yeah, I will give you a brief about limits and what the limits are, and there are lot of the things which we'll talk about, as well as we'll talk about how to evaluate the limits using various techniques, which we'll study in the next video. Basically, in this video, I'll just give you what exactly the limits is. Okay, so we'll see lot of examples to understand why this is called the microscope of maths. So it's this very nice nice things which have invented so far in the history of math. And I think that differentiation, the formal definition of differentiation will define using the limits property. Okay, so now let's get started with one of the example which is in front of you, which is that maybe you are familiar with this plot. It is the parabola plot, if you know, because we had a talk on this. And how you plot, you just plug in the x value, just put the point on the x coordinate and the y coordinate, and then you join the points. So this is what you get, and this is not a best parabola diagram in the history of math, but yeah, this is the basic stuff which you're seeing over here. Now, what I'm going to do is make a piecewise function. But before that, what I'm going to do is to just talk about with this function, and then we'll make a piecewise function. But before that, what I want is to find the value. I want to find f of 2. So what it will be? So we give to the x, and this will be nothing but 4. Assume that this is a 4. Okay. So just want to make it some over here. So it is a 4. Okay. So this is nothing but 4. But what do I say? We have a function g of x. You have a function g of x. You have a function g of x. You have a function g of x where you first of all what is x squared for every values except x equals to 2. Except x equals to 2, there is x squared. Okay. And another is when the input value is 2, then the output will be 1. When x equals to 2, then the y value will be 1. In the first is telling x squared in every input values except 2, and 1 for the input value equals to 2. So that is, these functions are nothing but called the piecewise function, which you might have observed already, and I hope that you had already. So now if I want to plot it over here, this plot g of x, if I try to plot it, the g of x, so oh my god. Yeah. So what if I want to plot it? So for plotting it, let me just remove this one because oh my god, I don't want to do this. I don't know how to select the eraser. Let's use very simple eraser. Let's first of all remove this, and there is a discontinuity. Okay. So if f equals to 2, then if input value equals to 2, we're just saying that it should be 1. Okay. So this is your function of your g of x. This is your function of your g of x, where we are saying this is a function, this is a graph of x squared, this is a graph for x squared, but we had told there is one discontinuity, which we'll talk about today, about discontinuity, but there is one discontinuity in this function, and we're saying if at x equals to 2, make that to 2, and this x squared does not work for x is equals to 2. Okay, so this is a function, this is a graph of your function g of x. Okay, this piecewise function, this is how it looks like. Now, coming to the next part is, I'm just asking one thing, what is the limit of your function g of x, when x approaches to, not exactly 2, when x approaches 2 from the right hand side and the left hand side. Okay, so it may be confusing to you. What exactly I'm saying? What is the limit of g of x when x approaches 2 from the right hand side and from the left hand side? So let's start with from the left hand side. So let's say the input values, so let's start from this value. So it gets closer and closer to 2. Okay, so it approaches closer and closer, so we simply write limit of g of x when x approaches 2. So this is your limit notation to write it out. So basically we are telling here we are telling what is the limit of when x approaches 2 from the left side. Okay, so when x approaches 2 from the left side, it seems to be approaching 4. It seems to be approaching 4. We are not taking exactly f of 2 because that is undefined. At that point, the function x square is undefined. But basically, there is discontinuity, and we are getting closer and closer to 2 from the left side. For example, we are taking the value 1.9, 1.999, 1.999, 1.99999. We are not getting exactly to 2, but we are taking these values and taking the square of it. Okay, so it seems to be approaching 4. How I am perceiving that? So let's do one thing. Let's try to do from the left hand side first of all. So we have an x value and we have a g of x. Okay, we have a g of x. So you give 1.9 to x. When you square it up, you get 3.61. Okay, and because it is defined else everywhere except x exactly equals to 2. So at 1.99, it will be 3.9601. That is the square of it. Okay, so we give 1.999. So that is 3.99601. Okay, we are not taking exactly, it's technically can get exactly 4, but if you use the calculator 1.99999, it will just take out the square, it will just round off that, but actually this is technically not true. Okay, so over here you are getting when you are approaching 2, when you are approaching x equals to 2 from the left hand side, it seems to be approaching 4. Your function g of x seems to be approaching 4. Let's take an example of this. So when you're approaching 2 from this side, when you're approaching 2 from the left side, it seems to be approaching 4. Okay, it's not exactly taking as a 2 as an input. We are saying if the limit of a g of x tells you when x approaches 2 from the left hand side, and when from the left hand side, so over here when the limit of g of x when x approaches 2 is approaching, okay, limit of g of x when x approaches 2 is approaching 4. The function is approaching 4. So it is approaching 4. It is approaching 4. It is approaching 4. So when you get closer and closer to 2 from the left hand side, it seems the function g of x is approaching closer and closer. It's approaching 4. It's not exactly 4, but it's approaching 4. Okay. Now let's see the same way going from the right hand side. So let's go with the right hand side. So when we try x and g of x, we give 2.1, 4.41, 2.01, 4.004, 001. So from the right hand side as well, from this side as well, from this side as well, from this side as well, it seems from this side as well, we are approaching 2 from this side. It seems like it is approaching, so it seems like it is also approaching 4. It is also approaching 4. So the limit from the right hand side, limit of f of x equals to 2 of g of x from the right hand side is equals to 4. And the limit of x approaches 2 from the left hand side is also 4. So the limit of g of x when x approaches 2 is exactly equals to 4. And this is how you take out the limits of a function. Okay, and this is damn easy. We had made use of tabular form using calculator, and and then we are done. Okay, this is what limits are. Limits are nothing. It's a function, limit of a function, if it exists, because limit cannot exist as well. I will tell you the reason later on. So limit cannot exist as well. For some x value c, and we denote, so we're just going to write the formal, let's make a new page. So I'm just going to write the formal definition. The formal definition says that limit it is not a formal definition, but this is an informal definition. But just now for the definition, okay, the limit of a function, limit of a function, if it exists, of course, if it exists, limit of function if it exists for some x value c, Okay, for some x value c, to the height of a function, to the height of a function, to the height of a function, the height of a function gets closer and closer, gets closer and closer, as we saw, that is, gets closer and closer, closer and closer to as x gets closer and closer, gets closer and closer to c, gets closer and closer to c from the left side, from the left and the right side, from the left and the right side. Okay, so for example, this is your function, this is your function, assume that this is your function, and there is a discontinuity over here, and you're telling that, okay, what is the value of x? So for example, it's something like this. Okay, and you're telling that's 2, so what is g of x? What is the limit of x approaches 2 of your function g of x? Okay, so when x approaches 2 from the negative side, sorry, the left side and the positive side, from the right side, it seems to be approaching from the, first of all, from here, and then it seems to be approaching 4. So exactly it is 4. Okay, so it's check the x value gets closer and closer from the left and the right side, and then you decide, and then if the both are equal, then you say, okay, that's the limit, which exactly equals to 4. Okay, so now we had seen the one example, and I hope you had got a very good idea about limits, and I will just give you the formal definition of a limit, because it's very important for you as well to understand what exactly a limit is. Okay, so what I'm going to do now is to take another example so that you could get a more good definition for you at least. We'll see that. Okay, so we'll just give you the good definition of the limits, and it's very important as well, mainly if you for getting more about what exactly the limits is. Okay, cool. So what I'm going to do is take another function, and the function is f of x equals to 3x plus 1. So what I'm going to do is to take a y, I will just take a function 3y equals to 3x plus 1. Y equals to 3x plus 1. So this is your function f of x. This is your function f of x. Okay, and you will identify the need of the limits from this function, and you will get to know the need. What's exactly the need of limits from this function? So let's get started. So what do I ask you to do? Take your graph paper, try to plot this function by putting the x values, and try to put the coordinates on your graph paper, and then you are done. Okay, so what I'm going to do is to make a quick diagram of this function. I don't know, it is a bit hard to make, but no problem, I'll try to make it as much as I can. So just what I'm going to do is, just wait for a second, I'm just checking the diagram. Yeah, so what I'm going to do is to make an x and y plane. So I'll just put this, let's make in blue because it works. Okay, so this is your y plane, y-axis, and this is your x-axis. Okay, what I'm going to do now is to plot it. Now is 2, it's approaches 7, so 1, 2, oh my god, what is this? Oh, I got to know about this now. 1, 2, let's make in a little bit more way. 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. Okay, so this is your let's make it an informal way. Now when I try to put the value of 1, so let's put the value of 1 over here. That is 4 when it is, so that is 4. Okay, put the value of 2, that is nothing but 7, I think so. Yeah, that is 7. Okay, so when I try to just join the points, I'm just trying to fully join the points. Okay, so this is what I get when joining it. Okay, so it is not a best function in the history of maths, but yeah, that's what I can draw in just now with quick graph. So this is a function y equals to 3x plus 1. So this is a function y equals to 3x plus 1. Coming to that, now this is a function. Now what I want to know is limit of your function, let's say f of x. Let's give the name of this function f of x. Limit of your function f of x when x approaches to what it will be. You can simply it is continuous. We have this is not a piecewise function. It is continuous, and over here we don't have any discontinuity. We don't have any hole over here. Okay, it is just a point, just for drawing the diagrams. But over here, this function is continuous, and if we go when we approach from the negative side as well as the positive side, and even when we get x equals to 2, even when we get x equals to 2, so you'll be getting y equals to 7, and that is the fully valid according to your function. That is defined. So the limit of your f of x when x approaches to from both the side is 7. When x approaches to from both the side, from this side and from that side, even if it gets 2, it will be defined, because your function is not set that okay, your y is 3x plus 1 is not equals to 2. So it is not something like this. It's not something like this. It is defined at x equals to 2. So the limit of your function, you can simply put the value of x and you'll be getting your limit value over here. So you can simply put the value over here and then you'll be getting your the limits. Even when you say it, it goes from the left side and the right side, and it seems to be approaching 7. Okay, coming to that, now we have seen this. Now what I'm going to do is to a little bit twist it so that you could get at least the idea of why limits are too much useful in this era. So what I'm going to do is say for an example, I'm just going to take this, and then I'm just to make a hole over here. Okay, so just make a hole over here. Oh my god, this is what I made the hole. Okay, so now the function is defined, this function y is defined everywhere except x equals to 2, and when it's x equals to 2, it is 1. Okay, so what is the limit of f of x when x approaches 2? It's 7. Of course it's 7. But you'll see the main idea that if your function has discontinuity, it will tell you that if we get closer and closer to 2 from both the side, from the left side and the right side, say for an example, you have x, so you put 1.5, so you go from left side, that is you have y function, so that is 1. When you put 1, you will get 4. When you put 1.5, you get 5.5. When you put 1.9, you get 6.7. You get 1.99, you get 6.97. You get 1.999, you get 6.9997. So this is getting closer and closer to 7. If we get closer and closer to from the left hand side, it is getting closer and closer to 7. Coming to that from the negative side. Coming to that from the right hand side. So that is nothing but 2.01, that is 7.003. 2.01, that is 7.03. 2.1, 7.3. So this is also, it seems to be approaching 7 from the right hand side. So the limit is 7. Okay, so this is how you take out the limits, and I hope that it's completely making sense, at least to you. Okay, coming to that later on. Now, what I'm going to do is to just go ahead, give you the topic, which is one-sided limits. Okay, so you all have seen the one-sided limits, but it's my job to make you familiar with these stuff. Okay, so I'm just going to take only this diagram. Okay, now just let me just make it in the new page so that I could make you understand a better way. Okay, So when x approaches 2 from this side and then that side. Okay, let's make a new function. Let's make a new function. Don't ask me what's the name of the function. Just let's draw a random function so that just we can understand visually. Let's call that function p of x. Okay, let's call that function p of x. Of course, this is a piecewise function. It will be like this: x squared for, and I will just tell you later on. Okay. Coming to that, so let's make a function. This one, let's make a function. Let me draw a dot line. At least a line, something like this, and then something like this. I want it a little bit big so that everyone could be able to see it. Now, just going to take this. Now, what I'm going to do, it will be something like this. Okay, so let's do it, and this is from this side. Okay, so assume that this is your function. It's just not a big function which you have ever seen in your era. Okay, let me make a little bit so that everything is, yeah. Okay, so you have so you have a piecewise function. So assume that this is a p of x. Which is a piecewise function which you ever see in your life. Again, just assume that is a function. And over here and over here, you have limit. What is the limit of x approaches 2? Okay, so what is the limit of x approaches 2 from the negative side of your function f of p of x? So when you get closer and closer to 2 from the negative side, means from the left side, it gets closer and closer to 5. That gets closer and closer to 5. It gets closer and closer to 5. That is nothing but 5. Okay, so when you get closer and closer to 2 from the negative side, that's get closer and closer to 5. And when you get closer and closer to 7, when you get closer limit of p of x from the right hand side, okay, it is getting closer and closer to 2. That is nothing but 2. So over here, you're taking the limit from the left hand side and taking the limit from the right hand side, and these both right hand limit and left handed limit are not equal. Okay, are not equal. And so that's why this limit does not exist. This limit does not exist. Why? Because the limit from x approaches 2 from the negative side of a function p of x is not equals to the limit of your p of x when x approaches 2 from the positive side. It's not equals to, which you can clearly see over here, that the x approaches 2 from the left hand side and x approaches 2 from the right hand side is not equal. But in previous cases which you have seen, they both were equal. So there the limit exists, but here the limit does not exist. Okay, so this is what the whole idea of the one-sided limit. When someone asks you to evaluate something like this, get the limit from the negative side, you're just going to go get closer and closer, make a tabular format, and then go ahead. But we'll see how to evaluate the limits in our next section of a function. So don't worry about that. Okay, I hope that everything is clear. And now what I'm going to do is have a small understanding of a function. Again, a piecewise function. This is a piecewise function. So let's take another piecewise function. So what I'm going to do it will tell you the idea of infinity, which we'll talk about. We will talk about this in our next video a little bit more way. I'm just going to give you the intuition about this. Okay, so this is your something like this. Okay, assume that this is 1, 2, 3, 4, 5, 6. Okay, this is also 1, 2, 3, 4, 5, and this is also 1, 2, 3, 4, 5, 1, 2, 3, 4. Okay, now what I'm going to do is to just make us over here. Okay, to make something like this, and when we say that when x approaches, when the limit of f of x, let's say the function f of x, when x approaches negative from the right hand side, even from the left, let's say from the left hand side, when the limit gets close and close to the left hand side, so it says that it's getting to infinity. It's getting to infinity. Okay, because you have a vertical asymptotes over here. Vertical asymptotes. Okay, so it's getting to infinity. So we say that is a infinity. That is the infinity. Okay, so this is a general idea when the limit can be infinite. Okay, so don't worry about this. We'll talk about vertical asymptotes because this is a vertical asymptote. So we say that when the x approaches 3, it gets the limit of the function gets to the infinity. Okay, cool. So what I'm going to do now is talk about the last things of the topic which we are left on, is about continuity. I think so. Yeah, we'll talk about continuity. But before that, I want to give you a formal definition of a limit, so that you could just write somewhere so that everyone is familiar with it. So the formal definition of a limit, let f be the function, okay, so let f be a function, and c be any real number, okay. Limit of x approaches c of your function. C is the arrow number. Mainly we call it an arrow number, which we have to approach. This limit exists if and only if 3 conditions are met. First condition: limit of f of x when x approaches c from the negative side exists. Second, limit from x approaches c from the positive side exists. And third one is limit of x approaches c from the negative side of f of x equals the limit of x approaches c of the function f from the positive side. So they should be both equal. Okay, so these are the 3 conditions where you all have seen in a real life examples, which I just showed you about this example or this example maybe. Okay, cool. So now let's talk about the last thing, which is nothing but continuity. So what I'm going to do is just spend some minutes talking on this. So we'll talk about continuity. So let me just give a definition. Continuity. Okay, continuity. A continuous function, basically the definition states a continuous function. Continuous function is simply a function with no gaps or holes in between. Okay, so a function which you can draw without taking, for example, I can draw something like this. So which has no gaps, okay, or and holes in between. Okay, so this is a continuous function. Okay, so we'll see some of the examples where the functions are continuous and where the functions are not continuous. So let's see some of the examples where the functions are continuous. So just going to make it something like this. Oh my god, it's not correct. So let's assume, oh my god, what is this? I think that I'm losing my mind. I think so. Yeah. So over here, this is a function this is function what let's say p of x, and this is continuous because you are drawing without taking out your hand. And since one of the main thing about continuous function, if you are making it draw without taking your pencil off the paper, then it's continuous. That's another cool definition which is provided in some of the book. Okay, so this is a continuous function. Let's draw something like this. It is also the continuous function. So this is also the continuous function of the absolute value of x. Okay, so this is also a continuous function. But what are not continuous functions? So let's take an example. Of this function. The function states you have maybe something like this. You have something like, oh my god. You have something like this. And let's do one thing. Let's just make a hole in between. Okay, let's just make a hole. And this is not a continuous function. Okay, another stuff is, I will tell you the good definition. Another can be. Let's take example of this. Okay, so this is I'm going to make a piecewise function. I'm going to just make a piecewise function, and this function is also not continuous function. Okay, this function is also not a continuous function. Let's draw vertical asymptotes. So this is also not a the function which is continuous. Okay, because you're taking off your hand. Another stuff which I'm going to talk about is another piecewise function. Another piecewise function, which is this one. Okay, make a hole over there, and let's make there's a hole over here. So this is also not a continuous function. Okay, so whenever there is some kind of piece, the constraints, it's difficult. So basically, you're seeing the two functions. So let me draw another function, another same function which you all had already seen, so that I could take one example of this. Something like this one and something like this one. Okay, so these are the two functions which are not continuous. So these two functions with the gaps are not continuous everywhere. These functions are not continuous. I'll not say, but the more precisely I would say, these two functions with the gaps are not continuous everywhere. These two functions are continuous everywhere, but these two functions are not continuous everywhere. But sometimes a function is continuous everywhere it's defined. Okay, such a function is described as being continuous over its entire domain. So if the function is continuous, that means that the function is continuous over its entire domain. Okay, which means that its gaps occur at x values where the function is undefined. Okay, so which you're seeing the function p of x is continuous over the entire domain. Is continuous over the entire domain, which you're seeing over here. It's continuous over the entire domain. It don't have gap in between. But over here, g of x, on the other hand, it's not continuous over its entire domain. Okay, so g of x is not continuous over its entire domain. Maybe for example, you have this diagram. So this diagram. So this function y is continuous over its entire domain except at x equals to 2, because at x equals to 2 it has a hole. So this function y is not continuous everywhere except x equals to 2. Okay, so this is how you say if the function is a continuous or not. Maybe you say you say that the function is continuous over its entire domain, but basically it's a more precise to say that okay, the function is continuous everywhere except at this point. Okay, so this was all about this continuity, and I hope that you got to know what limits. It's a good definition to just take in your mind, and I hope that you will consider this in your own, and I also hope that this limits got in your mind. In the next section, we'll talk about the evaluating limits, and then we'll get on differentiation, my favorite topic, and then we'll talk about integration, calculus over. Okay, and then we'll go to probability theory, because probability theory is also very, very important in this era. And let me know that I was reading a book not what you want to gift in a Christmas, because I'm thinking that I should make a very, very, very comprehensive data science 1-year plan, master plan, or roadmap to complete and in depth to get in FANG. What do you say? I'm not in FANG, but I think many of my students got into FANG. So I think I'll be eligible. I'll be taking help from a lot of people to make that roadmap available. Okay. So I think that if you want that, please comment it down below. I'll be very happy to give you as a Christmas gift to make a full data science plan. Data scientist plan, which goes from very scratch maths and just go step by step with book recommendations, with every stuff. Let me know in the comment box below. I'll be catching up your next video. Till then, bye. Have a great day.
Hey everyone, welcome to this video. Basically in this video we'll talk about how do we evaluate the limits, because in the previous video I've just given you an introduction to limits. We haven't solved, as I've just shown you the numerically how, maybe graphically, how do we even go ahead and take out the limits with only few examples. In this video, what I will do is I will try to show you some of the methods for how we evaluate the limits. We'll talk about substitution, mainly the plugging one, and then we'll talk about how do we evaluate limits using calculator. And even if it does not work, there is algebra, which is always there for you in maybe factoring, evaluation of a limits using factoring, and rationalizing and conjugate, and Sarah will talk about that today. Okay, and I will just give you a brief about squeeze theorem so that you could be familiar with what a squeeze theorem is. Okay, just a sandwich theorem. Cool. And the frequency of the video will be bit low these days. The reason why CS001 preparation is going on, and a lot of work is on my head, so it's bit slow. But yeah, it's just like 3 videos per week is coming, as mentioned, as promised. But previously there was 5 videos, 6 videos were coming. But I think it's my apology that I'm not going to upload more than 3 videos per week. Okay, and the homework set is updated on the homework set will be updated on your LMS. Please go there and try to solve it. I'll just have our TAs to grade your assignments. Okay, cool. So plugging and using the calculator. So let's talk about plugging. Let's talk about plugging. So limit of x approaches 3, okay, and of a function x squared minus 10. Okay, so what is telling, this is your function f of x. So function f of x is nothing but x squared minus 10. Okay, so what is the limit when x approaches 3? Okay, so maybe just when you plot this function, and when you approach x from the left hand side and when you approach x from the right hand side, it seems to be approaching minus 1. Okay, but it's not possible for every time for you to draw a graph and then go ahead. So what you do, you first of all try the substitution. So over here it seems to be approaching 3, and it seems like a continuous function. Okay, and it is a continuous function. So over here, what you do, you put 3 into that x. You put the 3 input to the f of x. So what do? You simply put 3 over here. Okay, so 3 square minus 10, which is equals to minus 1. So the limit of x approaches 3 of this function is equals to minus 1. It says that it's the function when x approaches 3 from the left hand side, and the right hand side seems to be approaching minus 1. Okay, or is approaching minus 1. So what you do first of all is to try direct substitution. You just give the value of x to the function, which is over 3 over here, and then you take out the answer of it. Okay, so this is called substitution method or plugging, and it only works with a function which is continuous. It only works with a function, only works when your function is continuous. Otherwise it works very well in most of the cases. Okay, but don't you think that this is just like a function? No, this is not like a function. It is just a method which we use everywhere. I will tell you how it is being used everywhere, but every time it is not possible that this case happen. Let's take another example. let's say an example that you want to take out the limit of the function, which is 10 over x minus 5 when x approaches 5. When you try this plugging method over here, what will happen? What will happen? It will simply, this is a function to 10 minus 5 minus 5, so you put x 5, that will be 10 over 0. That is indeterminate form. We say that is indeterminate form, and this is undefined, and the limit does not exist, but the limit do exist in this case. Okay, maybe in some time we'll see the tools that will say the limit that will help us to evaluate these kind of limits, but over here this is undefined. So that's why the substitution does not work everywhere. Because it is giving you the indeterminate form if it is even a continuous. Okay, cool. So now this is the first method which we have seen. Let's see the second method, which is of using the calculator. So using calculator, let's say for the sake of example, I will take another example. Limit of x approaches 5 of the function x square minus 25 over x minus 5 equals to what? Okay, so this is the thing. So what I will do, I'll make use of calculator. What you can do first of all is to put the values of 5 over here. So maybe 5 square minus 25, so 5 minus 5, so 5 square 25 minus 25 over 5 minus 5, that will be 0 over 0. And when you divide something by 0, that is undefined. So the plugging method is not working over here. So what method will work over here? So what you do, you take your calculator, okay, you start putting the values of x from the left hand side, and start putting the values on the right hand side, and make a table of it and see to whom it is approaching. Okay, so say for an example, this is your x, and this is your y, so x maybe, let's say 4.9998. Okay, so 4.998. Now when you put this 4.998, when you go from the left hand side, when you put this in function 4.998, that will be 9.998. Okay, now you put 4.999. Okay, so that will be 9.999. Okay, and when you put 5, it is undefined. Okay, now you have seen from the left hand side, it seems to be approaching what? Y is approaching what? It seems to be approaching 10. So the limit of x approaches 5 from the left hand side of this function x minus 5 is equals to what? 10. It seems to be approaching 10 from the left hand side. Okay, but the definition of the limit, what we have seen, the limit, I'll just draw it, the limit of x approaches a from the negative side of the function f of x should be equals to limit of x approaches a from the positive side to be the limit called as, so that the limit x approaches a is equals to whatever. Okay, so if this is 10, this should be also 10, so that it could be called as so that the limit from the both sided limit should be same. Okay, so over here when we put 5, when we put 5.001, okay, so when we go from the right hand side, it seems to be approaching also 10 to 10.001. So when we put 5.002 from the right hand side, I'm telling 10.002, so 5.002, it seems to be approaching 10.002. Okay, so basically the limit of x approaches 5 from the positive side of this function f of x, let's assume this function f of x is also 10. So as per the definition of a limit, the limit of a function f of x when x approaches 5 from both the sides, it seems to be approaching of the function f of x, it seems to be approaching 10. So using the plugging, our limit was undefined, but using the calculator, the limit, we define the limit. Okay, the limit do exist. Okay, so this is the second method, using calculator. But every time calculator does not works. Okay, maybe the advanced calculator may work, but basically your computer calculator or mobile calculator does not work, maybe some other cases. So that is using the calculator. Now let's see another thing, another method for solving of it is using algebra, but I do want to see the timing of it. So what's the timing? It's 9 minutes. Okay, I just want to complete it very fast way so that I could not take more of your time. Cool. So what I'm going to do is to solve limit, just to solve limit using your basic algebra. Okay. First of all, what we'll do, we'll try factoring, okay, and then we'll do the rationalizing or conjugation. Okay, so what's the limit when x approaches 5, of the function x squared 25 of x minus 5? That's the same function, you know that it should be 10, it should be 10 x minus 5. We have seen that. Now we'll make use of factoring to evaluate this limit. So basically the limit, what it tells, when x approaches 5, when in this function, when x approaches 5 from both the side, what it is approaching. Okay, so that's what it is. The limit tells what happens when x approaches 5 from the right hand side and the left hand side, and what will be the y value of it. Okay, so the first thing which you'll try is plugging. The first thing always you have to try is plugging. Okay, if now the plugging will be the indeterminate form or undefined. Okay, so plugging is undefined. Over here. So first of all, every time you have to try the plugging first. Second, what you have to do is to factor x square minus 25. So it is basically x square minus 5 square. So a square minus b square. So what it will be? So a square minus b square will be a minus b plus a minus b, and then a plus b. Okay, so that you have already studied. So what I'm going to do, the limit of a function x approaches 5, x square minus 25 over x minus 5 will be what? The limit of x approaches 5, and that we have factored it out. Okay, that is x minus 5 and x plus 5, and in the denominator we have x minus 5. Isn't it? So what we will do, we'll cancel out these two. So what we have left with? X, limit of x plus 5. Now what you do, now you put your x value over here. Now you use substitution. Limit of x approaches 5 of a function 5 plus 5, so that will be 10. So limit of x approaches 5 is nothing but 10. So what you have done, you factored it, you do some algebra manipulation, and then you at last you plug in the value. Now you are left with something. Now you plug in, and then you plug in or use the substitution method, and then you are done with the limit of this function will be 10. That's exactly what we have seen before. Okay, I hope that this is pretty much clear to you. What I'm going to do, just recapitulate once you again, is basically what we have done is to first try the plugging method. Tried the plugging method. Second, what we have done is to factor x square minus 25, and 25 is perfect square of 5. Okay, so x square minus 5 square. Okay, and then using the a minus b and a plus b. Okay, we can write something like this so that it could be cut in like this. Okay, so and then we'll be left with this, and then we'll plug in the values of x, and then you are done with this. Okay, that's pretty much easy. This for evaluation of the limits is. What I'm going to do now is to take another example to showcase you the rationalization stuff, and so that it would be very easier for you at least. So another example is, what is the limit when x approaches 4 of this function root x minus 2 by x minus 4. Okay, so this is where basically you have to evaluate the limit. It's just simply telling when x approaches 4 from both the side, what it is approaching on the y-axis. Okay, so first of all, what I have told to you, is to try out a plugging method. So let's try out. So it will be nothing but 4 root minus 2. Okay, 4 minus 4, whatever above comes, 4 minus 2, that is undefined. Okay, so plugging does not working at a first. Second thing what I've told to do, the second thing what I've told to do is to now we have to think of something like this. So limit of x approaches 4, x minus 2, x minus 4. What we can do so that this x minus 4 cuts off, okay, because this is what is causing the problem at the denominator. So if you know about the conjugate, please see the definition of conjugate, simply changes the sign of it. Okay, please see the conjugate over the internet. It's very one minute definition. You multiply with the conjugate of x minus 2. You multiply the conjugate of x minus 2. So times x plus 2, the conjugate of x minus 2, x plus 2, x plus 2. Okay, now what you will do? So you are left with x minus root x minus 2, root x plus 2. So a minus b and a plus b, that will be what? A square minus b square. So root x square minus b square. Okay, and this will be left with x minus 4 and this root x plus 2, root x plus 2. Now when you do this, x minus 4 above will be x minus 4, x minus 4 root x plus 2, root x plus 2. Okay, I think I'm correct. So this is cutting out, so the left will be root x plus 2, root x plus 2. Now this is your, now what you do, you put the value of 4 over here. Okay, so 1 over root 4 plus 2, so that will be nothing but 1 over 2 plus 2, that will be 1 by 4 is the limit when x approaches 4 of this function x minus 2, x minus 4 is nothing but equals to 1 by 4. That is your answer. Okay, so you have tried plugging, mainly the substitution. The second thing which you have done is to the second thing which you have done is simply factoring, mainly not exactly factoring, multiply the conjugate so that what is causing the problem will be eliminated, and then you put in the value, then again use substitution to take out 1 by 4 is the answer of this eval limit. Okay, I hope it's pretty much clear to you at least. Now what I'm going to do is to talk about nothing but a squeeze theorem. I think that I'm very bad at this, means at drawing squeeze theorems, but I'll fully try to just help you understand what this squeeze theorem tell you. I'm just going to not spend so much time on it, but yeah, it's a good theorem. So basically this is also called the sandwich theorem. Okay, so say you have a function f, g and h. So let's draw a function f, g and h. So let's draw a function f, g. Oh my god, this is not f and g. Okay, so this is your function. So let's draw something like this. Oh, what the hell this is? Just want to take simply this one. Okay, so this is your thing, and what I'm going to do is to add, wait for a second. Okay, and this is your another function. Okay, so this is your, I think that this is your f, and this is your g, and this is your h. Okay, so I hope that this is a squeeze theorem, something like this. So I can just explain you this. So you search online for the exact picture so that it will be better for you at least. So you have a function, you have three functions f, g and h, where g is sandwiched below your function f and h. Okay, so basically this g is sandwiched between your function f and h, and you can see the when this, let's assume this is 1, this is 2, okay, and this is also 1, 2, and this is 3. Okay, so what is the limit of x approaches 2 of a function f of x, okay, what is the when it goes from this side and this side, it seems to be approaching 3. Okay, so this seems to be approaching 3, but It seems to be approaching 3. What is the limit of h of x when x approaches 2? It is also 3, because h is lower than your f. Okay, but when we see when we go from right hand side and left hand side, it seems to be also approaching 3. So the limit of x approaches 2 of a function f of x is equal to the limit of x approaches 2 of your h of x is equal to the limit, and if they both are equal, then that is also the limit when x approaches 2 of your g of x is also equals to 3. So these three will be equal to 3. Okay, so this is what the squeeze theorem tells you. The rigorous proof of this theorem can be seen on the internet if you want to dive in. Okay, so basically what it's telling, the limits of these three theorems will be the same. Okay, don't worry about this. It's kind of not a big deal. Just a basic example to help you understand when x approaches 2 from the left hand side and both ends, right hand side and all the three functions. Cool. So we had, if you haven't understood squeeze theorem, don't try to understand. It's not even on your deep learning syllabus. Okay, so we have seen this very precisely, and I also hope that you understood it as well. In the next video, we'll start off with the differentiation. I will try to complete differentiation as much as I can. I will try to, there is 3 to 4 videos on differentiation. I just want to talk in a very cool way so that everyone could understand what the differentiation is. And it's nothing but the change, mathematics of change. When one change is just a fancy slope, we'll talk about that in detail. I hope you will understand it. I'll be catching up in your next video. Till then, bye-bye. Have a good day. Hey everyone, welcome to this lecture. In this lecture, we'll talk about differentiation. I think we'll just get some idea. We'll reach till the formal definition of derivative. We'll try to define derivative which is using the different coefficient definition. So we'll try to define derivative. We'll try to take out the derivative of a function, which you can think of something like 1 over 4x squared. We will derive these kind of function, f of x equals to, or we'll derive the function like f of x equals to x squared. You will get the tools after this video where you will be able to derive these kind of the functions which are not too much funky functions, something like this. Okay, so it is important as per the AI and ML. If you are just want to get an idea about how differentiation works and how do we take out the derivative, or you want to do your back propagation, because in deep learning we are going to do everything from scratch, maybe deriving the back propagation using derivatives, and we'll try to derive we'll try to take out the derivative of the function when doing the back propagation, and then we'll do the lot more stuffs from very scratch. Okay, so that's why I want all of you to just take a very good attention at this in the next couple of videos, as well as, because in this video I'll give you a geometric intuition as well as the intuition of the definition of differentiation. The next video we'll see the differentiation rules, the quotient rule, power rule, chain rule, and a lot more. We'll also see the vector calculus after we complete differentiation and integration, because I'm just going to cover up integration as well. It's the only reason because in probability and theory, probability theory and statistics, in probability density functions, CDFs, they require you to have a knowledge of integration, and as well as some of the deep learning research papers. It is not too much found integration in deep learning, but yeah, it is in behind of the concepts of PDF, CDF, which you usually do. Okay, so we had a lot more talk. Now let's get started with defining differentiation, and I hope that you will be able to understand. But before that, what I want you to do is just recall the slope, and then using the slope, if you have seen my previous videos, I told you differentiation is the process of taking out the derivatives, and derivatives are nothing but the slope of a curve, okay, or slope of a function. So let me just take one example. Example states, oh my god, yeah. Example states that you have, for example, you have this line. Okay, so let me just draw the line. You have this straight linear straight line, okay. This is on your graph paper where it goes on x-axis 1 unit and it goes above 1.5 unit, okay, and it is the linear, so it is same at everywhere, so 1/2 and etc. So you pick any two point and you see, okay, it is running towards it is running 1 unit and is going above, rising 1.5 units, okay. So it is running 1 unit and it rising 1.5 unit. So slope formula is nothing but a rise over run, okay, or y2 minus y1 and x2 minus x1. We are seeing that is running 1 unit and is going rising. It is running 1 unit and it is rising 1.5 unit, okay. So it is rising 1.5 unit over 1, okay. So the final slope which you will get, which will be 1/2, okay. That is the slope of this function. Let's give this function name as g of x, okay. So the slope of this function is 1/2 and simply means how much y changes when x changes. You can think something like this, as x is changing 1 unit, x is going 1 unit and y is rising up 1.5 unit, okay, when x changes, okay. So that's you can think of slope or the steepness of your line. That's also you can understand by the slope, okay, the steepness of your line, okay. So this is your slope. Now coming to the calculus term, what is the derivative of this function g of x? What is the derivative of this function g of x with respect to x? That will be nothing but 1/2. That will be nothing but 1/2. Why it is 1/2 is because the derivative, as I told, derivative is nothing but the slope. That how much this g of x or y changes, how much this y changes when x changes, how much this y changes when x changes, okay. So that is nothing but a slope. But the fancy term in calculus we give, which is derivative. Of course, there is a lot more difference between your regular slope and the derivative, which we'll see later on. But as of now, what you can see that the derivative of this function g of x is nothing but 1/2. And how this 1/2 came is, we are seeing that, okay, it is a linear line, so derivative is nothing but a slope. But the slope is rise over run, and we are going 1 at this side, running towards 1 and rising 1.5. Okay, so the derivative of this function g of x with respect to x, how much x change or how much y changes, or it is just equivalent to y2 minus y1 over x2 minus x1. You can think of like that because this is a slow formula. Okay, so that is the derivative of this function is nothing but 1/2, and this derivative is nothing but telling exactly the same, how much this function or g of y changes, how much this y changes when x changes a little bit. Okay, so you can think of like that. Okay, so now I'll take another example so you are more comfortable with. Okay, so you have a line, let me just draw a straight line, something like this. Okay, you're moving towards, you are running one unit. Let's assume you're running 1 unit. Okay, and you're running 1 unit and you're rising 3 units. Okay, so you're running to one unit, you're running 1 unit and you're rising 3 units. So what is the slope of this function? So the slope of this graph or the function is maybe 3/1, which will be nothing but 3. Okay, what is the slope? Slope is 3. Okay, what is the derivative? And derivative of this linear, we don't require derivative over here, but what is the derivative? So derivative dy by dx, which just tells how much y changing when x is changing. X is changing 1, it is going 1, and it is rising 1, then y is rising 3. Okay, so that is how much y changes when x changes. Okay, so that will be nothing but 3 over 1. Okay, 3 over 1. Y changes 3 when x goes 1, then y goes up 3. When x run 1, then y rises 3. Okay, so that the derivative will be also 3. So we write this is a formal way we write dy by dx. Okay, so derivative of this function y with respect to x, derivative of y with respect to that point x. Okay, with respect to x. So for example, if you wanted to take out derivative of this point, so you'll get the same thing. You're going 1 at this side and you're moving up. Okay, so I'm not taking the exact stuff, but in the function you will be going. So this is a point. Okay, so that will be 3. Okay, so the slope of the linear lines will be always constant. So any point you go on x, for example, if I go any point on this, the slope will be same. The slope will be same. Of course, the slope will be same. The derivative at this point, for say x1, the derivative of y with respect to x1 will be also, maybe it goes 1 unit and 1, that will be 1. Okay, so it is writing dy by dx, which is the derivative of this function y. We can name the function, but you know the function, for example, we can remove this f of x, we can just write y. Okay, so the derivative of this function with respect to x. Okay, and x can be point. Okay, over here. Okay, so this is the formal way of representing dy by dx. Another way to represent derivative, it is read as dy by dx. Okay, dy dx, which is nothing but derivative of the function with respect to that x. Okay, another way we can write in various ways. We can write the derivative of function in various ways. Let me make you familiar with the ways as well. Okay, so we can write, let's assume we have some function f of x. Okay, which is, let's assume any function. Okay, any function, let's assume f of x. So when you want to take out the derivative of the function f of x with respect to x, you can just write derivative dy dx. Okay, the derivative of function, it is equivalently equals to this. It is, we can also write f prime x or f dash x. That tells you the derivative of this function, derivative of the function f with respect to x. It is also, we can also write this as a y dash, because y is a function and we say what is the derivative of the function y with respect to x. Or we can write f like this, or we can write y this. There are a lot more techniques we can write, d x f, something like this. So they all are equivalent, but we'll follow the formal notation, which is this one. Okay, dy by dx, which is nothing but how much y changes when x changes, and that is nothing but the slope. But don't worry, I'll give you the formal definition of a limit in just a second when we try to define differentiation with the help of a rate. Okay, so we'll come on that, don't worry. Okay, so I'll just give you the formal definition of a limit so that you could just define limit what it is. But as of now, how much y changes when x changes. Okay, so there are tons of, not exactly tons of ways, there are so many ways for writing the derivative notation. Okay, as you know, the peoples are very smart on the earth. They just invent these kind of stuff. I don't know why they haven't stick with that dy by dx, because I like that notation. I don't know what the researchers have thought of. Maybe Isaac Newton has thought of this one, and then a lot of researchers have thought this one, and they all fight it together to get the work done. But I don't know what they have done. I have to go at the past and then ask them. Okay, cool. So we have seen the derivative of a line, and I hope that you understood it as well. So one thing which do we want to go ahead? Yeah, let's go ahead. Let's talk about one similar example so that everything. I don't think we should go ahead and see one more simple example because we have already seen it. Now we have seen the derivative of a line. Now we have seen the derivative of a line, which is nothing but a slope of the line. Okay, so you may think, hey, I use derivative, is that simple? No, it's not that simple. We'll see. But yeah, it is not. It is doable if you keep your good mind concentrated over here. Okay, cool. So one of the example which I want to highlight is from Calculus for Dummies book. Okay, example is from Calculus for Dummies book. You can check out this book. It's amazing book which I ever seen on Calculus for beginners. Is what I use for teaching as a reference. There's an example where there are two students. Let's assume my name Ayush. Let's assume there are two students, Ayush, and let's assume their second student, which is Rishabh. Okay, which is Rishabh. Maybe Rishabh is my best friend over the school, but these are the two students. These are two friends. Okay, which is around, I think they are I don't know the name of this, seesaw. Yeah, that is seesaw. When one goes down, then up. For example, this one. Okay, when one is sitting above on the bench, one goes down, and when this goes down, this goes up. Okay, that's seesaw. I don't know what the name of the game is, but that is the game. Okay, so here it is telling that the Ayush is the weight of Ayush is twice as much as Laurel. Okay, as much as Rishabh. Okay, so Ayush weight is twice as much as Rishabh. Okay, so the Rishabh age is 20. Weight is 20. Then Ayush weight is 40. Okay, so if the Rishabh age is X, then Ayush weight is 2X. Okay, that is twice of Rishabh. Now they are on a sprint. They are on seesaw. And this is something like this. This is a ground. And Rishabh is sitting here, and Ayush is sitting here. Okay, and Ayush is sitting here, and Rishabh. This is Rishabh, and this is Ayush. And of course, I just changed the name so that it is not too much, so that it will be understandable to you all, because I find those names very hard to pronounce, and you can more connect with the Indian names if you're an Indian. Okay, so there are two students, Rishabh and Laurel, where Ayush weights is twice as much as Rishabh. Now Rishabh has to sit twice as much closer, so they have to sit as much closer to Rishabh, okay, for them to balance out. Okay, because it is so much heavy, it's very hard to balance. Okay, and for every inch Ayush goes down. For every inch Ayush goes down, Rishabh goes up by 2 inches. Okay, so when the Ayush goes down by 1 inch, okay, then Rishabh goes up by 2 inches. Okay, so if the Ayush goes down by 10 inches, the Rishabh will go over by 20 inches. Okay, so Ayush weights of course higher, so just listen. My thing is, when Ayush goes down by 10 inches, then Rishabh goes up by 20 inches. When Ayush goes down by 1 inches, then Rishabh goes up by 2 inches. Down, up, something like this. Okay, so when Ayush goes down by 1 inch, then the Rishabh goes over by 2 inches. So Rishabh moves twice as much as Ayush. So Rishabh moves twice as much as Ayush. Okay, so then you got that's a derivative. You got the derivative. So we'll see it. You got the derivative, and you may recall this is nothing but your favorite rate. Okay, we'll see it. So Rishabh moves twice as much as Hardy, twice as much as Ayush. I'm just taking the book's example because I have written my notes over there, that the name of the Hardy over there. But basically, Rishabh moves twice as much as Ayush. Rishabh moves twice as much as Ayush. So dr, okay, so I denote Rishabh with r, is equals to the d2da. Okay, so the Rishabh moves twice up as Ayush. Okay, so with the calculus symbol you can write it something like this. And when you divide both sides by dA, or you move it over here, dr by dA is equals to 2, and that's nothing but your favorite derivative which you got. That's nothing but the favorite derivative which you got. And over here, this derivative, this your basically this what you're seeing is the derivative of r. Okay, so the derivative of your Rishabh, okay, derivative of Rishabh with respect to Ayush, derivative of Rishabh with respect to Ayush. So dr can be thought of as a change in Rishabh position, as dA can be thought of as a change in Ayush position. Okay, so if Hardy goes down, if Ayush goes down by 1 inch, then Rishabh goes up by 2 inches. So dr can be thought as change in Rishabh position, and dA can be thought of as a change in Ayush position. Okay, so that this is what you got when you do the calculation. This is what you got as a derivative, and this that dl by dh, so it's just telling derivative of r with respect to a. Okay, derivative of Rishabh with respect to Ayush. So what does it mean that Rishabh is moving 2 times as much as Ayush? Rishabh moves 2 times as much as Ayush. Okay, that's exactly what you're telling, that this is dy by dx, which is derivative of r with respect to a, is nothing but telling the Rishabh moves 2 times as much as Ayush. Okay, so that's how you got the derivative. You can take a look. This is the derivative which we taken out from the Rishabh point of view. Okay, because the Rishabh was moving up. But over here, you can take out the derivative from the Ayush point of view. Okay, so the dA, the derivative dA can be thought of as a change in a Ayush position, is equals to 1 over 2 dh. When Ayush, it is just telling Ayush moves half as much as this guy Rishabh. Okay, so Ayush moves half as much as Rishabh. Okay, so dA equals to dr. So when we do the calculation, dA by dr is equals to 1/2, and that's your derivative which you got, and that is nothing but the derivative of Ayush with respect to Rishabh, and it simply means that Ayush moves 1.5 inch for every inch laurel that Rishabh moves. Okay, so basically what is doing is it is the derivative saying that Ayush is moving 1.5 when Ayush moves 1.5 inch for every inch Rishabh. Okay, so how much, as I told, how the change in position, so how much A changes when R changes. Okay, so when A is changing 1.5 when R is changing. So when Ayush moves 1.5 inch when Rishabh moves 1 inch. Okay, that's pretty much clear. I hope so. It is. If you are getting confused, please recall the video again so that you could be easily understandable. It is very easy to understand. Again, I'm recalling that this is dA by dr dA by dr is the derivative from the Ayush point of view. So it is just telling how much Ayush changes when R changes, when Rishabh changes, and is how much Rishabh changes when Ayush changes. Okay, so these are two from two point of views. So it is just in this one how much Ayush changes, how much Ayush changes, how much Ayush changes, how much Ayush changes when, how much Ayush changes, oh my god, how much Rishabh changes when Ayush changes, and how much Ayush changes, how much Ayush changes when Rishabh changes. Okay, so this is from different point of view, and we taken out the derivative from the same. Okay, so I hope that everything is clear. I'm not going to talk about too much on that because we have already taken a lot of time on it, and I hope that is very understandable to you as well. Coming to different thing, I think I'll just give you a proper definition of I'll not able to give you the proper definition because it is already, let me the timing that this one helps up. So just see the timing, it's 24. Okay, I can continue it. I think I can continue it. Yeah, so let's talk about, let me give you the formal definition. Let me give you the formal definition of just a English definition, the English definition which the example you saw, is the derivative. So as I already told you 1,000 times, a derivative is simply a measure of how much one thing changes compared to another. Okay, so dA by dr is saying how much Ayush changes compared to Rishabh. Okay, that's exactly called the derivative. Cool. So another we can think of, let's another example can be when a person driving at a constant speed of 60 miles per hour. For example, there is a car. I don't know how to draw a car. Oh, I got to know about the car. Okay, so this is a car. This is a car, and this is going with a constant speed of 60 miles per hour. 60 miles per hour. Okay, 60 miles per hour, and is driving at a 60 miles per hour. So what is the derivative of P with the dP by dt? So it is telling how much position changes when time changes. If there is 2 hours, then where's the car is. Okay, so that we can think of it as a derivative as well. Okay, so we had talked a lot about linear only, and I hope that you understood it as well. Okay, so we have only talked about linear. Over here it is going to the constant speed. It is just going at a constant speed, and we have talked about only the straight lines. We are not talking about the derivative of a curve. Okay, so the derivative of a curve where the slopes are constantly changing at every point, where the slopes are constantly changes. So this is a parabola where the slope are constantly changing at each and every point. So let's say you want to take out the slope at this point C. How you're going to take out? Let's say you want to take out the point F. How you're going to take out? Let's say you want to H. How you're going to take out? So we'll see today about this. Okay. So what I'm going to do is just tell you what's the derivative. Okay, so just going to tell you what's the derivative, but how I take out I will talk about in the next video, or in the next video where we'll learn about the difference coefficient, or I'll try to cover the different coefficient in this video only. Oh, okay, let's try to cover the different coefficient in this video only. Say you have a function f of x equals to 1 4 x squared. So the diagram for this will be like will be like something like this. I'm just going to make it something like this. So that's a graph of this function. That's a graph of this function. That's a graph of the function. I hope so. That's a graph of function. So you have an x, you have an y, and the derivative of d by dx. So derivative. So say for an example, you want to take out the derivative of this point, and this x is 2 and y is what? Let's assume or x is 1. So let's assume x is 1 and y is 0.25. Okay, so that is derivative 0.25 d1. Okay, so what it will be? It will be, I'll just take what is the slope at this point? That is, we can use the derivative to take out the slope at that point. I already explained you how we'll see how it does, but later on. But over here, the derivative of this function is nothing but 1 over 2x. You can plug in the values of x. Say for an example that I plugged in 1 over 2 times, or x over 2 times I plug in 2. Okay, so it will be 1, and the derivative at this point 1, it will be 1. It will be what? It will be 1. The slope at this point will be 1. Okay, you have the derivative, and you can put any point, you can put in any x value, you will get the slope at that point. Okay, because we make use of derivative to take out the slope at exactly that point. Okay, so you can make use of 1 by 2x. We'll come to that, how we evaluated 1 by 2x in the later videos, but in differentiation rules, what I will cover in this video only. So this is how you take out the derivative. We have saw using the derivative, you can put in any value of x after taken out the derivative of a function, which is how much y changes when x changes. Okay, so which is 1 over 2x, and x, which is the value which you have to input in to get the slope at that point, or to get the derivative at that point, or to get the rate at that point. Okay, or you all know. Okay, so we had this. We'll see how do we got 1 over 2x. But before that, let's talk about the difference coefficient. Let's talk about the difference coefficient, because it is the most important concept which one need to know. Okay, because most of the things in calculus is based on, it's just because it is needed, because I think if it just tells you how it gets infinitely closer to make the line from curve to a straight line. Okay, so we'll see today only. Okay, let me find the copy which I want, so that I can at least go ahead and help you out. Okay, because I usually make notes before teaching in a video, because I can just hope that I don't make any mistakes in the videos. Say for an example, you have a graph something like this. Okay, you have a graph something like this. Okay, let me just draw this one graph at this point. Yeah, it's good. Okay, and you pick 2 points, let's say this one, x, and this one. Okay, so you pick the 2 points, and you assume that this is a point x, there on the x coordinate is x, and there's a h distance between this point, so this is x plus h. So this is h. So for example, this was 2, and the distance from this to this is h equals to 2. Then over here it will be 4. Okay, so you can assume like this. So h depends on h. Okay, so the distance is h. Okay, the distance is h. So this is a point. The x coordinate is x, and y coordinate. So and another point. So this is x1 at one coordinate, and this is the second coordinate, x coordinate. Okay, so what is the coordinates of this point? It will be x, which is on x, and this is your f of x function. Okay, so this is f of x. Okay, And what is the coordinate of this point? The coordinate of this point will be x plus h is your x-axis, is the point is x-axis, and that will be nothing but f of x plus h. F of x plus h, because we want, this is also the distance of h. Okay, so f of x plus h, which you're seeing over here. Okay, now we got the coordinate of this, we got the coordinate of this. So the coordinate of x comma f of x, and there's h distance where this there on x plus h. Okay, and this one is x, the coordinate of the x-axis, and this is of y-axis. Okay, so I hope so it is making sense. Try, if it is getting confused, try to think on yourself. Is if you move this x plus h, and if you try to put in that function f of x, and we can add some value h. So that's it. That's pretty much the common sense. This is a very common sense to understand, x plus h. Okay, now coming to this. What we can do, we can draw a secant line. We can draw the secant line. So let me draw a secant line, something like this. A secant line, the definition of a secant line is a line which intersects two points on a which intersect 2 points on a graph. That's a secant line, or a more formal definition of a secant line. Let me just have you the more formal definition of a secant line. A secant line is a line that intersects a curve at 2 points. Okay, and to intersect a curve at 2 points, this way we draw the secant line. And the secant line is something like this. Now what you can do, if you take this point, oh my god, I think I have to choose a pen. Yeah, if you take this point, okay, you make it closer to this point. Okay, so when you slide this point with your secant line, you slide this point to over here with your secant line. Okay, so let's do the thing. Now you'll be getting, just make sure that you are following me. Just make sure. You will be having something like, oh my god, the secant line does not work correctly over here. Let me make something touching over there. Okay, now what you do, you now this point has come to over here. Now what you do, you take this point, you slide a little bit with the secant line. You slide a little bit, OMG. You slide this a little bit. Okay, now let me just draw it. Okay, you slide it with the secant point as well. You slide with the secant line as well. Okay, you now what you do, you take this point, again you slide it, again you slide it. Okay, now let's slide it again. It will be, make sure that it intersects at both the point. Okay, now you again take this red one, slide a little bit over here, and let's continue doing that. Okay, that will be intersecting at the 2 points. Okay, at some point it will be, so let's draw the graph again. So what you're actually doing, you are making this h to be to approach 0. Okay, you are making this h, we can make use of limit. We can make it as we want to go closer and closer to not exactly x, but what we can do, we can make this h approaches 0. When h approaches 0, it will be f of x. So, oh my god, when f of x, okay, f of x and this f of x plus h, when this h approaches 0, then that will be, so let me just make you familiar, let me complete that thing. Okay, so we'll come to this, we'll come to this. Okay, so this was yours and this was your 2 points, Now when you do this, you will be left with something like this, a secant line a tangent line, or over here from the secant, when you take your h approaches 0, when you just make your h make use of limit, make use of limit when h approaches 0. When h approaches 0, okay, so this point will go over here, here. So at some point it will become a tangent. It will become a tangent, and the derivative of any function, of a function, is the slope, okay, of a tangent. The slope of the secant would be, if I draw a secant line, the slope would be, we go at this point, so we go to something like this, so rise over run. So it is very easy. So the secant line becomes the tangent line, and the slope of the tangent line is nothing but the slope, the derivative. The slope of this tangent line is nothing but the derivative. So what you do, so the slope of the secant line, so let's start writing the formal definition. Formal definition. I think it would be very easy for me at least to draw it again. Okay, so everyone is on same page. OMG, let me make a little bit up. Yeah, so this is your 1 point and this is your second point. Okay, let's draw a secant line over here. Okay, and so what will be the slope? What will be the slope of this secant line? So we were having our x coordinate, okay, and then we were having x plus h, and this was the distance of h, okay, and this was x comma f of x, and this was nothing but x comma f of x plus h. Okay, so this is what you have. So what would be the slope? The slope of this would be y2 minus y1, x2 minus x1. Okay, so f of x plus h minus f of x divided by x plus h minus x. Okay, so this plus minus, this cuts down. Okay, so you will be left with f of x plus h minus f of x divided by h. Okay, so now you got the slope of the secant line. That is nothing but called the difference coefficient. Okay, quotient. Okay, why I'm pronouncing it wrong? So that is the slope. This is the slope of your secant line. So when you make your h approaches 0, so this will become a tangent line. So it will go slide over here. You slide it over here. You slide over here, so it will be something like this, and then it will be something like this, and it will somewhat become like this. It will only touch. Okay, it will become something like this. This is the tangent line. This is a tangent line. So how you can do this? You can make use of limits to make your h approaches 0, because if the f of x, so it make in other words, you're either sliding this point to this point, and that will be equivalent. The coordinate will be equivalent. So you just want h to be 0. So h approaches 0, not exactly 0. Technically, you can't get exactly 0. F of x plus h minus f of x divided by h. Okay, and that's the derivative of your function with respect to x. That's the derivative. That's the definition of a derivative with respect to x. Okay, so the secant line becomes the tangent line when you approach h to the 0. So I hope that this makes a complete sense. Okay, so it just tells how much the function is changing when x is changing. It is what it does. So what it does, again I'm telling, it slides. You can see the slides over here. It started to become the tangent line. So it started making h approaching 0. Okay, you made use of limit to define this derivative, and the formal definition of a derivative. Let me just define it for you. Okay, I think I have to find a good definition of it. Yeah. So the definition is derivative of f of x with respect to x is equals to limit when h approaches 0. f of x plus h minus f of x divided by h. Okay, that's the formal definition. And what it does, this slope, or this simply the shrinking, we are shrinking rise over run. We are shrinking the rise over run. Okay, we are making shrinking, we are making use of limit property, we're shrinking over here, sliding this coordinate to this coordinate. Okay, so we had a talk a lot, and I hope that you are enjoying it as well. Even I am enjoying it. Okay, but one thing, just one question which I want to solve is take out the derivative of the function f of x, which is 1 over 4x squared. Which is 1 over 4x squared. We are going to take out the derivative now. Okay, which you've seen, we have taken the derivative. Okay, 1 over 2x. I will just show you how I taken out. So this is your function. Now let's go ahead. Now let's put in, we have a definition. Now we can limit of h approaches 0. Limit of h approaches 0. We can put this x. This x is the coordinate which he wants. So we are just going to give x, and we can take this 1 over 4 as a coefficient. Okay, because that only wants 1 over 4. Okay, x plus h, and we don't have to leave a square because this is the one x we want. Okay, minus your whole function 1 4x squared. Okay, 1 4x squared. Cool. Divided by h. Divided by h. Okay, so this is your, now we are going to evaluate this limit. So the limit of h approaches 0, 1 over 4x squared plus 2xh over 4 plus h squared, a plus b ka whole square, 1 over 4x squared. 1 over 4x squared. So this one cuts out this one, this one cuts out this one, so you are left with limit of h approaches 0, 2x plus h over 4 plus I can write it something h square. Okay, you can write the 4 over here as well. You can write this 4 over here as well. Okay, because when you multiply this, oh my god, why I've left this, when you multiply 1 over 4 with every member of this, so that will be nothing but let me be a little bit transparent. Let me be a little bit transparent then. I think that I've done wrong a little bit. I don't have to do wrong over here. Yeah, let me be a little bit transparent. So, oh my god, sorry for delays, but 1 over 4 just expand in x squared plus 2xh plus h squared minus 1 over 4x squared. Now you simply limit of h approaches 0, 1 over 4x squared plus 2xh by 4 plus h squared by 4 minus 1 over 4x squared. This cuts out with this. Limit of h approaches 0, 1, and now it cuts down. So 2x h 4 plus h squared 4. Okay, let's keep on working on it. So that let's write the same thing again. H approaches 0, 2x h by 4 plus h squared by 4 by h. I think I forgot in everything. H, we don't have to forget h. Okay, by h, so h is there, don't forget. Okay, now what I will do, I will try to add it when h approaches 0, 4. Okay, so that will be nothing but 2x h plus h squared. Okay, so the limit of h approaches 0, we take common h, 2x plus h by 4 by h, and this cuts out, this and this cuts out. Okay, so the limit, now it's very easy, 2x plus h by 4. Now you can do the substitution, limit, now we don't have right limit, 2x plus 0 by 4, and that will be nothing but 2x by 4, and that will be nothing but x by 2, or 1 over 2x. Okay, this was that much easy to calculate the derivative of a function, okay, using our formal definition of a limit, and we showed you the geometric interpretation of the differentiation, and I hope you really enjoyed it. Try to take out the derivative of x square. So just for your convenience, the limit, it will be x plus h square minus x square divided by h. Okay, divided by h. So let me see if it is exactly equals to the same. Yeah, it is divided by h. Okay, so this, now try to take out the derivative of a function f of x, which is x square, and using the limit formal definition. Okay, so I hope that this is pretty much clear to you, at least. I hope so. It is very much clear. Although you get a very complex function, it is not we can't use our we have a differentiation rules which will help us to take out the derivative very quickly, which we'll talk about in the next video. Till then, bye-bye, have a great day. You have done a great job today. Meet you in the next video.
This video, in this lecture, basically we'll talk about differentiation rules. And in our previous video, we talked about differentiation, which is approximately 40 minutes of video. So sorry for that much long. The only reason is I just completed the whole differentiation definition, because in the previous video we given you the geometric intuition of differentiation. And in this video we'll see some of the rules for taking out the derivative of a function, of even a complex functions. We'll try to take out in this video and the next couple of videos. So try to see that, and then we'll see local minima and maxima. We'll try to see that in the future videos, and then we'll go on integration. We'll complete the integration the same way as we completed differentiation. However, we'll not focus on that much on integration because it is not being used too much, but we'll surely take a look, because sometimes integration comes over the research paper. Then we'll go to the probability theory and statistics, and then we'll start with deep learning. And you may be thinking, hey Ayush, why we are learning these much things? And just let me tell you what happens if the beginners get very confused. Oh my god, what is happening behind the algorithms when they study deep learning? So when we are going to start with deep learning, then we are going to go very fast way. Okay, it's because you'll be understanding each and everything whatever I'm going to write it out. And if you don't see these videos, if you don't know what is calculus, if you don't know what is differentiation, integration, you'll be not getting the actual point of view of deep learning, and you'll be not understanding deep learning. So that's why we are doing all those things, and it's very useful to learn these as well for your professional career, because it will, maybe if you want to go in research, it will you'll be able to understand hardest research papers in this era. Okay, so let's get started with the differentiation rules. I'm not going to recap the previous video, but I want you to see the previous video, which we have already had a talk on that. But we had formulated a definition. We have formulated a definition of differentiation. So let me just give you what definition we have formulated. If you want to take out the derivative, dy by dx, and y is a function. Okay, so we are solving for y. So if you want to take out the derivative dy by dx, we were having a limit definition. Okay, it is using the difference coefficient. When h approaches 0, f of x plus h minus f of x by h. Okay, and by solving this, by using this, we are able to get it. But when you have too much complex functions, it would be very tedious and almost impossible for you to achieve using this. Okay, so that's why we have differentiation rules, which will help us to take out the derivative of the functions. Okay, so let's get started. So let's get started with today's video. The first rule which I'm going to talk about is the constant rule. Okay, so everyone should be familiar with it. It's a constant rule. The first rule which I'm going to talk about is the constant rule. So what this rule tells, if you have a function, let's say f of x equals to 5. Okay, f of x equals to 5, and
and the derivative will be 0. The derivative will be 0 and the slope will be also 0, because derivative is nothing but a slope, and over here the derivative, the change, it is nothing is changing, so derivative will be 0. So the derivative of this function, so basically we'll write y equals to 5. So derivative of f of x with respect to x, so we write f of x is equals to 0. Okay, for this function, the derivative for this function f of x is with respect to x is equals to 0. Nothing is changing. Okay, nothing is changing. Just I want to introduce to you the notations. I want to introduce to the notations. We can write this in a short form as well. F prime x equals to 0. So this is this notation d f of x by dx, d of f dy by dx is equivalently equals to this. Okay, so it is just telling f prime x, just a short form which we'll use interchangeably. We'll use this consistently, both the format, so that everything is crystal clear. So we'll use both the things very frequently at the same time, okay, so that it saves the time. And I like this notation much better, but for the definitions of the rules, we'll use this notation so that everything is clear. Okay, so we'll use these two notations very frequently over this video. So let's take some more examples. So this was the one of the example. The another example which I want to talk about is g of x equals to 7. G of x equals to 7. So what is the derivative? Of this function g of x, with respect to x, which is also equals to 0, or f g prime x is equals to 0. Okay, so this is the constant rule which we had a talk on. Okay, now let's go ahead. Let me just finish this stylus. Now let's go ahead. Let's talk about the functions. Like, let's take an example. You want to take out the derivative f of x equals to x to the power 5. X to the power 5. You can use this lemma definition to do this, but there is a very quick way to take out the derivative of this function. Okay, how much x is changing when y is changing. Okay, so you see the definition in my previous video, because you will be getting more broader view what this derivative is trying to do. Okay, so we can use a rule called power rule. Okay, this is a very extensively used in other rules as well. So please make sure that you understand each and everything. So f of x equals to x to the power 5. Okay, so let's take an example. You take out the derivative of this function f of x, with respect to x. So how will you do it? So derivative of this function f of x with respect to x, which will be nothing but what you do. You take this power and bring as a coefficient of x. So you will take this power, okay, bring that in the front of the x, okay, and reduce that power by 1. Okay, so 5 minus 1, so it will be nothing but 5x to the power 4. Okay, 5x to x to the power 4. So there are two things which you have done. The first thing which you have done is to brought the power to the just as a coefficient of that x, okay, and reduced the power at that x value by 1. Okay, let's see some more examples of it, so that it would more make sense, at least to you. Okay, so let's take an example that you have a function. Again, let's use the function name of f of x, which is equals to x square. Okay, so how you're going to take out the derivative of this function, so how you'll take out. So what we do, we take this 2, bring in front of x, 2x 2 minus 1, so it will be left with 2x, and this is 1, so we can neglect it, but this is your actual derivative. This is your derivative of your x squared. Okay, so this is the derivative of this function f of x. Okay, if you use this limit definition, it would take around 2 to 3 minutes or maybe 5 minutes for you at least to take out to reach till 2x, but in 2 steps or 2 seconds or even 1 second we completed it. Okay, so that's why these rules are very, very important as well. Let's talk about one more example. You have another example, x to the power minus 2. X to the power minus 2. So what will be the derivative of this function? So the derivative of the function, which is dy by dx, which is nothing but equals to, you bring this minus 2 in front of it. Okay, now what do? X to the power 2 minus 2 minus 1. So it will be nothing but minus 2x minus 3. And this is the derivative of this function. Okay, bringing the power in the front of the x and then reducing that power by 1. Okay, so that is called the power rule. Okay, the another rule which is related to power rule, which is nothing but the constant multiple rule. The constant multiple rule. Okay, the constant multiple rule. So let's take an example that you have f of x. Okay, you have a function. Let's name it a y, because I have to write f of x times and times. So let's use y equals to 4x to the power cube. Okay, the 4x cube, and you wanted to take out the derivative. You want to take out the derivative of y prime or dy by dx, the derivative of the function with respect to x. Okay, so what you do, you simply take this scalar, okay, that multiple 4 times the the derivative of x cube. Okay, Okay, so what you will do, dy by dx of this x cube, or wait for a second, let me just make it more transparent at least, so that it will be very, very useful for you at least. Dy dx x cube. Okay, so 4 times the derivative of x cube will be, what? You can use the power rule, bring the 3 in front of it and reduce the power by 2. 3x squared. It will be nothing but 12x squared is the derivative of the function y. Okay, so dy by dx, which will be nothing but 12x squared. Let's take another example. Y is equals to 2x squared. Okay, what you do, you take out the derivative of this, and after you taken out derivative and then multiply by 2. Okay, so the derivative is equals to 2 times the derivative of x squared will be what? Bring 2 in the front, subtract, which is 2x, which is 4x is the derivative of this function. Okay, so that's called the constant multiple rule. Are you getting what I'm trying to say? Yeah. So this is the 2 example. Let's see one last example so that it may completely sense to you. 4x to the power 3. Okay, 4x to the power, oh my god, I've already taken it. 5x to the power maybe 4. Okay, so how do you take out the derivative of this? So what you do, 5 times the derivative of x4 will be, bring 4 in the front, then subtract 4 minus 1, which is 3, which is 20x cube. Okay, so this is the derivative of this function. The derivative of the function will be 20x cube. Okay, so this is called the constant multiple rule. Another rule which we are going to see, which is called the sum rule. Okay, which is again the useful rule.
It is fairly simple rule. Okay, so let's see the sum rule. So the sum rule states, let's say you have a function, f of x, which is equals to x to the power 6 plus x to the power 5 plus x to the power 3 plus x to the power 2 plus x plus 10. What is the derivative? What is the derivative of this function? Or what is the derivative of this function? What is the derivative of the function? So the derivative of the function will be, so what is the derivative function? So what do? You take out the derivative of every terms. Okay? Take out the derivative of every terms. Okay? So what is the derivative of x cube? Sorry, x to the power 6. So we can use the power rule. So what is the derivative, which will be, bring 6 in the front, okay, 6x to the power 5 plus bring 5 up in the front, 5x 4 plus bring 3 in the front, 3x square plus bring 2 in the front, 2x 1 plus it will be what? It will be 1. Okay, so because this is 1 minus 1, which will be what? 0. Okay, so x to the power 0, which will be equals to 1. So 1, and this is called, this was the constant rule. Okay, so this what is the derivative of 10, which will be 0, because there is nothing is changing over there in that for that function. Okay, now this is your actual derivative, so we can simplify it. 5x to the power 4 plus 3x squared plus 2x, and this is the derivative of this function. Okay, so this is called the sum rule. Okay, the same way the difference rule works. Okay, so instead of plus there will be minuses. Okay, instead of plus there will be minuses. The one example which I want you to work on is g of x, which is equals to 2x to the power 5 plus 6x to the power 8 plus 10x to the power minus 1. Okay, try to work in it and take out the derivative. If the function is differentiable, take out the derivative of it. Okay, maybe it is differentiable, maybe make it plus. Okay, so you want to take out the derivative of this function g of x. Okay, cool. So try to do this. Just pause this video and try to do this. If you can, go ahead. Otherwise, let me try to do this for you. So let's do this. So 2 times it is 4 x. So sorry, I just mind it's my habit. I don't know why. 5x to the power 4 plus 6 times 8x to the power 7 plus over here it will be 10 times 1. Okay, 10 times 1, and over here the left will be 10x4 plus 6 8 48x7 plus 10. Okay, so this is the derivative of this function. Okay, so try to work on several examples. The problem set which will be released through your LMS. Okay, you can see from there. Soon the LMS will be updated with the prior information, the certificates of the chapter number 1 and the chapter number 2 will be given to you. Okay, please see the LMS for the same, and the email if you have enrolled in LMS, because there are only around 100 students which have enrolled. I want more of the people to enroll, at least 400. Okay, another now we have seen the constant rule, power rule, multiple sum rule, and difference rule. Now what I want you to do is to remember how do we differentiate trig values, and it will be very tedious start for me to at least showcase. So what I want, I have seen a lot of people to memorize this, because this is very, very handy. Okay, so we are going to talk about differentiating. Just don't memorize it. You don't have to see how it came and how we derived it. Okay, this is most of the people just remember this. Means whoever is good at this. Okay, just you can what is the derivative of sine of x with respect to x, which is nothing but cosine of x. Okay, the derivative of sine of x with respect to x is cosine of x. derivative of tangent of x with respect to x, which is nothing but secant sec square x. Okay. Another is derivative of sec x with respect to x, which is nothing but sec x tan x. Okay. Another is derivative of cosine of x with respect to x minus sine of x minus sine of x. Another is derivative of cotangent of x with respect to x, which is nothing but equals to minus cosecant square x. Okay. And the last one is derivative of cosecant of x with respect to x, which is nothing but minus the cosecant x times the cotangent of x. Okay. So these are the 6 trig values which I want you to remember. Okay. Because it will be very useful when we talk about further rules, and very handy as well. Okay, you can always review, means if you do the lot of practices, it will be automatically memorized in your mind, because I haven't seen the lecture notes for writing these. Even whatever I'm teaching, I'm not seeing my lecture notes, because I practice a lot of it. I remember everything. Okay, so try to just practice it out. It will be very easy for you to at least understand it. These are 6 trig values which is very handful in your calculus journey till now. Okay, and this is taken from one of the most famous book on calculus, Calculus for Dummies. Okay, so now what I'm going to do is we have seen some of the derivatives of some of the trig values, which is 6 trig values. There you can search for online if you want to see the steps how they have come up with, and if you want me to do, just feel free to comment it below. Maybe I can make a next video on it, but again, this is a totally optional one. Okay, so now what I'm going to do is talk about the last thing, differentiating exponential and logarithmic functions. Okay, at least this is very important as well. How do we differentiate a logarithmic function, and how do we differentiate exponential functions and logarithmic functions? And then we'll see in the next video, we'll try to see the product rule and the quotient rule, and in the next then in the next video we'll try to see we'll try to see the chain rule of differentiation. We'll try to see how to use different like products rule in chain rule, how it is very useful in that. Then we'll see the implicit differentiation. We'll see the logarithmic differentiation, which is very useful in your calculus journey at least. Okay, let's get started with exponential functions. Okay, exponential functions, let's get started with that. Differentiating exponential functions. Let's start with it. So what is the derivative? What is the derivative of e to the power x by, with respect to x, which is itself, okay? So that the derivative of this e to the power x is itself, the derivative is its own function. Okay, so e to the power x. Okay, if you want to see how it came, I would just link some video, some resources which I really like to, because if I again go ahead and teach you, it will very boring, and also it is out of the bound. So what I did suggest you to see the link in the video description. Okay, so the derivative of any exponential function means the e to the power x is equals to the itself. Okay, but what if we have a function f of x which is equals to 5e to the power x, 5e to the power x. So what is the derivative? What is the derivative of the function? What is the derivative of this function? What is the derivative of this function? What is the derivative of this function? So the derivative of this function will be, what you can do, you can use the constant multiple rule over here. Okay, you can use the constant multiple rule. So here's how I'm going to do it. So dy by dx 5ex. So what I'm going to do is to take that 5 outside to it, 5 times d by dx e to the power x, okay, so which will be nothing but 5 times which will be nothing but 5 times, and the derivative of the e to the power x is itself e to the power x, so that will be nothing but 5ex, and which yields the same thing. Okay, so the derivative of any exponential function, most of them which I've ever seen, is itself a function. Okay, so I hope that is pretty much everything is clear, and here we use the constant multiple rule, okay, to take that 5 outside the derivative and then multiply with the derivative of e to the power x. Cool. So we have seen some exponential functions. You can try out 6ex, 10ex, whatever you want to try it, man. Okay, so we have seen exponential function. Now let's see another thing, which is logarithmic function, which is a game changer over here. And if you don't know about logarithms, I'll link a video. I'll link a simple Nancy Pai video, which I really like her videos, because she is an MIT graduate, and she teaches very well. These things she teaches very well, and now she stopped making the videos, but her videos on calculus, I know it is bit half or incomplete, but she taught these things very well, like logarithms, some of the rules like chain rule. I even watched her video, amazing videos by her. So you can check out the channel. I'll just give you a link in the description. Okay, so another thing which I'm going to talk about is logarithmic functions. How do you differentiate the logarithmic functions? Okay, so let's take an example. You want to differentiate the function which is f of x, which is nothing but natural logarithm of x. Okay, so how do you take out the derivative of this function, which is natural logarithm of x? Okay, so which is nothing but log base ex, isn't it? Log base ex. So which will be nothing but which will be nothing but 1 over x. So the derivative of the natural logarithm of x, which will be nothing but 1 over x. Okay, we will see when your base is not when your base is something, because what we do, we tend to memorize some of the different derivatives. Okay, and then we'll solve further things using that whatever we had memorized, and it's not a big deal to remember 4 to 5 derivatives. Okay, so this is your derivative of natural logarithm f divided with respect to x, which will be nothing but 1 over x. 1 over x. So if the log base b is a number other than e, if it is other than e, you can tweak this derivative a little bit. Okay, so let's say for a sake of an example, you have a function f of x. So make it f of x equals to oh my god, my hand is paining now. So f of x, which is nothing but equals to log base 2x. Okay, now log base 2x, and how we do it? So what we do, we simply, if you take out the derivative of this function, which is nothing but 1 over x, okay, which is your natural logarithm by, okay, ln 2, natural logarithm of 2. Okay, so natural logarithm of 2. Okay, so when you do this, 1 over x natural logarithm of 2. This is how you do it for if the log base is different. Let's take another example. If you want to take out the derivative of a function which is log base 10x, you also write as log x, which is by default the base is 10. Okay, so I'm going to take out the derivative of this, d by dx of this function log base 10x, which will be nothing but equals to, first of all, 1 over x. You all agree, 1 over x divided by natural logarithm of 10,
and when you do this, 1 over x ln 10. Okay, and that is the derivative of this function. So this is how you take out the derivative of the logarithmic functions, and I hope this is pretty much clear to you. Okay, what if we try to cover this in this video about product rule and quotient rule? Just wait for a second, I have to see the timing which we have covered. We can do, yeah, let's cover the product rule, let's cover the quotient rule. Okay, so no, let's get on to the next video to cover these two, the product rule and the quotient rule. It would be better for us at least, so that the video duration should be short. Okay, so we had seen a lot in this video. I'll be catching up in the next video. So now let's get started with product rule, because in the previous video we had a talk on this various basic differentiation rules, which is far more very easy to understand, and from this video the things will get started a little bit difficult, but as a sum rule, as the difference rule, the same will be the product rule, but the product rule is a bit important, and quotient rule is also a bit important for solving the derivatives questions, and as well as the reason why I'm teaching these, because this product rule and quotient rule is important in your chain rule and implicit differentiation, and chain rule is the far most important thing which you have to cover for deep learning. And then so that's why I don't want to leave this product rule and the quotient rule, otherwise I would have definitely skipped. But these two important rules which I can't forget, the reason why you all know is these are my favorites, because it is easy to teach. Okay, so assume, that's what I can say to you. Assume that you have two functions. Oh my god, my hand is paining again. I don't know what happened to my hand. And what do you think? I should take some break or what? No, let's not take break. Let's continue working on. Otherwise tomorrow I will die, and no one knows what will happen. So you have a two function f of x and g of x which are differentiable. Okay, which are differentiable means we can take out the derivative of this. We'll see when the function is differentiable and when the function is not in our later videos, or you can search online for the same. But say you have a function which is differentiable, and now if you take a if the function are in this format, so you have a h of x which is f of x times g of x. Okay, so you have like a product of kind of thing. For example, you have a function y x cube times sine of x. So how you're going to take out, so this is your f of x, this is your f of x, and this is your g of x. Okay, so how do you take out the derivative of this? So the derivative of these kind of function dy by dx of a function f of x g of x, which will be nothing, which will be equals to f of x times, okay, the derivative of g of x, okay, of g of x plus g of x times the derivative of f of x, okay. So this is how you do it. First of all, you leave the first thing and then you multiply with the derivative of the second function, then you plus it, then you leave the second thing, you multiply the first one. Okay, you can write in this way, because just to make sure that you will not be confused, I can write in different ways. First of all, I can take this derivative and then this one. Okay, so for example, d by dx f of x, okay, times g of x, leaving the second function alone, plus then leaving the first function alone, times taking out the second function, changing the position, which does not matter at all. Okay, because you will see it, that I will do it because that's my way of doing these, everything interchangeably. Coming to the next notation, we can write this out. Let assume u be f of x, and v
let's assume v be g of x. Let's assume v be g of x. So you can also do this, but you will just replace f of x with u and g of x with v. Okay, another notation which I'm going to write it out, which is very important. F of x times g prime x, so this we can write the derivative in this way, so this can be written in this way, plus g of x times f prime x. Okay, so this is the quotient rule, which is the definition of a quotient rule. Now let's see some of the examples, so that is pretty much clear to every one of you. So y equals to x cube times sine of x. Okay, so what is dy by dx? It will be nothing but, so you take this x cube, so x cube times d by dx sine of x, okay, plus you leave the now what do? You leave the second one as it is, times you take out the derivative of the first function first. Okay, first for f of x, which is x, the derivative of x cube, which will be something like this. Coming to now x cube times the derivative of sine of x. Remember the derivative of sine of x, which is what equals to cosine of x, plus now you leave the sine of x as it is, times the derivative of x cube, so you bring 3 in the front of it, x squared. Okay, now it will pretty much everything is clear, everything will be clear, which will be nothing but x cube cosine x plus sine of x. Okay, so you can do something like this, maybe a bit more cleaner, 3x squared sine of x. Okay, so this is the derivative of your function. Okay, so let me just make it a little bit more transparent so that everyone is able to see this. So this is the derivative, and this is the product rule from which we have achieved. Let's take another simple example so that it will be very much clear to everyone. 6x squared plus 7x cubed. So what is the derivative of this function? Dy by dx. So first of all, you take out the first one and leave the second one. So 6x squared prime. Okay, so this prime, I'm saying this is the derivative of this function, 6x squared plus 7. Okay, let's multiply. We have to multiply 7x cube plus, now you take out the second one prime, times you leave out the first one, and then when you do this, you just 6 times 2x squared, which is nothing but 2x, which is 12x, times 7x3, okay, times 7x3. Now you simply you can simplify further it, and then you can do it, and now you take out the derivative of this, and then you can simplify it further on, which is very easy for you at least. Okay, try to do it and answer me in the comment box. Coming to this was the product rule. Now let's talk about another rule, which is the quotient rule, where you may have already been guessed, your functions are being divided. Okay, so let's do this. Let's do this. So let's say you have you want to take out the derivative of a function like y equals to sine of x divided by x to the power 4. So how you're going to take up? So we have something called as the quotient rule, which you can use to take out the derivative of these kind of function. D by dx. Let me write the formal definition first, because I do believe in formal definition. So let's write a formal definition, and then we'll come up with, and then we'll solve this example. Okay, so what you will do, so the derivative of this, the quotient rule states something like this: g of x times f prime x minus, you leave the f of x, now you simply multiply with g prime x, okay, and then divide it with gx squared. Gx squared. Okay, leave g of x, multiply with the derivative of f of x minus f of x, leave f of x and then multiply the derivative of g of x and then multiply with g of x squared. Okay, sorry, divide by g of x squared. Okay, and this is the your quotient rule. We can write it in this way format as well. G of x times the derivative of f of x, okay, minus f of x times dy by d gx. Okay, so you and then divided by gx squared. Okay, now using this you can take out the derivative, okay, of these kind of functions. So now let's do one of the example. Let's do one of the example, which is d by dx. Okay, you have to take out of sine of x over x to the power 4. Okay, so how you will do it? So first of all, this is your f of x and this is your g of x, which is, first of all, you take out f of x, sine of x, derivative of this, times, leave x to the power 4, minus sine of x, leave that, times, take out the derivative of this, okay, divided by x to the power 4 squared. Okay, now what do you do? The derivative, which you all remember, cosine of x times x to the power 4 minus sine of x, so times it is nothing but 4x to the power 3, okay, and divided by x to the power 8. You keep doing this. Now let's simplify it a little bit. X to the power 4 cosine of x minus 4x cubed sine of x divided by x to the power 8. Okay, now you keep on doing this. Take as a factor x to the power 3. Okay, and then x cosine of x for this minus 4 sine of x. Okay, and take that as x to the power 8. Now you can simply use the exponents. You can simply you can simply minus it out. Okay, you can simply minus it out, so it will be left with x cosine of x minus 4 sine of x. Okay, when you x, which will be the x to the power 5. Okay, this is x, and this is your final derivative. After you simplify everything, this is your derivative. Either you can go with this, but I suggest some simplify as much as you can, so at least it is doable. Just you can put in the values of x, and then you are done. Okay, so we are done with this quotient rule, as well as we are done with this product rule. Okay, I hope that this is pretty much clear to everyone. If you have any problem, any doubt, you can ask in our Discord server, or you can see the student manual if you don't know how to enroll in LMS. Just to update, let me write in enroll in LMS. So just enroll in LMS. Everything is free. Your TA support is free. Everything is free, so you can go there, enroll there, and I hope that you will take this opportunity to learn deep learning from scratch and learn as comprehensive as you can. Okay, so thanks for seeing this video. I'll be catching up your next video talking about the chain rule and implicit differentiation. Till then, bye bye, have a great day. Hey everyone, in this lecture we are going to talk about chain rule of differentiation. We'll try to know more about it, and it is very used in deep learning, or whether we learn backpropagation. We'll be using this rule, which is a chain rule, to take out the derivative when we backpropagate. Okay, so I ask you to pay a special attention at this rule. So basically, this rule tells, if you want to take the derivative
of a function, okay, so let's assume dy by dx, it's nothing but the derivative of inner function leaving the outside function and the derivative of the inside function. Okay, so derivative of the outside function leaving the inside function times the derivative of inside function. But it I know it does not make any sense to you. So let's talk about wait for a second, let me just delete it out. So let's take one example and then we'll formulate this definition. Then we'll formulate this definition of chain rule. So the example states, let's say you have y equals to 3x plus 1 to the power 7. Okay, so this is your function, which you want to take out the derivative. So you can actually use a power rule, and then you can use a lot of rules available, but it will be very hectic for you to do it. So we have a chain rule of differentiation which will help you to do this. So what is the derivative of this function? So dy by dx or dy by dx. So using the chain rule, what we do, first of all, let's use the power rule. Okay, so let's use the power rule to just make that 7 into the front of 7. So what we are doing is taking out the derivative of the outside of function. So the derivative of outside of a function. Okay, we are not touching inner one. This is our inner one. So we are taking out the derivative of the outer one. Okay, so outer one is some value, okay, 7. So what we will do, derivative of this will be, we bring 7 into the front of it, so whatever will be, and this will be 6, 7 minus 1 using the power rule. Okay, so leaving the inside function as it is, and then using the power rule, we have bring the 7 over here and subtract 1 from there, and this is the derivative of the outside function, derivative of outside function. Okay, derivative of outside function. Okay, and the outside function was we have some value and just to the power 7. Okay, that's the derivative. Now the times the derivative of inside function times the derivative of inside functions. So what is the derivative of over here, 3x? The derivative of 3x will be what? Will be 3 plus, we will use the sum rule, and derivative of constant is simply 0, so that will be 3. Okay, so the derivative will be 7 times 3, 21, 3x plus 1 to the power 6, and this is the derivative of your function, which is this 3x plus 1 to the power 7. Again, I'm recapitulating so that it could make more sense to you. Okay, let's take another example. Let's say you have g of x, which is nothing but let's say 2x plus maybe 4. Okay, and we are squaring this up. So now let's try to solve it. So first of all, what we will do, we'll take out the derivative of the outside of function. The derivative outside of function, which will be, we bring 2 in the front of it, 2, leave this as it is, subtract 1 from there, that will be 1, that's fair enough. Times, we have taken the derivative, now we'll times 2x plus 4, constant, this is a constant, so this is a 0, the derivative of this will be 0, and this will be 2. Okay, times 2, so it will be 4. 2x plus 4 is the derivative of this function g of x. Okay, so this is what the chain rule says. Now let's take another example so that it could make more and more sense to you. Otherwise it will be very hectic for you at least. So let me just remove it out. Let me take another example. So another example is, let's say you have f of x, okay, which is equals to sine 3, okay, 5x squared minus 4x. So what is the derivative of this function? So the derivative of this function we can write in this way. So the derivative of the function will be sine 5x squared minus 4x. So we can write in this way as well. Okay, so we can write in this way. Okay, because you all know that trigonometry is not just on this. So it will be 3 over here. Now we can go ahead and taking out the outer derivative. We can take out, we can go ahead and take out the outside of this function. So outside of the function will be, so outside of a function will be this will be 3. We bring 3 in the front of it. We bring 3 in the front of it. Sine f of x square minus 4x. The same inside we'll leave inside 1. Okay. Subtract 3 from 2 as a power rule states, times the derivative of inside of a function. Derivative of inside of a function. So the derivative of inside of a function sine 5x square minus 4x. Okay. Take out the derivative of inside of a function. Okay. So I hope that this is pretty much clear as of now. Now you can go ahead and take out the derivative of this inside of a function and you will be good to go. Okay. And you will be good to go. You just take out the derivative and this is your homework. You all know how to take out. So just try to take out and please give me in the comment box. Okay. Now another example, you can just take out the derivative as sine as cosine. You can actually use the product rule, which you all know. So go ahead and try it out. Coming to the next example is, let's say you have let me take another example. You have a k of x or g of x. Let's say you have a function g of x where you have a function sine x squared minus 3x. So what you will do first thing is take out the derivative of outside of a function. So the outside of function, so that is nothing but there is a sign of something. Okay, so when we take out the derivative outside of function, so what is the derivative of a sine? We have studied the cosine. Okay, and leaving the inside as it is, times the derivative of inside of a function. Okay, so the x square, the derivative of x square is 2x minus 3. Okay, so the derivative will be what? The derivative will be cosine of x squared minus 3x times 2x minus 3 is the derivative derivative of a function g of x. Okay, so I hope the chain rule is giving you some of the definition or some of the way to think about it, how this works. As you see, these are composite functions. Okay, so that's why this chain rule works. You can see online why this chain rule works, because it is important to know about that. Another example which I want to put in front of you is here. I want you to work in this example. You have h of x, which is equals to x squared plus 5x minus 6 to the power 9. So what do? You bring 9 into, so first of all you take out the derivative outer of a function, that will be 8 x squared plus 5x minus 6 to the power, this is 9, this is 8, okay. Now times the derivative of inside of a function. So the derivative of inside of a function with 2x plus 5, okay. So that is 2x and 5 and this constant is 0. Okay, so 9 x squared plus 5x minus 6 to the power 8 and 2x plus 5 is the derivative of h of x. Okay, so now I hope that is pretty much clear. So let's write the formal definition. Let's write the formal definition of chain rule. So let's say you have a function, if you have a function, okay, which is f g of x, which is just like a composite function, okay, and it is a composite function, then the derivative of y of a function will be first of all we take out the derivative outer side, okay, I'm denoting this is f prime, times the derivative of the inside of a function g prime x. Okay, so we are taking out the derivative of outside of a function, leaving the inside as it is, multiplied by the derivative of inside of a function. Okay, so over here this is a derivative of outside leaving the inside, and this is the derivative of inside of a function. Okay, inside of a function. So we can write down different notation. So let's write it out in different notation. So the different notation will be, let's say if y is equals to the f of u, okay, and u is equals to g of x. So basically it is just saying f of g of x. Okay, so u is equals to this. Now we can write that out into the other formal notation which we mostly see, which is nothing but just like, wait for a second, let me just drag it over here. The derivative of function this dy by dx will be dy by du. Okay, so first of all taking out the derivative of a function, okay, times du by dx. Okay, so first of all taking out the outsider, then taking out the insider. Okay, so this is what the formal definition states. So I hope that this is pretty much clear with a lot of examples which we did. Now coming to the chain rule can be used with different rules. Okay, chain rule with product rule, quotient rule. So that's why chain rule makes it easy for you to work on. So let's go ahead. Okay, let's go ahead and do one example, which is example 4x squared, okay, sine of x cubed. So in this example we'll make use of product rule and chain rule to take out the derivative. Take out the derivative. So just have to remind about the product rule. If you want to take out the derivative of the two functions which is being multiplied, this one and this one, okay, when two functions being multiplied, okay, so which is f of x times g of x, so that will be the derivative will be, first of all we leave the first function as it is times the derivative of the second function, which is g of x, plus the derivative of the first function, times the leaving the second function as it is. So this is the product rule which we have studied. Now coming to this, what if we let's frame this function as a f of x. Now we want to take out the derivative of it. So the derivative of it will be 5 prime x, which will be nothing but first of all by going we can have this as a first and we can have this as a second, so order does not matter. First of all, let's take out the derivative of the f of x. So let's assume that this is of g of x and this is your f of x. Okay, so let's take out the 4x squared. Okay, so the derivative 4x squared, okay, take out times leaving the other function as it is, okay, plus taking out the derivative, so multiplying f of x, first of all 4x squared times the derivative sine of x cubed, okay, derivative of the second function, okay, second function. Now let's take out the derivative. So after we take out the derivative, which will be nothing but 8x sine x cubed. So when we multiply, so that derivative will be 8x, and when we multiply with it, so 8x sine x cubed plus, now over here which we'll get as the derivative of sine of something is cosine of something. But before that, over here which you're seeing, there is some chance of chain rule. Which in this case which you're seeing, we'll use the chain rule in this case because we have outer function and we have an inner function, and we are a bit confused because we are not seeing any power rule. We can't do easily with the power rule on anything. Okay, so we'll leave 4x squared times what is the derivative outside of function? So we have a sine of something. So this is the outsider function. So what is the derivative of outside of function? Which will be cosine, leaving the inside function, times the derivative of inside function, the x cube is 3x. Okay, and using the chain rule, we got the derivative. Now we are good to go. Now the derivative which of this function 8x, let me just use a different color. So which will be 8x sine x cube, okay, plus 12x to the power 4 cosine of x. When you simplify it, you will be getting this x to the power 3. Okay, and this is your derivative of a function. So we use product rule, and then in one of the functions or one of the part, we use the chain rule to differentiate. Nice. So we are good to go with chain rule of differentiation, and I hope that you got to know about it much better, and I hope you will be remembering these stuffs. Now let's talk about logarithmic differentiation. The last thing which I want to talk about is logarithmic differentiation. Using logarithms, you will be easily able to take out the to differentiate. Okay, and these are used to quickly take out the derivatives. Okay, so the last thing which I talk about is logarithmic differentiation. Okay, so we want to take out the logarithmic differentiation. Now coming to this, you have a function f of x which will be equals to this is the question we have to take out. So x cube minus 5, 3x to the power 4 plus 10, 4x squared minus 1, 2x to the power 5 minus 5x squared minus 10. We want to take out the derivative of this function. And you may be thinking, here you, oh my god, what the hell this is? And you will be also in like, oh my god, how I'm going to approach this problem. So let me tell you, this is very easy problem, but we will use something called logarithms to solve this. So what we are going to do now is to take out the logarithm. We'll just take out the logarithm on both the side. Okay, so take out the logarithm of f of x equals to logarithm, just the same thing. Okay, so let me just snap it out. How I'm gonna to snap it out? No, wait. Let me just do it for me at least, so that I could not add to the current page over here. Okay, so you take out the logarithm. Of both the sides. So, oh my god, I think I have done wrong. Yeah. So now you take out the logarithm of both the side. Now coming to this. Now what do? You know the property of a logarithm. If you have a lot of fun in this, you know all the property of logarithm, which will be logarithm of x cube to the individual terms inside it, and to individual these things. Okay, so times logarithm 3x to the power 4 plus 10 times logarithm 4x squared minus 1 times logarithm 2x 5 minus 5x minus 10. Okay, now when we when you all know when we take out when we take out the derivative of a logarithm, and you all have studied, because I've already talked about this, it is nothing but when you take out it will be nothing but 1 by f of x times f prime x. Okay, so we can write it out, f prime x over f of x at this side, and in this side, what do? You simply 1 over x to the power 3 minus 5 times the derivative x to the x3 minus 5 derivative. So it will be nothing but 3x squared by x3 minus 5. x3 minus 5. Okay, now times, do the same thing with this, then we'll get 12x cube by 3x to the power 4 plus 10 times 8x, so it will be 8x by 4x squared minus 1. So you can recheck how we got it. It's simply 1 over 4x square minus 1 times 4x square minus 1 derivative. So that will be 8x and this is 0. So that is 8x by, so times the last one, which will be 10x to the power 4 minus 10x, and we can write it out below things, 2x to the power 5 minus 5 plus minus 10. Okay, so this is what you got when you take out the derivative of the natural logarithm. Okay, basically when you take out the derivative of a natural logarithm, you will do something like this. Okay, and it should be plus when you go ahead, when you take out the natural logarithm of this is a property, it will be becoming plus. Okay, it will be becoming plus. Now then you differentiate it and then you get it. Now at last, let me just go ahead, or let me just keep working on it. Now you will get f prime x, which is equals to the step number 4, which is equals to, what you will do, you will use something called as will simply multiply with the logarithm and the actual thing, this one, okay, and this one, whatever the differentiate we got it. Okay, so that will be nothing but, first of all, we write whatever we got after taking out the derivative of our logarithm, 6, this one, plus 12x cubed divided by 3x to the power 4 plus 10 plus 8x by 14x squared minus 1 plus 10x to the power 4 minus 10x divided by 2x to the power 5 minus 5x squared minus 10 times the quotient x to the power 3 minus 5, 3x to the power 4 plus 10, 4x squared minus 1, 2x to the power 5 minus fx squared minus 10. And this is your derivative of your large function which you saw over here. And you may think, hey, this is also a long process. I agree, this is a long process, but if you go and solve with other process, I assure you, you can use product rule to solve it, but it will be this is the very easy to solve this particular problem by logarithmic differentiation. So we talked about chain rule, and the most important thing was chain rule. If you haven't understood the logarithmic, you can safely ignore this. Okay, so I hope that you got the problem, and I'll be catching up in the next video with the introduction to integration, and then we'll start off with probability and statistics. Thanks for watching this video. I'll be catching up in the next video. Till then, bye-bye. Hey everyone, from this lecture we are going to start off with deep learning. We'll start off our journey with actual deep learning, which you all are waiting from a lots of time. And I just want to make a disclaimer is I assume you that you have already covered the previous videos and some videos of probability which is not yet uploaded, which will be uploaded in coming days. But I assure that whatever the videos is uploaded like mathematical prerequisite, please be sure that you complete those lectures first. You can watch that in 2x lectures, because all the things which you'll study, it will heavily depend on the previous one. Okay, so please make sure that you have a better understanding of mathematical intuitions, which I already taught. If you faced any problem, just join our Discord server. Maybe we can get on a live with some TAs. You can just discuss that and make your doubt clear. And you can simply ask at our Discord server, which will be in the description box. The link will be in the description box. Okay, so what is deep learning? So we'll try to answer in this lecture. So first of all, I'll try to answer what is machine learning. machine learning is an artificial intelligence domain where we extract patterns from the data and analyze the data and make intelligent predictions on the new data according to the pattern which we has already learned or our machine has already learned. Okay, so we have a function f that takes some input values and that map that input values to an output variable y. Okay, so I'm talking about in the context of supervised learning. So basically you have a function f that takes the input value x and that maps the input value to y. So you want to construct a function. So you learn a function f that extract patterns from the data, or learn from the data and analyze the data and make intelligent predictions. So we can give x to this input value, it will give us y variable. For getting the desired y variable, we do need a very good function which actually does that specific job. So exactly what machine learning tries to do is to make a function f that maps the input value x to the output value y. If you haven't already familiar with machine learning, I'll ask you to take an introduction video or introductory course of machine learning. Maybe you can go to ML01 or you can go to some other machine learning course, but I highly suggest ML01 is the best course for you to consider at this point. Cool. So you got to know about the definition, but there are different machine learning algorithms. So you may ask that how we are going to extract patterns from the data and how we analyze the data. So that is the first question which may come in your mind: how we extract the patterns from the data and how we make intelligent predictions, or how do we analyze the data. Okay, so for making intelligent predictions, first of all you need to extract patterns from the data. So how are you gonna to extract patterns from the data, which we'll see in a review of machine learning in the course. But there are different set of algorithms which will help you to extract patterns from the data or analyze the data. Some of the examples are logistic regression, we have linear regression, and I'm preparing, I think, 4 to 5 hours of lecture on linear regression. Is the mainly video title as multivariate analysis. You can go on New Era YouTube channel to, maybe it will be uploaded till the end. So maybe you can just go there, you will be seeing a title multivariate and regression analysis. I have taught linear regression in great detail there. Cool. So back to our topic. So there are different set of algorithms which will help you to extract patterns from the data. Say for example, logistic regression, and logistic regression is a classification algorithm we can use for classification tasks, and linear regression is a regression algorithm which will help you to perform regression tasks. And many people just think about linear regression is very simple algorithm. It does not perform well, but just go in statistics term and then you will see the power of linear regression. Mainly people forget to use linear regression in a right way. So you can watch the multivariate regression analysis which will be uploaded soon. So Naive-Bayes, which is another yet powerful classification learning algorithm which can be used to predict whether an email is a spam or ham. So using Naive-Bayes, you can construct a function f that takes an email and classify that as a spam or non-spam, and let's denote spam with 0 and let's denote non-spam with 1. Okay, so you have to learn a function f that takes the input value x and that maps either 0 and 1, or in other words we can say y be the member of 0 and 1. Okay, so there is Naive-Bayes. Cool. So the performance of these simple algorithms heavily depends on the representation of the data which you have. Okay, you should have a good data for your machine learning algorithm to perform well. If you have a bad data, your machine learning algorithm will not perform well. But this extract or this paragraph is taken from a book written by Deep Learning by Ian Goodfellow. I only know the one author name, and others are, I think, I don't know exact name, but Joshua Bengio. So you can just go there and see the book by Ian Goodfellow. So this is an extract from that book, and what is it indicates? The performance of these simple algorithms depends heavily on the representation of the data which you have. The representation of the data which you have or which you're given. Say for an example, you're using linear regression to predict the house prices. Okay, so basically what exactly is trying to tell, you're using linear regression to predict the house of the prices. So on time of prediction, say so you train an algorithm which takes size as an input, okay, and number of fans of a house, and then using these two features it predicts your y variable. Okay, so this is how you train a function f that takes size and number of fans and then give you the price of the house. So basically it is saying that you are using linear regression to predict the house prices. So now you trained it using these two features. Now when the time of prediction came, user have to provide only size and the number of fans. Okay, so let's take a bedroom rather than fans, so number of bedrooms to make predictions. Okay, but when you give number of fans and then ask your model to predict the price, your model will not be able to predict. Do you know the reason why? It's very simple. Because you have trained your model on the size based on two features and the number of bedrooms, and then you getting price. What if you give only the fans? You'll be not able to predict it, isn't it? So that's the major problem of representation, that these performance of these machine learning algorithms depends heavily on the representation of the data which you have given. And these are features. So size is also a feature, number of fans is also a feature, number of bedrooms is also a feature. So I hope that this is clear. We'll come to that. We are coming to definition of machine learning. Sorry, deep learning. Cool. So the problem of feature representation. So as I've taken one example to start with the problem of feature representation or feature learning. So we'll talk about that. AI tasks can be solved if we have right set of features and make a mapping from feature to desired output. So all the AI tasks which is available today. Okay. So say for an example that you wanted to predict the price of the house. Okay, you want to predict the price of the house. You want to predict the price of the house. So for predicting this, you should have the right set of features for this to get to particular answer. So you want to learn a function f, okay, that correctly maps from some feature x1, x2 all the way down to the xn. Given these n features, it predicts your y variable. And these n features should be right set of features. If you have bad set of features, where our AI model will not able to perform very well. Okay, so we do want the right set of features so that we can train our model on these right set of features and then get the desired output. One of the example which I want to represent to the real world example. Say for example that you are learning some science concept where you have feature of the particular thing. So say for an example, I'll take a simple example so that it will be very easy. Let's take example in real world concept, car. Okay, so a car, and what are the features of it? What are the features of it? So the features of it can be, it should have four wheels. It should be not too much big. We have steering. We have seat belts. So these are some of the features we use to identify cars. Okay, and they come in different color. So there are a set of features. We need a right set of features to understand that is a car. And how do we learn it? Say for an example that these seats and then four wheels, steering, these are the right set of features that we use to identify whether that's a car or not.
Okay, so that's how a baby learns. It identifies some set of features. Okay, my father is telling that okay, it is the steering. So based on that, I will identify, okay, that's a car, because I've identified some of the features of that. Because I've identified some of the features of that, one of the main thing which I want to highlight is identifying the brand of a car. Okay, brand of a car, identifying the brand of car. That's a very that I face in real world. Is for every car we have identified feature. Okay, say when I see a car, I'll take a look at a logo of that in front of the car. So in front of that there is a logo, and if it is logo in something like this, then it's Audi. Okay, then it's Audi car. Because of this logo, I'm able to identify what's because of this feature, mainly the logo. Because of this feature, I'm able to identify, okay, that's Audi car. So this is the right or unique set of feature that this car have. So for example, so when you can train your model, okay, so you need right set of features. Okay, so your model is able to identify that. I hope that this gives you pretty much lot of sense to you at least. Okay, say for example, you want to detect the cat in an image, so you want to build a model that given an image I, that will detect whether that is a cat or non-cat. Okay, so a cat can have different set of features, so you can hand design right set of features by yourself. Like you can just the values are in pixel format, okay, the picture. So you can take only the pixel which are of ears. You can take only the pixel which are of ears, so you can design the right set of features like ears, nose, and which are very time consuming task, because you need to be very good at the background of that domain, or you should have a good domain background for identifying the right set of features. Because in this example it's very easy, cat in image. But what if in real world you don't have a problem like this? You do have a problem like this, but like wave detection, like in weather, you should have a great background inside that. So you should design right set of features, and that will be very time consuming task. And getting the right set of features for your model is very challenging in today's era for many tasks around us. Okay, say for example, like wave detection or whatever, where we don't know what are the right set of features. We think okay, every feature is the right set of feature, but getting the right set of features in today's era for many tasks is also very challenging. Okay, using machine learning, what we are able to do, we are hand designing the right set of features. So we get an input, and then we hand design right set of features. So this is a car, so we taken out the pixel of maybe wheels for that image, and then we taken out right set of features like wheels, steering, logo. Okay, so there are some set of features we hand designed by ourselves by programming and whatever, and then we train a machine learning algorithm on these pixels or whatever, on this whatever are features which we have extracted, let's say x1, x2, all the way down to the xn. Okay, we train a model f, let's put in a giant X. Okay, and then we give this set x, and then we train our f. Maybe it can be classification algorithms like logistic regression. It takes the value of x and then classify that either a car or a not car. Okay, so in machine learning what you're doing is you're hand designing the right set of features by yourself. Because when you see your machine learning data which you have, you're given several input values, 1, 2, 3, 4, 5. Okay, and you're given the target label, and these features are hand designed. Okay, so this is how this is what today's machine learning is able to do. Is it also require feature extraction? It also require to extract features from the data by human will do it. Human will design right set of features. So this is what the problem which we have is hand designing the right sort of features, which are very challenging and is very time consuming task for designing the right set of features. So what is the solution to the problem? The one solution to this problem is making machine learning not only learn the mapping from features to target labels, also learn the representation to Y. Okay, so basically we are asking our computers to not only learn this classification stuff, not only make a model given the set of features, also learn features by itself. Okay, so given a car, learn feature, extract feature automatically and make a model on the feature which you extracted. Okay, so say for example, in machine learning you are hand designing set of features and then you're giving to the model whoever the right set of features is. But in deep learning, what exactly you are doing is given a car, an image to your system. What it does, first of all, it extract features. That's called feature extraction or feature learning or representation learning. It extract right set of features. Let's say wheels, let's say anything, okay? And based on extracted features, it builds a classification model or whatever learning algorithm, and then is able to classify. So there's a huge amount of time which is preserved, and this actually perform very well in today's era with state-of-the-art models, which are doing very perfectly. So again, I'm going to repeat that one solution is to not only learn mapping from X to Y, but also learn X's as well. Also learn the features of it as well. Okay. Of course, you're going to give the input, which is the car. But if we have to identify that problem that can be solved using deep learning, or that problem that can be solved using machine learning, you have to identify that. Okay. The model takes the raw data as an input, which is the image, and perform feature extraction by learning the feature representation. So it automatically extract the features and learn the parameters to perform the necessary task, or to build a model F that maps from features, the learned features, to output. But one thing which you will ask question, that how do we go on performing feature extraction? So how it performs and what these three things means. Don't worry about it. Just I will briefly talk about it in this future detail. Don't worry about anything. Just understand what exactly deep learning trying to solve. Okay. So I think it's very much clear. I just want to move forward. Cool. So what is the definition of machine learning? So this is a definition by the book. Again, I'm saying this is by Ian Goodfellow, Yoshua Bengio book. And deep learning methods aim at learning feature hierarchies, with features from higher level of features formed by composition of lower level features, and automatically learning features at multiple levels of abstraction, allowing a system to learn complex function mappings from the input to the output directly from the data without depending completely on human crafted features, and learning deep architectures for AI. And I personally know that you are very confused with this statement. So let's get ahead and make you understand that what exactly the definition trying to tell. Maybe you know about hierarchies. Okay, the hierarchy means like we have this hierarchy of a feature. So you have different features, different levels. So basically, this is in this level you are extracting some level of features. Some level of features you are extracting. So that is visible layer, that is the input pixel. So you give this pixel, this pixel, this pixel, this pixel, this pixel. So these are input level pixels which is given to your model, which is the raw input, and then it is passed. Don't worry about what is this arrow. Just assume just only understand what exactly I'm telling. First, the input which we give to our model,
or whatever algorithm is the pixel value, is the pixel value, okay? Is the pixel value which we given in, which is visible to us. Now we give to the second level, we give to the second layer, which you usually call as a hidden layer, but don't worry about it. Just don't worry about it. Then we give the next level, which extract some patterns, some feature like this, okay? Then we go, then we give to the next feature whatever the information contained, whatever the information is given to the next feature, and then we learn some set of features again. Then we extract from this image some set of features. Then again next level, we extract some set of features, and then based on these learned features, you're getting whether that person is a car, whether person or animal. Okay, so basically what exactly you are doing is extracting features till this level. You're extracting features, and at last you're making a model here and then making prediction whether that is a car, person or animal. Don't worry about it, what exactly what exactly is trying to, what exactly this arrow represent, and how are we making classification model. Just don't worry about that. The only thing to worry about that you are understanding the right thing here. The right thing is that you are learning features at different levels, and you are learning feature hierarchies with features from higher levels of the hierarchy. So here you have some set of features learned, and then the second and the third. So you have multiple levels where you are learning different features, and because of this you are able to make complex functions. We'll talk complex mapping from the pixels to the car, person or animal. Okay, you're here, no human loop is needed. It is automatically creating, it is automatically extracting his her glasses or whatever. It is automatically, no involvement, no human crafted features. At level 1 it extracted some set of features, at level 2 extracted some set of features, at level 1 it extract edges, okay, mainly this edges. Level 2 extracted corners, mainly this one, and contours. Level 3 it extracted object parts like this, okay, level 3. So it is learning complex features. Now your model is able to make complex function f that takes the input image and then powerfully making a very good prediction comparable to human score or accuracy. So I hope that this is very clear on the definition of deep learning, and general idea what exactly deep learning trying to solve is learning feature hierarchies. Okay, with feature hierarchy from higher levels of the hierarchy formed by the composition of lower level of features. So you're not involving any human loop, just you're learning exactly what the deep learning is trying to solve. Cool. So we'll again precisely define. You will learn when you will learn neural networks, then you will understand what exactly deep learning is. But I hope so that give you a better sense over here. Coming to the different applications, there are thousands of applications which can be solved, which are in production today, which are using deep learning to solve the real world problem. The first one is classification problem. Given an image, classify that whether that image is a cat or a non-cat. So how does it helpful? And maybe when you go to the company, you just show your face and that allows gate opens, and then you go inside. That's face recognition, where it identifies whether you are that person or not. Okay, classification plus localization to localize that where that object is. For example, it can be used in self-driving car, which you're seeing in front of you. It is able to localize the stuff so that it would make their own decision to where to go further. And then we have art generation using from text. So given a beautiful woman, it will generate the image of beautiful woman. It can be possible. I'll show you one demo today. And then we have chatbots. Chatbots like AI coder, AI Q&A system using GPT-3, and then lots of things. Search recommendation system like Google is using, San Francisco, whatever is there. So I think these are some of the examples. Another examples are speech recognition task. You can just make use of Alexa, how are you? And then it will give you the answer. music generation using deep learning. You can actually generate the music using deep learning. And then brain tumor detection, it is used also used in medical industry. So these are some sort of applications which I highlighted for you at least to get to know much in much more detail. So I hope that this is very clear now. And now what I'm going to do now is to show you some of the cool application which I built as a project by myself. So I hope that that will give you more sense to you. So I'm just going to show it to you. The first one which I want to show it to you is the chatbot which we had developed at Anton. So let me just let me just make it a little bit wait for a second. I'll just make it 1080p so that it will be more precise for you to at least see that. So you can see over here AntChat, which is able a Discord chatbot which is able to chat with me which you can see. No problem, let's talk about something else. And then I seriously haven't heard about this song, we did it, and this is AntChat, which you can of course opt for it. You can just make that in your own Discord server. If you have, just email us. My company has launched this product which is AntChat, which uses GPT-3. So this is one of the example of deep learning. The another example is, I want to show you another example. We have Encoder, which actually given program for taking the factorial, it gives a Python program for that, which you're seeing in front of you, that it is able to solve any kind of programming question which you are presenting in front of your screen. And I hope this is Encoder, which is again, you can email us to get the access of it. Now coming to the next part is Q&A. Q&A system, which you can see over here that we have Q&A. You can just ask what is a circle and whatever, it is able to answer your question, and that is even answering in machine learning tasks. And I hope that this is what the Q&A system we have developed, and it is available for which you can email at Anton. Will be happily giving you in your own Discord server to make your server productive. Coming to the next project is art generation using deep learning, which is generative adversarial networks, which we will do in this course using GANs, and which you can see that how this is generating the image, and this is its image which is generated by, and this is on my own YouTube channel. This is image which is generated by peoples. Okay. Coming to this, we have another art which is generated, which you can see over here, using text to image. And I really hope that it made a lot of sense to you. You can just go at my YouTube channel and just subscribe this YouTube channel if you want, and then go to playlist, go to MLO2, and also what I want to highlight is you can just enroll in LMS. You can just go there and enroll in LMS by going to this doc and then going to reading all the course and then assignments and lots of stuff. You can go there and enroll in your LMS, which I've written over there. You can enroll in your Neo LMS. Okay, so I hope that this is pretty much clear, and I also hope that you have enjoyed this video. If you haven't, please leave a comment that how I can improve these lectures. Otherwise, I hope that this video given a lot of intuition behind deep learning. I'll be catching up in the next video. Till then, bye bye. Have a great day. Hey everyone, welcome to this lecture. We'll be finally starting off with Introduction to Neural Networks. So let's get started with this lecture. First of all, we'll talk about biological neural network, as it is very important that how our neurons in our brain work. So I'll try to relate the biological neural network with our neural networks. Specifically, we'll talk about perceptron. So in this particular lecture, here's the outline of this lecture. We'll start off with the biological neural network. We'll get into that how we can relate this to something called as perceptron, and then we'll go ahead talk about different things activation functions, and whole outline can be found on a course website, as we had detailed sections and subsections provided there. Cool. So let's start with biological neural network. So here in front of you are seeing is a neuron in a human brain. So basically human nervous system contains, which is something called as cells, and you know cells are the basic unit of a life. You have already studied in class 9. So human nervous system contains cells called neurons, and the neurons are connected to one another with the use of axons and the dendrites, and the connecting regions between axons and dendrites are referred as synapses. So what exactly it is telling, that you have several neurons. Let's assume this as a specific neuron. So you have a neuron, and this is connected with another neuron, okay, with the help of axon and dendrites, and these are the regions which connects the axons and the dendrites are called synapses. But you may be thinking, hey, you are not in biology class, then why you all are teaching this? So I'll try to relate this with the particular stuff like this, the keywords. The dendrites are the input terminal which takes some input from other neurons. Say for an example, you have a neuron over here. So this is your particular neuron, and this gives some input to the another neuron. So they are connected to each other. So this is a neuron which gives an output which is connected to another neuron, and the output is taken, the output of another neuron. For this particular neuron, it acts as a input terminal where it takes the output of the previous neuron. Okay, and so that's why we have a dendrite, which is nothing called the input terminal. Okay, the next thing is the axon, which is the output wire. So axon terminal is an output wire. So whatever it outputs, the neurons, whatever it outputs, so what a dendrite receives from the dendrites is called the input terminal, and whatever it is outputted is from the axon terminal, because it's the axon which is the output wire and which outputs something, and axon terminal are the output terminals which output something. Let's say output something, let's say this, and this is again transferred and taken input from using the dendrite. So again, I'll recapitulate this stuff, as dendrites are the input terminals, the axon is the output wire, and the axon terminals are the output terminals. And this is a particular structure of a neuron. So I hope that this gives you a better sense of movement. Cool. So we'll not only talk about this biological neuron. We'll go ahead and talk about, we'll try to relate this with artificial neural networks. Okay, so let's take an example. You have a neuron which gets an input. Say for example, you're getting x1, you're getting x2, x3, x4, which is an input received in dendrites. So you have a dendrite, which is a dendrite terminal, which is the input terminal. So let's say you get 4 inputs. Don't see this diagram as of now, just only see this diagram and listen to what I'm saying. So the information which dendrite receives is called x1, x2, x3, x4. Okay, so for this example, you have x1, x2, x3, x4, which are the input which is received in dendrites, and the information x1, x2, x3 and x4 are weighted by some weights, and W1, W2, W3 and W4, and it determines the effect of your input. So say for example x1, how much this effect of an input in this neuron. Okay, so we'll take a specific example. Say for an example, you saw something. Okay, so you have a human eye, and you saw something like a dog. Okay, so you saw different thing, like its eyes. Let's assume this eyes is x1, its ears x2, its tail x3, and its legs x4. So all these in your mind, all these contain some weights. Let's say example that you saw that you are quite familiar with the mouth or the eyes of the dog to be similar. So let's take a W1 X1. Okay, so this input, how much weight it contains, how much effect to because you want to identify that dog, so that's why you want to identify how your maybe mind knows how much effect your eyes there. Okay, so eyes of a dog, how much effect does that ear of a dog affects on for you, so that you are successfully able to classify that as a dog. Okay, so most important thing, say for example, its tail may be having the biggest weight, because by seeing the tail you're able to identify whether it is a Doberman or anything. So tail would be the containing the highest weight. So the whole thing of weight is that the W1, W2, W3, it contains the information is weighted. We give some weights to every information whatever we get in the dendrite, so that we'll be able to identify the effect of each input in your dendrite. Okay, so basically in an overview, it determines the effects of the input. So W1 X1, so what we do, we simply multiply with the input. So all x1 has its respective weight. Say for example X1, X2 and X4. So we have four features. And let's say that X1 is more important in doing that task. So X1 is weighted more, W1, W3, W4 and W5. Let's say X1 is important, so its weight will be high because it is weighted, and this X1 has the most important effect of the input. Okay, so we'll come to that weight a ton of time. The whole deep learning is based on that, getting good weight. So we'll talk about that. Okay, just assume that you have any weights. We still don't know how do we get the actual weights. We still don't know about the formal definition. I'm just defining it informally. So the weighted information, now what do? You multiply the weights with the inputs, so you can determine the effect of the input using that weights. Okay, so the weighted information are aggregated in the nucleus. So basically this is a nucleus, which is nothing but the powerhouse. Okay, so it's aggregated in the nucleus as a weighted sum, as a weighted sum. So what you specifically do, you simply multiply the weights with the respective inputs and add it up. Okay, so W1 X1 plus W2 X2 plus W3 X3 plus W3 times X3 plus W4 X4. Okay, simply add it. That's it. That's what you do. You simply aggregate it in a sum variable or a nucleus. Let's call it as a Z. Okay, that's a nucleus. That's a nucleus where you aggregate all the information at one point. Plus you add some bias term. Okay, let's add some bias term. And that is a bias term which we will have a detailed talk in this section. Please don't worry about that. We'll have a detailed talk on that. Just you can ignore this or assume some constant like 0.1. Okay, don't worry about that. What W1, how we'll choose W1, we'll see in the whole section. Then what we do? So here we came to a nucleus, and nucleus perform one action to it. So this nucleus, now this is done. Here you apply the non-linear function. The non-linear function. So on Z, on Z you applied some kind of function. Don't worry what that function do. Okay, just assume that we apply some kind of function. Maybe you have already seen something called as sigmoid function. I'm just taking an example of a sigmoid function. There is a lot of functions which we apply, which we will formally define in this section. Don't worry about that. The only thing which you need to worry is to understand the whole process of neural networks. And I'm just trying to informally define the neural networks with the help of your neuron. So where we are, we have set of inputs which we got from a dendrite. then carrying these input carries the weights, or the information is carried by the weight, okay, weighted by the weights, which is W1 all the way around to W4. Why all the way to W4? Because we have 4 inputs which we got. Okay, it determines the effect of each input by taking or the product between their respective inputs, and then what we do, and then we reach to the nucleus where all the information is aggregated by taking a sum, where we add one bias term. We'll talk about it later on, what exactly that bias term do. Okay, and then after aggregation, now some processing applies, like non-linear function, which is a sigmoid function in this case. Maybe if you know about it, if you know about logistic regression, then you might be knowing that. And then it is further sent, and then it is further sent for further processing to axon y. Okay, so it is further sent to another. Now we got our output, which is some some function on z, and then we get our output y. Okay, and then it is sent to as an input to another neuron, or we get a final output, or we reach to the destination what we wanted to reach. So what does it mean it reaches to destination? So let's take an example. You saw something, you saw a dog. Okay, you saw a dog, and here the information, let's say you want to identify whether that dog is a German Shepherd or a Doberman. Okay, Doberman Pinscher. So specifically what you will do, you all know that a German Shepherd has a long hair and kind of a wolfy nature kind of stuff, and Doberman is very thin and don't have a long tail, as well as they are very strength and kind of stuff. You have a specific mind in your specific picture in your mind. So when you see Doberman, or when you see a dog, you need to, and that dog is either German Shepherd or Doberman Pinscher. Okay, so here is a dog, that dog is either German Shepherd. So how your mind will work, and I'm just taking an example of it. So what happens is, you see his hair, you see his tail, so all the information get into your eyes, and through eyes you get into your mind. Through eyes it gets into your mind, and all the things like hair, Doberman, so these are your input. Hair, tail, ear, eyes, these are your input. And over here, let's say hair is carried by some weights, all the weights, so that we can understand the effect of our inputs. So say for example that your hair has the weight of a hair, because in your mind, in at least in my mind, I'll be having more influence of hairs, so W1 here will be very large. Okay, so I'll be able to identify that. And then what happens after we aggregate the information? We simply aggregate this information in a nucleus. So every feature is very important. So you aggregate the information as a nucleus, and then you apply a non-linearity or some kind of function. Don't worry about what is non-linear, etc. What this function does. Just simply we apply some kind of function or some kind of processing, and then we reach to the destination, whether that dog is a Doberman Pinscher or German Shepherd. Okay, so or maybe that output, whatever output we get after applying that function, it will be sent to another neuron, so that will be so maybe if required. I don't know about much more about brain. Cool, but is this exactly happens in our maybe a specific neuron? It's kind of a no, absolutely no. It's just an inspiration from a neuron. It's not like that how these kind of exact maths is being calculated. It's not that. It's just an inspiration, so that like his scientists previously just taken inspiration of it and made a mathematical model out of it. Okay, so do not relate it to exactly how neuron works. You can see other videos on how neuron and how brain works, but specifically this is taken for inspiration for this kind of statements that I've described up. Okay, cool. So I hope that this gives you a better sense about how everything works. Let's go ahead. Over here, the pictorial representation of a workflow. So exactly this is the artificial neural networks. So this is a mathematical model. This is whatever you're seeing is not a real neural network or a brain. It's just an artificial neural networks where we'll talk about what is neural, what is networks later on. But this is a pictorial representation of what our workflow states. So just recapitulate you. You have a set of inputs. You have a set of inputs x1, x2, x3 all the way down to the x4. Okay, and all these inputs are carried by all the information is carried by the weights, which we denote with w1, w2, w3, w4 and a bias term. Okay, and these weights determine the effect of your input, and this is a nucleus. This is a nucleus where all the information is aggregated by taking out the sum of, and this is the summation notation, w1 x1 plus w2 x2 plus w3 x3 plus w4 x4, and then we add the bias term, and then in that, and then let's assume that this is the nucleus, and then we apply, and in nucleus we apply some kind of a function on it. So let's say sigma on z. Okay, and then we get some output y, and then it is either your destination, which you want to achieve, or it is sent to another neuron, the same neuron like this, where it again multiply with output, which we'll see later on. Okay, cool. So I hope that this gives you a very specific sense about artificial neural networks, and I hope that you are able to understand how exactly it is working. So now what I will do, I'll just make a remark that neural networks, whatever artificial neural network which you see is called exactly, this is what artificial neural network is. Okay, so neural network basic units is inspired from machine learning, and machine learning is obviously inspired from our brain and stuff. So here, which you're seeing, if I know the course prerequisite is machine learning fundamentals, I either recommend in my MLO1 course or anything, but you're exactly seeing that this logistic regression or whatever we have studied, it's exactly logistic regression if you see. Okay, so basically this is the one unit. So this is what you are seeing. This is a logistic regression. What do? You simply multiply with the given weights and the inputs, and then we aggregate it, and then we apply a nonlinearity or the sigmoid function, which you usually know 1 over 1 plus e to the power minus z, and then you will get some output, let's say a, and then if a is greater than 0.5, you identify okay that value let's 1, or if it is, or else if it is smaller than or equals to 0.5, then 0. Okay, then 0. So this is usually used for classification problems. And why do we apply this sigmoid function? We'll talk about in detail in this deep learning. We'll talk about this sigmoid function in very detail. But what this sigmoid function tells you, so what it does, you get your output in a range, in a continuous manner. Okay, so it simply squeezes that output into between 0 to 1. Now this was your basic unit, which you already seen in machine learning. What do? You take that basic points and you put several units and stack them up. Okay, and take that stacked layer and make several layers. Okay, so this is a particular unit, which is exactly what computation is doing. Is simply multiplying with different weights and then applying processing, etc., and putting up different basic units, and then at last with that kind of stacked or basic units, you're able to generate predictions. So this is the deep neural. So we'll talk about that later on, but the basic idea that this slides want to give you that neural networks are inspired from basic units of machine learning, or puts up lots of basic unit together and then get your output. But don't worry what this exactly diagram states. Forget about it if you don't understand. Okay, please rewatch the video if you don't understand. Otherwise, you can simply ignore what exactly each neuron is doing. We'll cover that in detail in a multi-neural network or perceptron section. Cool. So the perceptron, now what we will do is formally define a perceptron so that it is very helpful for you at least. So let's take an example. So now we will formally define the perceptron. So here you can see the simplest neural network is referred as the perceptron. Where we have the basic, which is the simplest neural network, which we refer as a perceptron. So what we are given? We are given the information from x1 to x dimensional. Okay, so I'll take an example. I'll take a simple example because I just want to have a conversation with you so that at least you can understand everything. And please make sure that you watch in kind of a 2x manner. It's okay for you. I don't care about that. So let's take an example of a diabetes, or maybe so diabetes prediction system. Diabetes prediction. So I'll just take a different pen so that at least it gives me good feeling. So what's your favorite color? I don't know. It's blue. So diabetes prediction system. So in machine learning, you're given set of features and you're told to take that set of features and map to, or make a function f that takes a particular set of features and maps to an output variable y. That's it. That's exactly what in machine learning you're trying to do. So let's say your x1 denote maybe some kind of let's say the BP, okay, and x2 denotes BMI, okay, x3 denotes your age, x4 denotes your maybe symptoms which have a certain symptom, or the height. Okay, x4 denotes your heights. So these are your information. Okay, and these information are carried by the weights. These information are weighted by weights, that how much this have effect, or how much our input affects. Okay, so how much our information carries information. Okay, W3 and W4. So W1, W3, W4. Okay, so you have a respective weights which tells you how much it affects. Okay, how much your information have weights, or how much weightage, or how much information it has. Okay, cool. So what I will do, I'll just have my x, and this is x1, x2, all the way down to the xd. Okay, and that is transpose, so that it's a column vector. I think, yeah, it's a column vector. It should, when you do the transpose, it becomes the row vector. That is a x, which is the input value, and output value y is either 0 or 1. I'm taking an example of a classification case. So your output is either 0 or 1. Cool. So specifically over here, you have a weights, which is carried by the weights, your information, where what is learning? So where learning occurs, how you learn the particular system, how you make a diabetes prediction system. So how you learn it? So learning occurs by changing the weights, and the goal of changing the weights is to modify the computer function to make the predictions more correct in future iterations. So what is the learning tells you? How do we learn it? Okay, so the whole learning stuff is getting the right set of weights, or identifying how much x1 contains, or identifying the right set of weights, so that we'll be able to identify which input have more effect. Okay, which input have the more effect. If you don't understand from this point that how learning occurs, Don't worry about it. We'll talk about in detail what exactly we call as the learning problem. Okay, sure. So what is learning? And in high level overview, what we do, the learning occurs by changing the weights W1, W2, W3 and W4. So we change the weights until and unless our prediction be more correct in our future iterations. Okay, and then you strive to find the best weights by choosing algorithm like gradient descent algorithm or stochastic gradient descent, and there are lots of optimization algorithms which are out there. Cool. So now what you do, you simply multiply or take out the product of the inputs and the weights, and then you aggregate the weighted information. Okay, whatever the information which you contain, you simply multiply with the inputs. I just not written xi. So simply aggregate the information xi and wi. So w1 x1. So we identify. So we are able to say, okay, in a nucleus you will be having the weighted information or the aggregated information, so that we are just adding it up, and then we are adding the bias term, and then we apply some kind of activation function, which is some non-linearity. Okay, which is some kind of function. Here it is a sigmoid function before sending it to the destination y. Okay, so now we are ignoring too much about bias term. We are ignoring bias term, and then we are ignoring non-linearity or activation function. Okay, let's talk about that, and then we'll end this video. Cool. So over here, the perceptron with the bias term. So what exactly bias term help you to do? Say for example, take a simple example. Y equals to mx plus b. Y equals to mx plus b. So you all know about it very carefully. So you all know about this specific term called y equals to mx plus b, where you have this. Where let me just erase it out so that it would be much better, because I don't know why I'm not able to draw very good kind of stuff. Oh my god, no problem. So you have this, and then you have this. Okay, cool. So this is the equation for this straight line, y equals to mx plus b. Okay, and m here is the coefficient, or coefficient of x, and b here is your y-intercept. B here is y-intercept, or we can say m is slope of this particular line. Okay, so what if just I'll not go into y equals to mx plus b, because you already know, because its course expects you to go good at algebra 1 and algebra 2. So what this b tells you, if we make that b to be equals to 0, what will happen? If we make that b equals to 0, what will happen? So over here your y will be 0. Okay, your y will be 0 and always pass through the origin, which is 0 and 0, where x is 0 and y is 0, and depends, and your straight line or your line will depend only on one parameter. So y equals to mx, where if you have b equals to 0, then we don't need to write it. So over here it only depends your slope. Okay, it only depends. You can either make this way or either make this way, but the only parameter which it will depend is m. Okay, is m. Now over here you're only able to make a function. You're only able to make a function which just maps, which is non-complex function, which passes only through origin and just only depends on one parameter. But when we add b there, y equals to mx plus, let's say 2. So over here let's assume 2. So you are able to make more complex. You're able to make more complex function and shift the graph. Okay, say for example, it's if we add b, if we have 0, then it does not shift the graph. When we add the bias term, it shifts from here to here. So what it does, it shifts the graph, and hence it is able to represent more complex situations which it was not able to make it before. So from this y equals to mx plus c example, it is simply saying it is able to represent the more complex example or shift the graph a little bit up. The same way it will work in your neural network. Bias allows you to shift the activation function by adding a constant to it, that is the given bias to the input. You can think of it as a linear constant, which we learn as a weight, okay, which we need to find a good bias, okay. We of course we don't we do not only need to simply add a bias, we do need to find a very good bias, which we'll talk about later on, that how do we get W1, W2, or how do we get B1 and etc. So, and make sure that W1, W2, W3, W1, W2, these are the weights, or we sometimes call them parameters. And I have already discussed these weights are the weights for your inputs, or every input has its certain weights. Okay, so specifically in this case, your bias term help you to shift the graph of your activation function. So if you have seen your logistic regression, the graph of logistic regression is S-shaped, okay, S-shaped like this. So when bias is 0, the origin is over here, and bias is 0. Now when we say bias 1, then it is able to shift the graph, and hence it is able to represent more complex situation. And when we do +1, then it is able to represent much more complex situation. So basically, bias term shifts the graph a little bit, or linearly, and then it is able to represent more complex situation. So that's why bias term is absolutely necessary in neural networks. It's not kind of it will not work without bias term, but it's very necessary part of neural networks. Cool. So over here, which you're seeing is neural network, which is, let's say you want to build a house price predictor, because we are only seeing out the examples of maybe kind of stuff like we are only seeing examples of maybe kind of a classification problem. But what if we get a regression problem where we want to predict the house prices? So let's say you are given the information x1, x2. So these information is carried by the W1, W2, W3, and for the bias term. And okay, so then we apply a linear activation function. We don't apply any kind of non-linearity. We don't apply that. We simply apply the linear activation function, which is just the identity function. Okay, it's a function when you give your z, which z is aggregated information in nucleus, which just gives z the input. Okay, which is a linear activation function. Okay, and then you reach to your output, and then we have your familiar MSE, mean square error. Okay, and then you take the partial derivative of it, but don't worry about it. We'll talk about gradient descent in greater detail. Okay, don't worry, ignore it. Just I have just written it out so that how training occurs you'll get to know, but just ignore this. Cool. So the last thing which I'll discuss in this video is intuition behind activation function. Why do we need this non-linearity which you're seeing? That why do we need this sigmoid function, and why do we need activation function? After we aggregate the information, why do we even need that next step, which is non-linearity? Why do we even need to think about that? So don't worry about what the picture tells. Worry about some a story. Okay, so if you smell something delicious, okay, I'm pronouncing it correct. So if we smell something delicious, think of your favorite food. My favorite is, let's say, an example of pizza. Okay, take an example, your favorite food. So if we smell something delicious, which is your favorite food, in your neurons, your summer neurons, which learn to identify that favorite food, will get activated and will help you to get sense or taste it. So you have several neurons, you have millions of neurons, and some neurons will get activated when you smell it. Okay, when you smell your delicious food, your some neurons will get activated, and then it will give the signals to your mind to just get a sense of something or taste something. Okay, and if you smell something which is not good, the same neurons do not get activated. Okay, now this is kind of critical in this case. It's very kind of a inspiration from brain. Like, say for example, you have a neuron 1, you have a neuron 2, you have a neuron 3, you have a neuron 4, you have a neuron 5, neuron 6, neuron 7, neuron 8. Okay, so several neurons. You smelled something delicious. So what will happen? Maybe the first neuron get activated, this neuron get activated, and this neuron got activated. These 3 neurons got activated, and then it helps, and then it tells your hand or tells your mind to just taste something or kind of that. But now what will happen? I'll just have this. Now the same neurons which we are having, now when you say something which is not delicious, the same neurons will not get activated. Other neurons which will get activated, which is not the same which is used for kind of so it will not get activated, the same will not get activated, but other neurons will get activated. That will help you to leave that food. So in general, same happens with your neural network. That can happen as 1 activated and 0 non-activated. Okay, so we can say if the value closer to the value to 0, the lesser it is activated. So in this example, say for an example, you have x1, x2, x3 and x4. Now these are your inputs. Now over here, this neuron got activated, this neuron got most activated, because it for this task, these two got more activated, as compared to this. These two are completely 0, and these two are completely 1, and maybe this is kind of a maybe 0.75. okay, more 1. Okay, so this is how the intuition of activation function, which activates a particular neuron so that it is able to do one task. This is kind of a relation to your brain kind of stuff. Using linear activation function. So why our activation function should be linear? Why do we need non-linear? So here your data is linearly separable. So we do not need any non-linear activation function. We are happy with, because here your data is easily separable by a straight line. So it is linearly separable. But in real world, your data is non-linearly separable. So that's why you have your favorite non-linear activation functions. One of the example of a non-linear activation function is sigmoid function, okay, which is 1 over 1 plus e to the power minus z. And all non-linear activation functions are differentiable. When you take out the derivative of this, with respect to z is nothing but times 1 minus z. Okay, but don't worry about it. We'll see the derivations later on. So over here, your data, you cannot fit a straight line to this or fit a straight line like this to separate it out. So for that, you need a line or a circle which separates it out. So it separates the green and this blue one, which is a non-linear, which exactly non-linear activation function achieves, is using to find a non-linear decision boundary. Okay, so here your data is non-linear. It helps you to achieve the non-linear activation function to help you to build a non-linear decision boundary. Okay, so I hope that this gives you a better sense of it. So I hope so I'll just start off with the last stuff. I'm saying from a lot of them. So basically using non-linear activation function, so you have a set of inputs x1 and carried by the weights, and then you aggregate in the nucleus, and whatever you get net j, and then what you do, you apply to a non-linear activation function. Because your data is non-linear, Okay, so provide that into a non-linearity. Okay, and then it gives your output, and then using a threshold like 0, if it is greater than 0.5, you'll just say, okay, the person has a, let's say the person has diabetes. So if it is a classification problem, but what if it is a regression problem? We'll use a linear activation function. Okay, just pass that the output or the net j rather than applying activation function. Okay, and then we get an output. But you may be thinking, you may be having some questions around it. Hey Ayush, you told can we have a non-linear data in regression problem? Yes, absolutely we can have. But you will soon realize in neural networks, you don't have only one neuron, you have several neurons, and at last you have one output layer, and in that output layer, there you don't apply any activation function, but other neurons you do apply activation function, but in output neuron you don't apply neural network activation function, and then you simply apply a linear, and then you get your output for regression problem. But don't worry about it, we'll discuss that in very detail. So I hope that this is very clear on activation functions, and I hope that you understood it very well. Now we'll talk about the training. How do we make it learn, or how do we make it learn a real world neural network, or how do we train this neural network so that it will be able to correctly classify the particular neuron, and what exactly learning means, and what is learning problem. So let's talk about that in the next lecture. Hey everyone, welcome to this lecture. So in the previous lecture, we had a talk on introduction to neural networks. We had defined artificial biological neural network. We also talked artificial neural network inspired by biological neural network. We had also told you about what are weights, etc. We had also given an intuition behind what are activation functions and why do we even need it. We talked about linear and non-linear activation function. So now we had seen that how we go ahead and make prediction, like with the information carried. So what eventually we do, so we'll just do the quick recap of it. So basically what exactly we do is, this is what the perceptron looks like. So you have the input feature x1, x2, x3, okay, and x4. So these are the 4 input features, and each feature is carried by the weights, and these weights like w1, w2, w3, w4, and we have a bias term. Please see the previous video to know why do we require bias term. So these are some of the weights. So these and we have x0, which is always set to 1, okay. So basically, and x0 is being multiplied with this. So x1 being multiplied with its weight, and it identifies the effect of our input. So x1 plus w1 plus x2 plus w2, all the way down to the x4 plus w4. And these information are carried into a nucleus, if we talk about in biological way, or we do the weighted sum of it, and then we apply some kind of processing on it, which usually call as activation function, whether to activate this particular neuron or not, okay. And if it gives 0, then we say okay, or maybe if let's say you are working on some classification problem, it gives 0.4. So if it is smaller than our threshold, if it's smaller than our threshold, let's say epsilon, then we say okay, say that it returns 0, and maybe 0 can be the person has a diabetes. And if it is greater than or equals to epsilon, then you can say return 1, and that 1 can be the person does not have a diabetes. So it is totally dependent on your case. So that was a particular neuron where we talked about that how the forward thing work. Okay, so how we do the forward propagation, this is called the forward propagation. This is called the forward propagation, where we are propagating forward to make prediction. Okay, so where we are forward, where we are doing propagating forward to make prediction or get our particular variable y. What exactly we are doing is multiply with these input feature with the weights and do the weighted sum of it, and then apply some null activation function, and then we get our output. Okay, and now who will tell us that we are getting the good output? And how do we how do we get these weights? How do we get this W1, W2, W3, W4, and D? Because these are the input feature which we'll get from the user. These are the input feature, but how we will identify these weights? How will identify these weights? Because it is playing a crucial role over here when being multiplied. So we need to identify what is the effect of our input, okay? Because we need to know how do we get these weights. So let's get started talking about this. So now let's get started. What exactly do we mean by learning this perceptron? So how we can make this perceptron learn to make good prediction, or can be used in the or okay. So what we will do now is to formalize our learning problem. So what exactly does it mean is you have your input feature and you have your inputs, and this is a giant X. So we'll say X is a set or a giant set which contains the input features. And please note, I'm not adding the design matrix. If you wanted to know what exactly what is design matrix, I would recommend you to watch my machine learning fundamentals or ML01 videos. Like first video, which was multivariable linear regression. It would be very nice for you to know about how we structure our inputs, so that you could get to know that exactly how the input is structured. Cool. So you have X1, X2, X3, and X4. Okay. So these are the input features, and input feature can be n features, X1 all the way down to the Xn. Okay. So we have n features in our input set X. Cool. Now, given these input features given by the user, so this will be given by the user. This will be given by the user, and then we'll be having our output. If this is a case of supervised learning problem, if this is a case of supervised learning problem, then we'll be having our label, or we can say then we'll be having our supervisor, which is target variable y, which will tell us which will help us our model to learn. Okay, so I hope that you know supervised learning. So if it is a case of supervised learning problem, then you're given the input set feature X, and then you're given output variable Y, and there's a ground truth that is a ground truth which we know because these X and X1, Y1, X2, Y2, these are your training examples which is given to you. Now we need to learn a function f which takes the input value X, and we want our function to map to target variable Y. So, okay, so to map a target variable Y, so you want to learn a function f that takes these input feature X and maps this to a target variable Y hat, and this Y hat should be equals to Y. Don't worry about the other cases like overfitting, etc. Worry about that, what exactly we need to learn. We need to learn a function X. We need to learn a function f that maps your input variable to some target variable. Okay? And then, and this target variable should be equals to your actual target variable while training, and then you can use this learn function to predict on new examples where you don't have your ground truth. Okay, so I hope that you're getting this. This is what machine learning tries to do. It tries to find a function f that maps your input variable to some output variable. And now, so here's the diagram of it. So you have an unknown function. You have not learned any kind of function, which is f, which maps your input variable to y. And now what do? You have your training example. With that training example, you give that training example to the learning algorithm. Let's say, in this case, neural network, or we can say linear regression, or we can say logistic regression, or we can say support vector machine. So you give to the support vector machine or whatever, and then it will output a learn function g, which maps these input variables to our output variable. And this course comes with the machine learning fundamentals prerequisite, so I hope that you know about these algorithms previously. Okay, cool. Very nice. Now let's go further. So this was the formalization of our learning problem. So what exactly is learning? So how our perceptron or any algorithm learns? So learning happens by changing the values of our weights. So what exactly we do? What I'm going to do is x1 and x2, okay? And I'm neglecting the bias term as of now, okay? So neglecting the bias term as of now, you have x2 and x1. We give to a neural network, which is a perceptron, what it does, and each information is carried by the weights, and we say x1 w1 plus x2 w2, and then you apply the processing or the non-linearity on this z, and z is this one. Okay, so you may be thinking, okay, you are getting x1 and x2, but who will give you w1 and w2? Whole learning depends on getting these good w1 and w2. Please listen me carefully. Whole learning means in all the learning, what exactly you need to do is find good weights. Find good weights and some odd parameters. Is something, if someone is telling you that this neural network is learning, eventually what it's doing is getting good weights, or getting the good set of weights that for the particular problem. So let's say in starting, what your perceptron will do, the perceptron will set your w1 to be 0 and w2 be 0. Okay, in starting we'll set all our weights to 0. Okay, and now it will output some y. Okay, that will be also 0, because when you simply multiply with 0 0 0, it will be eventually 0. So what exactly it is doing is change the value of weights in every iteration. So now when you initialized your weights, let's say w1 to be 0 and w2 to be 0, and we'll see the initialization techniques later on, but let's say for this example we had initialized our weights. Now we'll start training it. Eventually what this training means is getting the good getting the good set of weights, or the right set of weights, like w1 and w2. So in first iteration, an iteration number we have to check. We have to give as a hyperparameter. Let's say that we want to do for 1000 iterations. Okay, so what eventually it will do, it will change the value of weights from 0 to maybe 0.2 and w2 to be 0.3. okay, that will change the value of weights and check. Okay, because you will get to know that we have something called as loss function, and this loss function, in this case, it's if we apply the non-linearity, which is a logistic loss, then it is a logistic regression or log loss, which we'll use over here. So basically we want so now after updating the weights, we'll check if the loss is decreasing or the error is decreasing by changing those weights. If it is decreasing, then we update these weights from 0 to 0.2 and 0.3. That's it. First iteration is done. We will do the second iteration, and in second iteration what we will do, we'll change those weights like 0.4 and w2 by 0.5, and I'm doing this completely because some people will ask, how are you writing these? These are completely random. Okay, you will get to know in later on that eventually when we do the back propagation, I'll do a step-by-step one example to show you every cases, but over here I'm just taking as a random. Okay, now over here you update in the second, this is a second iteration, this is a second iteration where w1 is this and w2 is this, where it changed the weights or tweaked the weights from 0.2 to 0.4 and from 0 for w2 to from 0.3 to 0.5. Now we check if the loss function loss function is decreasing. If it is decreasing, then we update from 0.2 to 0.4 and 0.5. Okay, so eventually what we are doing is changing the values of weights until and unless we get our good or our loss function is equals to 0 or our error is 0. So in brief, we'll use our batch gradient descent algorithm. Maybe you already know about batch gradient descent algorithm to minimize our loss functions, So eventually our goal, what is our goal? To minimize our error with respect to so we need to minimize the error. we need to minimize our error. That's our end goal. So we'll use gradient descent algorithm to find good weights. Don't worry, you don't have to do by your hand. You make use of the algorithm, which is gradient descent algorithm, to find the global minima of our function j of theta. And in the case of regression problem, your j of theta is 1 over 2m I equals to 1 all the way down to the m h of x minus y and squared. So that is a mean square error. And what you do, you have a function and you need to find the global minima in this function. Okay, and when you find the global minima in this function, that will be here. Okay, and we'll cover this. So we need to find the unless our loss is equals to 0 or it reached to global minima in our function j of theta. Cool. So I hope that this is pretty much clear about what exactly learning means. Learning simply means is changing the values of our weights in every iteration and checking if the loss function is decreasing. If it is, then update those values to the new weights, from the old weights to the new weights. Cool. And in brief, what we do is use batch gradient descent algorithm in this example, but there are lots of optimization algorithm that covers the limitation of these gradient descent, which will help us to find the global minima of our function or to converge or to get the good values. Okay, so in an iteration of gradient descent, what exactly it's doing, don't worry, we'll cover gradient descent. We have already covered actually gradient descent in our machine learning course. If you want to go there, you can go there and watch that, what exactly does it mean. But don't worry, if you don't want to watch that, we'll cover gradient descent again to let you know how exactly the working means, how exactly the geometric purpose of gradient descent works. Cool. So let's go ahead talking about the gradient descent so that you could understand. If you haven't understand, don't worry about it, you will understand it later on. Cool. So we'll use our standard gradient descent algorithm to train our perceptron. Means, what do we mean by training? We mean by training is getting those good weights, W1 and W2. Okay, and of course we do need a bias term as well. So we need a bias term. So we need to get W1 good, we need to get a good W1, W2 and the B. We need to get these three parameters or weights which are good for your problem. So here how it works. So in every iteration, okay, it changes the value of weights, okay, of our parameters, and check how well your model is performing with the current weight. If it is performing well, it simply update the weights with the current value. It keeps on doing this unless you converge to your global minima. Okay, so over here, let's say you have your loss, which is very high loss, very high error, which is j of theta, let's say 500. Okay, that is your error, which is pretty big. Now over here, when your loss was 500, your weights was theta 0, oh my god, W1 to be 0 and W2 to be 0 and bias to be also 0. So these are all our zeros when your all thetas were, or sorry, when your all weights are 0, then your loss was very high. Okay, now when you update these loss, now what do you do using gradient descent? What exactly it's doing, it's changing the weights of this, of all of these. Like now it changes the weight to W1 to be 1.2 and W2 to be 0.4 and B to be 0.1. So it changed the weights. Now checked if the loss function is decreasing. So you have a less loss, and now when we updated it, loss function seems to decreased. It came to 400. Now we update our weights to be not this, to be this. Okay, now again what we do in next iteration, it updates these weights to be the new weights and checks if the loss function is decreasing. And over here, when updating those weights again, tweaking this means let's say 4.1. So in this over here, by tweaking these weights, we are getting the loss function to be 200, which is eventually very low. Okay, so you keep on doing this until unless you reach to be here, because here your loss function is 0 and you get good set of parameters W1, W2, W3 all the way around to the W1, or in this for example W1, W2 and B.
So when you reach at this where your loss is 0, you have good parameters. And this is this is a parabola and something like that, because it should look like parabola, just for showcasing you all. So I hope that what does it mean. If you want to know this in depth, I have a video on my ML01 course. Please go there and watch that, and on my YouTube channel, New Era. So this was a geometric purpose of it. This was a geometric purpose of it. Now let's get ahead. To talk about like the formalization, the mathematical part of it. Like what strategy do we use to update the weights or tweak the weights, etc. So we have already studied the derivatives. It is just a fancy slope. So what does a slope means? How much y changes when x changes? So what do we need to know in this case? What do we need to know in the case of here? We need to know how much loss is changing. How much loss is changing when we change W1. Okay, the same question again. How much loss is changing when we change W2? How much loss is changing when we change to W or B? Okay, for this example, so it will tell us how much loss is changing. Cool. So I hope that this gives you pretty much sense about. Now this is exactly slope, and that is a slope. And in calculus term, if you want to take out the slope of a non-linear or a curve, if you want to take out slope of a curve, we call that as a derivatives, which you have already studied. If you don't know about derivatives, something will pop up, or you can just go on New Era YouTube channel. There is a playlist called Single Variable Calculus. Okay, go there and complete all set of videos. Then you'll be knowing the geometric purpose of the derivatives. It's just a fancy slope. It just tells how much that loss changes when that weight changes. Okay, how much that loss changes when that weight changes. So how much cost function is changing when feature weights changes. So we have a loss over here, and this example we have taken the log loss. Because we are dealing with a classification problem in this case. Let's be honest, we are dealing with a classification problem in this case. Cool. So over here you have 1 over m, where m is the number of examples. It is looping through I equals to 1 all the way down to the m, yi log of h of xi plus 1 minus yi log of 1 minus h of xi. If you don't know about this log loss, I'd again recommend to complete ML01 course, which is machine learning fundamental course. Now over z means theta transpose x, and h of x means sigmoid of x, and sigmoid is nothing but 1 over 1 plus e to the power minus z, and e has some value which you all know. Now we have a loss. What our goal is, we need to optimize we need to minimize our loss function and find the good weights. We need to find the good weights. So it should not be here, it should be here. We need to find the good weights, good set of weight, and that minimizes this loss function. We need to find good set of weights, W1, W2, all the way around Wn, that minimizes the loss function j of theta. Okay, so how do we solve this optimization problem? Because you all know about this, that maybe if you have already not studied calculus, I'd again recommend you to do my calculus course, because in this course you will get to, means it's total, because I don't ignore calculus in this course. Please go there and watch my single variable calculus videos, and then it will make pretty much every sense to you. So now we need to solve this optimization problem. So what exactly we'll do is, the first step is to initialize all weights to be 0. Initialize a W1 to be 0, W2 to be 0, all the way around to the Wi to be 0, with the bias term also equals to 0. Okay. Now you keep on doing this, you keep on doing this step until and unless it converged, or until and unless it is greater than or equals to that iteration, the number of iterations you want to do, or until and unless it finds the global minima in your loss function, or until and unless your j of theta minimized.
Okay, so you have your gradient. So this is your gradient, which you already studied in that course of single variable calculus, and this is, maybe you will see in vector calculus, this is just a notational argument to write the derivatives. So what exactly we'll do for vectorization, we'll put that all in a column vector. So this is a column vector, we'll make that as a row vector now. That is the partial derivative of your loss function j with respect to w. So that is the vector of gradients, gradient vector. Now this vector contains the partial derivative of j with respect to w1. Why are we taking the partial derivative of j with respect to w1? If you don't know about the difference between the partial derivative and the derivative, it 90% means the same. It's kind of a don't worry if you don't know about the difference between partial derivative and derivative. For this, if you don't know about the difference, please understand as a same. Okay, so it's just saying how much the loss function is changing when we are changing this w1. Okay, when we are changing this w1. So eventually you're taking out the derivative of a loss function with respect to w1. We are taking out the derivative of a loss function with respect to w1. Okay, now when we take out the derivative, so let's say w1 equals to w1 which was old. So I'll just write w1 old, the old, which in this case will be 0 if it is the first iteration, minus the alpha, which I'll come to that. Let's assume that is 0.1. I will come to this alpha in just in a second. And then you write partial derivative of j with respect to w1, where you say dou j by dou w1. Okay, so this is what it is doing. It's simply what taking out the partial, how much the loss function changes when w1 changes, and multiply with the alpha. Okay, and then subtract this particular whole operations with this old one. Okay, and then update that w1 to be the new whatever you do get by doing this operation. And you do this for every example, and these keep changing. The w new and w old will keep changing. Okay, for example, this is w1 is over. Now it will do for w2 all the way around to the wj. That is the first iteration. Okay, that is the first iteration. In the second iteration, it will do the w1, w2 all the way around to wj. Okay, for the second iteration. For third iteration, it will do the same. Okay, so this is what does it mean? What do I mean with this? So you take out the partial derivative of j with respect to w1. If you don't understand till now, don't worry about it. I'll again keep on talking about this, but I can just hope that you know about this particular thing, what exactly we are doing, because you already have studied in your machine learning course. So I just don't want to focus more on this. So the learning rate gives engineers some additional control over how large the steps should be made. So if the learning rate is too large, you can overstep the minimum and even diverge. So you all know that we are doing this and we are here. So if we have now we need to identify which rate we need to go to the minimum, which rate we need to go to this local minimum. But this rate is set by the learning rate alpha, learning rate alpha, or you will see sometimes this notation. Okay, so you want to know the learning rate, or the rate by which you can control how large your iteration or steps should be for your change. So if the learning rate is too large, you can either diverge. So let's say you have this loss function, and this you need to go here. Now your learning rate is around 1. What you will keep on doing is go there. It will just do like this. It will never converge into local minimum. It will just keep on diverging in the zigzag manner. Okay, and if you have a small, you will I think you'll never converge. Okay, so you can go there, https developers.google.com machine learning class course filter/graph. This gives you a geometric or graph view of the learning rate. So over here we are on solving this optimization problem. So again, I'll repeat what exactly we are doing or where we are. We are initializing the weights to a 0, and we are repeating this step until and unless convergence. So what exactly it's doing? It is simply, what exactly doing? It's first of all taking the partial derivative of j with respect to w, and that is w is old. Okay, not the current. Means what? W is obviously whatever the W you have. So you take out the partial derivative of loss function with respect to W1, and then what you do is, what exactly is telling how much the loss changes when W1 changes, and then we get to know about that, and then we multiply with the alpha, which is a learning rate, which gives you additional control over how large the step should be, and then you're subtracting from the old weight whatever you get from this operation, which is this one, and which is this one, and then you get your new weight. Cool. I hope that this gives you a pretty much clear sense about it. But then the next step is update rule. So we are updating our old one with a new one, and you may think, hey Ayush, why are we subtracting it? So one way to understand it is, the way I understand it is, we are subtracting. Why are we subtracting this operation from the W1? Is because if you need to reach global minima, if you need to reach the global minima, so let's take an example of this. So you want to move down, not up. You want to not go above. You want to you want to go down, right? So you are subtracting it to go down. Okay, not you want. If you add it, it will go above. It will go above. Okay, so I hope that this gives you pretty much sense about it. So why we are subtracting it is the one reason to go down. It's kind of a one way to understand. There are several ways when you would do the partial derivative by your own hand, you will understand in more detail. You'll get in problem sets. So we are updating our old weights with the new weight, and instead of addition we are subtracting is the only reason, because we need to reach our global minima. Over here you want to minimize your cost function, so you need to reach the global minima, so we need to subtract to go down. So why gradient descent use derivatives? So you may be thinking, why are we needing this kind of a partial derivative or derivative? Why do we even need it? So what exactly is doing? Let's take an example that you are at this point, and this is your function of your loss, or let's say this, of course this is a parabola, and let's assume that this is a function of j of theta, where your loss is very high at this point. Your loss is very high at this point, but you need to reach over here. But you need to reach over here. So when you take out what it does, it draws a tangent line on this. Okay, tangent line on this point. When you take out the partial derivative of j with respect to W1, it takes out the, in geometric view I'm saying, it takes a tangent line at this. So what is it telling? If we draw a tangent line at that, so let me just say, if we draw a tangent line at the green point, we know that if we are moving forwards, okay, so if we draw a tangent line, or how does that tangent line is drawn at that point, is taking out the derivative of your loss function or whatever that function is. So if you draw a tangent line at that green point, if we are moving upwards, we are seeing that we are going away from our global minima, or the minima of the function where we need to reach, where our loss function is 0. That we exactly want. And when your loss function is 0, you know that you have a good weight. So if we draw a tangent line at the green point, we know that if we are moving upwards, we are moving away from the minima. And if we go down, we are going close to our minima. Okay, so tangent gives us a sense of the steepness of our slope of a function. Okay, another thing which is a very crucial, this derivative tells. Another thing which is very crucial, this derivative tells, is the first is the direction to move theta in, or the parameters in. So over here, if we see that we are moving upwards, we are going away from the minima, but if we go downwards, we are moving, or we are getting closer to minima. So it will tell you, okay, we need to go down rather than going upwards, we need to go downwards. Okay, the first thing it tells is to move theta in. The second is how big a step to take. Okay, that how big step to take. If the slope is large, we need to take a large step because we are far away from the minimum, and if the slope is small, we need to take a smaller step because there the slope is smaller. Okay, and for this illustration, what do I recommend you to do? Maybe if you go to this website or the link, when you put it, if first of all it takes a larger steps, but when it starts reaching to the minima, it start taking small steps, because there your slope is small. Okay, so it tells you how big the step to take. So these are the two things which this derivative tells, and what exactly we do need. Okay, so I hope that the calculus is again the very good thing which you need to know. I'd again recommend you to know about the geometry purposes by going on my YouTube channel Numera. It is very helpful for you. Cool. So now over here you have below is a perceptron, which you all see, which we haven't seen, which we have already seen it. Now what we will do is see how we will train this perceptron to perform well. And what does learning means, or what does training means, is getting good set of weights, W1, W2, all the way down to the W4 with the bias term. So this is a perceptron which you're seeing over here. Now I hope that I hope that you got to know about the perceptron and everything out here. In the next video, what I will try to do is to make you train everything, give you equations that how we will do, and we'll do one work example, as well as we'll work on some activation functions. For taking the we'll do the lots of derivative stuffs in our next video. Till then, bye bye, have a great day.
So in the previous lecture, we had a talk on the introduction to neural networks, and I hope that you really liked that lecture and understood every concept, because most of the concept later on will be dependent on the previous one. So basically, now we'll start talking about the learning problem, and you don't need to worry about if you don't understand it. It's just for giving you an intro. If you know about machine learning, you know about gradient descent, how gradient descent works, then it will be pretty much clear to understand this section. If you don't know about it, I will ask you to watch my calculus videos to understand it better. And if you don't understand, even if you know calculus, I'll ask you to wait for the next lecture, because we'll be doing a step-by-step example using numeric example to help you out. Cool. So over here, what I'm going to do is to formulate the learning problem. So basically in this, we are formulating the learning problem. So here you're given the input variable x, and then you have an input variable y. And then make a function f which takes this big or the big x or set x and maps it to output variable. And we want our function to map our input to output variable. So you all know in machine learning what we do. We take a set of inputs. Let's say you wanted to build a diabetes prediction system. So you take let's say the age of a person, the height of a person, the BMI, and etc. What are the foods they eat, and you take the inputs and then you make a function f, and then using that, and then it learns to predict, given those input features or those input values or those information, to map it to output variable, whether the person has a diabetes or not. Okay, so you want to learn a function f, and your data, I assume that you already know machine learning and a bit of machine learning, machine learning fundamentals. So basically in machine, what do you do? You have data. So x1 and y1, which is the one training example, x2 and y2, which is second training example, x3 and y3, which is third training example, and x and yn. But over here you have, for example, input and the target variable, input and the target variable. Okay, so this is your data. Now you want to learn f, which takes that input variable x and then maps to output variable y. So when you pass it through this algorithm, which is NN, and you pass through this algorithm, you pass f to this algorithm, you will get g, which is trained function, or which is learned function, which is what do you say? Which is very good function to maps your input variable x to the output variable y. So that's a case about learning formulation. So I hope that you already know about nonlinearity. I don't want to jump into this. So what is learning? So learning happens by changing the values of our weights, and in every iteration of it, we should decrease. In brief, we'll use our batch gradient descent algorithm to minimize our cost function. So we had already had a talk on this. We also talked on our gradient descent algorithm. We had also seen and now we also seen the learning rate. We have also seen the update rule. We have also seen the y gradient descent uses derivative. Now what we will do is jump on the training a perceptron. So you have a perceptron where you have a set of inputs. You all know what exactly perceptron does. It takes set of inputs with a biased term, and then pass it to nucleus or a neuron, which we say. In neuron, it do two things. First of all, aggregate the information and take the weighted sum. Exactly what it is doing there. And the second half, it applies the processing in it, which is 1 over 1 plus e to the power minus z, which is an activation function, whether to activate this neuron or not. And then we get our output y hat. And then we check, now we got a y hat, which is a model prediction. Now we check whether this y hat is equals to that y, which is the ground truth, and if it is, which we take a loss using the log loss, which is the negative log likelihood, which you're seeing over here. Okay, so now what we have planned to do is to use gradient algorithms. So we have already seen what exactly learning means. Learning means changing the values of weights until and unless we get a good model, until and unless our loss is minimized. So basically W1, W3, all the way down to the B are the parameters or the weights which we need to find perfect weights, which works very well. So basically in whole deep learning era, what do we need to do is to find the set of weights, which is W1, W2, W3, W4, and all the way down to the B. And B, to get, if we have good weights, we'll be able to get good output. And if you have bad weights, we'll be able to get the bad output. So you may be thinking, hey Yush, how we are going to get these weights? If so basically we initialize the weights. So before training our neuron, or before learning these weights, what exactly we do? What exactly is we do? We initialize all our weights. So basically, we initialize W1 to be 0, W2 to be 0, W3 to be 0, W4 to be 0, and B to be 0. Okay, and then we start training it, because now we have the weights. Now your model will be performing very bad because everything is 0. So you'll get your final output to be 0. Okay, and that is very bad, right? So what you do? You take out the derivative, because you need to find the global minima, but in this case it will be able to find the local minima. So you need to find the minima of that function loss, okay, of the loss. So what you need to do, you need to take out the derivative of L with respect to W1. So basically what it's saying, how much the loss changes, or J of theta changes when W1 changes, when your weight changes. Okay, so basically it's just a pretty much easy version, like how much your loss or how much your error changes when you change W1 a little bit. If it decreases, if the loss changes when W1 is 0.2, then you update that weight W1. Okay, so that's why we take out the derivative, because it tells a lot of things to us, which direction to move theta in, and yeah, so and it will tells us the slope, and etc, etc, etc. Okay, so basically, so that's why we take a look at, in the previous video we have seen that why gradient descent use derivative. Please see that. So over here we get our output. Now what we need to do is to take out the derivative of L with respect to W1. Okay, that tells how much L changes when W1 changes a little bit. So let's go ahead, and so over here you need to take a losses there, and then there is a path, a full path. Okay, so basically this is here we'll use the multivariable chain rule of calculus. So for taking out the dou L by dou W1, which is partial derivative of L with respect to W1, what do you do? First of all, partial derivative of L with respect to sigmoid of z. Okay, the sigmoid of z, because we can't directly go to we can't directly take out the derivative of L with respect to W1. We have to go through the path. So over here we'll use the chain rule of differentiation, multivariable chain rule of differentiation. What exactly we are doing in this computational graph is derivative of L with respect to that sigmoid function, which is sigmoid of z. Okay, and the sigmoid of z is 1 over 1 plus e to the power minus z. Okay, so you take out the derivative of L with respect to y hat, because that's a y hat, not the it is basically this sigmoid of z is nothing but your prediction, what you're getting as an output, right? So you're taking the derivative of L with respect to y hat. Equivalent, it does not matter. And then you take the derivative of this sigmoid function with respect to this one. Or you can say with respect to this one and with respect to this one, but it does not need to be, because this is your one neuron. This is your one neuron, which is okay. You take out the derivative and then you can simply go to W1. Okay, without even going here, just have marked a line to make you understand, but this whole process takes in one line. Okay, cool. So here we have used, so we'll simply derivative of L with respect to this neuron, and then using the derivative of this neuron with respect to W1. Okay, cool. And then for taking out the derivative of now over here, the derivative of sigmoid function with respect to W1, which here over here. So now let's go ahead and take out the mathematically about, let's solve this particular problem. So we'll be getting out derivative. Okay, so let's solve it. So let's get ahead. So we want to take out a derivative of L with respect to W1, the first parameter. So we need to choose, because we need to find W1, W2, W3 and W4. Okay, these 4 parameters to be good parameter. Okay, and then we'll getting out good output. So basically what do you do? Derivative of L using the chain rule of calculus. Okay, so let's take out let's take out the derivative of loss with respect to y hat. Okay, with respect to y hat, or a prediction. Okay, so basically your log loss is nothing but minus I'm writing the negative log likelihood y log of h of x, which is your prediction, or we can say the sigmoid of x, which is a prediction, plus 1 minus y log of 1 minus sigmoid of z. Okay, so basically you have this, and then when you take out the derivative of it, when you take out the derivative of L with respect to this z, so a sigmoid of z, so basically what you'll do, so just for your information, the derivative of log x with respect to x is nothing but 1 over x. So that's your derivative, 1 over x. So you'll be left with minus y sigmoid of z plus 1 minus y 1 minus sigmoid of z when you take out the derivative of this. If you don't know calculus, don't worry about it. You can just think about, okay, when we take out the derivative, we'll get this calculation, or you can learn calculus or see on some YouTube videos to understand how it came. But specifically, it's very easy to understand. First of all, the derivative, this is a constant, this is a variable, this is your so when you take out the, what do you say, 1 over this, that you'll be left with the derivative of log x, so that will be this, and plus 1 minus y, and then you simply add 1 by 1 minus sigmoid of z. Okay, so that's it. That exactly how we take out the derivatives. Now let's go further, and now we had found this one, which is this one. We are done with this one. Now we need to find this one. So basically we're taking out the derivative of sigmoid of z with respect to W1. So sigmoid of z, which is the function 1 over 1 plus e to the power minus z. So that's your function, which is a sigmoid function. So you need to take out the derivative of that with respect to this z, because we can't directly go to W1, but with respect to z. And then we'll be having this one. So from here to here, and using this z, we'll get our W1. Okay. So basically, how you take out? So 1 plus e to the power minus z to the power minus 1, because we had converted to this fractional form to a line form. So you can take a look like this, and then you use the power rule of differentiation. So what you did is to transfer this over here. So let me just how I come up with this. You can simply feel free to ask me over comments or see any online video, because I assume that you already know these what do you say, sigmoid function or the derivatives calculus. Don't worry, we'll derive this in our next lecture. Now you have taken out all the now we have taken out all the derivative of L with respect to W1. We can simply multiply with this. Derivative of L is this, and derivative of sigma of Z with respect to is this one. And how this x1 came, how this x1 came. So because the derivative of Z with respect to W1 and Z was nothing but W1 times x1 times x1. Okay, we just assume that W1 times x1. Over here, when you take out, so over here we need, so you'll be left with x plus 0. Okay, so you're left with W1, x1, x. Now let's go further. So that's why we got x1, and then you got the derivatives of L with respect to W1. But if you haven't understood, don't worry about it. Pretty much easy. We'll again revisit the same thing, but we'll do all the calculations by ourselves, so that you get a very good understanding of it. But don't worry if you haven't understood. It's just for those who knows calculus. For those who knows calculus. Okay, to take out an algebra, who are good in mathematics. So we have taken sound. So now we have seen our. So now we'll see some of the activation functions. So now we'll see some of the activation functions and then take out the derivative of those activation functions. Okay. So this first activation function which we have already seen is the logistic function. The main reason why we use segment function is because it makes that the output of Z into a range of 0 to 1. Okay. So when you take out the derivatives, which you are seeing in front of you, we had already taken out by derivative of Z with respect to segment of Z with respect to Z. Okay, cool. Let's go further. So we have another activation function, which is the tanh activation function. The hyperbolic tangent activation function is often referred as a tanh activation function. It is very similar to activation function. It's just similar to activation function, but rather than making that Z in the range of 0 to 1, it makes in the range of -1 to 1. It makes in the range of -1 to 1 rather than making it to the 0 to 1. So that's why we define as a tanh activation function. What is the function formula? The formula for that, e to the power minus x minus e to the power minus x divided by e to the power x plus e to the power minus x. So you just, instead of Z over here, it's x. So you can just put the x value or the input value to convert into range of -1 to 1. When you take out the derivative, it's a bit hard, and I don't want you to get into this because it's kind of, you just need to know about this particular stuff. You don't need to you need to know about the derivative. But if you are seeing over here, the derivative of that e to the power minus z is nothing but 1 minus tanh h squared. Okay. So all the derivatives which we are using the chain rule of differentiation, exponential derivative, etc. to get it to 1 minus tanh h z square, which is the derivative. So why I'm telling you the derivative? Because we'll use it in our later lectures. So that's why. If you're not getting it, why we are using it, please be sure to complete the whole class, and then you'll be understanding why do we need to use these. So then the next activation function, and widely used activation function, ReLU activation function, which is a rectified linear unit. The main advantage of this ReLU activation function over another activation function, it does not activate all the neurons at the same time. So basically, if what it does, it takes the max of 0 and z. Okay, assume that your input value z is 1. So when you take out the max of 0 and 1, what it will be? The answer will be 0. So that particular neuron is not activated, because the neuron, we have a particular z, and then you have some kind of activation function. So z is let's say 1, and when you apply this max, then the neuron is not activated. Okay, at the same time, because it really helps. And the special property of all the activation function, ReLU activation function, whether it be tanh h activation function, or whether it be, what do you say, sigmoid activation function, all these functions are non-linear in nature and is differentiable. So all are differentiable, so that's why we are able to take out the derivative. But what do you think about the derivative of this? So we have the equation max of 0 comma z. So the derivative of activation function is 1 if x is greater than 0 and 0 if x is smaller than 0. Okay, so the derivative is this, which we can represent through this diagram. Cool. So we'll discuss about its advantages and disadvantages later in the course, and we'll continuously revisiting these activation functions a lot to help us better understand, and we'll be introducing later extensions of some activation functions to overcome their advantages. So if you don't know about any of these things, and if you didn't got it really, don't worry, directly move to the next lecture. You'll be understanding everything, because there I have gone very slow in understanding step-by-step gradient descent example. So here's a recap. So exactly perceptron learns is by changing the weights, and here the path you follow from going to L to W1 by, first of all, the partial derivative of L with respect to that sigmoid of Z, and then partial derivative of sigmoid of Z going to sigmoid of Z, and then partial derivative of sigmoid of Z going to W1. Okay, and this is the same for every particular, every particular feature over here. Okay, so I hope that's pretty much clear to you, and I hope that you are able to understand everything out here. In the next lecture, we'll start off with multi-layer perceptron. I hope you'll enjoy that. Let's go on next video. Hey everyone, welcome to this lecture on multi-layer neural network in our course MLO2, and I hope that you are really liking this course. So let's get started with multi-layer neural network. So what is multi-layer neural network? So in perceptron, which we have seen, we have a particular unit, I would say. We have particular unit like this, and in multi-layer perceptron, we include lots of perceptron and stack them together. Okay, so let's take one example. So taking one example, which you're seeing that we have a particular, which we have seen in previous videos, we have several inputs, and we give to a particular neuron, and then we get our output Y. Okay, so what we will do is have multi perceptron like this. Say for example, we have information x1, x2, and x3. We give to this particular neuron, and then the output from this neuron is given to another neuron, and then we get our output, right? So this is a multi-layer perceptron. This is a multi-layer perceptron where we have a multiple perceptron or more than one computational layer. Okay, in perceptron, you were having an input layer and an output layer, right? So you have an input layer, which is x1 all the way down to the x4, and then you were having the output like this, right? So you're having the neuron, and then you're getting output. So from this particular neuron, you're getting the output. So this was called as an output layer, right? Output layer. And because from this neuron we are getting the output, so that's why we call this as an output layer, where all computation was happening only in output layer, right? So all the computations, like the aggregation of the information like this, I equals to 1 all the way around to the j, xj, and wj, and then we apply the non-linear activation function. Over here we are applying the sigmoid activation function like this, and then we were getting our output, right? So all the computation was happening in this neuron. Now over here in multi-layer perceptron, our input is passed through several layers. So we have our input. x1, x2, and x3. It is passed to one neuron, and then the output from this neuron, the output after doing the computation, and computation what it does, first of all, the aggregation of I equals to 1 all the way around to the j, xj, and wj, and then the pre-processing, okay, or the activation function. So this processing is same, okay. So we do all the computation, and then the output from this is passed to another neuron, right? And then it performs aggregation and the processing, then passed to another neuron that we have to specify. Now you may ask me a question. Here, Yush, can count how many number of layers which we have. So over here in this example, and then we get our output. So here in this example, we have total of 3 layers. Which is called these two are called the hidden layer, and then we have then we have an output layer. So let's discuss about the terminologies which we will eventually use a lot in this.
Say for an example, you have this example, and then you have an input layer. You have an input layer, and then you have a weights for with respect to every input, and then we have one bias, right? And then we give to the one neuron, and then the output from this neuron is carried by some weights with the information from the previous neuron. So this weights is need to be learned, because over here we need to learn these weights as taught in the previous video. We need to learn these weights. So basically the information from this neuron is carried by some weights which we denote by W. We'll talk about what this 2-1 means later on, but over here the information is carried by the weights, right? And then it is passed through in over here. Now what will the computation in this neuron will be W21 times the H11, okay, the information which we got from here, right? Plus the bias term, okay, and then we get our output. Then we get our output, which is our Y. So over here we have a total of two layer. So we, in this particular example, we have 2 layer network, and here we have one hidden layer. The reason why we call this, because we are not the user is not seeing this, right? What the hidden layers, that's why we call this as a hidden layer, but we are seeing the output. So that's why this output layer, this is called the output layer. We do not count our input layer, because eventually we are not doing any computation in input layer, but in hidden layer and output layer we are doing computation, right? So that is our favorite, output layer and hidden layer. So again I'm repeating that through several layers which is not visible to the user, that's what we call it as a hidden layer, right? So that was pretty much easy to understand it in much better way. Now let's talk about we will talk about these terminologies to or notational arguments, what exactly this 1,4 and 1,5 means, and what does this relates to, what this relates to, and what this relates to, and all the stuff. But over here this was an introductory kind of a slide for making you understand about multilayer perceptron, like how we just extend the idea of perceptron to multilayer perceptron, right? So let's go on the next slide to understand much better way. Let's go over here. So let's take one example over here. But before that, I want to make you familiar with terminologies. So let me just show it to you. So here it is. So over here you have an input layer, then you have one hidden layer, the layers which is not visible, of course, and this is called the output layer, the layer which is the output layer, right? So information is carried by some weights. So information is carried by the weights W1, W2, W1, W3, and all the way to the bias term. And then we have 4 input layer, and then we have a hidden layer, and then we have an output layer, right? So the notation which you're following to be very much consistent is we have a W to denote a weight, and then we are saying layer number, and weight number, okay? So this weight is of which layer? It's for layer number 1. So we write layer number 1, and what is the number? What is the weight number? Is the first weight, right? So we write as a layer number and the weight number. So that we have layer number 1 because it's going in layer number 1, and then we have a second weight. First layer, third weight. First layer, fifth weight, right? So over here we'll change the argument, but for being precise I'm doing like 1,5. We have fifth weight which we need to learn, but as we go further we'll slightly change our notations to help you much more better on more concrete or industry standard wise, right? So just for information you can assume that a 1,5, okay? And this is layer number, this is layer number which is going for layer number 2, and this is the weight number. There is only one weight, since there is only one weight, so we have 2, 1, right? And over here you have a hidden layer, so we denote by H, which denotes the hidden layer, and then this is your unit number, this is your unit number, and this is your layer number, okay? So this is the first hidden layer, so we denote by 1, and this is a 1, there is one perceptron. Later we will see that we will having several perceptron like this, and each denotes a unit, right? So over here we have the first unit, right? So we have the first unit, okay? And then over here we have an output layer which is denoted by O, and then we have, and then this is nothing but your layer number or output number. You can understand in this way. So sorry, that, yeah, that is the output number, or we can think of in different way. Yeah, that is an output number, and this is your layer number, okay? But we can slightly change it to our formal notation is like this. I think we can slightly do the changes like this, where this denotes the unit number, where this denotes, I think there's a typo, it should be 1 over here, and it should be 2 over here, okay? That denotes the unit number, and that denotes the layer number, to be consistent over here, okay? I hope that that's pretty much clear about the notations. So let's go on our example, which we have seen previously. So let's go on examples. So over here we have a very good example to understand in a much better way. So diabetes prediction system given age, height and BMI, okay? So you have 3 information or 3 input value, and there is one bias term where we always set x0 equals to 1, okay? And then here we're taking example, let's take an example. Age is 4.5, understand this way, age can be 4.5 years old, and then height is 5 centimeters, and BMI is 6, and then x0 is obviously 1 by the convention. So we taken a default value for this example. No need to understand how this example came. It's just a random example which I've taken. Now I've given the random weights. Don't worry how these weights come. We'll learn how to get good weights just a random stuff, right? Just to make sure that you're clear about the process which is going on. So over here you have weight 1, which is 0.1. We had just defaulted this, okay? So we have W11, weight 1, weight 2, weight 3, weight 4, and then you have one bias term like this, okay, which is randomly initialized. Now we go to the first hidden layer. In the first hidden layer we have one Z, and then we have an H. So what this Z does? Z aggregates the information, right? So it just multiplies the weights with the input values. So over here, if you multiply 0.1 times your input feature 4.5 plus the 0.2 times 5, 0.3 times 6, 0.4 times 1, okay? So that is 0.4. So sorry, 0.4 times. I think did wrong over here. I think this should be removed. Oh my god, this should be removed. Please ignore this. And then we have one bias term. Please ignore this, okay? And then we have an H11, which is over here 1 by 1 to 1 plus e to the power minus z, because here we are applying the sigmoid activation function, which squeezes your output into the given range, right? So over here we have 0.99999, okay? So you get your the output from the first hidden layer, and this is your output from the first hidden layer, okay? And then we give to the, let me just do this a little bit concrete. It should be 0, 2 and 1. That's the output layer. Now you simply have we initialize a random weight 0.3 times the information from the previous layer, and then we add the bias term, and the bias term which you have taken over here is 0.2 as a randomly bias term is 0.2, and then we get our output, and then we apply the activation function which is 0.622, and then we get our output. Now if this is a diabetes prediction system, we can have a rule which is our prediction is 0, the person is not having a diabetes if the probability is smaller than 0.5, okay, and over here it is greater than 0.5, so it is nothing but 1. The person is having a diabetes with these information, okay? However, don't just think this is wrong, right? Means this is just I've taken one example, a very random example, a very abstract example, a very imaginary example, okay? Don't worry, this is for actual case. This is just to show you how we are going forward in our network with multi-layer perceptron. So how we are going forward in our network. So we call this as a forward propagation. We call this as a forward propagation, which we call, because we are propagating forward in our multi-layer perceptron, right? So that is our that is our just an example to help you better understand these things. Cool. So we have talked about rotations. So now we can do for multi-class classification prediction as well, with lots of hidden layers in between, like this. Okay, so over here, so I'll just make you understand much more detail. So over here you have an example of multi-class classification prediction. You're given the color size and the size of the bird. So you're given the color of a bird, and then you're given the size of the bird. You need to predict and you're given the sound of a bird, right? So you're given the color of a bird, size of a bird, and sound of a bird. You need to predict whether that bird is a sparrow, or parrot. Okay, given these three information, you need to predict whether that bird is a sparrow or parrot. Okay, so you're given these three information. Every information is carried by those respective weights with one bias term, right? So over here, the number of weights which you will get, so you have over here you have one hidden layer, you have second hidden layer, you have third hidden layer. Okay, and then we can increase lots of hidden layers. That's what we have to choose. Now you may ask one question, hey Yush, is there any way we can have the number of layers defined? Like how are we going to choose the number of layers which we want, right? The number of hidden layers which we want. So this is a very active area of research, that there is no fixed number of hidden layers which we can use to get optimal results, but it is just an active area of research. We just check with 2 hidden layers it works or not. We just tune our hyperparameters like this to get our output, right? To analyze which number of hidden layers are working well, right? So over here you have the first hidden layer. You simply do the information aggregation and the processing step, right? So activation step. So over here you have a total of, so the size of our input layer, the size of our input layer is n times 3. The number of weights at this hidden layer is 4 times 1, because there are 4 weights times there is only one unit, because further we'll see we'll be having several units. So that's why that is your 4 times 1, which is the number of weights. Okay, and the information is carried by the output from the H11 is at subscript 1 to the power superscript 1 is carried by the weight W subscript 1, and over here you have one bias term as well. So you have a 2 times 1. So over here you have W31, and then it is carried by, and then the output from this lay is carried by some weights with one bias term like this. Now over here we need 2 outputs. First of all for sparrow, and second for parrot. Okay, so every O output is carried by some weights, or the information is carried by different weights for different units, right? And then we get our particular output, the maximum. So we say, let's assume that this is for sparrow and this is for parrot, and this is for 3 times 2. Over here we have 3 weights for the sparrow, for the parrot, and the bias term. Okay, and the information is carried by the information of the weights for the information got, or the output got from this hidden layer is carried by three weights. The first weight is for the sparrow, second is for the parrot, third is the bias term. Okay, and then we have a total 2 units over here, right? So there are a total of 6 weights. There are a total of 6 weights over here. Okay, so I think there's a typo. We have total of 3 weights over here, but we eventually don't count it, right? So over here you take out the maximum of pi, right? So you take out the maximum of the probability of 012. So let's assume we get 0.7 and this is 0.4. So what is the maximum? 0.7. So we classify, given these 3 information, our the bird is a sparrow. Okay, so that is your with multiple hidden layers as well as with multiple output.
So now we'll see one hidden layer neural network. Now what we will do is to stack different perceptron in a particular layer for getting our output, right? So over here, assume that you have two inputs. So I'll just make you familiar with it. So you have two inputs, x1 and x2, okay? And then you have the one unit, second unit, third unit, and fourth unit, okay? So that is the first neuron, second neuron, third neuron, and fourth neuron, and then we are having the output layer. So this is a one hidden layer neural network. So over here, let's go with so now your information x2 is carried by weights like W21 for the first neuron. For the first neuron in layer number 1, it's carried by the weights, right? And these weights need to be learned, right? Weights are the thing which we need to learn, right? Which we use optimization algorithms to learn these, which we'll do in our couple of next videos to understand how we learn these weights. Okay, so x2, information x2 is carried by the W2, carried by different weights for different neuron. Say for example in this, the W2 is the weight for H1 by this x2 is carried by this. For the x2, the information is carried by this weight for this particular neuron, and the information of this weight, the information of this is carried by this weight for this neuron and for this, okay? And then we get our output like this, and then the output from this is carried by this, the output from this is carried by this weight, the output from this is carried by this weight, the output from this is carried by this weight, and then we do our formal, in every step we do our formal multiplication or aggregation and activation stuff, right? So in every neuron, this is what is happening, okay? These two steps which is happening in a particular neuron, and assuming currently I'm neglecting, so I'm over here for simplicity neglecting a bias term, okay? So I'm currently neglecting bias term over here. So that is for the second. Now let's go further to understand this in this way. So for the first, we have the first information carried by this weight for this particular neuron, and then for this we have this particular neuron, and for this information is carried by this weight for this particular neuron, and for this information is carried by this weight for this particular neuron. Okay, so you may have, and then we do the formal process to get our output. So over here, if we combine those things, this is how it looks like. This is how it looks like. So let me just show it to you. So you have W11 and 1, W12 superscript 1, W2 W13, right, 1, and W14 1. Okay, so this indicates the layer number. This indicates the layer number. This indicates from where it is coming, right? So from where it is coming, the unit 1, the input unit 1 or input unit 2. So it is coming from input unit 1. So that indicates the input unit, okay? Input unit, right? And this is the weight number, the weight index. So this is the first weight, right? So over here, weight index. So the same goes with the input number. So let me just change the color so that it makes sense. And W2 is your weight index, and this is your layer number. Same goes with this, and then goes with this. Okay, so this is how the notation is working. For this particular example, we have W21, and then we have W22, W23, and W24, right? So you have a W21. So over here, this is the input unit 2. This is because x2, and this is the weight index, and this is your layer number, right? So this is how we denote the weights over here. And if you see this example, this has changed. This one over here, W112, this indicates your the hidden unit, right? Hidden unit, and this indicates your weight index, and this indicates your layer number. So that is your notation arguments. Now
in every particular what is happening in every this neuron, what is happening. So I've done a very good analysis over here. So I'll just tell you that what exactly is happening in every neuron, or the hidden units. Okay, so first of all, I have given different names. So for aggregation steps, I'm using Z. Okay, and for post activation, I'm using H as our final output, right? So over here, so let's assume for this, what is happening over here. So basically this indicates the hidden unit, and this indicates the layer number. Okay, so for the first unit and in the first hidden layer, we are multiplying the weights of the first W11, this weight, okay, and then we are multiplying for the first information and the second information, right? So we are not just because the first information and the second information is carried by different weights and then given to this neuron, okay, because we have several neurons. So for the two neurons is given to this, the two input values is given to this neuron, right? Okay, and then we add the bias term over here, and then this is what the aggregation step means, and then we apply the ReLU activation function on the output which we get. And then over here, what is happening in this? We are simply multiplying the weight from the information x1 is carried by the weights to the H, the hidden unit number 2. Same goes with the information number 2 is carried by some weights to the second hidden unit. Okay, and then we add the bias term and then we get our output. Same goes with J3. J3 is our this unit, right? So over here, this is your pre-activation function. In pre-activation, the information is aggregated, okay, with the respective weights and then applying the ReLU. For J4, we are for this one, we are doing the pre-aggregation step and then applying ReLU. Okay, and then we get our output, which simply multiplying the weight with the output which we get from the particular unit. This is also this is the weight which is carried by the information by the H2. This is the weight, this one is carried by the weight, the information is carried by this weight, and the information of this carried by this weight, and this is the bias term. And then we get our output, and then we apply some kind of activation function over here, like ReLU or sigmoid or tanh, whatever we apply over here, and then we get our output. Right? So I hope that makes sense. Let's go further. So if we can write in vectorial format to have it much more better way, so I'll just see. So we'll cover till different area. So let's cover over here, and then we'll go from the next video. Let's cover the vectorial format, and then we'll cover the rest in the next videos. So we can write in this way. We can write in vectorial format. So we can have our big Z. We can have a matrix or a vector which is Z, okay, and we can store all our weights in a matrix, and for this particular example we can store this our weights in a particular matrix. So we store for the first for the first information we store this weights, and for the second for the weights for this information, and the weights for this information is stored like this, okay, where we have for this which are for first information weights, these are second information weights or the second input weights, okay. I store them into a particular weight which is weight matrix 1, okay. For this indicates the layer number. Now we make for the second, which is stored as a column vector, which is 1 1 2, which indicates which you can see over here, which is weight number 2, and this weight number 2 contains the weights for the particular for every or you'd say like this, okay. And we can write in this way, we can write in this way in the vectorial format, and then we can simply take out Z, okay. So what you can do, you can simply multiply the weights with the
column vector, which is x1 and x2, we can put that into a vector as well. And when you apply a matrix vector product with a bias term, so we'll add the bias term in every neuron. And the bias term is like this. So when you add this, so you'll be getting your, when you do the matrix vector product and then add the bias term, you'll get a vector is 1, 2, 3, 4 for this particular example, and then you apply the sigmoid function, and then you have a big H1, and then you apply the activation function, like this, and then you'll be getting your output vector big H1, where you'll be having these things. So this is more efficient or more computationally efficient over here. And then what you do, and then you do the same for O12, where you apply the sigmoid function, every element sigmoid function on these on the particular vector which you'll get from here. Okay, so that's what we have written in a vectorial format. So there's no any kind of a theoretical concept which needs to be explained over here. Everything is very, very clear in terms of writing these things out here. Main part will be your back propagation stuff, which needs a little bit of more explanation, but these examples are pretty much easy to understand. I hope that this makes sense to you. I'll be catching up in next video. Till then, bye, have a great day.
So welcome to this lecture on neural networks. So in this lecture, what we will do is maybe we'll start talking about chain rule of calculus, and try to start off with backpropagation. But before that, I'll just take some examples or worked examples of multilayer perceptron, just to be very clear in calculating all those things. And maybe we'll talk about applying different activation functions on your in neural networks, and how things works in fodder prop. So maybe we'll revise it, and then we'll go on computational graph, which is of chain rule of calculus, and then we'll try to see through the computational graphs, like how do we calculate about great info about chain rule. And then we will go ahead and end this video on starting introduction to backpropagation. Cool. So let's get started. So till previous videos we talked till 9 slides, so I just want to make you familiar with it. Right, so we talked till 9 slides. So what we will do, we'll just recapitulate it so that it will be better for you. So we have a z variable, we have a variable z, and then we have a variable x, and then we have a bias term b, right? And then if these are our weights, this is the input feature, this is matrix vector multiplication plus the bias term, and then you get your, and the bias term is the vector, then you get your a vector, which is where we apply the post activation the activation functions on each z, right? So when you take out the dot product between your weights and input values x, or the information, then and then you apply the pre-processing stuff like this sigmoid in this case, and then you get your output, which is a vector, a vector which you will get over here, and then this vector is multiplied with another weights vector. This vector h1 is multiplied with another weights vector plus the bias term. So basically we are taking the dot product between these two vectors, maybe, yeah. So we are taking the dot product between these two vectors, and then we were getting this O12. Okay, so this was our basic revision of our previous lecture, and I urge you to basically have a good understanding of these things by watching our previous lecture, because we had discussed a lot in that. Cool. So now let's start seeing the worked example of one layer neural network. So basically the current neural network which we have is one layer neural network. So basically we have 1, 2, 3 and 4 neurons, right? We have 4 neurons, and then we have one particular output neuron, right? So we have output neuron, and over here we have two input features,
and x0 is always equals to 1, so we don't need to worry about that. All right, and for assumption, for simplicity, we have taken our bias term all equals to 0 for all neurons in this case. So basically we have weights like 0.1. So we have the first weight in the W from the first to the first neuron. So we have 1 to be 0.1 for the first layer for sure. So 0.1, then for 0.2 for the first information. So for the first information x1 is carried by these weights into the 4 neurons for the first neuron, for the second, for the third, for the fourth, and then x2 for the first, for the second, for the third, for the fourth. So you have a weight vector. We call this as a weight vector. We call this as a weight vector, right? And this is your input vector which you're seeing, which is 2 1, right? So we have taken a very dummy example to showcase this is 2 and this is 1, and the weights for the second layer is 0.9, 1, 1.1 and 1.2. that are just random, and just for the sake of example of a forward propagation, like how do we multiply and do all those stuff, right? So first of all, when we do calculation till here, we get the vector. For this we have 0.7, for this we have 1 after doing all the processing, and the processing which is over here in every neuron is, the first one is your the aggregation wi times xi, and then you apply the processing. Currently we are not applying the processing over here, but the first one is the weighted average, or what do you say, the dot product between your input features and the weight values, right? And then we have done the first part of it. The second part is applying the activation function. So in this case, where for particular getting h1 then we apply the activation function on z, which we get like z1, z2, z3 and z4. We apply that, and then you get a final vector which is the output from this particular hidden layer. So this hidden layer is this h1. Okay, the first hidden layer outputs this, and then this is multiplied with weights over here. We have another vector weight and of h1 times the weight for the second layer. We take out the dot product between both of them, and then we get our final output. Okay, so this was your applying the sigmoid activation function, where it squeezes the output in the range of 0 to 1. So this 1 is squeezed into 0.73, 1.6 into 0.832, 1.3 into 0.785. Okay, so this was your basic example of applying sigmoid function. Let's go ahead and see the next neuron. So we are done with the h1. So we are done with h1. Now we do for o1 for this. So basically what I can do, that indicates it's the second layer and this is the first unit, right? And this is what it does. And now if you see, this is your output. This is your the weights. This is your weights w2. So this is your weights for the second layer, and this is your h1 which you got from the previous layer. So information from the previous layer. So this information from the previous layer is multiplied with the given weights, and then you get the particular output. And then over here, first of all, you did the what do you say, weighted average now by taking the dot product between those two vectors. Now what you do, you apply the sigmoid function. And on 2.5 it gives you a range of 0.93, right? And then you get your 0.93 as an output. So that's a one hidden layer neural network, right? So there we are using the sigmoid activation function. Now let's go ahead and talk about ReLU activation function. The same example carries out. So we have a 4x2 matrix where it contains, I think, a 4x2 matrix of weight matrix. We have 2x1 input matrix, and we have 4x1 not matrix, 2x1 vector, and 4x1 4 times 1 bias vector, and then we are getting the output. And then we have an h1, which is what it does. Over here we are, instead of applying the sigmoid activation function, we are applying ReLU activation function. So basically what you mean in ReLU, what it does, it squeezes your output between 1 and 0, right? So basically not 1 and 0, it just takes out the max, of 0 and 0, I think, yeah, so it takes out the max of 0 and z. So whoever is bigger, it just gives that as an output. Okay, so 0.7 is bigger than 0, 1 is bigger than 0. So if there is -1 and your and let's say 0 and -1, so your z is -1, then the output will be 0. So there will be 0, right? So ReLU, just what it does is the equation is max of 0 comma z, and whoever is bigger, it just information for the next hidden layer. It is widely used ReLU activation function, and we'll see the advantages and disadvantages later on. Here we apply the tanh activation function. The tanh activation function, what it does over here, which you can see, it's oh my god, I think there's a typo over here. We are applying the tanh activation function, over here, and this is the formula for it. So we urge you to watch the previous lectures if you haven't seen about these activation functions in detail. So we had a talk on a one layer hidden neural network. Now here we see an example of two layered hidden neural network, where we have for the first hidden layer, our weight matrix look like this, We can also write in this format W1, right, and then we can write in this format transpose. We can write in this format. So for the first weights, right, so we can simply write this as this row vector into our column vector, right? So sorry, row vector, this column vector into a row vector, and then we can either transpose over here. But for simplicity, let's stick with our example. So basically we have W1, and then we have another, this is a weight matrix, right? And over here, this is a weight matrix for the first layer. The weight matrix for the second layer looks like this, where for this you have the particular column vector. For the second hidden unit, you have this red vector for this, which you can see in detail. So we have this weight matrix for the second layer, and then we have a third weight matrix or the column matrix for the third layer, right? So basically for the output neuron. Okay, so you can see it out. Just pause this video if you want to go ahead and see it out how it works. So we have different layer of neural networks. So basically here we have a two-layered neural network. We have, I think in previous example, this is three-layered neural network, but if we include this particular output neuron, so this is three-layered neural network. Okay, cool. So over here we have several kind of different layers neural network, and these are all carried by the weights, and our primary goal is to optimize these weights to get good theta, okay, or the parameters or the weights over here. So we can have L-layer neural networks like this, and we'll formally introduce you to the L-layer neural network maybe at the end of this video, maybe at the end of the backpropagation, when we'll formally give you the tools or the definition of neural networks, both forward propagation and backward propagation for L-layer neural network, and when we'll implement our own neural networks, right? So that's why I think we can skip this L-layer neural network right now. So let's get ahead. So now we'll talk about the chain rule of calculus. So the chain rule of calculus, so first of all, we'll start off with the derivatives of the computation graphs. And over here, let us assume that you want to take out the derivative of p, the partial derivative of p with respect to x1, right? So the partial derivative of p with respect to x1, okay, the partial derivative of p with respect to x1. So what it will be over here, we can't directly take out the partial derivative of p with respect to x1. We need to go with the path, and this is where the chain rule comes in, right? So the chain rule comes in. First of all, you take out the partial derivative of p with respect to z1 times the partial derivative of z1 with respect to x1. Then you will get to this. So basically, first of all, you make a relation with this by taking the partial derivative of p with respect to z1, and then times, right? So that is the chain rule of calculus, multivariate chain rule of calculus, times the partial derivative of z1 with respect to this particular x1, right? So for reaching from here to here, you need to follow the path. But there is one more way we can reach to this x1.
Okay, so that's why we add a plus sign. Here, the partial derivative of p with respect to z2 times the partial derivative of z2 with respect to x1. So there's one more way. So there's one path to go here, and there is another path to go here, right? So basically, and then we'll be having our partial derivative of p with respect to partial derivative of x1. The first path is this path, and the second path is going by this path, right? So basically, you over here. This is the partial derivative of a chain rule of calculus. So basically, again, I'm repeating the partial derivative of this particular p. Don't worry about these things, what they are. Just assume that all are differentiable, and we are able to calculate the partial derivative or the derivative. The partial derivative is quite similar to derivative. There's the difference between the partial derivative and derivative is just you can see my matrix calculus course for this. But basically, the difference between them is the difference. It's more partial derivative is involved in vectors, right? So that's why we add the partial derivative of it. The partial derivative of this p, right? So with respect to x1, so it is asking how much this p changes when x1 changes. So this is basically saying how much p changes when x1 changes. So that's what the derivative is. Derivative is a slope, right? So change in y over change in x, right? So for understanding the change in y, change in p over change in x, you need to follow the root to understand the change in x when you change p, right? So when you change x1, how much p changes, okay? Or how much p changes when x1 changes. So basically, for taking out the change, you for this with respect to this, then you need to follow the two paths. The first path is the partial derivative of p with respect to this z1, and then multiply the partial derivative of z1 with respect to x1. This tells how much how much p changes when z1 changes and how much z1 changes when x1 changes. So here indirectly it is telling how much p changes when x1 changes, right? But there is one more path, which is the partial derivative of p with respect to z2, and then multiplied by the partial derivative of z2 with respect to x1. This is telling how much p changes when z2 changes and how much z2 changes when x1 changes. Okay, and then we get our final partial derivative of p with respect to x1. Now coming to the next part. The next part state the partial derivative of p with respect to x2. The partial derivative of p with respect to z2, right? And so basically, if you want to calculate the partial derivative of p, means how much p changes when x2 changes. So there are a total of two paths. The first path which we can go is by this, and the second part which we can go is by this, right? The partial derivative of p with respect to z2, and then by following this path, the partial derivative of z2 with respect to x2, right? With respect to x2, and then you get your how much p changes when x2 changes for the first path. For the second path, the partial derivative of p with respect to z1 and partial derivative of z1 with respect to x2, right? So how much p changes when z1 changes and how much z1 changes when x2 changes, and then you'll be getting a partial derivative of p with respect to x1 and partial derivative of p with respect to x2. So it's basically, if you have seen a gradient descent thing, we were doing, we're simply taking the partial derivative of z with respect to theta or w1. So it just tells how much j changes or loss changes when w1 changes. So I'm just teaching you the concept so that you could understand the backpropagation in a much easier way when we study about backpropagation later on, right? So that's the first thing about the derivatives of the computation graph when we talk about the chain rule. Now let's get ahead. I hope that this makes sense to you. And this is now let's keep talking about the deep computational graph. If we have a deep computational graphs, how things work, right? So we had a talk on forward propagation, all these things which we talk on forward propagation. But now we'll start talking about the backward propagation, how we backpropagate. Okay. So the first thing which I want to talk about is chain rule in deep computational graphs. So over here you have this h1, this h1 takes information. It's h1 is the function of x1 and x2, and this h12 is a function of x1 and x2, right? And this h21 is a function of h11 and h12,
and this h22 is a function of h11 and h12, and p is a function of h21 and h22. So it takes these two values to compute their output, right? So that's what these indicates over here. So now I want to talk about is what is the partial derivative of p with respect to the partial derivative of p with respect to x1. So first of all, the partial derivative of p with respect to h21, so first of all we go this way, times the partial derivative of h21 with respect to h1, it's x1, yeah. So that x1. So basically we do this way, right? So there's for sure the path, but using this we are able to reach x1, right? And the partial derivative of p with respect to h22, right? And the partial derivative of h22 with respect to x2, right? But over here, if you see, we can calculate, but when calculating h21, which h21 we have one object over here. There's one blockage. So first of all, what you do, partial derivative of h21 with respect to partial derivative of what do you say, h11 times partial derivative of h11 with respect to x1, right? This is how you calculate it. This is how you will calculate it. Okay. Just for simplicity, let me showcase to you how we calculate the partial derivative of p with respect to x1 is partial derivative of h21 with respect to with the partial derivative of p with respect to h21. First of all, we get 2 here, and then with this we calculate the partial derivative of h21 with respect to x1. We have another path, partial derivative of p with respect to h22 times the partial derivative of h22 with respect to x1, right? So there's two paths. But in the second path, h21 with respect the partial derivative of h21 with respect to x1 and partial derivative of h22 with respect to x1 has a blockage in between, right? So basically, for calculating the partial derivative of h21 with respect to x1, what you will do, you will calculate the partial derivative of h21, the partial derivative of h21 times the partial derivative with respect to h11 times the partial derivative of h11 with respect to x1. So the blockage clears out. So the blockage clears out, right? Plus there is one more way we can get to this x1. So basically the partial derivative of h21 with respect to h12 and partial derivative of h12 with respect to x1, and then we calculate this particular partial derivative of h21 with respect to x1. So there's two paths over here which we can get to how much h21 changes when x1 changes, over change in h21 over change in x1, right? So this is how we calculate for x1, right? And then we'll do the same for this particular, because there's some blockage in between, right? So let's do for that as well. So basically, when we do the partial derivative of h22, the partial derivative of h22 with respect to x1. So okay, so we are calculating for x1. So for x1, it is nothing but the partial derivative of h22 with respect to h11. So there's a blockage in between, right? So there's a blockage in between, and then the partial derivative of what do you say? Okay, so over here I think I did a little bit wrong over here. I think so. Yeah, so basically over here is basically telling we have another path which we can go in this way. So basically if you see over here, it starts calculating, but over here if you see the partial derivative of h22 with respect to h11 and the and times the partial derivative of h11 with respect to x1, it should be x1 over here, right? And then it goes with the same with this for h22. I think the diagram is a bit wrong. I'll just put the picture, right, so it understand much well. You can simply ignore this. This is kind of misleading diagram. So for calculating the partial derivative of h22 with respect to x1, so first of all the partial derivative of h22 with respect to h11, right, h11, right, and then times the partial derivative of h11 with respect to x1, right, plus the partial derivative of h22 with respect to h22 with respect to h12, right? So we have another path which is like this, times the partial derivative of h12 with respect to x1,
So we calculated this as well, and then we were having two parts, this path and this path, and then we eventually will get our output as our final output, right? So this was a little bit misleading. This was also a little bit misleading, but I will change it. So basically, this is the two paths which you calculate, right? So that's a particular thing which I'll talk about, and then same go, and then we can write in this format, and then like which you're seeing over here, and then we can calculate our partial derivative of p with respect to how much p changes when x1 changes. So that's a lot of things which is over here. I hope that you understood this deep computational graphs. So in the next video, what I will do, I'll make you go through the iteration of backpropagation. So we'll solve one example of an iteration of backpropagation out here to understand much very well like how everything works and how everything does not works. All right. So we'll do in our next video of an iteration of backpropagation, and we'll try to formally define the backpropagation in detail. So thanks for watching this video. I'll be catching you next. So everyone, in our previous lecture, we had a talk on propagation. We had talked about computational graphs. We had talked about how do we backpropagate in computational graph, and I hope that given you so much sense about backpropagation. And backpropagation is not an algorithm. It's a part of gradient descent which we do, which will come to that later on. But basically, today what I'm going to do is to do an iteration of backpropagation mathematically by solving a neural network where I'll be doing one iteration of backpropagation and show you the updated weights, which optimizes the loss a little bit. Okay. So I'll be doing only one iteration, but in practice we usually have the parameters of how many iterations which you're going to do, which we'll talk about later on in our hyperparameter optimization sessions. So basically, the backpropagation which I'm going to talk about is just is taken from a blog which I'll link in the description box below. So the explanation of this written is also available in the form of blog, which I'll link to the description box below. I would like to give a big shout out to that guy, and I'll try to explain it much more detailed way so that you could also understand by watching this video. So basically this is the basic stuff which is in front of you, which is a basic two-layered neural network where we are having one hidden layer and one output layer with two outputs from your neural network. So basically, let me take my pen. So basically, you have several weights, which is carried. Your information is carried by several weights. So basically, this x1 is carried by this w11 or w11. Okay. So basically, what I'm going to do is to vectorize this neural network and write this in the form of linear algebraic format, or I would say matrices format or vectors. So basically, what I'm going to do is to store our input. So basically, the input which it will go is just 0.05 and 0.10, and they're just I've just taken a sake of an example. This is nothing much more to worry about. So basically, this is your inputs x1 and x2, 0.05 and 0.10. That is your input to your model, and that's your column vector, which is the x. And I should denote with the small x rather than big X. So basically small x, and you have a weight matrix for the first hidden layer. So the weight matrix for the first hidden layer, so for the layer, this is a layer. So basically you have 0.15 and 0.20, right? So 0.15 is a weight is a weight for x1, and 0.20 is a weight for x. Of course, x1 going to, if you see, x2, okay? So 0.15 is x1 and 0.20 is for x2. So basically your information is carried, x1 is carried by 0.15 from the first information to the first hidden layer or the neuron, and your second information is carried by some weight to the first hidden layer. So basically that is 0.20. Okay, now we have the another neuron. As I said, we stack the neurons or the basic units, right? So we stack the so basically this H21, basically this is the hidden layer, and we have two neurons in it, and this X1 is carried by weights and being aggregated at H21, which is the second hidden neuron in the first hidden layer, and then this and then the h2, then x2 information is also carried by some weights for particularly this neuron, so 0.25 and 0.30, which is weights for this for the first layer. Weights for the second layer is w2 is equals to 0.40, which is going just is carried this h1 h superscript 1 subscript 1 is carried by some weight with 0.40, and then this information is also carried by 0.50 for the second neuron, and the second h2, the second neuron also gives out some information which is carried by some weights which goes in the which goes in the second output, the first output neuron, and the same information is carried by another weights for the second neuron. Okay, so this is the basic neural network which you have, and you have a bias term. Yeah, and you have a bias term which is first of all for B over here, where for this you have 0.35, and for this you have 0.35, for this you have 0.60, for this you have also 0.60. Pretty much it. Okay, so now what I'm going to do is to do a forward propagation. So basically that's what I'm going to do is to do a simple forward propagation, and basically what I'm going to do forward propagation is get some predicted value over O superscript 2 subscript 1 and O superscript 2 and O subscript 2. So that's what I'm going to get. So let's go here, let's go in our first hidden layer and in the first unit or neuron. So when you go there, as I already say to you, a neuron is a neuron in a hidden layer consists of two things. First, it gets aggregated in a nucleus, which we call this as a Z, and then we have something called as a activation function, which activates this neuron, which decides whether to activate this neuron for the particular task or not. Okay, so basically if this is 0, then the neuron is not activated, but if this is something, then the neuron is activated, and that contributes some information that can go into the second layer of the network. So basically, if you're seeing that Z superscript 1 subscript 1 can be calculated by using something like W transpose X plus B. And basically your W, if you think for this, your W was 0.15 and 0.2, right? So this was your for the first information is carried by two ways into two different neuron, right? But basically over here, which you're seeing over here, which we have this over here, this is carried by two ways, 0.15 and 0.2, right? 0.15 and 0.2 from two different inputs, and then we add a bias term which is 0.35, and we multiply by 1 because x0 is always equals to 1, and then you get your output. So basically this is your weights, this is your input x1, this is your w21, okay, for the first, and this is w11, okay, and this is your bias term, right? So this is basically your W transpose X plus B, which is your hypothesis, and then this is aggregated, and then what you do, you simply apply an activation function. Here we are applying a sigmoid activation function, but we'll see that this sigmoid activation function has a really big fall of vanishing gradient descent problem. So which we'll talk about that later on, but for simplicity, let's go with sigmoid. So when you apply the sigmoid to this output of Z1, it says 0.59, it means this neuron is activated, right? And then you get your final output for this is nothing but 0.59, blah blah blah. Okay, so that's your output from this. For this you have again the Z1 and A1, and this is this in this neuron, x1 is carried by some weights and x2 is carried by some weights, and then we aggregate that, and then we add the bias term which is 0.35, and then we get our output, and then we apply an activation function which is sigmoid activation function, and then you get your output, right? So that is for the first H11 and H12. Now let's go ahead and talk about the output neurons, right? So that's a prediction. So basically, if you're seeing over here Z2, if you're going over here, so this is a second layer of course, and the first neuron, right?
So basically when you calculate that, this output neuron is carried by two information from the previous layer, which is this information and this information. So this information is carried by some weights and this information is carried by some weights. And please note that these informations or the weight value are random as of now. Okay, your algorithm, main goal of your algorithm to learn these weights. Okay, that's what, which is super important. And this A12 is, then we apply an activation function on top of it, and then we get our O21 as an output. Okay, same we do with O22, for which we get an output as like this. So now we have got our output. Now what we want to do, we want to calculate the error as well, like how, with these weights, with these particular weights, how well our model is performing, or how's the loss function, or how's the cost function, or what's the error is, or how well our model is performing, right? So basically, let us assume that our ground truth is 0.01, and O22, for O22 we have 0.99, but our model given 0.75 for the first one, and 0.77 for the second output neuron, which is your model output. So what your model will do, so basically we can calculate the error by subtracting 0.75, then this one, and then 0.77 with this one. Okay, so basically you know how to take out the loss, which is a mean square error, whatever you can use over here, and then you can you make use of mean square error to calculate the error, which is 0.20, 29837, blah blah. Okay, so that's what we are done with forward propagation, where we got the error j with all of these parameters. Now we need to optimize these this j. So basically what I told you in our previous lectures, or our previous gradient descent lectures, is we take the partial derivative of our cost function j with respect to our parameters, whoever over there, and what we do, we simply adjust these weights and check if the loss function is decreasing. If the loss function is decreasing, we update those weights, right? So that's what we do when we talk about derivative. So derivative tells you two things: how much weight to change, and in which direction your weight will go in. So please note that you watched the lecture of gradient descent so that you have understood in much more good way. So what I'm going to do is to take out the partial. First of all, we need to update this weight, W211. So what I'm going to do is take out the partial derivative of j, cost function, with respect to W21, which tells us how much loss changes, or cost changes when that W21, that W changes, or that parameter changes, or that weight changes. Okay, so how we can calculate that? So that's quite easy to calculate. So if you want to take out the partial derivative of cost function with respect to your W12, so you have some blockage in that. So first of all, you need to calculate the partial derivative of j with respect to A12, so the activation function of this. So if you're seeing that you want to calculate the, first of all, you have to go over here, multiply it by as we invoke the chain rules. So basically this A12, so first of all you take out the partial derivative of j, because over here if you want to go back, then over here you have two things, z and a. Okay, and z, this is nothing but a, like this. Okay, so that's what we need to do. So that's what we need to do is just take out the partial derivative of j with respect to A12. After that, now we need to because we still haven't reached there. to our W12. So basically we calculated the partial derivative of A1, this one with respect to this. Okay, because we need to calculate the partial derivative of that. So we calculate that, and then using z1, we can go to this parameter to know how this is changing. Okay, so basically here's the calculation which is involved. So here's our cost function, where I have, for simplicity, I have written this, of course, and then you take out the partial derivative of j with respect to A12. So basically what I'm doing over here is to using the chain rule of calculus and the power rule of calculus to perform this calculation. So basically what I'm doing is
is performing the first of all the partial derivative of the inner function and the partial derivative, or the taking of the derivative, not partial derivative, the derivative of inner function leaving the outside function as it is, partial derivative of outer function leaving the inner function as it is, and then taking out the times the partial the derivative of inner function. So first of all, when we take out the derivative of outer function, so basically here it's 2, so using the power rule we take it over here, right, and subtract -1 from this, right. So when we do 2 times 1 by 2, that is cuts down, so we are left with y minus h of x. Now that is the derivative of outer variable. Now the outer function somehow, because over here we have something, but there is something which is 1/2 something, and this is 2. So the derivative of outer function, where we take 2 over here, multiply with it. As I said, as you have listened me, that I told in gradient, when doing gradient descent, it cancelled out. So that's why we do that, and then we leave this as it is, times the derivative of inner function. Okay, so when you take out the derivative of inner function, when you take out the derivative of inner function, this y, this y have I'll say if you take out with a1 2, so this eventually becomes -1 plus 0, and 0 is nothing but, I would say, the reason why we got 0, because the derivative of any inner constant is 0, and here we are using the sum rule because we are applying the derivative of on every function. And then the reason why we have -1, because when you multiply this -1 with this, so you'll be left with this final formula, which is a partial derivative of j with respect to a1 2. So that's your the partial derivative which you got. Okay, now this tells us how much cost changes when that activation function or a21 changes. Okay, so that's what you got over here. Now you can plug in the values to get that value, right? So when you plug in the values, so basically put the -1 as it is. This is a ground truth, and this is a model predicted, which you get, which is 0.74, right? So that's you got the value of this one. Now you go the same for the derivative of a1 2 with respect to z1. So basically this is your, as usual, sigmoid function, and we have already derived this in our intro to NN chapter. So when you take out the derivative of your activation function, this something looks like this, and then when you take out and then you put in the values of sigmoid of z1. So basically your z1 was what? What was your z1? We have just calculated priorly when doing for propagation. So it was this times -1 minus this, and then you get your final output, which is 0.186, which you got the value of this as well. Now the last one which you are left with is z12, where we are simply the z12 is in this. So we're going to take out the partial derivative of z12 with respect to this variable, this parameter. So basically when you calculate that, you are only left with this particular value, which is h1 1. Okay, that's what you're left with. Let me just make you show that what exactly you're left with. Yeah, so when you go back here, so when you take out the partial derivative of z12 with respect to w11, then you're left with 593, because because that's a constant, right? And you have xi which is left. So when you do the calculation, you'll be getting this 0.59, which is quite well to understand. Okay, so that's the first parameter updation. Now what I'm going to do is to just change the little bit of calculation so that you're up to the standards of the calculation which are going on. So delta rule. The delta rule is when you take out the partial derivative of j with respect to w1, as how much cost changes when that changes, right? So that is which we have just taken out. As you're seeing over here, we have just taken out. We have this, so we can fill in the formulas. W012, that is your ground truth, minus your actual value. Model predicted value, and we have minus over here. Just we add a little bit of notations, times this one,
which is partial derivative of z1 with respect to, and then etc., which is the partial derivative of your segment function which you got. Okay, this formula and this formula, and then in this, when you take out the partial derivative of z1 with respect to whatever with respect to your parameter, you have the output as a a12. So basically, when you go there, this a12, which is a11, so basically that that particular value. So yeah, so basically you're left with a11, which is over here. Okay, so basically you're left with a11, and then you using that a11 you get that w12. So basically using that a1, because this h11 have the a11, of course, you h11 is an output of your z11 and a11, right? So your a11 is the final output, of course. So basically you have this a11 over there. If you're confused a little bit on that, so let me just make sure that you're understanding what I'm saying. So over here, I think there is a slightly change. It should be 7, 6, whatever. But basically we are going here, and this is where we are using. This is where we have this h11. Basically we are going backwards, right? So here we have z as w11, w2 times whatever the output from a11, right? So this is your constant of this, so that is your a11 which is an output. When if you've studied about calculus, then you might be familiar with this. So that's your partial derivative of z1. So basically that was a partial derivative of z11 with respect to your parameter w. And please be sure that I'm making lots of errors over here, because I think that it's very tough to at least pronounce their name, but no problem in that. But now we can write this into delta notation, and delta notation here we can take this and put that into a delta 012, which for that variable, right? And then multiplied by a11, and that's your partial derivative of j with respect to w211. Okay, so that's a delta rule which you also see in real world. So now we can just go ahead and do all the calculations. So we had taken out all of these in over here, and now what we can do, we can multiply with that, and then we get a final output. And now what we can do, we can update our weight, because now we need to update our previous weight, right? So that's the first update which we want to do. Let us assume we have taken a learning rate which is 0.5, which is fairly a large learning rate, but previously our weight was 0.4, but minus which 0.5 times the derivative, okay, and then you get the new weight. Okay, previously 0.4, now it is 0.35, which optimizes the error. Now what I'm going to do is just have something which is partial derivative of j with respect to w21, and basically over here what we are doing is take out, first of all, go back, and then first of all take out a21, because over here you have something like this, right? So basically you need to go back, and this is for a21, right? So basically this is for second weight going into first neuron, as far as I know, right? So basically you have this a12, which is the second second activation function. So basically you take out a partial derivative of j with respect to second activation functions. You can do the calculation now by your own, and then using that you go to over here, and using z you take out the partial derivative of z with respect to w21, which tells how much g changes when this parameter changes. And when you do that, you'll get this 0.822, and when you update your parameter by the old one by minus 0.5, which is the learning rate, you get the 0.40, which is previous one was 0.45, now it is 0.40, right? You do the same for the other two, for the second layer neural network, for the second layer for the output layer weights. So you can do in this way, the same way, the same will follow up, right? And there is something called a memoization. Which I just want to tell is, when you take out, say for an example, you take out the partial derivative of j a1 to in your previous iteration. You will come to the instance where you will see the partial derivative I already taken, which can be used in next iteration. So we just make use of that rather than redoing the partial derivative of that. So that's what we just make use of that of the one we already created. But there will be a separate video coming up on this. So we had now updated our all parameters, which is all the parameters of this till now. Now we need to update the parameters of this because we are back propagating over here. So now we're updating the values of the parameters of the first hidden layer. So basically we have to calculate the partial derivative of j with respect to w11 for the first parameter. So basically what I'm going to do is partial derivative of j with respect to a11, right? First of all, we need to go there times the partial derivative of j with respect to a11 with respect to z1, because we also go to z1, and then using z1 we go to w1. Okay, so as you know, we first go here, the partial derivative of j with respect to a11, and then using this we go over here. You would take out the partial derivative of this with respect to z11, right? And then using this we take out the partial derivative of z with respect to this, and this tells us if, and using the chain rule, as I told, this is a chain rule, and there is some notion called intermediate variables and all those stuff, which I will come to that later on. But basically this is the basic idea. If something is causing blockage, that's the chain rule, which if you have already known about that. So you take out, when you do the calculation, you'll get your partial derivative of j, like how much cost changes when w11 changes. Subscript 1 and subscript 1 changes. So now if we go over here, for calculating the partial derivative of j with respect to a11, so there is a one blockage which is causing over there. So we need to calculate the partial derivative of e01, because that's our output with respect to a11, right? Plus the partial derivative of e02 with respect to a1. Okay, because as we know, as we go over here and from this side as well, as I told in your previous section, in our previous lecture. So that's the path, because there are two paths which we can go further. So basically the partial derivative of z with respect to a11. So here's your two paths. The first path for going to a11, and this is the second path for going to the z11, like this and like this, right? As I told. So first let's take out this partial derivative of e01 with respect to a11. So when you take out the partial derivative of e01, that is your a, that is nothing but a12. That's what it is, right? That's the output of it, right? As far as I know, that's sorry. Just wait for a second. Let me confirm it if I'm correct over here. Maybe I should. Yeah, I guess that I'm correct. 0.75. Yeah, I'm correct, I think. So basically, this is not an error. I think you can ignore this. This is an output of the this is basically an output, not an error. Please ignore this as of now. This is an output, not an error. Okay, so basically this is an output, not an error between the ground truth. It's just an output which is a21, a12. Okay, so and this is a22. Okay, so that's activation function which you get from output. Now basically basically you have to go from here to here. So basically you are here, so you take out the partial derivative of this with respect to this, and then using this you go over here. That's what we need to do, right? So you do the same, and then for taking out the partial derivative of e01 with respect to z12, right? So z12, we need to first of all take out the partial derivative of a11 with respect to a12 times the partial derivative of a12 divided by with respect to z12. So basically this is quite confusing as of now, I know, but basically what we are doing, we have two different paths to go above. Okay, we have two different paths to go above. Sit down and see where it is going. Okay, sit down and see where it is going, and then you'll understand that we have two paths where it's going from this side, from this side, and from this side, and you'll be seeing that we have taken from this side. This is partial derivative of e01 with respect to a11,
and this is the and when you take out the partial derivative from this side as well, okay, from this side as well, right? So basically what you can do is have this particular, which you're seeing, which is your which you can calculate that, and then you got your final. So basically you can plug in the values of that, because we need these two for calculating the z, how much j changes when this changes. Plug in the values, and then we get our values, and then we simply plus that, because that's the two path to go at that a11. Okay, so after that we are done with this. Now we calculate. So basically we are done with calculating the partial derivative j with respect to a11. So partial derivative of j a11, because it involves lots of calculations. Not only from this side, it will go from this side as well. If there's a two paths for that, and that's why back propagation is one of the hardest stuff in deep learning. But it comes over learning all the stuff. I suggest you to maybe read a blog with it, as well as watch the video. That would make more sense. So basically now we're done with that. So we take out the partial derivative of a11 with respect to z11, because without that we can't go. So basically the partial derivative of your sigmoid function is always, and then you have a z when you take out that, which gives x1, which is output. Now you can simply plug in the values, which is 0.036 times 0.24, which is another derivative, then times 0.05, and then you get your output as a final output. Okay, so that's the derivative of how much j changes when w11 changes. And now what you can do is just update your values. 11 is equals to w is new one. This is the old one, right? This is the old one, minus you're learning at alpha, and the derivative of j with respect to 11. Okay, and this is your output, which is 0.04, and then you can calculate for 11. Same you can do with w12 for the first layer, but you need to identify the paths, right? The number of paths, and then do it in that way. Okay, so that's what the iteration of backpropagation means. So we did a one-to-one iteration of backpropagation, and I hope that this was a really nice session. Basically this was a really nice session on backpropagation. If you like this lecture, let me know. If you have any questions or any doubts.